10. Adaptive neural fault-tolerant observer-based stabilization of uncertain MIMO time delay nonlinear systems with dead zones and faults in actuators.
Abstract.
This chapter addresses the stabilization of a general class of multi-input, multi-output MIMO nonlinear systems with time-varying time delay, unmeasurable states, and in the presence of dead zones and faults in actuators. The method deals with asymmetric dead zones and tolerates faults due to loss of effectiveness and bias. A suitable observer is designed to estimate the system's unmeasurable states. Furthermore, based on the universal approximation theorem, radial basis function neural networks, RBFNNs, are employed to tackle the unknown nonlinear functions within the system. To overcome the time-varying time delay, the synthesis approach is used. Thanks to this approach and the interval method, the adaptive laws are derived, and it is proved that all the adaptive parameters remain bounded while the controller avoids singularity issues. It is rigorously shown that all the closed-loop signals remain bounded, and the state estimation errors and actual states converge to zero asymptotically. To show applicability and effectiveness, the proposed method is applied to the unified chaotic system with unknown nonlinear functions, unknown time-varying time delay, unmeasurable states, and unknown dead zones and faults in actuators.
10.1 Introduction.
Time delay can be observed in many practical systems, such as engineering, biological, and economic systems 1. The necessity to transfer information and energy is the physical phenomenon responsible for time delays 2.4. Time delays can arise in system states and control inputs due to inherent reasons or external factors such as computation time, communication lags, and physical transport delays 5.6. Since time delay causes the past states and outdated control to affect the current system's dynamics, controlling systems in the presence of time delay is challenging and not straightforward. 1.7. From the frequency point of view, time delay causes phase lag in the system, reducing both the phase margin and the gain margin, eventually pushing the system toward instability 2. Moreover, there are constant and time-varying time delays in realistic systems. Constant time delays are more accessible to handle and estimate, while time-varying time delays add more complexity since the time delay is difficult to predict. As a result, this causes the degradation of the system's performance and corrupting stability 8. Due to the importance of controlling time delay systems, various robust methods such as in 9.11, adaptive methods for example in 12.14, and predictive methods for instance in 15.17, have been proposed to address the complexity and guarantee effective control. Actuators play a critical role in any control system by converting control commands into physical quantities to manage the system's behavior 18. However, actuator faults are unavoidable in practical applications 19. The two most common actuator faults are loss of effectiveness and bias. Loss of effectiveness reduces the actuator's output, while bias significantly causes offsets to the desired actuator's output 2021. If not considered, both faults will push the system into undesirable behavior, instability, and catastrophic failures. Therefore, early actuator fault diagnosis and fault tolerant are vital for many safety-critical systems, such as industrial processes and aerospace 22. One of the effective strategies in overcoming actuators' faults is fault-tolerant control, FTC. FTC is a control strategy that ensures system stability and maintains satisfactory performance in the presence of faults 23-24. Many effective adaptive FTC methods have been proposed in the literature to cope with actuators' faults in time delay nonlinear systems, such as 25-28. Another issue with actuators is their nonlinear behavior. Different nonlinearities such as backlash, saturation, hysteresis, and dead zone have already been studied in actuators 29. If they are not considered, they can significantly deteriorate the system's performance or jeopardize its stability 30-31. One of the most common actuator nonlinearities is the dead zone, in which the actuator's output is 0 until the input does not reach a specific value. This causes significant problems in practical applications, such as delays and loss of accuracy and efficiency in regulation and tracking 38. Moreover, it is a non-smooth nonlinearity. Thus, the methods that need, such as or mean value theorem-based methods, are not usable to cope with this nonlinearity. 33-34. Some valuable adaptive methods have been considered in the literature to address the issues caused by dead zone nonlinearities in time delay systems, for instance, 3540. The states of the system are required for effective and applicable control designs. However, in reality, measuring all the states is impractical and in some cases impossible due to many reasons, such as cost, physical constraints, and the system's complexity. 41-42. One of the effective approaches to cope with this issue is to use observer-based design methods. An observer is a dynamic system based on the process model that uses the measured states to estimate the unmeasured states. 43. Then, the estimated states can be utilized for the control design. Since observer-based control design is a valuable and practical approach, some adaptive observer-based control methods have been proposed for time delay systems with actuator faults such as 44-46. Notably, although the methods in 39-40 can handle dead zone nonlinearity and fault in actuators, they need all the states to be measurable. Furthermore, the method in 39 is suitable for NSSO interconnected systems, and the method in 40 is suitable for known constant time delays. This chapter considers stabilizing a general class of multi-input, multi-output, MIMO, uncertain nonlinear systems in the presence of time-varying time delays, dead zones, and faults in actuators, and with unmeasurable states. The dead zones in actuators are considered asymmetric, and the faults can contain both loss of effectiveness and bias. An observer is proposed to estimate the unmeasurable states. To tackle the unknown continuous nonlinear functions in the model, radial basis function neural networks, RBFNNs, based on the universal approximation theorem are utilized. The synthesis approach is used to cope with the time-varying time delay just by knowing the upper bound of the time delay's derivative. The adaptive laws are derived based on the interval method, which guarantees the boundedness of all adaptive laws and avoids any singularity issues of the control signals. It is rigorously proved that all the closed-loop signals are bounded, and the state estimation errors and the actual states tend to zero asymptotically. This chapter is organized as follows, in sect. 10.2, the problem is formulated, and mathematical preliminaries and assumptions are stated. Moreover, the universal approximation property of RBFNN is concisely explained to ensure the continuity of the discussion. The proposed observer, adaptive, and control laws are expressed in sect. 10.3.1. Section 10.3.2 proves rigorously the closed-loop stability of the proposed method by introducing the needed lemmas. Section 10.4 applies the proposed method to the time delay unified chaotic system to study the effectiveness and applicability of the proposed method. Eventually, sect. 10.5 concludes the chapter by explaining the advantages and disadvantages of the proposed method and discussing future work. Notations is the n-dimensional Euclidean space for a symmetric matrix P. P0 means P is a negative semi-definite negative definite matrix. Similarly, for a symmetric matrix P0 means P is a positive semi-definite positive definite matrix. For a matrix AN, A is the minimum eigenvalue of A for X. X is the Euclidean norm of X, i.e. XX. A vector function ft(L2) if ft is square integrable over 0. A vector function ft(F1t) if of t, I1 and t0 is finite. 10.2 Problem formulation and universal approximation. 10.2.1 Problem formulation. The dead zone in each actuator, I1. The disturbances Txt and actuator biases high T, I1 are unknown but bounded functions, and the bounds are also unknown. In this chapter, to avoid repetition and for the sake of simplicity, the argument of functions will be omitted when the context clearly explains their meaning without any confusion. Radial basis function neural network, RBFNN. 10.2.2 Universal approximation. In order to tackle the uncertainties in vector function fx, we use radial basis function neural networks, RBFNNs. A schematic of a multi-input single-output RBFNN can be seen in Fig. 10.2. As can be seen, the RBFNN has three layers: input layer, hidden layer, and output layer. In the RBFNN, the inputs are mapped to the hidden layer, and the weighted sum of the values in the hidden layer gives the output value. Parkins 50 proves that the RBFNN in Fig. 10.2 has universal approximation property for continuous nonlinear functions, i.e., the following theorem has been stated. 10.3 Proposed method and stability analysis. 10.3.1 Proposed method. 1. The unknown constants belong to the following known intervals: I1 M J1 C, where are positive constants. The unknown constants belong to the following known intervals: I1 M J1 C, where are positive constants. 2. The unknown positive constants belong to the following known intervals: I1, where and are positive constants. The unknown positive constants belong to the following known intervals: I1, where and are positive constants. 3. The unknown constants belong to the following known intervals: 0, I1, where are positive constants. The unknown constants belong to the following known intervals: 0, I1, where are positive constants. It should be noted that the positive constants and can be arbitrarily large. According to 51, if the initial conditions W0, I0, and I0, I1, and J1C in 10.26, 10.28 are chosen respectively inside the intervals, and in assumption 10.4, then WT, IT, and IT will remain respectively inside intervals WW plus I1 M J1C I plus I1, I0, I plus I1 for all T0. Therefore, WT, IT, and IT will remain bounded for all T0. Furthermore, by choosing such that 0, then I can be away from 0 for all T0. In addition, the inequalities can be directly concluded from the discussions in 51 and the adaptive laws in 10.26, 10.28. 10.3.2 Stability analysis. Before the stability analysis of the proposed method, the following lemmas are considered. Tx defined in 10.32 is bounded. In other words, there exists a positive constant d such that t, x d. Consequently, there exist positive constants d, I1, such that dtxd, where dtx denotes each entry of tx. Slemma let v r be a uniformly continuous function on 0, and 0p exists and is finite, then vt052. Let v r be a differentiable function and have a bounded derivative, then vt is uniformly continuous 53. Let GTRR if GTL2L and GTL on 0, then GT0 54. Consider VTG2T, then VT2GTGT, and since GTL and GTL we have VTL on the other hand, GTL2, thus 0VP exists and is finite. Using lemmas 10.4 and 10.5, we have VT0 and thus GT0. Consider the uncertain MIMO faulty time delay nonlinear system, along with the dead zones in actuators in 10.1. If the observer is designed as in 10.16, the control law as in 10.3, and the adaptive laws as in 10.26, 10.28, then for bounded initial conditions, all the closed-loop signals are bounded. Furthermore, the state estimation errors and the state vector tend to zero asymptotically. 10.4 Simulation example. Parameter values for system in 10.41. A 125 a plus 10. A 228 35 a 329 a 1. A 4 a plus 83. B105. B210. B35. B45. B502. B615. Phase planes of system 10.41, with UF0 and DTX0 for a 0-2 type with time-varying time delay, and B a 0-9 type with time-varying time delay. States of the system 10.41, with UF0 and DTX0 for a 0-2 type with time-varying time delay, and B a 0-9 type with time-varying time delays. Firstly, the behavior of the open-loop system is studied, UF0 and DTX0. Without loss of generality, the initial condition is assumed 12 3T2 values of are considered as a 0-2, and a 09 for type and type chaotic systems, respectively. For a 02 and a 09, the behaviors of system 10.41 are depicted in figs. 10.3 and 10.4, respectively. Figure 10.3 demonstrates the phase planes, and Fig. 10.4 shows the states. It can be seen that the behaviors are significantly different. Two RBFNNs cope with the unknown nonlinear functions in Fx. For each RBFNN, 27 activation functions are considered, where the centers are evenly spaced in 1, 2, 3, T11, I1, 23, and the widths of the activation functions are 1, I12, J1. The occurrence of faults, both loss of effectiveness and bias, at T12 sec. Regulated state X1 in the presence of time-varying time delay, dead zones, and faults in actuators. Faults in actuators, loss of effectiveness and bias, occur at T12 sec A02 and B A09. Regulated state X2 in the presence of time-varying time delay, dead zones, and faults in actuators. Faults in actuators, loss of effectiveness and bias, occur at T12 sec A02 and B A09. Regulated state X3 in the presence of time-varying time delay, dead zones, and faults in actuators. Faults in actuators, loss of effectiveness and bias, occur at T12 sec A02 and B A09. Estimation error E1x1x1 in the presence of time-varying time delay, dead zones, and faults in actuators. Faults in actuators, loss of effectiveness and bias, occur at T12 sec A02 and B A09. Estimation error E2x2x2 in the presence of time-varying time delay, dead zones, and faults in actuators. Faults in actuators, loss of effectiveness and bias, occur at T12 sec A02 and B A09. Figures 10.6, 10.7, and 10.8 show the actual states X1, X2, and X3 for both a 02 and a 09. Besides figs, 10.9, 10.1, and 10.11 depict the state estimation errors. It can be seen from figs 10.6, 10.7, 10.8, 10.9, 10.1, and 10.11 that the proposed controller can effectively bring all the states and the state estimation errors to zero in the presence of dead zones in actuators and time delay in states. Moreover, the presence of faults at T12 sec does not considerably affect the performance, which shows that the controller can effectively tolerate the faults. Estimation error E3x3x3 in the presence of time-varying time delay, dead zones, and faults in actuators. Faults in actuators, loss of effectiveness and bias, occur at T12 sec A02 and B A09. Control signals U1 and U2 in the presence of time-varying time delay, dead zones, and faults in actuators. Faults in actuators, loss of effectiveness and bias, occur at T12 sec A02 and B A09. 10.5 Conclusion. This chapter proposes an adaptive fault-tolerant observer-based stabilization method for a general class of uncertain nonlinear time delay multi-input multi-output MIMO systems in the presence of unmeasurable states, faults, and dead zones in actuators. The time delay can be time-varying, the dead zones can be asymmetric, and the faults can include loss of effectiveness and bias. To cope with unmeasurable states, a suitable observer has been proposed, and to cancel the effect of time-varying time delay, the synthesis approach has been utilized. The unknown continuous nonlinear functions in the model have been tackled using the universal approximation theorem for radial basis function neural networks, RBFNNs. The dead zones and the faults have been tackled by proposing suitable adaptive parameters and an adaptive robust term in the control signal. The adaptive laws have been designed based on the interval method and derived using the synthesis approach. It has been proved that all the closed-loop signals are bounded, and the state estimation errors and the actual states tend to zero asymptotically. The proposed method has been applied to the unified chaotic system with a 02 type and a 09 type in the presence of different faults and dead zones in actuators and time-varying time delay. In future work, the proposed method can be extended to relax some conditions in assumption 10.3, especially the equality constraint, and consider other input nonlinearities such as saturation and hysteresis. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder.
References.
1. Richard J.P., Time Delay Systems, an overview of some recent advances and open problems. 3910, 1667-1694, 2003 MathNet. 2. IC, a survey of recent advances in fractional order control for time delay systems. IEEE Access 7, 30951-30965, 2019. 3. VD&K, KV, Time Delay Systems, Recent Trends and Advancements. IFAC Papers Online 55-1, 292-97, 2022. 4. Tutorial on Based Methods for Time Delay Systems.
J. Control.
26, 271-283, 2014 MathNet. 5. Sun JQ, Song B, Analysis and Control of Deterministic and Stochastic Dynamical Systems with Time Delay. In Complex Systems, Time Delay and Synchronization. 119-203. Springer 2012. 6. W. Delays Effects in Dynamical Systems and Networks, Analysis and Control Interpretations. In Nonlinear Systems, Techniques for Dynamical Analysis and Control. 123-136. Springer 2017. 7. Sunt PM and PB, Age of Loop for Wireless Networked Control Systems Optimization. In 2021, IAIE 32nd Annual International Symposium on Personal, Indoor and Mobile Radio Communications, PIMRC. 1-7-2021. 8. Lee Z. Lay S. YJ. L. Event-Triggered Neural Control for Time-Varying Delay Switch Systems with Constraints Relate to Historical States Under Average Dwell Time.
IEEE Trans. Man.
54-3, 2024. 9. LC, Robust Stability and Performance of Time Delay Control Systems.
ISA Trans.
46-2, 233-237, 2007. 10. CL Guan X, Robust Control for Nonlinear Time Delay Systems. Springer 2018. 11. Yang R. F. Sun L. Jo P. B. Finite Time Adaptive Robust Control of Nonlinear Time Delay Uncertain Systems with Disturbance. J. Robust Nonlinear Control. 29-4, 919-934, 2019 MathNet. 12. CE M. D. An Enhanced Adaptive Time Delay Control-Based Integral Sliding Mode for Trajectory Tracking of Robot Manipulators.
IEEE Trans.
Control.
Technol.
31-3, 1042-1050, 2023. 13. J. S. Han S. Practical Time Delay Control with Adaptive Gains for Trajectory Tracking of Robot Manipulators.
IEEE Trans.
And Electron. 65-7, 5682-5692, 2018. 14. S. AM S. Dowling AP. Adaptive Control of a Class of Time Delay Systems.
J. Dine.
Control 125-2, 186-193, 2003. 15. JS, Control of Surgical Robots with Time Delay Using Model Predictive Control. Day Thesis, University of Ottawa, 2018. 16. S. A. Model Predictive Control for Transparent Teleoperation Under Communication Time Delay.
IEEE Trans.
Robot. 22-6, 11-30-11-145, 2006. 17HZ, Time Delay Prediction-Based Smith Predictive Control for Space Teleoperation.
J. Guida. Control. Dine.
44-4, 872-879, 2021 MathNet. 18B, EBIMM, Abstract Entity Patterns for Sensors and Actuators. Computers 12-5, 93, 2023. 19F Shan, Y Tang, Y, Actuator and Sensor Fault Detection and Isolation for Uncertain Switched Nonlinear System based on Sliding Mode Observers.
J. Control.
19-9, 3075-3086, 2021. 20 LZC, Adaptive Neural Network State Constrained Fault-Tolerant Control for a Class of Pure Feedback Systems with Actuator Faults. 490, 430, 1440, 2022. 21 YC VT, Adaptive Tracking Control of Robotic Manipulator Subjected to Actuator Saturation and Partial Loss of Effectiveness.
ISME. Dine. Control.
4 2024. 22Z Shen Y Model-Based Fault Diagnosis, Methods for State Space Systems. Springer 2023. 23 Ding SX, Advanced Methods for Fault Diagnosis and Fault-Tolerant Control. Springer 2021. 24 MMJM, Diagnosis and Fault-Tolerant Control. Springer 2016. 25 MZ XY Han R Yao JY, a finite-time H-infinite adaptive fault-tolerant controller considering time delay for flutter suppression of airfoil flutter.
Proc. Mecca. Part GJ.
234-2, 293-3, 2020. 26 HA, Adaptive Delay Dependent Sliding Mode Fault-Tolerant Controller Design for Nonlinear Systems with Unknown Time-Varying Input and State Delays.
J. Control.
69 100756, 2023 MathNet. 27 TW, Adaptive Fuzzy Decentralized Fault-Tolerant Control for Uncertain Nonlinear Large-Scale Systems with Unknown Time Delay.
IIT Control. Theory and
1018 2437 2446, 2016 MathNet. 28 Li YX Yang GH, Robust Adaptive Fault-Tolerant Control for a Class of Uncertain Nonlinear Time Delay Systems.
IEIE Trans. Man.
47-7, 1554-1563, 2017. 29 Tau G Lewis FL, Adaptive Control of Dynamic Systems. Springer 2001. 30 Yu Dong H, Disturbance Observer-Based Attitude Control under Input Nonlinearity.
Trans. Control.
4310, 2358, 2367, 2021. Sage Publications, Sage UK, London, England. 31 W Lee H X, L2 Gain Analysis and Fault-Tolerant Control for Uncertain Nonlinear Switch System with Actuator Saturation and Time-Varying Delay.
Asian J Control.
26-4, 2024. Online Library. 32 Yang Si Su S Z, Decentralized Model Reference Adaptive Control for Interconnected Systems with Time-Varying Delays and Unknown Dead Zone Inputs. J Robust Nonlinear Control. 34-6, 3679, 3696, 2024. Online Library. 33X CCP SU S, Adaptive Neural Dynamic Surface Control for Feedback Systems with Output Dead Zone.
IEIE Trans.
Neural.
Learn.
2911, 5200 5213, 2018.
IEIE.
34 Ma Z Ma H, Improved Adaptive Fuzzy Output Feedback Dynamic Surface Control of Nonlinear Systems with Unknown Dead Zone Output.
IEIE Trans.
Fuzzy. 29-8, 2122-131, 2021.
IEIE.
35 pan W, X lay, H, adaptive event-triggered output feedback control for large-scale nonlinear time delay systems with dead zone input. J control. 21-7, 2191-220-1-2023.
Springer.
36 UA, HY, lay, JM, adaptive fuzzy dynamic surface control for a class of perturbed nonlinear time-varying delay systems with unknown dead zone.
J.
95s 545 554, 2012.
Springer.
37 LPC, adaptive control of time delay nonlinear HOFA systems with unmodeled dynamics and unknown dead zone input. J robust nonlinear control. 33-4, 2615-262-8, 2023. Online libraries. 38KH, finite time adaptive fuzzy tracking control for high-order nonlinear time delay systems with dead zone.
IIT control. Theory and
1816, 2094-2107, 2024 MathNet. 39Z SMBO-C, prescribed performance adaptive fault-tolerant control approach for nonlinear large-scale systems with time delay interconnection and dead zone input. J robust nonlinear control. 32-1, 5282, 2022. Online libraries. 40 VM, design of disturbance observer based on adaptive neural control for large-scale time delay systems in the presence of actuator fault and unknown dead zone.
J adapt. Control. Signal process.
35-2, 285-309, 2021. Online libraries. 41J Ding B, one step ahead robust MPC for LPV model with bounded disturbance.
J control.
52, 59, 66, 2020 MathNet. 42Z AM, adaptive output feedback control with closed-loop reference models for very flexible aircraft.
J GUID. Control. Dyn.
39-4, 873-888, 2016. 43 HK nonlinear control.
2014.
44 HMLA, polynomial adaptive observer-based fault-tolerant control for time delay polynomial fuzzy systems subject to actuator faults.
J fuzzy.
25-4, 1327-1337, 2023.
Springer.
45 UY D Lee H Lee C Joe J, observer-based adaptive output feedback fault-tolerant control for nonlinear hydroturbine governing system with state delay.
Asian J control.
22-1, 192-203, 2020. Online libraries. 46D HLAM, adaptive fuzzy observer-based fault-tolerant control for descriptor nonlinear systems with time delay.
Circuits.
Signal process 37-4, 1542-1561, 2018. 47F, the complement and its applications.
4.
Springer Science and Business Media, 2006. 48J YALMIP, a toolbox for modeling and optimization in MATLAB. In 2004, IEEE International Conference on Robotics and Automation, IEEE CAT.
No.
284-289, 2004.
IEEE.
49 AM, on the universal approximation property of radial basis function neural networks.
Maths.
92 691 701, 2024.
Springer.
50 Park J IW, approximation and radial basis function networks.
Neural.
52 305 316, 1993.
MIT Press.
51 HK, adaptive output feedback control of nonlinear systems represented by input-output models.
IEEE Trans. Control.
41-2, 177-188, 1996.
IEEE.
52 HK Nonlinear Systems 3rd. Prentice Hall 2002. 53 JJ Lay W. Applied Nonlinear Control. Prentice Hall Cliffs NJ 1991. 54 Tau G. A Simple Alternative to the Lemma.
IEIE Trans.
Control. 42 5 698 1997.
IEIE.
55 Tang LJJ. Interlayer synchronization on a two-layer network of unified chaotic systems. The role of network nodal dynamics. Chaos solitons fractals 174, 113,887, 2023. 56 YJ YQ. Adaptive robust fuzzy control for a class of uncertain chaotic systems. Nonlinear dynes. 57 3, 431 439, 2009.
Springer.
11. Nonlinear fault-tolerant tracking control for DC-DC boost converters with measurement faults.
Abstract.
Power converters aim to provide power suitable for loads, which can widely be found in our daily life and industrial systems. DC-DC boost converters can achieve a higher voltage on the load compared with the supply voltage, and a closed-loop controller is used to track desired inductor current and capacitor voltage. Due to age or unanticipated reasons, measurements via sensors could be faulty or distorted. The faulty measurements are sent to the controller, which may cause incorrect control commands, leading to distorted trigger signals, so that the inductor current and capacitor voltage depart from the desired values. As a result, there is a strong motivation to design a fault-tolerant tracking controller for the boost converter to achieve a fault-tolerant performance under faulty sensor situations. In this chapter, fundamentals of boost converters, including modeling and nonlinear tracking controllers, are firstly reviewed. A nonlinear current observer is then presented to achieve a simultaneous estimate of system states and current sensor faults, from which a real-time monitoring and fault diagnosis is attained. By using current sensor signal compensation, a fault-tolerant current tracking nonlinear controller is designed, and the passivity of the closed-loop boost converter system is proved. Nonlinear fault-tolerant voltage tracking control approach is next addressed under faulty measurement of the capacitor voltage, using real-time voltage sensor fault estimation and sensor compensation under nonlinear control scheme. For the scenario considering faulty measurements for both voltage and current sensors, a nonlinear dual fault-tolerant control strategy is proposed by using estimates of both voltage and current sensor faults, dual compensation and dual tracking under nonlinear dynamic control. The proposed nonlinear fault-tolerant control algorithms for boost converters are well demonstrated by simulation studies. 11.1 Introduction. Power electronics is the application of electronic circuits to energy conversion, which converts electric energy of the supply into a voltage or current with suitable frequency and amplitude for the load 1-3. Power electronics converts around 70% of electric energy to consumers, which plays a critical role in the development of energy conversion nowadays, particularly for clean energy systems 4-8, including electric vehicles 9, photovoltaics 10, and wind turbines 11, and so forth. Power converters are categorized into 4 types of converters, including AC-DC, AC-AC, DC-AC, and DC-DC converters. AC-DC converters convert AC powers to DC powers, which are called rectifiers. AC-AC converters convert AC powers to AC powers with different amplitudes or frequencies. DC-AC converters are also called inverters, which convert DC powers to AC powers. DC-DC converters can step up voltages, called boost converters, step down voltages, called buck converters, either boost voltages or reduce voltages relying on the operation range of the duty cycle values, called buck-boost converters. All these converters can find various applications in industrial systems. DC-DC power converters play a crucial part in modern industrial systems and our daily life, and fruit results were reported on modeling and control of DC-DC power converters during the last 4 decades. Modeling of power converters using average model and small signal model was investigated well in 12-13. As for control design, there were many results reported from the conventional proportional and integral pi control 14, 15, to fuzzy control 16, 17, sliding mode control 18, 19, model predictive control MPC 2021, and nonlinear control 22, 23. Due to age and unexpected situations, components in power converters may be faulty. Sensors are crucial components for power converters, as their malfunctions may produce distorted measurement signals sending to the controller so that an incorrect command is generated for the PWM block, leading to an incorrect trigger signal. The wrong trigger signal causes the power converter to misshape outputs such as capacitor voltage and inductor current. As a result, it is motivated to develop an effective real-time monitoring, diagnosis, and tolerant control scheme to improve the reliability and performance of DC-DC power converters. There were some results reported on diagnosis and tolerant control for DC-DC power converters. In 24, a sensor fault detection approach was presented by using extended filters for DC-DC power converters in hybrid electric vehicles. A fault detection algorithm was addressed in 25 for DC-DC power converters subjected to faulty sensors by using adaptive parameter identification. In 26, 27, fault-tolerant schemes were illustrated by using switching strategies for DC-DC power converters with sensor fault. It is observed that fault detection methods in 24, 25 were based on the generated residual, which can detect a sensor fault but cannot isolate and identify the sensor fault in a power converter. The fault-tolerant schemes in 26, 27 used switching strategies, which could cause system performance deterioration during the switching reconfiguration. As a result, there is a strong motivation to develop a new diagnosis and tolerant control algorithm for DC-DC power converters. Descriptor observer approach for fault estimation and fault-tolerant design schemes using sensor signal compensation were initiated in 2000's 2830, which provided a powerful tool to solve real-time sensor fault reconstruction and fault-tolerant control for industrial systems. Motivated by 2830, real-time fault estimation and fault-tolerant control for DC-DC boost converters subjected to sensor abnormalities are investigated in this chapter. The organization of this chapter is as follows. Followed by the introduction, fundamentals of boost converters are introduced in Sect. 11.2. Current sensor fault estimation and nonlinear fault-tolerant current tracking control are presented in Sect. 11.3. Voltage sensor fault estimation and nonlinear fault-tolerant voltage tracking control scheme are addressed in Sect. 11.4. Nonlinear fault-tolerant dual tracking control schemes are analyzed in Sect. 11.5. The entire chapter is ended by the summary in Sect. 11.6. It is worthy to point out that voltage sensor fault estimation and diagnosis were presented in the online conference 31, but Sect. 11.4 is a totally rewritten version with updated simulated results. Moreover, the contents in Sects 11.3 and 11.5 are the very first time to be addressed in this chapter. 11.2 Preliminaries of DC-DC boost converters. 11.2.1 Modeling for DC-DC boost converter. Circuit scheme of DC-DC boost converter. Curves of 11K and 11K2 via duty cycle K1122 Model validation of DC-DC boost converter. Parameters of the boost converter. Inductor L36mH capacitor C045mF load resistor R100 switching frequency F100 kHz. Voltage drop of power switch. 0.6 V voltage drop of diode. 0.7 V model validation, circuit and average state space model. Steady value comparison of two models. Measurements. Inductor current. Capacitor voltage. Circuit 1.529 A5906 V average model. 1.5 A60 V relative error. 1.9%. 1.6%. 1123 Nonlinear control for DC-DC boost converter. Voltage tracking control for boost converter. Inductor current and capacitor voltage. Voltage tracking control with 60V current tracking control for boost converter. Inductor current and capacitor voltage. Current tracking control, 15A inductor current and capacitor voltage. Current tracking control with 155A 11.3 nonlinear fault-tolerant current tracking control for boost converter. 11.3.1 Motivation. Current sensor fault signal and inductor current measurement. Inductor current and capacitor voltage, current tracking control under sensor fault. 11.3.2 Current sensor fault reconstruction. For the boost converter R2 and 1K to 1K. However, the presented observer 11.14 can be applied to any nonlinear system models with R2, provided that I11 and 0. Signal reconstruction, current tracking control under current sensor fault. 11.3.3 Fault-tolerant tracking control against current sensor fault. Schematic block diagram of fault-tolerant current tracking control. It is time to discuss the passivity of the boost converter described by 11.34 1137. For a system with passivity, the storage function at a future time t is equal or less than the summation of the storage function at the initial time 0, and the supplied energy from the external source during the interval 0t, which means no energy created internally. Without external inputs, the passivity reduces to the stability 22. The fault-tolerant current tracking boost converter described by 11.34 1137 is passive. Fault-tolerant current tracking control against current sensor fault. 11.4 Nonlinear fault-tolerant voltage tracking control for boost converter. 11.4 method and design. Schematic block diagram of fault-tolerant voltage tracking control. The fault-tolerant voltage tracking boost converter described by 11.34, 11.35, 11.45, and 11.46 is passive. Using the similar proof method of theorem 11.2, one can obtain the proof, which is omitted here. More details can be found in 31. 11.4.2 Validation via simulation. Fault-tolerant voltage tracking control against voltage sensor fault, signals and their estimates. Fault-tolerant voltage tracking control against voltage sensor fault, voltage signals. 11.5 Nonlinear fault-tolerant dual tracking control for boost converter. 11.5 method and design. Schematic block diagram of fault-tolerant dual tracking control. The fault-tolerant dual tracking boost converter described by 11.57 1162 is passive. 11.52 Validation via simulation. Fault-tolerant dual tracking control, states and their estimates. Fault-tolerant dual tracking control, sensor faults and their estimates. Fault-tolerant dual tracking control, states and their estimates with references updating. Fault-tolerant dual tracking control, sensor faults and their estimates with reference changes. 11.6 Conclusion. In this chapter, the fundamentals of the average model and nonlinear tracking controller for DC-DC boost converters have been introduced, which could provide the beginners, such as senior undergraduate students and M students, a chance to get insight into alternative controllers for boost converters except for conventional pi controllers. Current sensor fault estimation and nonlinear current tracking fault-tolerant controller have been presented with rigorous mathematical proofs and detailed simulation studies. Voltage sensor fault reconstruction and nonlinear fault-tolerant voltage tracking control have also been briefly addressed. For the scenario with multiple sensor faults, a nonlinear descriptor observer has been used to estimate both voltage and current sensor faults. A nonlinear fault-tolerant dual tracking controller has been designed to achieve desired voltage and current tracking. The effectiveness of the proposed real-time sensor fault estimation and fault-tolerant control algorithms have been well demonstrated. It is hoped that the proposed control algorithms could bring a bit light to promote the reliability and performance in DC-DC power converters. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder.
References:
1NTW Power Electronics, Converters, Applications, and Design.
2003.
2RD, Fundamentals of Power Electronics. Springer 2001. 3AR, Voltage-Sourced Converters in Power Systems, Modeling, Control, and Applications.
IEEE Press 2010.
4G Lazy BW, Power Electronics Converters, Past, Present, and Future.
Renew, Sustain,
Energy Rev. 81 2028 2044 2018. 5M, Electric Renewable Energy Systems.
2016.
6TTJ, Power Electronic Converters, Dynamics and Control in Conventional and Renewable Energy Applications.
2017.
7AMH, Power Electronic Converters and their Control for Renewable Energy Applications.
2023.
8SMS, Power Converters, Drive and Controls for Sustainable Operations.
2023.
9PSM, the state-of-the-art of power electronics converters configurations in electric vehicle technologies.
Power
11001, 2022. 10MDS, Power Electronics for Photovoltaic Power Systems.
Springer 2015.
11FML, Power Electronics in Wind Generation Systems.
Rev
234 250, 2024. 12WPR, State Space Average Modeling of Converters with Parasitics and Storage Time Modulation. In IEEE Power Electronics Specialists Conference. 119-143, Atlanta, GA, USA 1980. 13 Does H. Lee Z. Lay S. Dong W. Small Signal Modeling, Control and Experimentation of Boost Converter including Parasitic Elements.
J. Control
32 956 967, 2021. 14M R. H. DC-DC Boost Converter Controller Design for PV Applications. In IEGCC Conference and Exhibition, Manama, Bahrain 2017. 15 Martinez M. J. He W. A robust nonlinear pi-type controller for the DC-DC buck boost power converter.
ISA Trans
129 687 700, 2022. 16 Gupta T. R. R. J. Implementation of a fuzzy controller for DC-DC converters using an inexpensive 8B.
IEEE Trans
Power 127986, 1997. 17 S Park J. Y. H. Fuzzy pi-type controller design for boost converter.
J.
141 143 156, 2017. 18 Tan SYC. A unified approach to the design of PWM-based sliding mode voltage controllers for basic DC-DC converters in continuous conduction mode.
IEEE Trans
Circuits I-53, 1816-1827 2006. 19 H. Arsley Y. Al. Fast terminal sliding mode control of DC boost converters with enhanced disturbance rejection.
IEEE J. Emerge Top Power
12 530 1542, 2024. 20 AG H. Al-Haddad, K. Model predictive control design for DC-DC converters applied to a photovoltaic system.
J.
Power energy. 103, 537, 544, 2018. 21 Wise Y Luo W. Model predictive control of double input buck converters.
J. Power.
21 941 950, 2021. 22 G. A new nonlinear dynamic output voltage controller for power DC-DC boost converters. In Proceedings of the 7th Mediterranean Conference and Exhibition on Power Generation, Transmission, Distribution and Energy Conversion, Napa 2010. 23 AI HTRM, Nonlinear Voltage Mode Control of PWM DC-DC buck converter.
IEIE Trans. Energy.
36 430 1440, 2021. 24 Al-Sheikh HGNN, a sensor fault diagnosis scheme for a DC-DC converter used in hybrid electric vehicles. IFAC Papers Online 4821, 713 719, 2015. 25 Q Z Su J Lei C Lei J, fault detection for DC-DC converters using adaptive parameter identification.
J.
35911, 5778 5797, 2022 MathNet. 26 Y Song Z J X, fault diagnosis and fault tolerant control for the sensors of DC-DC boost converter. In Proceedings of the 37th Chinese Control Conference. 7594 7599, Wuhan 2018. 27 SB, a novel fault-tolerant control scheme for power converter. In Proceedings of the IEEE International Power and Renewable Energy Conference, 2020. 28 ZH, Descriptor Observer Approaches for Multivariable Systems with Measurement Noises and Application in Fault Detection and Diagnosis.
Land. Control.
55-4, 304-313, 2006 MathNet. 29 ZX Ding S, Fuzzy State Disturbance Observer Design for TS Fuzzy Systems with application to sensor fault estimation.
IEIE Trans. Man.
Part B Cybernetics 38-3, 875-880, 2008. 30 Z Ding S, Sensor Fault Reconstruction and Sensor Compensation for a class of nonlinear state space systems via descriptor system approach. IIT Control Theory, and 13-578-585, 2007. 31 ZPA, Sensor Fault Estimator and Fault Tolerant Controller for Boost Converter. In IEEE First Industrial Electronics Society Annual Online Conference, ONCON, 2022. 32 RAPH, Passivity-Based Control of Systems. Springer, 1998. 33 L2 Gain and Passivity Techniques in Nonlinear Control. Springer, 2000. 34 HRGN, a robustly output feedback saturated controller for the boost DC-to-DC converter.
Land. Control.
4018 2000 MathNet. 12. Distributed fault-tolerant consensus tracking for nonlinear MASs with unmatched inputs.
Abstract.
This research delves into the problem of distributed adaptive failure compensation output feedback consensus for nonlinear multi-agent systems, MASs, specifically focusing on scenarios with multiple actuator failures that may exhibit unmatched redundancy and directed switching communication graph. By leveraging estimates derived from neighboring agents, we design a novel distributed reference generator. To tackle the challenge of unmeasured state variables within each agent, we devise a reduced-order dynamic gain filter. Leveraging this generator and filter, alongside a recursive design approach, we construct a distributed adaptive protocol. This protocol employs adaptive techniques to effectively compensate for actuator failures, significantly loosening constraints on the communication graph, which can momentarily disconnect at any point in time instant. Furthermore, our approach reduces the number of introduced variables and the filter's dimensionality, thereby mitigating numerical complexities. This work represents a pioneering effort in addressing output feedback consensus for nonlinear MASs, accounting for actuator failures and the possibility of unmatched actuator redundancy. Notably, the consensus error can converge to an arbitrarily small set, uninfluenced by actuator failures, ensuring global stability of the closed-loop system. Finally, simulation results verify the effectiveness of the proposed method. 12.1 Introduction. Over the past few decades, the problem of distributed leader-following consensus in multi-agent systems, MASs, has garnered immense interest among researchers, driven by its promising applications in vast robotic networks and biological systems, as in 1.4 and their respective citations. The aspiration is for all agents' trajectories to seamlessly align with a predefined trajectory orchestrated by a control node or a virtual leader, solely relying on information exchanged with neighboring agents through the network. The central challenge lies in the fact that not every agent has direct access to the leader's trajectory signal. To surmount this obstacle and achieve leader-following consensus, numerous existing studies have often presupposed the existence of a directed path extending from the leader agent to each follower within a fixed communication topology, forming a spanning tree rooted at the leader, as demonstrated in works ranging from 5.11. These studies have developed both state feedback and output feedback consensus protocols for nonlinear MASs, offering effective solutions to this problem. Practical systems often grapple with unreliable communication sensing, narrow communication channel bandwidths, and constrained communication sensing ranges, as discussed in 12. These factors can trigger topology failures or reconstructions among agents, jeopardizing the stability of multi-agent systems, MASs. In response, researchers in 13 through 15 delved into leader-following consensus for both linear and nonlinear MASs under dynamic topologies that switch, ensuring a spanning tree rooted at the leader persists at all times. Meanwhile, 16 focused on devising strategies for generating, motion planning, and managing switching topologies for persistent formations in persistent MAS formations, using distance-guided leader-follower relationships. In 1720, an alternative approach was explored, considering undirected communication topologies that, while possibly disconnected momentarily, maintain joint connectivity over time. Extending this, studies in 2123 investigate directed jointly connected topologies with serving as the leader, capable of producing a diverse range of signals. However, these studies either focused on linear MASs 21 or constrained the order of followers and the leader to be identical, with nonlinearities confined to the final dynamic layer 22-23. Thus, a pressing challenge remains: investigating leader-following consensus for heterogeneous, high-order nonlinear MASs tasked with tracking general-shaped trajectories under directed switching networks with minimal restrictions. This gap in knowledge motivates the present work. Additionally, actuator malfunctions introduce extra system uncertainties, necessitating enhanced reliability in closed-loop systems. Consequently, fault-tolerant control has garnered significant attention from researchers, as evident in 24, 25, and related works. Prior studies such as 24-27 explored partial actuator ineffectiveness and bias faults in nonlinear systems and MASs, but these systems lacked redundant actuators, a common design feature in modern control systems, limiting their ability to address complete actuator loss. For systems with multiple actuators, 28 investigated adaptive compensation for parametric nonlinear systems with actuator failures. In 29, adaptive asymptotic control was developed for nonlinear MASs with unknown actuator faults and control directions. Works in 3033 delved into state and output feedback consensus control for high-order nonlinear MASs, yet these systems assumed matched actuator redundancy. A recent study 34 extended state feedback control to nonlinear systems with unmatched actuator redundancy and disturbances, focusing solely on stuck actuator faults. However, the design of an output feedback strategy to stabilize nonlinear systems with unmatched actuator redundancy and failures remains underexplored, serving as a second driving force behind this chapter's research. Drawing from the aforementioned foundations, This chapter introduces a distributed adaptive output feedback consensus scheme for a class of high-order nonlinear MASs, incorporating unmatched actuator redundancy and potential failures. Our approach distinguishes itself from prior works in several key aspects. 1. We devise an innovative distributed reference generator that exponentially tracks the leader's trajectory, even under directed switching graphs where disconnections are permissible at any instant. This generator expands the applicability of existing MAS frameworks in 7, 8, 19 by relaxing their communication topology constraints. 2. We present a reduced-order dynamic gain filter, significantly reducing the number of dynamic variables compared to those in 10, 11, 32, 33, 35, effectively compensating for unmeasured states. 3. Leveraging solely neighbor estimation information, we formulate a distributed adaptive failure compensation protocol that ensures the output consensus error converges to an arbitrarily small set, unaffected by actuator failures. Notably, the considered MASs cover a wide range of practical scenarios, including actuator failures, possible unmatched actuator redundancy, and general nonlinearities, which, to our knowledge, have not been fully addressed by existing methodologies. Notations: in this work, we utilize P and P to signify the smallest and largest eigenvalues, respectively, of the matrix P, denotes the Euclidean norm of vector. A denotes the induced norm of matrix A by the Euclidean norm. A matrix A11, A1n, and 1 can be written as AI S1n. For clarity and without ambiguity, the component of a vector X is denoted simply as xi. 12.2 Preliminaries. 12.2 Graph theory. The interconnection of agents within the communication network can be visualized through a directed graph G, comprising a set of nodes or agents I0, 1, n, and a set of edges. Node 0, designated as the lighter, serves as the root. An edge connecting to n is denoted. We introduce the adjacency matrix ARnn plus 1 with elements, where 0 indicates the existence of and 0 otherwise. A sequence of connected edges, 1, 2, 2, 3, plus 1, forms a path from 1 to plus 1, enabling reachability from 1 to plus 1. A directed spanning tree rooted at node 0 is a specific directed graph configuration where every node is reachable from the root, node 0. Assuming a constant switching signal t, we define a time-varying directed graph GTT with edge set t. Correspondingly, we have a switching adjacency matrix ATTI10n, as detailed in references 21, 22. 12.2.2 Problem formulation. Equation 12.2 serves as a comprehensive representation of actuator failures. It encapsulates various scenarios, including the absence of failure when 1. Partial loss of effectiveness, PLOE, characterized by a constant within the range 0-1, total loss of effectiveness, TLOE, when 0. Bias fault signified by a non-zero U, and the lock-in-place condition where U remains constant. For all J1, in 12.1, the relative degree associated with each triplet CI may vary, indicating that the control inputs for J1 may manifest in diverse dynamic pathways, leading to unmatched actuator redundancy and potential unmatched failures, as discussed in 34. To our current knowledge, the challenge of addressing the output feedback stabilization problem for 12.1 has yet to be tackled. Furthermore, numerous practical systems can be accurately represented or encompassed within the framework of 12.1. For example, the single-link robotic arm as described in 25.31, the parallel active suspension system, page 38 of 35, the pendulum dynamics studied in 37. The aims of this chapter are twofold. 1. To develop distributed reference generators for each follower, enabling the trajectory Y0t to be exponentially tracked under switching communication topologies. 2. To devise estimation filters that compensate for unobservable state variables. 3. To formulate an adaptive output feedback control strategy, ensuring that the distributed leader-follower consensus is achieved despite actuator failures, while maintaining the semi-global bounded stability of the MASs. In order to achieve the stated objectives, the subsequent assumptions and lemmas are utilized. There exists a subsequence of I01, with tick plus 1 tick for some positives such that the union graph J plus 1 1G contains a directed spanning tree with node as the root. Under assumption 12.1, the connectivity requirement does not mandate the presence of a spanning tree rooted at the leader at every instant in time. Furthermore, it does not impose an undirected nature on the graph. Rather, it accommodates graphs that are directed and potentially disconnected at any given time instant. Assumption 12.2 imposes a condition on the inherent characteristics of the system, specifically related to the functions s plus m and s for m plus 1, s plus, and s1. This assumption naturally extends the conditions outlined in 35 p 327 for the design of K-filters. Specifically, if s plus m0 and the polynomial plus plus 1s plus 0 with constant 0 is, then assumption 12.2 is automatically satisfied. For the uncertain function's vector fit, xi, there exists a known positive smooth function f such that fit, xi f. At any given time, there exists at least one actuator that is not subject to total loss of effectiveness, TLOE failure. The total number of actuator failures is limited, meaning there exists a specific time instant t, final, which marks the conclusion of all failures in the follower. The proof can be found in the appendix. For any continuous function fy, rr, and bounded reference signal y, there exists smooth function y, and bounded constant such that fyyyy plus the detailed proof has been located in the appendix. 12.3 Main results. This section presents the development of a distributed leader-follower consensus protocol tailored for the MAS described in 12.1, which contains 3 parts: distributed reference generator design, filters design, and controller design. The formulated generator solely relies on the information exchanged with neighboring agents under the dynamic switching network topology. For the agent, the devised filters employ only the output data y and control inputs to compensate for unobservable states. Leveraging the constructed generator and filters, a distributed controller is designed to fulfill the prescribed objectives. 12.3.1 Distributed Reference Generator Design. Given assumption 12.1 and the additional assumption that the magnitude of the nth derivative of t, with respect to time, denoted as t, is bounded for any positive integer n, the output yi produced by the designed reference generator 12.4 is capable of exponentially tracking the desired trajectory y0, while is able to exponentially estimate the value of. Pursuant to Theorem 12.1, the output yi is capable of estimating y0 for a broad range of trajectory shapes, encompassing constant, time-varying, and even unbounded signals such as ramp signals. Notably, only the first derivative jt is utilized in constructing the generator and is accessible to all agents, indicating that the initial conditions of the basis functions do not exert any influence on the proposed methodology. Leveraging this design generator, several constraints can be alleviated, enabling the system to function with directed switching graphs that do not necessarily possess a spanning tree at any instant. Moreover, the state dimensions of the heterogeneous agents can vary, accommodating systems such as single integrator, double integrator, chained MASs, nonlinear MASs explored in 7, 8, 19, and stochastic MASs studied in 11. It is important to emphasize that when adopting the method to devise control schemes for high-order MASs based on 12.4, by leveraging Young's inequality, terms involving Tj1 and Ty1y0 can be decoupled from the virtual controllers. This ensures the smoothness of the virtual controllers and the distributed nature of the control strategy in subsequent steps of the recursive design process. The exponential convergence property of these terms facilitates a seamless extension of the methodology. Distinct from prior works like 22, 23, T, can be freely chosen to exhibit arbitrary time-varying behaviors, allowing for y0 to encompass a wider range of signal combinations. 12.3.2 Output Feedback Consensus Controller Design. For the purpose of designing the filter and controller in this section, we consider a sequence of time intervals denoted by tick t k plus 1 for k012 with t00. Here t1, t2 are defined as the specific time points at which the vector by t by 1 undergoes changes, signifying the occurrence of either total loss of effectiveness, TLOE, or partial loss of effectiveness, PLOE, in certain actuators. The subsequent design steps apply within each of these intervals tick tk plus 1.
In Sect
12.3.3, we will delve deeper into evaluating the effectiveness of the proposed approach over the entire time span 0 plus. To ensure output consensus for the MASs in 12.1, an additional assumption regarding the desired trajectory y0t of the leader is introduced in this work. For J1, Q, the basis function and its derivative are bounded. Under assumption 12.6, it is inferred that the desired trajectory y0t is bounded, aligning with a commonly adopted requirement for the desired trajectory in prior studies like 6.8.19. This boundedness serves as a fundamental prerequisite for ensuring that all state variables within the closed-loop MASs remain bounded as well. Dynamic gain filter design. From 12.21 to stabilize the error system, 12.12, the controller design in the next section needs to be integrated. In 12.9, the factor Li-Ui is incorporated for establishing the state estimation process. This adjustment enables a reduction in filter order while ensuring adherence that the inequality, 12.19, holds. If 0, then Li can be set as 1, and 12.7 can be considered an elaboration upon the filter, as detailed in 35 p. 327. To explicitly demonstrate the parameter selection process within 12.7.12.8, the design procedures are given as follows. 1. Using LMI toolbox in MATLAB, solve pi AIIT plus AII1 to get pi, and from 1 pi plus pi to 1 further get 1 2. 2 from 12.18, obtain 1 y, and from 1 plus 1 you get 3 from 12.19, get 3 and 0. 4. Based on 1 to 3.12, specify consensus controller design. In the initial step, the barrier function, 12.23, serves to counteract the detrimental influence of switchings by t on the difference UII, ensuring optimal transient performance. During each subsequent step, Young's inequality is employed to disentangle yi from the virtual controller, preserving its continuity and smoothness, a crucial aspect for the successful formulation of the final control algorithms. 12.3.3 Stability and Convergence Analysis. In this section, we will delve into the leader-following consensus and stability analysis of the MAS 12.1, adhering to the outlined assumptions and utilizing the designed controllers. The primary findings are subsequently presented in the form of the following theorem. Consider the nonlinear multi-input, single-output MAS 12.1 with actuator failures under directed switching graphs. Suppose assumptions 12.1, 12.5, and 12.6 hold, then the distributed adaptive controller 12.39, together with the reduced order filter 12.7 and adaptive law 12.28, can guarantee that the consensus tracking error UI0 converges to any arbitrary small set, and all the other state variables are bounded. Besides, the transient performance of UI0 will not be affected by actuator failures. At the instance TT1 where either TLOE or PLOE occurs, there is a shift in by T, causing jumps in the functions and V. Given that the variation in by T is finite and all variables were bounded immediately prior to T1, the difference between the sums of and V before and after T1 is also finite. Consequently, the sum of these functions after T1 remains bounded. Since the functions 1 plus J12 are unaffected by changes in by T, ensuring their continuity at T1, the overall function T1 plus remains bounded. Furthermore, the condition holds true. Extending this analysis to the interval T1, T2, in a similar manner as for T0, T1, we conclude that all state variables remain bounded within this interval, with the condition I1, T1, T, I2, T preserved. Incorporating assumption 12.5, we ascertain that all state variables remain bounded, and the aforementioned condition holds true for all time T0 plus. In the literature 5.6, parameterized function have been employed to mimic unknown nonlinear functions that arise during the controller design process. Comparable intelligent control methodologies can also be found in 26.38.40, which offer valuable tools for managing uncertainties in nonlinear systems. If the function Fi in assumption 12.3 remains unknown, by integrating these function approximation techniques, it is still possible to attain tracking consensus using the proposed approach. 12.4 Simulations. Communication topologies of the MASs. Switching signal on graphs. Estimate error of generators. Outputs of the MASs. Responses of the states. Responses of the dynamic gains. Output of the actuator in Agent 1. Outputs of the actuators in Agent 2. Outputs of the actuators in Agent 3. Outputs of the actuators in Agent 4. 12.5 Conclusion. This chapter delved into the distributed adaptive consensus problem for nonlinear MASs subject to actuator failures and potential unmatched actuator redundancy, operating under switching communication graphs. A novel distributed reference generator is devised to estimate the leader's trajectory, thereby relaxing the constraints on the graph's connectivity. A reduced-order dynamic gain filter is implemented to compensate for unmeasured states, significantly minimizing the number of introduced variables and alleviating numerical challenges. Subsequently, leveraging the approach, a distributed adaptive control protocol is formulated. This work marks the first attempt to address the output feedback consensus for nonlinear MASs with actuator failures and possible unmatched actuator redundancy. Notably, the consensus error can converge to an arbitrarily small set, unaffected by actuator failures. However, the use of the technique in controller design poses a complexity challenge due to the repeated differentiations of virtual controllers. As future work, we aim to explore linear-like controller designs utilizing dynamic gain methods to reduce computational complexity, inspired by 9. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S, and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder.
Appendix.
Proof of Lemma 12.1. Proof of the Lemma 12.2. Based on 41 Lemma 12.1, there exist smooth functions f1yy0 and f2y0 such that fyy plus y f1yy plus f2y. Since f1yy f10 vanishes at yy0 by the mean value theorem, there exists smooth function y such that f1yy f10 yy hence fyyyy plus f2y plus f10. Since y is bounded, the result of Lemma 12.2 can be obtained.
The proof is completed. References.
1 Murray R. Recent Research in Cooperative Control of Systems.
ASME J. Dine.
Control 129.5, 571-583, 2007. 2C v. Trajectory Design for Formations of Robots by Kinetic Energy Shaping, in Proceedings of the 2002 IEEE International Conference on Robotics and Automation. 2593-2598, 2002. 3 Saber R. Flocking for Multi-Agent Dynamic Systems, Algorithms and Theory.
IEEE Trans.
Control 51.3, 401-420, 2006 MathNet. 4 Ren WC. Distributed Coordination of Multi-Agent Networks, Emergent Problems, Models, and Issues. Springer, London, 2011. 5 Does A. Lewis, F.L. Cooperative Adaptive Control for Synchronization of Second-Order Systems with Unknown Nonlinearities.
J. Robust.
Control 2113, 1509-1524, 2011 MathNet. 6 SJ. Distributed Consensus Tracking of a Class of Asynchronously Switched Nonlinear Multi-Agent Systems. 87 421-427, 2018 MathNet. 7 W. J. Wen C. Fan, H. Distributed Adaptive Control for Consensus Tracking with Application to Formation Control of Mobile Robots. 50 1254-1263, 2014 MathNet. 8 Jin X, Adaptive Iterative Learning Control for High-Order Nonlinear Multi-Agent Systems Consensus Tracking.
Land Control
89-1623, 2016 MathNet. 9XLG, Leader-Follower Consensus of Time-Varying Nonlinear Multi-Agent Systems. 52-814, 2015 MathNet. 10W1C, J. Lee Z, Hierarchical Decomposition-Based Consensus Tracking for Uncertain Interconnected Systems via Distributed Adaptive Output Feedback Control.
IEIE Trans.
Control 617, 1930-81945, 2016 MathNet. 11 Lee Y. C. Guan X, Distributed Output Feedback Adaptive Fuzzy Leader Following Consensus of Stochastic Nonlinear Interconnected Systems.
IEIE Trans. Man.
2020. Org 101109, TSMC 20203002331. 12 Y Ren W. M. Distributed Containment Control with Multiple Stationary or Dynamic Leaders in Fixed and Switching Directed Networks. 48-1586-1597, 2012 MathNet. 13 W. Zhou C. J. Xiang Z. Global Adaptive Leader Following Consensus for Second-Order Nonlinear Systems with Switching Topologies.
IEIE Trans.
Circuits. II Express Briefs 2020. Org 101109 TCSI 20203-009291. 14 P when G, X, W, Y, Consensus Disturbance Rejection for Linear Systems with Directed Switching Communication Topologies.
IEIE Trans.
Control 71-254-265, 2020 MathNet. 15 X Yang G, Fault-Tolerant Consensus Tracking Control for Linear Systems under Switching Directed Network.
IEIE Trans.
55-1921-1930, 2020. 16 D Philip CLP, Automatic Leader Follower Persistent Formation Generation with Minimum Agent Movement in Various Switching Topologies.
IEIE Trans.
54-1569-1581, 2020. 17 H Z R, Consensus of In-Switching Networks Using Input-to-State Stability of Switch Systems.
IEIE Trans.
Control 6311, 39-643971, 2018 MathNet. 18 B X Lay Z, Event-Triggered Consensus of Homogeneous and Heterogeneous Systems with Jointly Connected Switching Topologies.
IEIE Trans.
4912-4421-4430, 2019 MathNet. 19 H X, Adaptive Consensus of Multi-Agents in Networks with Jointly Connected Topologies. 48-1783-1790, 2012 MathNet. 20 W D, Leader Following Consensus of Multi-Agent Systems under Fixed and Switching Topologies.
Land
Control 59-209-217, 2010 MathNet. 21 Y J, Cooperative Output Regulation with Application to Multi-Agent Consensus under Switching Network.
IEIE Trans.
Man Part B 42-3-864-875, 2012. 22 W J, Adaptive Leader Following Consensus for a class of higher-order nonlinear multi-agent systems with directed switching networks. 79-8492, 2017 MathNet. 23 Y Yang G, Prescribed Performance-Based Consensus of Nonlinear Systems with Unknown Control Directions and Switching Networks.
IEIE Trans.
Man 52-609-616, 2020. 24 Ma H Yang G, Adaptive Fault-Tolerant Control of Cooperative Heterogeneous Systems with Actuator Faults and Unreliable Interconnections.
IEIE Trans.
Control 6111, 32-43-255, 2016 MathNet. 25 G Song Y Lewis FL, distributed fault-tolerant control of networked uncertain systems under actuator faults.
IEIE trans.
47-7, 1706-1718, 26 L. Y. Tong S. Neural networks-based adaptive finite-time fault-tolerant control for a class of strict feedback switched nonlinear systems.
IEIE trans.
49-7, 2536-2545, 2019. 27 R. Ma J. Lee D. SS. Finite-time adaptive output feedback control for MIMO nonlinear systems with actuator faults and saturations.
IEIE trans.
Fuzzy. 2020. Org 101109 TF uses E202029967009. 28 W Wen C. Adaptive actuator failure compensation control of uncertain nonlinear systems with guaranteed transient performance. 46 2082 2091 2010 MathNet. 29 K. C. Lewis FL S. Adaptive compensation for nonlinear time-varying systems with actuator failures and unknown control directions.
IEIE trans.
49-5, 1781-790, 2019. 30 J. C. Su Y. Distributed adaptive output consensus tracking for high-order nonlinear time-varying multi-agent systems with output constraints and actuator faults.
J. Franklin.
357, 1091-117, 2020 MathNet. 31 Lee Y. C. X. Lee L. G. Neural network-based distributed adaptive asymptotically consensus tracking control for nonlinear systems with input quantization and actuator faults. 349, 6476, 2019. 32 C. Wen C. Y. Adaptive actuator failure compensation for a class of nonlinear systems with unknown control direction.
IEIE trans.
Control 62-1, 385-392, 2017 MathNet. 33 Su L. Ma H. Distributed output feedback cooperative tracking control of nonlinear multi-agent systems with unknown actuator failures.
IIT control theory and
2019. Org 10104920186207. 34 K. B. X. Mao Z. MM. Fault-tolerant control for systems with unmatched actuator faults and disturbances.
IEIE trans.
Control 2020. Org 101109 TAC 2020299737. 35 M. I. PV. Nonlinear and Adaptive Control Design. New York, 1995. 36 H. M. Wen J.T. Adaptive Motion Coordination, using relative velocity feedback to track a reference velocity. 45-4, 1021-025, 2009 MathNet. 37 J. Ren, W. Ma, G. Distributed coordination for second-order multi-agent systems with nonlinear dynamics using only relative position measurements. 49 1419 1427, 2013 MathNet. 38 Y. R. Robust adaptive fuzzy controller design for a class of uncertain nonlinear time delay systems.
J. Uncertain. Fuzziness-based.
19.2, 329, 360, 2011 MathNet. 39 RE S. Development of fuzzy controllers with non-homogeneous dynamics for integral-type plants. 85, 155, 168, 2003. 40 RE ML. Stable fuzzy logic control of a general class of chaotic systems.
Neural.
26 540 1550, 2015. 41 X W Y. Dynamic partial state feedback control of cascade systems with time delay. 77 373 79, 2017 MathNet.
13.
Neural network-based fault-tolerant adaptive synchronization for high-order multi-agent systems.
Abstract.
This chapter is concerned with the fault-tolerant adaptive synchronization issue for high-order multi-agent systems, MASs. Since the considered MASs are in discrete time forms and involve nonlinear dynamics, a novel-based framework is introduced for implementing the controller. More specifically, under the proposed novel framework, the virtual controller designs in the intermediate steps are avoided. Therefore, the corresponding NN approximations are released. For each agent, only two NNs, an action NN and a critic NN, are needed. The first NN is employed for the implementation of the controller, while the second NN is utilized to estimate the cost function. By utilizing the difference approach, the stability of the MASs is rigorously proved. Finally, the effectiveness of the proposed strategy is validated via the simulation studies. 13.1 Introduction. Since the concept of multi-agent systems, MASs, was proposed, many scholars have dedicated themselves to the related researches. As a consequence, numerous algorithms have been developed and applied to various fields, such as electrical power systems 1, intelligent driving 2, and spacecrafts 3, 4. Noticing that in the practical engineering applications, most systems have nonlinear dynamics. Therefore, it is of significance to develop algorithms which could accommodate the nonlinear dynamics. In consequence, the approaches such as sliding mode control 5, data-driven control 6, and adaptive fuzzy neural control 7-9 were proposed correspondingly. Among these approaches, it is worth highlighting that the fuzzy neural-based approaches have obtained extensive concentrations on account of the remarkable approximation capacities for nonlinear dynamics 10, 11. For instance, in 10, the gamed-based optimal NN controller is designed for a class of nonlinear continuous time systems under the event-triggered mechanism. In 11, fuzzy logic systems are employed to complete the nonlinear controller design for the interconnected systems with unmodeled dynamics. Despite the aforementioned satisfactory results, these results are all obtained for continuous time systems. As everyone knows, computer systems cannot directly process analog signals. To enable a computer to process these signals, they must first be converted into digital signals via an analog-to-digital converter, ADC. Once the processing is completed, if the output needs to be in analog form, the digital signals are converted back using a digital-to-analog converter, DAC. In consideration of the above facts, it is also important to develop discrete time algorithms. However, as illustrated in 12, the continuous time algorithms cannot be directly applied to discrete time systems since the concept definitions and design procedure are different. For example, controller design for continuous time systems relies on derivatives, while for discrete time systems, it relies on differences. As such, most of the skills applied to continuous time systems are no longer effective for discrete time systems. Recently, the authors in 12 developed the state output feedback NN controllers for a class of nonlinear strict feedback discrete time systems. By developing the n-step ahead predictor scheme, the causality contradiction problem was solved. Afterwards, based on the results in 12, numerous results were obtained in combination with other approaches, including but not limited to event-triggered control 13, 14, and model predictive control 15. So far, under the approach, the virtual controller designs in the intermediate steps are essential. Nevertheless, when dealing with high-order nonlinear systems or a large number of agents, a significant number of NNs are required. This leads to the issue commonly known as the curse of dimensionality. To tackle this issue, a novel-based framework was first constructed for a class of nonlinear discrete time systems under multiplicative noises in 16. Unlike the existing results, the approach in 16 avoided the intermediate NN approximation. However, these results have been effective only for single-agent systems, and no results have been established for MASs under this framework. From another aspect, safe operation is an essential requirement in the practical scenarios as well. With the rapid advancement of modern industry, ensuring the stability and safety of control systems has become a focal point in various disciplines 17-18. It is well recognized that the actuator plays a crucial role in control systems, and due to its continuous operation, it is particularly prone to faults. Such actuator failures can compromise the stability of real-world production systems and potentially result in significant damage. Therefore, fault-tolerant control (FTC) techniques have been developed to address these faults and sustain acceptable system performance. Generally, there exist two FTC methods, namely active methods 19, 20, and passive methods 21. Active methods reconstruct the control strategy via the fault accommodation mechanism. On the contrary, passive approaches employ robust control methods to ensure closed-loop systems that remain unaffected by specific faults. Involving these two approaches, numerous results have been obtained for continuous time systems and discrete time systems, respectively 22-24. To mention a few, an adaptive finite-time fault-tolerant controller was developed for a class of non-lower triangular nonlinear continuous-time systems in 22. The authors in 23 investigated the issue of reinforcement learning-based fault-tolerant control for a class of multiple-input, multiple-output nonlinear discrete-time systems. Nevertheless, there still exists the issue of curse of dimensionality for the existing FTC methods of nonlinear discrete-time systems. Motivated by the aforementioned discussion, this paper attempts to investigate the issue of neural network-based fault-tolerant adaptive synchronization for high-order multi-agent systems. The main contributions of this chapter are summarized into two aspects. 1. A novel-based fault-tolerant framework is constructed to implement the NN-based controller design. It is worth highlighting that the virtual controller NN approximations are avoided. 2. The sufficient conditions to achieve the output synchronization are provided. Furthermore, all signals are guaranteed to be uniformly ultimately bounded, SGUB. The remainder of this chapter is organized as follows.
In Sect
13.2, the problem formulation is given. Section 13.3 provides main results of this paper, including the critic NN design, the NN-based fault-tolerant controller design, and convergence analysis. Simulation studies are analyzed in Sect
13.4.
Section 13.5 finally concludes this paper. 13.2 Problem formulation. 13.2.1 System dynamics. The output of the leader is known for all followers. The objective of this chapter is to develop a fault-tolerant adaptive controller for MASs 13.1, such that 1. The output synchronization is achieved, and 2. All of the signals in the closed-loop system are uniformly ultimately bounded SGUB. 13.2.2 Radial basis function neural networks. 13.3 NN-based controller design. 13.3.1 Critic NN design. 13.3.2 Fault-tolerant controller design. 1. The output synchronization is achieved. 2. All of signals in the closed-loop systems are SGUB. 3K by 1 by H to by to K 4K 1I 5K 2I to K. WC, WI. High by in are positive constants. The time responses of the followers and the leader. The time responses of the fault adaptive parameters 1K and 2K. The time responses of the fault-tolerant controllers and NN-based controllers, 26 for followers. 13.4 Simulation studies. The initial conditions are designed as X10.0001001T, X20.010.1T, WC0W0000500005T, 10.20.00007. The design parameters are selected as C0I C1I02, C2 I095, 05, High 075, and HID 02. The center of the action NN with 20 neuron nodes is evenly spaced in -55, 55, 55, and its width is 2. As for the critic NN, 25 neuron nodes are chosen. Its center is evenly spaced in -30, 322, with width designed as 2. Figures 13.1, 13.2, and 13.3 illustrate the simulation results by utilizing the developed fault-tolerant strategies.
In Fig
13.1, the output trajectories of two systems are given, from which it is shown that the tracking is achieved for both systems. Therefore, the synchronization is guaranteed. Figures 13.2 and 13.3 provide the evolution of the adaptive parameters and control signals. According to these figures, it can be concluded that all signals are SGUUB, which is consistent with the theoretical results. In consequence, the developed fault-tolerant control strategies are effective. 13.5 Conclusion. In this chapter, the fault-tolerant adaptive synchronization problem is investigated for high-order MASs. A novel-based framework is developed to simplify the controller design process. To be specific, the NN-based virtual controller design in the intermediate steps is avoided. As a consequence, there only exist an action NN and critic NN for each agent, which largely reduces the computation burden. On the basis of the difference scheme, it is proved that the output synchronization is achieved. Furthermore, all signals of the MASs are guaranteed to be SGUB. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder.
References.
1 Ren FMDX, Conceptual Design of a Multi-Agent System for Interconnected Power Systems Restoration.
IEIE Trans.
Power 27-732-740, 2012. 2AY Deep Reinforcement Learning for Intelligent Transportation Systems, a Survey.
IEIE Trans. Transpo.
23-1-1132, 2022. 3YQ Event-Driven Connectivity Preserving Coordinated Control for Multiple Spacecraft Systems with a Distance-Dependent Dynamic Graph.
IEIE Trans.
5211, 12551, 12560, 2022. 4YQ Observer-Based Spacecraft Formation Coordinated Control via Unified Event-Triggered Communication.
IEIE Trans.
Electron 575, 33073319, 2021. 5 Li Y Yang G Adaptive Integral Sliding Mode Control Fault-Tolerant Control for a Class of Uncertain Nonlinear Systems.
IIT Control Theory.
1213, 1864, 1872, 2018 MathNet. 6D Ha M. J. Data-Driven Iterative Adaptive Critic Control toward an Urban Treatment Plant.
IEIE Trans.
Electron 688, 7362, 7369, 2021. 7 Sun K. J. H. H. A novel finite time control for feedback saturated nonlinear systems with tracking error constraint.
IEIE Trans. Man.
516, 3968, 3979, 2021. 8MSB Adaptive Neural Control of Uncertain Nonlinear Systems Using Disturbance Observer.
IEIE Trans.
4710, 3110, 3123, 2017. 9H Tong N. X. B. Yang M. Predefined Time Adaptive Neural Tracking Control of Switched Nonlinear Systems.
IEIE Trans.
5310, 6538, 6548, 2022. Tensu W. T. J. X. A novel framework for game-based optimal event-triggered control of multi-input nonlinear systems.
IEIE Trans.
Control 697, 4867, 4874, 2024 MathNet. 11 Su B. Lei Y. C. Small gain approach to fuzzy adaptive control for interconnected systems with unmodeled dynamics.
IEIE trans.
Fuzzy. 3011-47024716, 2022. 12 S. Lee G. Lei T. Adaptive NN Control for a class of strict feedback discrete time nonlinear systems. 39.5-807-819, 2003 MathNet. 13 Lei Y. Yang G. Event-based adaptive NN tracking control of nonlinear discrete time systems.
IEIE trans.
Neural.
Learn.
29.9-4359-4369, 2018. 14 Xi W. X. H. Jo Y. Event-based optimal output feedback control of nonlinear discrete time systems. 540-414-434, 2020 MathNet. 15 L. X. The synchronization between two discrete time chaotic systems using active robust model predictive control. Nonlinear dynes. 74-4-905-910, 2013 MathNet. 16 M. Z. Dong H. Han Q. A novel framework for base control of discrete time strict feedback nonlinear systems with multiplicative noises.
IEIE trans.
Control 66-4, 1484-1496, 2021 MathNet. 17 Z. L. Wu Y. H. Optimal fault-tolerant control for discrete-time nonlinear strict feedback systems based on adaptive critic design.
IEIE trans.
Neural.
Learn.
29.6-2179-2191, 2018 MathNet. 18 Lee H. Wu Y. M. Adaptive fault-tolerant tracking control for discrete-time systems via reinforcement learning algorithm.
IEIE trans.
51.3-1163-1174, 2021. 19 S. YAW Ding SX Luo H. An adaptive advanced control strategy for KPI-based optimization of industrial processes.
IEIE trans.
Electron. 63.5-3252-3260, 2016. 20 Yin S. H. J. O. Descriptor reduced order sliding mode observers designed for switched systems with sensor and actuator faults. 76-282-292, 2017 MathNet. 21 Zhou K. Ren Z. A new controller architecture for high-performance, robust, and fault-tolerant control.
IEIE trans.
Control 4610, 1613-1618, 2001 MathNet. 22 H. W. P. Finite time adaptive fault-tolerant control for nonlinear systems with multiple faults.
IEIE CAAJ.
66-1417-1427, 2019 MathNet. 23 Z. L. H. G. Fault-tolerant controller design for a class of nonlinear MIMO discrete time systems via online reinforcement learning algorithm.
IEIE trans.
Man. 46.5-611-622, 2016. 24 S. Yang G. Fault-tolerant controller design for TS fuzzy systems with time-varying delay and actuator faults, a K-step fault estimation approach.
IEIE trans.
Fuzzy. 22.6-1526-1540, 2014. 14. Intelligent diagnosis and prognosis of mechanical systems with big data era.
Abstract.
Mechanical systems play a vital role in industry and society, but they inevitably suffer from faults and accidents, leading to both economic losses and life-threatening consequences in the production process. Prognostics and Health Management, PHM, offers an effective way to enhance the safety and reliability of mechanical systems. Over the past few decades, PHM technologies have evolved through three phases: reactive maintenance, preventative maintenance, and predictive maintenance. With the rapid development of cutting-edge information technologies, such as the Internet of Things, IoT, and artificial intelligence, AI, the increasing volume of data from mechanical systems now contains abundant health information, driving a new trend of intelligent maintenance in the big data era. This chapter introduces a series of intelligent fault diagnosis and prognosis methods, which are key components of PHM in mechanical systems. First, an unsupervised learning-based intelligent diagnosis model is developed to automatically extract fault features from the monitoring big data. This model links the learned features to the health states of mechanical systems, informing users about the fault's location, type, and severity. Second, deep transfer learning is employed to construct the intelligent diagnosis model when there is insufficient data for training. After fault diagnosis, a data model fusion stochastic process model is established to predict the remaining useful life (RUL) of mechanical systems using the 3-interval and particle filtering algorithms. Experimental and industrial case studies are conducted to demonstrate the effectiveness of these methods. 14.1 Intelligent fault diagnosis via unsupervised feature learning. 14.1.1 Introduction. Intelligent fault diagnosis framework, A the traditional one and B a new one. Machines have been widely employed in modern industries and have attained higher levels of automation, precision, and efficiency compared to the past three. This, in turn, has rendered the health condition monitoring of machines more arduous. To conduct a comprehensive inspection of the health conditions of machines, condition monitoring systems are utilized to gather real-time data from them. After a prolonged period of operation, multiple sensors obtain large volumes of data. Given that data is typically collected at a faster rate than diagnosticians can analyze it, the question of how to effectively extract features from this big data and accurately identify mechanical health conditions has now become an urgent research topic. Since intelligent fault diagnosis is capable of swiftly and efficiently processing the vast amounts of collected signals and furnishing accurate fault diagnosis outcomes, it might prove to be a valuable tool for dealing with mechanical big data. Traditionally, the intelligent fault diagnosis framework encompasses three principal steps, namely signal acquisition, feature extraction and selection, and fault classification 4, as illustrated in Fig. 14.1. In the signal acquisition phase, vibration signals have been widely employed because they offer the most fundamental information regarding mechanical faults. In the subsequent step of feature extraction, the objective is to extract characteristic features from the collected signals by means of signal processing techniques, such as time domain statistical analysis, Fourier spectral analysis, and wavelet transformation 5. Although these features can depict the mechanical health status, they may incorporate redundant or unresponsive information, thereby influencing the diagnosis results and computational efficiency. Consequently, feature selection is employed to pick out sensitive features through dimension reduction strategies, including principal component analysis, PCA, distance evaluation technique 6, and Fisher discriminant analysis 7. In the fault classification stage, the selected features are utilized to train artificial intelligence techniques like K-nearest neighbor, KNN, artificial neural networks, and support vector machine, SVM, and ultimately the mechanical health conditions are ascertained by these techniques. It is evident that numerous studies have been carried out in the realm of intelligent fault diagnosis and have yielded favorable outcomes 8. Nevertheless, these studies possess three drawbacks as follows. 1. Conventional artificial intelligence techniques lack the capacity to directly extract and organize discriminative information from raw data. As a result, a substantial portion of the actual work in intelligent diagnosis methods is dedicated to the design of feature extraction algorithms with the aim of obtaining representative features from the signals. These processes exploit human creativity, but rely heavily on extensive prior knowledge of signal processing techniques and diagnostic expertise, which is both time-consuming and labor-intensive. 2. The features are typically extracted and selected based on a particular diagnosis problem and are likely to be inappropriate for other issues. When confronted with a new diagnosis task, the feature extraction algorithms may require redesign. 3. Owing to the absence of a comprehensive understanding of mechanical big data, it is frequently challenging to guarantee that the extracted features contain optimal information for classifying mechanical faults. Consequently, diagnosticians need to expend a significant amount of time analyzing a large number of signals and comprehending their characteristics, which is a difficult task. In order to surmount these limitations, it is highly advantageous to learn the features from the raw data in an adaptive manner through the utilization of advanced artificial intelligence techniques, rather than relying on the manual extraction and selection of features. This would render intelligent fault diagnosis methods less reliant on prior knowledge or human effort, thereby enabling novel applications to be implemented more expeditiously. More importantly, it would propel mechanical fault diagnosis in the direction of genuine artificial intelligence 9. Unsupervised feature learning might possess the capability to address the aforementioned drawbacks in traditional intelligent diagnosis methods. It represents a collection of algorithms that enables artificial intelligence techniques to process raw data and automatically acquire the features essential for classification 10. The learned features unearth the explanatory details concealed within the raw data, magnify the information crucial for discrimination, and suppress the irrelevant fluctuations 11. Unsupervised feature learning has been extensively applied in diverse fields, including image classification 12, object detection 13, speech recognition 14, and high-energy physics 15, among others, and has achieved cutting-edge performance in these domains. Motivated by the concept of unsupervised feature learning, this section proposes a novel framework for intelligent fault diagnosis, as depicted in Fig. 14.1b. Within this framework, the features are directly derived from the mechanical raw signals, and a classifier is employed to categorize the mechanical faults based on these learned features. The distinctive feature of this framework is that the features are learned from the raw signals through a general-purpose learning process rather than being manually extracted by diagnosticians. The new framework liberates us from the arduous task of devising feature extraction algorithms and simplifies the construction of a diagnosis system, thereby making it more intelligent compared to the traditional approach. 14.1.2 Local Connected Intelligent Fault Diagnosis Model. Sparse filtering. Unsupervised feature learning methodologies predominantly strive to model the favorable approximation distribution of the collected data, such as sparse, restricted machines, sparse coding, and the like. These approaches may offer decent feature representations of mechanical signals. Nevertheless, they frequently demand the adjustment of diverse hyperparameters to achieve satisfactory performance, which poses a significant obstacle. For example, the adjustable hyperparameters of the restricted machines encompass the number of features, weight decay, sparsity penalty, learning rate, and momentum. If these hyperparameters are configured inappropriately, the learned features might lead to inferior diagnosis accuracy. Hence, AL 16 introduced an unsupervised feature learning technique known as sparse filtering. The crucial feature of sparse filtering is that the sole requisite parameter is the number of features. Thus, sparse filtering does not invariably involve hyperparameter tuning and readily converges to an optimal solution 17. Regression. 14.1.3 Two-stage learning for health state recognition. The proposed two-stage learning method of the training process and B illustration. This part elaborates on the proposed two-stage learning approach for the intelligent fault diagnosis of machines. The illustration and of this method are presented in Fig. 14.2. In the initial learning stage, sparse filtering is utilized to extract local discriminative traits from the raw vibration signals, and the learned features of the signals are acquired by averaging these local characteristics. In the subsequent stage, regression is employed to categorize the mechanical health conditions based on the learned features. The vibration signals of machines are acquired in diverse health conditions. These signals constitute the training set Xi1M, where Xi-RN1 is the sample containing N vibration data points. E is the health condition label of the Xi, and M is the number of the samples. The first learning stage. For the purpose of obtaining the local characteristics from the training samples, sparse filtering is employed. The structure of sparse filtering is where indicates the dimension of the input segment and represents the dimension of the local feature. The second learning stage. Once the learned feature set 1M is acquired, we combine it with the label set 1M to train regression. The regression model computes the probability that the feature, has the health condition label y as in 14.5. The sum of probabilities across all class labels being 1 guarantees that the right side of 14.5 defines a correctly normalized distribution. After being trained, the maximum posterior probability in Xi indicates which health condition class belongs to. After the 2 learning stages, we use test samples to validate the proposed method. For each test sample, we first divide it into segments alternately. Then the trained sparse filtering model is employed to obtain the local features from these segments. Next, the learned features of each test sample are obtained by averaging these local features. Finally, the health conditions of the test samples are determined by the trained regression model using the learned features. 14.1.4 Intelligent Fault Diagnosis of Bearings. Data description. In this section, the motor bearing signals provided by Case Western Reserve University 22 are analyzed. The vibration signals were gathered from the drive end of a motor in the test rig under 4 distinct conditions: 1 normal condition, 2 outer race fault OF, 3 inner race fault IF, and 4 roller fault RF. For the OF, IF, and RF cases, vibration signals for 3 different severity levels, 0.18, 0.36, and 0.53 were collected separately. All the signals were collected under 4 load conditions, 0, 1, 2, and 3, and the sampling frequency was 12 K. These vibration signals form the motor bearing dataset, which is utilized to verify the performance of the proposed method. The dataset encompasses 10 bearing health conditions under the 4 loads. The same health condition under different loads is regarded as one class. There are 100 samples for each health condition under one load. Consequently, the motor dataset contains 4,000 samples in total, and each sample is a 1,200 data point vibration signal of bearings. Parameter selection of the proposed method. The proposed method has several parameters, such as the input dimension and the output dimension of sparse filtering and the weight decay term of regression. We study the selection of these parameters separately. It should be noted that 20 trials are conducted for each experiment in the subsequent studies to minimize the impact of randomness. Diagnosis results using various input dimensions of sparse filtering. Diagnosis results using various output dimensions of sparse filtering. Diagnosis results using various weight decay terms. Comparing with related work. Classification comparison of the motor bearing dataset. Methods. No. Of training samples %. Load. No. Of health condition. Testing accuracy %. 22. 75. 0. 10. 88.9. 23. 10. 3. 10. 92.5. 24. 40. 0, 1, 2, 3. 4. 95.8. 25. 40. 0, 1, 2, 3. 11. 97.91. Proposed. 10. 0, 1, 2, 3. 10. 99.66. The comparisons are shown in Table 14.1. L. 24 proposed a method based on wavelet leaders' multifractal features and SVM. When this method was used to classify the 10 health conditions of the motor bearings, an accuracy of 88.9% was achieved. In 25, 9 time domain statistical features combined with 6 features related to the percentage of energy corresponding to wavelet coefficients were utilized to represent 10 bearing health conditions under a 3-load. Then these parameters were classified by the trace ratio linear discriminant analysis trained with 10% of the samples, and finally a 92.5% diagnosis accuracy was reached. Li al. proposed a method 26, using 19 time domain and frequency domain features combined with a semi-supervised self-organizing map. This method was employed to classify the bearings with multiple roller defects, with diameters of 0, 0.178, 0.355, and 0.533 respectively, and a classification accuracy of 95.8% was obtained.
Al
27 proposed a bearing diagnosis method integrating permutation entropy, ensemble empirical mode decomposition, and optimized SVM. This method was used to distinguish 11 health conditions and achieved a 97.91% testing accuracy. Compared with the above-mentioned methods, the proposed method is trained with a lower percentage of samples and attains a higher accuracy. Moreover, those methods require manual feature extraction based on numerous signal processing techniques, such as bandpass filtering, wavelet analysis, and ensemble empirical mode decomposition. To properly implement these techniques, in-depth knowledge of mechanical vibration signals and extensive diagnostic expertise are indispensable. In contrast, the proposed method adaptively learns the features from the raw vibration signals, making it less reliant on human effort. Thus, new applications can be easily achieved based on the proposed method. Sparse filtering shares a physical interpretation. Illustration of the inner product operation in sparse filtering. A selected weight vectors for the motor bearing dataset and the fitted vectors by function, and be the corresponding Fourier transforms. 14.1.5. When dealing with mechanical big data, especially in the feature extraction process, it's ideal to make intelligent fault diagnosis less dependent on prior knowledge and diagnostic skills. Therefore, this section proposes a two-stage learning method based on the concept of unsupervised feature learning. In this method, sparse filtering adaptively acquires features that can capture discriminative information from vibration signals in an unsupervised manner. Subsequently, these features are provided to the regression for classifying health conditions in a supervised way. Through case studies of the two bearing datasets, it's demonstrated that the proposed method can adaptively learn features from raw signals for various diagnostic problems and is better than existing methods in the fault diagnosis of the motor bearing dataset. The proposed method can make use of unsupervised learning to enhance its diagnosis accuracy as the quantity of unlabeled data increases. Additionally, a physical interpretation of the weight vectors of sparse filtering has been explored, and these vectors have properties similar to those of the filters. 14.2 Deep Transfer Learning-Driven Intelligent Fault Diagnosis. 14.2.1 Introduction. Intelligent Fault Diagnosis, IFD, has achieved significant progress with the rapid development of deep learning. However, this success often relies on the assumption that sufficient labeled data is available to train reliable diagnostic models. 28. In engineering scenarios, labeled data is challenging to obtain, making it difficult to train models that can yield accurate results. Transfer learning is considered a promising tool to address this issue, aiming to transfer knowledge from one or more tasks, source domain, to other related but distinct tasks, target domain. 29. In IFD, researchers have explored deep transfer learning, parameter-based, and GAN-based approaches. 30. Among these, deep transfer learning is widely favored for its ability to reduce distribution discrepancies between source and target domains. 31. Generally, deep transfer learning involves two steps. 32. 1. Using deep hierarchical models to extract transferable features from both domains, which helps mitigate distribution differences. 2. Using a distance metric to measure and minimize feature distribution discrepancies, enabling the classification layer trained on labeled data from the source domain to be reused in the target domain. A commonly used metric for this purpose is maximum mean discrepancy, MMD, which measures feature distribution discrepancies by mapping features to a reproduced kernel space RKHS and calculating the mean distance. 33. MMD-based methods have been widely used in fields like computer vision and speech recognition. 34. In IFD, researchers like Al. 35 Wen Al. 36 and Li Al. 37 have used MMD to address varying working conditions, while Yang Al. 30 have applied multi-layer and multi-kernel MMD for cross-domain diagnosis. Despite its effectiveness, kernel-based MMD GKMMD has several limitations. Firstly, it only considers the mean distance, ignoring higher-order moments, which reduces its accuracy in measuring distribution discrepancies 33. Secondly, GKMMD has high computational complexity, which becomes resource-intensive as data volumes grow. Lastly, the of GKMMD is sensitive to kernel parameters, making it challenging to achieve optimal distribution adaptation. To address these limitations, this section proposes a polynomial kernel MMD, PKMMD, as an improved distance metric. PKMMD considers weighted higher-order moment distances and allows kernel parameter adjustments, potentially addressing various transfer learning tasks. It also improves computational efficiency by using polynomial kernels instead of kernels. 14.2.2 Polynomial kernel-induced maximum mean discrepancy. Task description. In this section, our primary focus is on transferring diagnostic knowledge from one machine to other related machines. Given the sample space X and its probability distribution Px, the domain is defined as a pair of X Px. Let and, respectively, represent the source domain and the target domain, and they are defined as follows 32. 1. The source domain, represented as P, serves to supply diagnostic knowledge from the source machine. The source domain includes labeled samples Zs, is I1 which follow the distribution. The label space 12 represents types of health states. The labels of the source domain samples are denoted as Is2, the target domain, denoted as P, that the diagnosis knowledge from the source domain is applied. There are unlabeled samples 1 from the related machines with the distribution of, and it should be noted that, because these two kinds of datasets are collected from different machines. 3. The diagnostic knowledge from the source domain should satisfy the conditions of the target domain, meaning the assumption holds. This constraint is illustrated by the example that it is impractical to transfer diagnostic knowledge from healthy rolling element bearings to bearings with inner or outer race faults. Basic principle of MMD. PKMMD. 14.2.3 Deep Transfer Learning-Based Diagnosis Model. The proposed RaisNet model comprises three key components: a domain-shared RaisNet, PKMMD-based distribution adaptation, and pseudolabel learning. Each part is explained in detail below. Domain-shared RaisNet. Architecture of the domain-shared RaisNet. Diagram of the residual block. PKMMD-based distribution adaptation. Pseudolabel learning. Training process. Illustration of the training process of RaisNet. 14.2.4 Transfer diagnosis from laboratory to engineering. Dataset description. Physical parameters of tested bearings. Specs. Inside. Diameter. Outside. Diameter. Ball. Diameter. NOOF. Rollers. Contact. Angles. SKF 62052 RS. 25. 52. 7.94. 9. 0. LDK UER 204. 29.3. 39.8. 7.92. 8. 0. 552,732 QT. 160. 290. 34. 17. 0. Details of bearing datasets. Datasets. Specs. Health. States. NOOF. Samples. Operation conditions. NIF. ARF. 1616. HP 1 HP, 2 HP, and 3 HP. Laboratory motor bearings. SKF 62052 RS. Of 404.4. 1730 R-min, 1797 R-min. F. RF. Of BN locomotive bearings 552,732 QT.
F
4368. 4 load levels
RF
1092-4, 490 R-min, 530 R-min.
of
The dataset A was obtained from Case, Western Reserve University. Vibration data were collected from tested motor bearings, SKF 62052RS with 4 health states. Each fault diameter was machined to 0.0014 inches. The sampling frequency was set at 12 K. Data for each health state were collected under 4 operating conditions: 0 HP, 1 HP, 2 HP, and 3 HP. According to Table III, dataset A contains 1616 samples, with each sample having 1200 sampling points. Dataset B was acquired from locomotive bearings installed in a hydraulic motor-driven system 43. The tested bearings 552,732 QT had 4 health states, normal and abraded faults on the inner race, roller, and outer race. The sampling frequency was set at 12.8 K. The bearings were loaded by a hydraulic cylinder, with a maximum load of 20 kN. 4 load levels were applied to the bearings. According to Table III, a total of 4368 samples were collected, with each health state having an equal number of samples. Each sample contains 1200 sampling points. In a laboratory setting, it's easy to simulate various bearing faults and collect sufficient labeled data. Therefore, the diagnostic knowledge from laboratory-used bearings can be applied to identify the health states of locomotive bearings, aligning with real-world engineering scenarios. To verify the proposed methods, 2 transfer learning tasks A-B were created. Analysis of computation cost. Mini-batch computation cost for PKMMD with varying mini-batches and polynomial kernel orders. Comparison of computation of cost for GKMMD and PKMMD. Number of mini-batches.
batch size. Computation cost S.
Dataset A, dataset B, GKMMD. GKMMD
5
323 873 148.69 0.53
10
161 436 36.28 0.12
15
107 291 16.05 0.06 20
80
218 8.92 0.03 25
64
174 5.68 0.02. The computation cost of PKMMD is also evaluated against that of GKMMD as the data volume increases, with PKMMD's kernel order set to 10. The comparison results shown in Table 14.4 indicate that the mini-batch computation cost of PKMMD is significantly lower than that of GKMMD, primarily due to PKMMD's incorporation of matrix multiplication in its calculation process. This demonstrates that PKMMD effectively addresses the computational inefficiency of traditional GKMMD, maintaining efficient performance even when managing large volumes of samples in transfer learning tasks. Comparison results with other methods. Comparison results with other methods for task A-B methods.
Architectures. Accuracy percent.
Raise net without transfer learning 55.89739.
DCA.
Nonlinear mapping plus GKMMD 52.68000.
DIFD.
plus GKMMD 59.72152.
GRaiseNet.
RaiseNet plus GKMMD 84.32829.
P-RaiseNet hours. RaiseNet plus PKMMD. 87.76462. RaiseNet hours. RaiseNet plus PKMMD plus PLL. 88.27427. The proposed RaiseNet achieves an average diagnosis accuracy of 88.27% with a standard deviation of 4.27%, outperforming all other methods in this comparison. P-RaiseNet achieves an accuracy of 87.76% with a standard deviation of 4.62%, surpassing the performance of G-RaiseNet. These results highlight the advantages of using PKMMD over GKMMD for feature distribution adaptation. Furthermore, the performance gap between P-RaiseNet and RaiseNet underscores the additional benefit provided by pseudolabel learning, enhancing the effectiveness of RaiseNet in handling unlabeled target domain samples. Distribution estimation of the learned cross-domain features on the task of A/B by RaiseNet, G-RaiseNet, and the proposed RaiseNet. As shown in Fig. 14.12, the transferable features learned by RaiseNet exhibit significant distribution discrepancies, which complicate the classifier's ability to accurately label the unlabeled target domain samples. G-RaiseNet reduces these discrepancies to a certain extent, thus improving diagnosis accuracy on dataset B. In contrast, RaiseNet effectively minimizes the distribution differences across domains, enabling the classifier trained on source domain samples to accurately identify target domain samples. These results visually support the superior diagnostic performance of RaiseNet as presented in Table 14.5. 14.25. This section introduces a distance metric called PKMMD to enhance deep transfer learning for fault diagnosis in machines. PKMMD uses polynomial kernels to estimate the value of MMD, offering an improvement over the traditional GKMMD. Theoretically, PKMMD can be seen as a weighted sum of the distances between the orderwise central moments of paired datasets. By integrating PKMMD, RaiseNet is developed to diagnose the health states of locomotive bearings, leveraging diagnostic knowledge from laboratory-used bearings. The results demonstrate that PKMMD provides more efficient computation compared to GKMMD. Moreover, RaiseNet shows greater robustness to kernel parameters and achieves superior transfer learning performance compared to other methods. 14.3 Data Model Fusion RUL Prediction, considering random fluctuation variability. 14.3.1 Introduction. Rolling element bearings are essential components in rotating machinery, commonly operating in harsh environments where faults can frequently arise. A failure in a bearing can lead to catastrophic machine breakdowns. Predicting the remaining useful life (RUL) of bearings in advance allows for predictive maintenance, helping to prevent such breakdowns and optimize uptime while minimizing maintenance costs. As a result, RUL prediction for rolling element bearings has garnered increasing attention in recent years. 46. RUL prediction methods can be broadly classified into data-driven and model-based approaches. 47. Data-driven methods leverage machine learning to analyze measured data and estimate the degradation process of bearings. For example, AL developed an artificial neural network model for RUL prediction. 48, while AL used relevance vector machines for the same purpose. 49. Additionally, several studies have explored fuzzy system-based approaches. 50. These methods are particularly useful when mechanical principles are complex or too costly to model accurately. However, their effectiveness relies heavily on the quantity and quality of the data, which presents significant challenges in practical applications. Model-based methods involve developing mathematical or physical models to represent a machine's degradation process and estimating model parameters from measured data. Liao al. proposed a method combining proportional hazards and logistic regression models for RUL prediction of rolling element bearings. 51, while AL also used a proportional hazards model for similar systems. 52. Liao further employed the Paris model with genetic programming to predict bearing RUL. 53.
These methods can integrate both expert knowledge and empirical data, making them effective for RUL prediction in rolling element bearings. An example of bearing degradation. One limitation of the exponential model is the subjective selection of the first predicting time, FPT. To illustrate FPT, a simple example of a rolling element bearings degradation process is shown in Fig. 14.13, using the root mean square RMS of vibration signals as the degradation index. The degradation typically has two stages: Stage I, where the bearing operates normally with a stable degradation index, and Stage II, the failure stage, where the index generally increases exponentially as the fault worsens. In Stage I, health monitoring and early fault detection are essential. When a fault is detected, the prediction process starts, marking the FPT, the point where RUL estimation begins. Selecting an appropriate FPT is crucial. If the FPT is chosen incorrectly, it may either introduce noise or exclude critical information, reducing prediction accuracy. Ideally, FPT should coincide with fault onset, yet detecting incipient faults is challenging due to their random occurrence and weak characteristics. Therefore, FPT is typically chosen subjectively, which restricts the model's applicability. Several FPT selection methods, such as those based on engineering standards like ISO 10816 or approaches using the longest time constant and statistical properties of a baseline, have been proposed 57-58. However, these methods select FPT based on fixed alarms derived from large datasets, lacking adaptability to the variations of individual systems. Another drawback of the exponential model is that random errors in the stochastic process reduce the accuracy of RUL predictions. In the error-free process, the degradation follows the true path without interference from random errors. A clear negative correlation is observed between the random errors and the prediction deviations. For instance, a positive random error at a time causes the predicted RUL to be shorter than the actual RUL, while a negative error leads to the opposite effect. This correlation arises because a positive random error at a time increases the degradation value, leading to an overestimation of fault severity and a consequently shorter predicted RUL. Thus, the presence of random errors decreases prediction accuracy. To address these issues, this section proposes an improved exponential model for RUL prediction of rolling element bearings. The main contributions are: 1. The introduction of an adaptive FPT selection method based on the 3 interval, and 2. The reduction of random errors using particle filtering, PF, which enhances the accuracy of RUL predictions. 14.3.2 First predicting time selection. Exponential models. As mentioned earlier, several variants of the exponential model have been reported in the literature 55. The model presented in this work extends the approach outlined in 56. In this improved exponential model, parameters are estimated using Bayesian updating and the expectation maximization (M) algorithm, with the RUL provided as a closed-form distribution. 1. Development of degradation models. 2. Parameter estimating. The PF algorithm. Particle filtering PF is an extension of traditional nonlinear filtering methods, such as filtering KF and extended filtering EKF59. It is rooted in Bayesian theory, which is used to estimate the system state based on observed measurements. PF employs a sequential importance sampling (SIS) algorithm, a key component in the filtering process 60. Leveraging both Bayesian principles and SIS, PF excels in estimating the states of nonlinear and non-systems, making it particularly effective in fields such as system diagnosis and prognosis, where it has been widely adopted 61-63. 1. The Bayesian theory. 14.3.3 RUL prediction based on joint filtering of parameter and state. Of the proposed method, the improved exponential model for predicting the remaining useful life, RUL, of rolling element bearings is shown in Fig. 14.14. In this approach, vibration signals from the bearings are first collected, and 2 key features, kurtosis and RMS, are extracted from the data. Kurtosis and RMS serve distinct roles. kurtosis is used for health monitoring, while RMS is employed for RUL prediction. Kurtosis is highly sensitive to incipient faults, making it effective for early-stage fault detection, although it does not provide much insight during the fault's progression. In contrast, RMS increases as fault severity rises, providing a clearer indication of the fault's development. 65. During the normal operation phase, kurtosis is utilized for health monitoring and selecting the FPT. Once the FPT is established, the prediction process is triggered, and RMS is then used to estimate the RUL of the bearing. To determine the appropriate FPT, an adaptive method based on the 3 interval is introduced. Initially, historical data from the bearing's normal operating phase is used to compute the mean and standard deviation of the kurtosis, establishing the 3 interval 3 plus 3. This interval serves to distinguish between normal and abnormal bearing states. When new measurement data becomes available, the kurtosis is monitored to assess the bearing's health. If the kurtosis value at time falls outside the 3 interval, the health state is flagged as abnormal. However, abnormal states can result from either actual faults or random noise. To minimize noise interference, a refined trigger mechanism is employed. This mechanism activates the prediction process only when L plus 1 consecutive kurtosis values exceed the 3 threshold, ensuring reliability in fault detection. The step-by-step process of this trigger mechanism is outlined as follows. First, set L0. Identify the first instance where the kurtosis value exceeds the 3 interval and mark this time as FPT0. Second, set LL plus 1. Locate the time where L plus 1 consecutive kurtosis values, plus 0, L meet the condition of plus K30, L assign the time as. Third, continue increasing L until 1, indicating stabilization. The stable value is then finalized as the FPT. The rationale behind this approach is that anomalies caused by random noise are highly unlikely to persist for L plus 1 consecutive measurements during the normal operational phase. When the FPT value stabilizes as L increases, it strongly indicates the emergence of an actual fault. Once the FPT is determined, RMS value is fed into the degradation model to predict the RUL of the bearing. To mitigate the impact of random errors within the stochastic process, this study leverages PF to provide a refined estimation of the system's health state. The detailed steps of the RUL prediction process using the improved exponential model are presented as follows. RUL prediction process using the improved exponential model. 1. Initialization. At the initial time t0, initialize the model parameters 20200202, 10 and 1202. Sample random particles S0II1 from the prior PDF. 0S00002 and assign equal initial weights W0I1. 2. Measurement update. Upon receiving a new measurement, at for K1 compute. 2K12 0K1 02K12 1K1 and 12 K12 using 14.41. 3. Parameter estimation. Using the updated measurement information, estimate the model. Parameters 2K20, K02, K21, K and 12 K2 via 14.42. 4. Particle sampling. Sample a new set of particles SKI I1 from the importance PDF. KSK1K derived using 14.57. 5. Weight update. Update the particle weights based on the measurement likelihood using 14.58. 6. Degeneracy check and resampling. Calculate the effective sample size NF using 14.55. If NF-NT, perform resampling to generate a new particle set SKI I1. And reset all weights to 1. 7. RUL estimation. Using the updated K, K2, K and K2 from step 2, K2 from step 3. And particle set 1 from step 6, estimate the RUL using 14.61. 8. Iteration. Let K plus 1. Return to step 2 and repeat the process until the stopping criterion is met. 14.3.4 RUL Prediction Case of Bearing Degradation Processes. Overview of the experimental system. Experimental demonstrations. The PRONOSDIA Experimental Setup 66, depicted in Fig. 14.15, is engineered to evaluate techniques for bearing fault identification, diagnostics, and RUL estimation. To expedite the degradation process and complete tests within a few hours, a radial force equivalent to the bearing's peak dynamic load, 4 kN, is exerted. This force is produced by a pneumatic cylinder and controlled via a pressure regulator. During the experiments, the bearings maintain a steady rotational speed of 1,800 RPM. Accelerometers attached to the outer race collect vibration data. The system samples signals at a frequency of 25.6 K, with each sample comprising 2,560 data points, spanning 0.1 seconds, and repeated every 10 seconds. These signals are transmitted to a PC for visualization and archiving through an NIDAQ card. The bearings concludes when the vibration amplitude surpasses 20 G vibration signals of 4 bearings: A bearing 1, B bearing 2, C bearing 3, and D bearing 4. FPT selection. In the proposed method, kurtosis and RMS are first extracted from the vibration signals to identify key indicators for fault progression. The FPT for the 4 bearings is determined using the selection method outlined in this study, while AL. Approach 57 is applied for comparison. The results displayed in Fig. 14.17 and summarized in Table 14.7 reveal distinct differences. Notably, NA in the table indicates that no FPT could be identified throughout the entire operational period. FPT selection results: A bearing 1, B bearing 2, C bearing 3, and D bearing 4. Selected FPT of 4 bearings. Case: bearing 1, bearing 2, bearing 3, bearing 4. Method: 21670 S18270 SNA22580 S proposed method. 14630 S16440 S10910 S22130 S RMS division results: A bearing 1, B bearing 2, C bearing 3, and D bearing 4. FPT selection results with different intervals: A bearing 1, B bearing 2, C bearing 3, and D bearing 4. RUL prediction. RMS estimation results: A bearing 1, B bearing 2, C bearing 3, and D bearing 4. RUL prediction results: A bearing 1, B bearing 2, C bearing 3, and D bearing 4. As shown in Fig. 14.2, the original exponential model's estimation results align closely with the actual RMS values. However, the 2 PF-based methods, namely the Paris model and the improved exponential model, reduce the random errors associated with the stochastic process, better capturing the overall degradation trends of the bearings. In Fig. 14.21, all models initially produce inaccurate predictions due to insufficient RMS data. Once enough RMS data become available, the original exponential model and the Paris model still exhibit significant prediction errors, especially for bearing 2. By contrast, the improved exponential model converges more rapidly to the actual RUL and provides the most accurate predictions among the 3 models. This performance can be attributed to the limitations of the other models. The original exponential model struggles to accurately estimate the health state of the bearings, resulting in predictions affected by random stochastic errors. While the Paris model improves state estimation with the use of PF, it fails to effectively estimate model parameters, leading to persistent random errors. The improved exponential model, on the other hand, combines the strengths of PF for state estimation with the Bayesian updating and M algorithm for parameter estimation, achieving superior prediction accuracy. To quantitatively evaluate the prediction performance of the models, cumulative relative accuracy (CRA) and convergence metrics 68 were calculated at time indices from the midpoint to the end of the bearing's lifetimes. 14.3.5. To enhance the RUL prediction performance of rolling element bearings, this section introduces an improved exponential model. The study makes two primary contributions. First, an adaptive FPT selection method based on the 3-interval is developed, incorporating a new trigger mechanism to mitigate the impact of random noise. Second, PF is employed to estimate the health state of bearings, effectively reducing stochastic process errors. The proposed model is validated through a simulation and 4 bearing degradation tests. To evaluate the adaptive FPT selection method, a comparison with SAPproach is conducted. Results indicate that the proposed method more effectively suppresses noise interference and selects a more suitable FPT. Additionally, the improved exponential model's state estimation using PF is compared with the original exponential model and the Paris model. The comparisons highlight the improved model's ability to minimize random errors and enhance the accuracy of RUL predictions. 14.4 Conclusion. This chapter has explored advancements in intelligent fault diagnosis and prognosis for mechanical systems in the era of big data. A progression from traditional methods relying on handcrafted features to adaptive frameworks employing unsupervised learning and deep transfer learning has been demonstrated. By leveraging state-of-the-art techniques such as sparse filtering for unsupervised feature extraction and polynomial kernel maximum mean discrepancy, PKMMD, for cross-domain feature alignment, the challenges of data-driven fault diagnosis, including distribution discrepancies and limited labeled data, have been addressed. Additionally, a novel data model fusion approach for predicting the remaining useful life, RUL, of mechanical components was introduced, integrating adaptive first predicting time, FPT, selection and particle filtering for enhanced accuracy. The experimental validations confirm the efficacy of these methods in diagnosing faults and predicting degradation trends with high accuracy, emphasizing their practical relevance in industrial applications. These advancements lay the foundation for intelligent maintenance strategies, significantly improving the reliability and safety of mechanical systems in complex environments. Future research will focus on integrating adaptive thresholding and real-time monitoring to further refine these diagnostic frameworks and enhance their applicability across diverse industrial scenarios. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Fr. Big Data, Distilling Meaning from Data. Nature 455, 30, 2008. 2. Wu X Wu GQ Ding W, Data Mining with Big Data. IEIE Trans. Data. 26-1-97-107, 2014. 3. Lay YJ MJ He Z, Condition Monitoring and Fault Diagnosis of Planetary Gearboxes, a Review. Measurement 48, 292-3, 5, 2014. 4. Y. Al. M. Fault Diagnosis in Internal Combustion Engines Using Extension Neural Network. IEIE Trans. Electron. 61-3, 1434-1443, 2014. 5. UDXS, Based Laser Welding Process Monitoring and Defects Diagnosis by Using and IEIE Trans. Electron. 62-1, 628-636, 2015. 6. Lay Y He Z, Y, Application of an Intelligent Classification Method to Mechanical Fault Diagnosis. Expert. 36-6, 9941-9948, 2009. 7. M. J. J. M. Tan ACC, EY, BK. reliable fault diagnosis for low-speed bearings using individually trained support vector machines with kernel discriminative feature analysis. IEIE Trans. Power Electron. 35 27 86 2797 2015. 8 Worden K. WJ JJ. Natural Computing for Mechanical Systems Research. A tutorial overview. Mech. Signal Process. 25 1s 4 111 2011. 9 YA Vincent P. Representation Learning, A Review and New Perspectives 2014. 10 YBs G. Deep Learning. Nature 521 7553, 436 444 2015. 11 Coates A. Lee H. An Analysis of Single-Layer Networks in Unsupervised Feature Learning. J. Mock. Learn. Raise. Proc. Track 15 215 223 2011. 12 KYJ. Learning image representations from the pixel level via hierarchical sparse coding. CVPR 2011, 1713-1720, 2011. 13 M. FJ YL Y. Unsupervised Learning of Invariant Feature Hierarchies with Applications to Object Recognition. In IAAE Conference on Computer Vision and Pattern Recognition 2007. 18-2007. 14 GL D Dal GA ARN Senior AVP TNB Deep Neural Networks for Acoustic Modeling and Speech Recognition, the shared views of 4 research groups. IAAE Signal Process. MAG. 29-6-8297 2012. 15 PSB D. Searching for Exotic Particles in High-Energy Physics with Deep Learning. 5 2014. 16 JZSPA Sparse Filtering. Advances in Neural Information Processing Systems. 24 2011. 17 Raja KB R VKC. Smartphone-based visible iris recognition using deep sparse filtering. Pattern. 57 3342 2015. Mobile Iris C Evaluation Part IMICHEI. 18 GERR, Reducing the Dimensionality of Data with Neural Networks. Science 313 5786, 504 2006 MathNet. 19 JV AB, Laser-Based Segment Classification using a Mixture of Bag of Words. In IEEE RSJ International Conference on Intelligent Robots and Systems 2013. 4195 4200 2013. 20 Han JD when SLT Lay X, two-stage learning to predict human eye fixations via IEIE Trans. 46-2, 487-498, 2016. 21 C. Robles v. P. Regularized Logistic Regression Without a Penalty Term, an application to cancer classification with microarray data. Expert. 38-5, 51-10-5-118, 2011. 22 X. Ka. Bearing Fault Diagnosis based on Wavelet Transform and Fuzzy Inference. Mech. Signal Process. 18-5, 1077-1095, 2004. 23 Marina JN Stan S. Beyond Accuracy, F-Score and ROC, a family of discriminant measures for performance evaluation. 4304. 1015-1021, 2006. 24 W Tau J Lay Y C. Wavelet Leaders Features-Based Fault Diagnosis of Rotating Mechanism. Mech. Signal Process. 43-1, 5775, 2014. 25 Jin X M Chow TWS PECT M. Motor Bearing Fault Diagnosis using Trace Ratio Linear Discriminant Analysis. IEIE Trans. Electron. 61-5, 2441-2451, 2014. 26 Lee W. S. He G. Distance Preserving Self-Organizing Map for Machine Defect Detection and Classification. IEIE Trans. 62.5, 869, 879, 2013. 27X Joe J. Y. A novel bearing fault diagnosis model integrated permutation entropy, ensemble empirical mode decomposition and optimized. Measurement 69, 164, 179, 2015. 28W Lai C. Peng G. Y. Z. A deep convolutional neural network with new training methods for bearing fault diagnosis under noisy environment and different working load.
Mecca.
Signal process 100, 439, 453, 2018. 29 Pan S.J. Yang Q. A survey on transfer learning.
IEIE trans. Data.
2210, 1345, 1359, 2010. 30 Yang B. Lei Y. F. Xing S. An intelligent fault diagnosis approach based on transfer learning from laboratory bearings to locomotive bearings.
Mecca.
Signal process 122, 692, 706, 2019. 31 Long M. J. Ding G. Sun J. P.S. Transfer feature learning with joint distribution adaptation. In IAAE International Conference on Computer Vision 2013. 2202-207, 2013. 32 Yang Bin J.F. L. X. A transfer learning method for intelligent fault diagnosis from laboratory machines to real-case machines. In 2018 International Conference on Sensing, Diagnostics, Prognostics and Control SDPC. 3540, 2018. 33 A KMB ITIL. A kernel 2 sample test.
J. Mach. Learn. Raise.
13.1, 723, 773, 2012. 34 HSS, Deep Learning Systems for Domain Adaptation in Computer Vision, Learning Transferable Feature Representations.
IEAE Signal Process. MAG.
34.6, 117, 129, 2017. 35 WB Y D Yang J T, Deep Model-Based Domain Adaptation for Fault Diagnosis.
IEIE Trans.
Electron 64.3, 2296-2305, 2017. 36 Wen L. Lei X, a new deep transfer learning based on sparse autoencoder for fault diagnosis.
IEIE Trans. Man.
49 1, 136 144, 2019. 37 Lei X W Ding Q, a robust intelligent fault diagnosis method for rolling element bearings based on deep distance metric learning. 310 7795, 2018. 38 Nair V GI, rectified linear units improve restricted machines. In Proceedings of the 27th International Conference on Machine Learning, ICML-10. 807 814, 2010. 39 He K X Ren S Sun J, Deep Residual Learning for Image Recognition. In IAAE Conference on Computer Vision and Pattern Recognition, CVPR 2016. 777-78, 2016. 40 J J Y H, How Transferable Are Features in Deep Neural Networks. 2014. 41 Lei DH, Pseudolabel, the simple and efficient semi-supervised learning method for deep neural networks. 32 896, 2013. 42 DP Ba J Atom, a method for stochastic optimization, 2017. 43 Lei Y He Z Y X, new clustering algorithm-based fault diagnosis using compensation distance evaluation technique.
Mecca.
Signal process 22.2, 419, 435, 2008. 44 Pan SJ IW JT Yang Q, domain adaptation via transfer component analysis.
IEIE Trans.
Neural 22.2, 199, 210, 2011. 45 Van L GI, visualizing data using T.
J Mach. Learn. Raise. 9-2579-2605-2008. 46A RX, prognosis of defect propagation based on recurrent neural networks. IEIE Trans. 63 703 711 2011. 47D Luo Y J Peng Y L Pect M. Lithium-ion battery remaining useful life estimation based on fusion nonlinear degradation model and algorithm. Neural. 25-9-2013. 48 NMRV, residual life predictions from vibration-based degradation signals, a neural network approach. IEIE Trans. Electron. 51-3, 694-700 2004. 49 FKLE, combining relevance vector machines and exponential regression for bearing residual life estimation. MECA. Signal process. 31 405 427 2012. 50 AHGDD, prognosis of bearing failures using hidden models and the adaptive fuzzy inference system. IEIE Trans. Electron. 61-6, 28-64-2874 2014. 51 Liao H.W.H., predicting remaining useful life of an individual unit using proportional hazards model and logistic regression model. In RAMS 06. Annual Reliability and Maintainability Symposium 2006. 127-132 2006. 52 Z Liao H. Condition-based maintenance optimization for multi-component systems using proportional hazards model. Land. Safety 96-5, 581-589 2011. 53 Liao L. Discovering prognostic features using genetic programming in remaining useful life prediction. IEIE Trans. Electron. 61-5, 24-64-2472 2014. 54 NM Lay R.J. Residual life distribution from component degradation signals, a Bayesian approach. Transactions 37, 543 557 2005. 55 N. Sensory updated residual life distributions for components with exponential degradation patterns. IEIE Trans. 34 382 393 2006. 56 C XS W MY CH JO DH, a degradation path-dependent approach for remaining useful life estimation with an exact and closed-form solution. J. Rays. 226-1, 5366, 2013 MathNet. 57 A I Golden J JL, automated feature selection for embeddable prognostic and health monitoring architectures. In IEEE 2006. 195-2-1 2006. 58 Tran VT Yang BS, an intelligent condition-based maintenance platform for rotating machinery. Expert. 39-3, 2977-2988 2012. 59 MSNT, a tutorial on particle filters for online nonlinear non-Bayesian tracking. IEIE Trans. Signal process. 52 174 188 2002. 60 A N and J, an introduction to sequential Monte Carlo methods. In Sequential Monte Carlo Methods in Practice, 2001. 61 Orchard ME GJ, a particle filtering approach for online failure prognosis in a planetary carrier plate. J Fuzzy Log. 7 221 227 2007. 62 BCCR Orchard MEG, a probabilistic fault detection approach, application to bearing fault detection. IEIE Trans. Electron. 58-5 2011-2018 2011. 63 EG, particle filtering prognostic estimation of the remaining useful life of nonlinear components. Land. 96.3, 403.409, 2011. 64 JS.R. Sequential Monte Carlo Methods for Dynamic Systems. JIM. Stat. 93.443, 1032.1044, 1998 MathNet. 65 Lei Yhizi, YQ. Fault diagnosis of rotating machinery based on multiple combination with gas. Mech. Signal process. 21.5, 2282.294, 2007. 66 PRKE Morello BNC. An experimental platform for bearings accelerated degradation tests, 2012. 67 and DJH NH Prognostics 101, a tutorial for particle filter-based prognostics algorithm using land Safety 115, 161, 169, 2013. 68 AJRBSK Metrics for Offline Evaluation of Prognostic Performance. J. Health 2021. 15. Relevance Vector Machine-Based Remaining Useful Life Prediction. Abstract. Remaining Useful Life RUL prediction is a core approach to achieving prognostics and health management, PHM, and a key technology for decision-making from preventive maintenance to predictive maintenance. As long life cycle data become increasingly scarce and difficult to obtain in a short time, the prediction of RUL based on the tendency to performance degradation has emerged as an inevitable trend in the study of equipment reliability. As equipment is highly susceptible to external loads, operational stress, working conditions, and intrinsic wear, it undergoes continuous performance degradation with a nonlinear and time-varying degradation rate. Furthermore, equipment is subject to various uncertainties during operation, including those caused by external disturbances, measurement errors, and incomplete data collection, as well as inaccurate regression models used for RUL prediction. Considering the nonlinear, time-varying, and uncertainty during performance degradation process, dynamic and adaptive degradation tendency and RUL prediction models are developed based on the relevance vector machine, RVM. The RVM method is essentially an approximation approach. Directly using RVM for prediction inevitably leads to low prediction accuracy. To address the limitations of evidence approximation in RVM, this chapter extends the RVM to a statistical manifold. First, degradation features are selected based on batch data. Then, a dynamic multi-step regression model is constructed, where the RVM model is extended to the statistical manifold to achieve more accurate degradation tendency prediction. Finally, the predicted degradation tendency is applied to estimate the RUL according to the first hitting time, FHT, method. Additionally, RVM model is limited to single output variables, whereas real-world degradation processes are influenced by multiple variables. This chapter further extends the classical RVM model to a multivariate setting. Specifically, a multi-step RVM model is first established, where a matrix distribution is introduced for the weight parameters in the RVM model. The unknown of the model are then estimated using the accelerated gradient descent method. Then the degradation tendency is predicted by the multivariate RVM approach. Finally, the RUL is estimated based on the predicted degradation tendency and the FHT method. 15.1 Introduction. Remaining Useful Life RUL prediction aims to forecast equipment's future health status or remaining operational time utilizing historical and current data. 1, 2. If the health status or remaining operating time of the equipment can be predicted in advance, it can significantly reduce the costs of expensive periodic maintenance and the corresponding consumption of human resources. Therefore, RUL prediction is an important technology to ensure the safety and reliability of equipment in practical applications. Existing RUL prediction techniques can be broadly categorized into physics-based empirical model methods, stochastic process-based statistical methods, and machine learning-based methods 3, 4. In recent years, machine learning-based methods have been widely applied in RUL prediction due to their ease of implementation. For example, an extreme learning machine is used to train the RUL prediction model in 5.
Although the extreme learning machine method can improve training speed, its prediction accuracy is still inferior to the support vector machine, SVM, method 6. Since the deterministic output of SVM makes it challenging to characterize the uncertainty in the degradation process, the RVM algorithm is developed, which is formally similar to SVM, based on the sparse Bayesian learning theory 7-8. Compared to SVM, RVM is no longer constrained by the Mercer kernel condition. Additionally, since the relevance vector machine performs predictions from a probabilistic perspective, the RVM method is more suitable for the prediction of RUL under uncertainties. The RVM method is essentially a multi-input, single-output approach. However, equipment in practical applications exhibits two or more degradation characteristics. When predicting the degradation tendencies of multiple degradation variables, it usually establishes an RVM model for each degradation variable, rather than directly using an RVM model to predict the multivariable degradation tendency. This significantly increases the complexity and computational load of the model. Based on this, some scholars have focused on extending RVM to a multivariate form. For example, Al. 9 proposed a multivariate RVM method by learning a one-to-many mapping from image features to state space, and applied it to the task of estimating the pose of a jointed object 10. However, the multivariate RVM proposed in the 9-10 has a limitation in that the different row vectors of the weight matrix share the same distribution form. Therefore, this method is essentially a combination of RVM approaches with different parameters and remains, in essence, a single-output RVM method. Subsequently, Al. 11 devised a relevance sample feature machine for feature selection and classifier design. Moreover, an incremental relevance sample feature machine is introduced to reduce the time consumed in model training 12. The weights are represented as two independent vectors in the relevance sample feature machine model. One governs the relevance of the samples, while the other controls the features. These two weight vectors are independent of each other and inherently fail to account for the potential correlations between samples and features. The RVM method still presents an issue with the accuracy of the prediction. Essentially, the RVM method is an approximation algorithm. Additionally, as the prediction distribution is in triple integral form, it is challenging to obtain an analytical solution. Thus, the and the triple integral are first estimated and then substituted into the prediction distribution, reducing the triple integral to a single integral. This estimation method is called evidence approximation in the RVM method, which leads to a relatively poor prediction accuracy compared to the analytical solution 13. To address the issue of low RUL prediction accuracy caused by evidence approximation in the RVM method, and to account for the fact that degradation variables in real-world degradation processes are not singular, this chapter focuses on predicting the degradation tendencies of multiple degradation variables based on extended RVM. Specifically, an asymptotic expansion form of RVM is derived through statistical manifold techniques. Compared to conventional RVM algorithms, the asymptotic expansion form of RVM introduces two correction terms to improve the accuracy of degradation tendency prediction, thus improving the accuracy of the RUL prediction. And the classical RVM is extended to a multivariate setting. In the extended multivariate RVM method, the weight distribution is no longer modeled as a vector distribution, but as a matrix distribution, which increases the complexity of estimation and the derivation of the prediction distribution function. To address this challenge, this chapter the posterior distribution of the weight matrix under the matrix distribution framework. The overall structure of this chapter is as follows. First, the preliminary of RUL prediction and the RVM method is introduced. Then, RVM is expanded to the probabilistic manifold for life prediction. Finally, RVM is extended to a multi-input, multi-output form under a matrix distribution framework. 15.2 Preliminary of RUL. Due to the long degradation time of equipment and the difficulty in obtaining long degradation data, this chapter focuses on life prediction based on degradation trajectories. First, the future degradation trend of the equipment is predicted using improved RVMs based on the available degradation data. Then, the RUL prediction is achieved using the concept of first hitting time. In the following subsections, the concept of first hitting time is introduced, followed by an overview of the theoretical foundation of the RVM. 15.2.1 Theory of first hitting time for RUL. 15.2.2 Theory of RVM in a regression aspect. The RVM is a supervised learning method for classification and regression, similar in form to the SVM7. It inherits many of the advantages of SVM while offering a more sparse model, leading to improved computational efficiency. Since this chapter focuses on RUL prediction, the following discussion will be limited to the RVM in a regression form. The core of RVM is to construct a regression model based on a given set of input vectors 1n and their corresponding target values 1n, enabling the prediction of an output t for any given input vector. The following provides a detailed explanation of the RVM method. 15.3 Statistical Manifold Relevance Vector, Machine-Based Remaining Useful Life Prediction. To improve the accuracy of RUL prediction, this section extends the RVM method into statistical manifold to address the limitations of evidence approximation in the classical RVM method. First, a dynamic multi-step regression model is established via RVM on selected degradation features. Second, the RVM model is extended to statistical manifolds to accurately forecast the degradation tendency. Finally, the FHT method is applied to predict the RUL based on the forecasted degradation tendency. 15.3.1 Dynamic Degradation Process Modeling. Since the parameters on the right-hand side of 15.27 and 15.28 depend on and to, these equations provide an implicit formulation in terms of the and to. Therefore, an iterative re-estimation process is required to obtain the estimated values and to. Under this approach, 15.29 provides a parameter-estimated PDF. However, relying on such an estimated PDF often leads to reduced prediction accuracy. To enhance prediction accuracy, it is crucial to explore a new method that can address the limitations introduced by the evidence approximation in the RVM method. 15.3.2 Degradation Tendency Prediction by Probability Manifold RVM. In the RVM method, to avoid solving the analytical solution of the triple integral, the evidence approximation is used to reduce the triple integral to a single integral. However, the resulting prediction distribution is inherently influenced by parameter estimation, which inevitably affects the precision of the prediction. In this section, the RVM is extended to the statistical manifold to address accuracy issues caused by evidence approximation. The PDF of the vector z, denoted as PZZ, is given by the following theorem. The log likelihood function of PZ is LZZ, and its -1 representation is L1ZPZ1. From 15.32, it is evident that the RVM is extended into a generalized form by incorporating a correction term, 1ZHZ, into the estimated density PZ. This correction consists of two components. An orthogonal term, 12ZI1K, serves as a rectification for the estimated density obtained through the evidence approximation in RVM. A parallel term, 1Z1J+, which shifts the estimated density along the RVM model. This term can be interpreted as a modification of the estimated density when using MLA, resulting from differences in the estimators. 15.3.3 RUL Prediction by First Hitting Time. The entire statistical manifold RVM algorithm, which includes modeling, prediction of the degradation tendency, and estimation of RUL, can be summarized in Algorithm 9. 15.4 Multivariate Relevance Vector, Machine-Based Remaining Useful Life Prediction. RVM is an effective tool for modeling degradation processes and predicting degradation tendencies. However, the RVM model can only handle single output data. Although in SECT 15.3, the RVM model was written in a multi-output form, it is essentially still a univariate RVM model.
This section proposes a degradation tendency and RUL prediction algorithm based on dynamic multivariate RVM, MRVM. Specifically, the approach begins by establishing a multi-step RVM regression model, introducing a matrix distribution for the weights in the RVM model. Then the model are estimated using the accelerated gradient NAG method, and the MRVM method is used to predict the degradation tendency. Finally, the RUL is predicted based on the degradation tendency. 1541 Dynamic Modeling by Multivariate RVM. The classical RVM algorithm is essentially a static single-output model, which can't capture the evolving degradation trends and is insufficient for monitoring multiple degradation states of a system. In practical applications, the degradation of most equipment is usually reflected by multiple variables. For example, as electrical equipment degrades, the degradation characteristics is reflected not only through current, but also through voltage. Thus, in this section, the dynamic MRVR model is extended to describe the relationship between the future degradation tendency and historical samples in the time domain. The matrix distribution of 15.42 can be converted into the corresponding vector distribution form using lemma 1. 16 W obeys a Mn plus 1 matrix distribution, i.e. Wmn0, if and only if Wt obeys a Mn plus 1 variate distribution, i.e. Wt nmn plus 1 0, where is the vector operator and is the product or tensor product. 1542 Parameter estimation via accelerated gradient algorithm. The accelerated gradient NAG method prescribes specific formulas for the learning rate and the momentum constant U. Typically, the learning rate is initially set high to ensure a fast convergence rate and then gradually decays to facilitate convergence to an optimal stable point. In this study, an exponential decay function, 010SS, is adopted, where 0 is an initial value of the learning rate, S denotes an iteration variable, and S represents the total number of iterations. The momentum constant U, 1, governs the decay of the velocity vector v. A higher value of U results in more rapid adjustments to the gradient updates. Therefore, U is typically set close to 1, with a common choice being 0.9. Similarly, the J12n plus 1 and 2I12m can be estimated using procedures analogous to those in algorithm 10. Given their similarity, further discussion is omitted. 1543 Degradation tendency and RUL prediction. Finally, an algorithm is proposed to outline the entire procedure for estimating the model, the degradation tendency, and the RUL prediction. It is presented in Algorithm 11. 15.5 Conclusion. As long lifecycle data are increasingly scarce and difficult to obtain quickly, RUL prediction based on performance degradation trends an inevitable approach in equipment reliability studies. In this chapter, dynamic and adaptive degradation tendency and RUL prediction models are developed based on the extended RVM. First, the RVM is extended to a statistical manifold to enhance the accuracy of degradation tendency predictions caused by parameters evidence approximation. Then the RVM is expanded into a multivariate setting by incorporating a matrix distribution for the weight parameters. The degradation tendencies are predicted using the extended RVM approaches, and the RUL is estimated based on the predicted degradation trajectory and the FHT method. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S, and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References.
1 CHFR, online fault prognosis with relative deviation analysis and vector modeling. 13822, 531 543, 2015. 2 Yin X Lei ZJ, decentralized fault prognosis of discrete event systems with guaranteed performance bound. 69 375 379, 2016 MathNet. 3 Z Su SQ CLP YXY, a three-domain fuzzy support vector regression for image and experimental studies. IEIE Trans. 44.4, 516 525, 2017. 4 CLP ZL, broad learning system, an effective and efficient incremental learning system without the need for deep architecture. IEIE Trans. Neural and Lear. 29 1, 1024, 2018 MathNet. 5 YB He B F SL YL JW, remaining useful life prediction of rolling bearings using PSR, JADE, and Extreme Learning Machine. Maths. 2016 113, 2016. 6 XL B NY CY, dynamic fault prognosis for multivariate degradation process. 275 11 12 1120, 2018. 7 Tipping ME, sparse Bayesian learning and the relevance vector machine. J Mach. Learn. Raise. 13 211 244, 2001 MathNet. 8 Tipping ME AC, fast marginal likelihood maximization for sparse Bayesian models. In Proceedings of the 9th International Workshop on Artificial Intelligence and Statistics. 113 2003. 9 ARB Tor PHS R, multivariate relevance vector machines for tracking. In 9th European Conference on Computer Vision, ECCV 2006, Part III Graz, Austria, May 7-13, 2006. 124 138. 10 ARB Tor PHS R, pose estimation and tracking using multivariate regression. Pattern. 29 1302 1310, 2008. 11 YHAMN, the relevance sample feature machine, a sparse Bayesian learning approach to joint feature sample selection. IEIE Trans. 43.6 22 41 2254, 2013. 12 YHS, incremental relevance sample feature machine, a fast marginal likelihood maximization approach for joint feature selection and classification J. Pattern. 60 835 848, 2016. 13 Wu YMEFA, a modified relevance vector machine for PEM fuel cell stack aging prediction. IEIE Trans. End. 52.3 2573 581, 2016. 14 XB Ding SX Al. Extended relevance vector, machine-based remaining useful life prediction for DC-link capacitor in high-speed train. IEIE Trans. 52.9 9746 9755, 2020. 15 JMF, a generalized Bayes rule for prediction. Scanned. JStat. 26.2 265 279, 1999 MathNet. 16 ZX BAN, multivariate and student T-process regression for multi-output prediction. Neural and 32.8 3005 3028, 2020. 17 XB Wu S Al. Multivariate relevance vector regression, based degradation modeling, and remaining useful life prediction. IEIE Trans. Electron. 69.9 95 14 9523, 2021. 18 Bishop CM, Pattern Recognition and Machine Learning. Springer, New York, 2006. 19 I Training Recurrent Neural Networks, 2013. 16 Equipment Maintenance Analysis with Censored Data. 16.1 Introduction. equipment maintenance plays a pivotal role in extending the of machinery. The prevailing approach to maintenance is scheduled servicing, where equipment is inspected and components are replaced at predetermined intervals. While this method ensures the safety and reliability of equipment operations, it can be resource-intensive. Therefore, it is crucial to develop individual maintenance plans for different equipment based on their degradation conditions 1-2. With the development of industrial digitization, the operational records of equipment throughout their entire are becoming increasingly comprehensive. If we can construct a model using historical maintenance and failure time data from similar types of equipment, we can then predict how long the failure time might be extended by adopting specific maintenance measures for new equipment facing comparable conditions. By integrating the costs of maintenance and the losses from equipment failure, we can make an informed decision on whether to implement those maintenance actions. Similar to analyzing the impact of maintenance measures on the extension of failure times, causal inference analysis of the effects of certain treatment plans on outcomes has garnered a significant amount of research in recent years. 1-2, primarily encompassing studies on the estimation of treatment effects at both the population and individual levels. The estimation of treatment effects at the population level, known as the average treatment effect, 8-3-4, aims to estimate the average prolongation of outcomes for the group of equipment that receives a certain treatment. The individual treatment effect, ITE, is designed to estimate the extension of outcomes for individual equipment units that undergo a particular treatment. 5. At the individual level, the outcomes for the same treatment can vary significantly among different individuals. The estimation of individual treatment effects has been garnering increasing attention. Estimating individual treatment effects from observational data relies on counterfactual analysis methods 6-7. Observational data typically encompasses baseline data, treatment data, and outcome data. The treatment data is classified into two distinct categories, maintained and not maintained. Outcome data can be binary, continuous, or censored. 5-8. Binary outcome data indicates that the outcome can be in one of two states, such as failed or not failed. Continuous outcome data represents measures like the time to equipment degradation. 9. Censored outcome data indicates that the equipment's outcome includes both the time of failure and the state of failure. 8. For the same piece of equipment, there are two potential outcomes under the conditions of being maintained and not being maintained. The individual treatment effect is the difference between these two potential outcomes. 5-10. If the individual treatment effect values are observable for each piece of equipment, it becomes feasible to employ conventional machine learning techniques to construct a mapping function that correlates the individual treatment effect with baseline data. Subsequently, this mapping function can be utilized to forecast the individual treatment effect for new equipment. In practice, if a maintenance plan is applied to a piece of equipment, the outcome of not maintaining it cannot be observed, and vice versa. This implies that for any given equipment, only one of the two potential outcomes, either with or without maintenance, can be observed. The unobserved outcome carries a counterfactual characteristic, meaning that the true value of the individual treatment effect in the observational data, which is the difference between these two potential outcomes, is absent. Therefore, it is not feasible to employ traditional machine learning methods to construct a regression model that links the individual treatment effect with baseline data, such as the current degradation indicators of the equipment. 10. To overcome the difficulties arising from the of counterfactual outcomes, current methods for estimating individual treatment effects begin by fitting models to approximate these unobserved counterfactuals. 11. For instance, in the case of the maintenance group, the potential outcome under non-maintenance is unknown. If the baseline data distributions between the two groups are consistent, one can use data from the non-maintenance group to build a predictive model for outcomes. By fitting this model, one can estimate the counterfactual outcomes and subsequently calculate the estimated values of the individual treatment effects. 12. However, there may be confounding variables in the sample baseline data of observational data, i.e., variables that simultaneously affect both the maintenance decision and the failure time. 10-13. Confounding variables interfere with the accuracy of counterfactual estimations. Therefore, when employing counterfactual analysis methods to estimate individual treatment effects, it is necessary to address the imbalance caused by confounding variables 5. Additionally, in observational data, some equipment may not have failed by the end of the observation period, resulting in observed times that are shorter than the actual failure times 14. In this case, the outcome data is referred to as censored data. In the estimation problem of individual treatment effects based on censored data, not only is the time of the counterfactual outcome unobservable, but the actual failure time may also not be accurately observable. This presents the estimation of individual treatment effects with the dual challenges of confounding variables and censoring of failure data, rendering the aforementioned methods for estimating individual effects for other types of outcome data, including binary and continuous outcome data, inapplicable in a direct manner. 8. Therefore, this chapter will investigate the equipment maintenance decision-making problem based on censored data. It will focus on addressing the shortcomings of existing counterfactual analysis by studying how to separate and balance confounding variables, how to handle data censoring, and how to fully leverage the characteristics of censored data itself. The aim is to enhance the precision of individual treatment effect estimation and provide decision support for the formulation of individual maintenance plans. 16.1.1 The basic concept of individual treatment effect estimation. The relevant concepts of individual treatment effect. A sample typically refers to the unit of study in treatment effect research, such as a piece of equipment, an object, etc. 5. Denote a dataset containing n samples as xm, where each sample xi for I1n includes m-dimensional covariates x. The sample dataset studied in this chapter is the equipment baseline dataset, which contains information on various current indicators of the equipment. Treatment refers to the action taken on the sample 5. This chapter studies the case of binary treatment, where it represents the two possible treatment options, with T1 indicating the treatment plan adopted by the maintenance group or the treatment group, and indicating the plan adopted by the non-maintenance group or the control group. The actual treatment plan used for sample xi is denoted as T. Potential outcome. The outcomes corresponding to the possible treatment plans that a sample may take are referred to as potential outcomes 5. For the same sample, there can be two potential outcomes. In this chapter, let T1 xi and T0 xi represent the potential outcomes for sample I under treatment T1 and non-treatment T0, respectively. The data type of potential outcomes can be binary, continuous, censored, and so on. Confounding variables. Confounding variables refer to variables that simultaneously affect the selection of maintenance plans and the failure time of equipment 5, as shown in Fig. 16.1. The relationships among various variables in the observational data. Non-confounding variables, instrumental variables, predicting variables, noise variables. Non-confounding variables are all variables in the sample baseline data other than confounding variables 5. They include instrumental variables that may only affect the allocation of treatment plans, predicting variables that only affect the outcomes, and noise variables that are unrelated to both the allocation of treatment plans and the outcomes. Literature 17 points out that when balancing confounding variables, it is also necessary to avoid balancing non-confounding variables, as doing so may paradoxically increase the estimation error of the treatment effect. Censoring. Censored data includes the event status and the time experienced until the occurrence of this status 18. Censored data originates from the medical field, where the censored status and failure time of patients are studied 18. In engineering and physics, it is referred to as failure time analysis. In censored data, the outcome consists of two parts, the event status and the observation time. The event status variable is a binary variable, including failure and censoring categories. If the equipment fails during the study, the time from the start of the study to the failure moment is recorded as the failure time, which means the observation time is equal to the failure time. If the equipment may not have failed by the end of the study, or if the failure status cannot be detected for unknown reasons during the study, this event status is called censoring. The time from the start of the study to the last observation when the equipment was not failed is recorded as the censoring time. When the event status is censoring, the observation time equals the censoring time, which is lower than the actual failure time. Furthermore, let be the event status variable, where 1 indicates failure and 0 indicates censoring. Let ZTI12N represent the entire set of observational data for all samples, including observed time, sample baseline data, censoring status, and treatment plan. Let DT111I1NT1 represent the set of observational data for the treatment group samples, and DT000I1NT1 represent the set of observational data for the non-treatment group samples. Clearly, sets DT1 and DT0 are subsets of the set, where NNT1 plus NT0. Assumptions. 1. Independence assumption 5.10. The potential outcomes of any individual sample are unaffected by the treatment choices and outcomes of other samples. This assumption underscores the lack of interaction, suggesting that samples are autonomously independent. Evaluation criteria. The evaluation criteria for individual treatment effect estimation include 2 types: precision in the estimation of heterogeneous effects and the estimation error of the average treatment effect 4.17, defined as follows. 16.1.2. The difficulties of individual treatment effects based on censored data. Estimating individual treatment effects based on censored data faces 2 challenges. On one hand, due to the unobservable counterfactual failure times, it is necessary to fit the counterfactual failure times based on observed data. However, confounding variables in the observed data can cause selection bias, affecting the accuracy of the estimated counterfactual failure times. On the other hand, in addition to the unobservable counterfactual outcomes, the censoring characteristic means that the observed time for some samples may be less than their actual failure time, making it impossible to obtain the true failure time of the samples in the study. Currently, among the methods for estimating individual treatment effects based on censored data, representation learning-based methods have received more systematic research in overcoming selection bias and dealing with censored data. In 2021, al. proposed the Counterfactual Survival Analysis (CSA) Model 8. The CSA model can simultaneously overcome the interference of unobservable counterfactual data and censored data on the estimation of individual treatment effects. Its modeling approach is as follows. Since counterfactual data are unobservable, directly training prediction models for the treatment and control groups can lead to sample distribution imbalances due to the influence of confounding variables. Therefore, the CSA model makes the sample distributions of the 2 groups as close as possible in the feature space, thereby reducing the impact of selection bias. Due to the existence of censored data, after extracting balanced features, the CSA model establishes non-parametric failure prediction models for the treatment and control groups through 2 subnetworks driven by random inputs. Specifically for non-censored samples, i.e. 1. The CSA model guides the failure time prediction Y to approach the observed time. For censored samples, i.e. 0. The CSA model guides the failure time prediction Y to exceed the observed time, thereby ultimately extracting key predictive information from censored failure data. For new samples, the CSA model predicts the potential expected failure times under both treatment and non-treatment conditions, and then uses their difference as the estimated individual treatment effect. Through simulation experiments and semi-synthetic data experiments, demonstrated that in the estimation of individual treatment effects on censored data, the CSA model outperforms models such as Cox, Aft, and BART, meaning that the representation learning-based CSA model currently has relatively optimal estimation performance, superior to meta-learning or decision tree-based methods. However, research on individual treatment effects based on censored data is far from mature, with the main shortcomings or limitations being 1. Utilization of prior knowledge. Among the large number of samples covered by observational data, there may be some samples that conform to existing prior knowledge operational procedures, which have significant reference value for individual treatment effects 20. For samples covered by operational procedures, these procedures effectively provide very valuable qualitative prior knowledge for the counterfactual individual treatment effect results. Although operational procedures may only provide prior knowledge for some samples, and this prior knowledge can only determine the direction of the individual treatment effect 20, i.e., weather is greater than 0, it cannot determine the exact magnitude of the individual treatment effect. However, such prior knowledge can provide important boundary information for estimation. Since the unobservable true individual treatment effect for each sample is the root cause of the difficulties in such estimation problems, operational procedures can directly provide qualitative counterfactual prior knowledge for some samples. But how to integrate such prior knowledge into representation learning methods is a question that warrants further research. In existing methods for estimating individual treatment effects on censored data, we have not seen relevant research. 2. Separation and balancing of multiple types of variables. For continuous or binary outcome data, there have already been numerous studies focusing on how to separate and balance confounding variables while avoiding the balancing of non-confounding variables. However, when estimating individual treatment effects with censored outcome data, the censoring characteristic of the censored data makes it impossible to directly apply existing methods. Current methods based on representation learning, while capable of addressing the estimation of individual treatment effects for censored data, treat all variables as confounders when the sample baseline data consists of multiple types of variables. This could lead to the situation where non-confounding variables are mistakenly balanced, thereby amplifying the estimation errors caused by confounding variables. 16.1.3 Research Focus. This chapter addresses two existing issues in methods for estimating individual treatment effects based on censored data, proposing new approaches from the integration of prior knowledge and the separation of multiple types of variables to enhance the performance of individual treatment effect estimation algorithms. First, considering that existing methods cannot effectively utilize the prior knowledge information, proposes an individual treatment effect estimation method that can incorporate conclusions. Specifically, by formulating a mathematical representation of prior knowledge, constructing a network model with counterfactual prediction branches, and introducing constraints for counterfactual predictions in the loss function to express the prior knowledge, an optimization problem is solved to obtain an individual treatment effect estimation method that embeds prior knowledge. Second, addressing the situation where baseline sample data contain instrumental variables, confounding variables, predictive variables, and noise variables, and considering that existing methods treat all variables as confounders, potentially amplifying estimation errors, proposes an algorithm for estimating individual treatment effects based on the separation and balance reconstruction of multiple variables. Specifically, a multivariable separation model for censored data is first proposed, constructing statistical quantities from hypothesis testing methods related to failure time factors to separate and exclude instrumental variables and noise variables, and designing a feature extraction network to separate confounding variables from predictive variables. Then an expression space is established for the separated confounding variables, balanced, and aggregated with predictive variables to obtain complete information related to individual treatment effects, free from the influence of selection bias. Finally, the data balanced and reconstructed in the expression space are divided into maintenance and non-maintenance groups, predicting failure times and estimating individual treatment effects for each. The subsequent discussion will be elaborated in detail. 16.2 Equipment Maintenance Model Incorporating Prior Knowledge. When estimating maintenance effects based on observational data, prior knowledge, such as operational procedures, can play a significant auxiliary role in the estimation of treatment effects. Typically, operational procedures will indicate whether a specific maintenance measure can extend the failure time under certain conditions, i.e., whether the individual treatment effect value is greater than 0. In the training process of existing individual treatment effect estimation methods, the observed time of samples can only serve as the label or boundary condition for the factual failure time prediction and cannot provide information for the counterfactual failure time prediction. If it is known that several operational procedures can be described as prior knowledge related to individual treatment effects, then such prior knowledge can suggest a potential association between the counterfactual outcomes and factual outcomes. At this time, the observed time of some samples can be transformed into labels or boundary conditions for the prediction of counterfactual outcomes. Therefore, this chapter adds a prediction branch for counterfactual outcomes to the existing model and further designs the loss function to use prior knowledge information to guide the counterfactual failure time predictions to approach their corresponding true values. A method for estimating individual treatment effects that incorporates such prior knowledge is proposed. This chapter first provides the expression form of prior knowledge from operational procedures, then proposes a network model with a counterfactual prediction branch, and revises the loss function, thereby forming an equipment maintenance model that can embed prior knowledge. 16.2.1 Mathematical representation of prior knowledge. Building an individual treatment effect estimation model from observational data may face dual difficulties caused by selection bias and censored data, while the conclusions of operational procedures can provide valuable boundary condition information for individual treatment effects. Below are two examples for illustration. Due to battery aging leading to unstable power supply, mobile phones will automatically reduce the processor frequency, resulting in a lagging phenomenon. Replacing the battery with a new one can provide a stable current output, allowing the processor to return to normal working conditions, thereby enhancing the smooth operation of the mobile phone. If a mobile phone exhibits the following four conditions simultaneously: 1. The battery drains extremely quickly, making it impossible to use without being plugged in. 2. Frequent spontaneous reboots. And 3. Inability to update to a new system, then even replacing the battery will not extend the service life of the mobile phone. Let UT10 represent the potential failure time of device I clearly, based on the research conclusion in example 1. If device I experiences lag, it is reasonable to infer that its effective usage time after battery replacement will be longer 21, i.e. the individual treatment effect value for device I is greater than 0, UT1 UT00. Therefore, when estimating the individual treatment effect of the device based on observational data, i.e. the difference in failure time after not replacing the mobile phone battery, the above prior knowledge can provide directional constraints for the quantitative estimation of the individual treatment effect. Similarly, let UT10 represent the potential failure time of device I clearly, according to the conclusion in example 2. If a device meets three conditions simultaneously, rapid battery drain, frequent spontaneous reboots, and inability to update the system, it can be inferred that there is no significant difference in the failure time of device I whether the battery is replaced or not, i.e. the individual treatment effect value is equal to 0 U0. It is worth noting that when quantitatively estimating the individual treatment effect based on observational data, the observational data includes baseline data, battery replacement status, and failure outcomes, but does not include the difference in failure time between the scenarios of replacing and not replacing the battery. Therefore, prior knowledge, i.e. devices meeting certain conditions show no significant difference in failure time, provides additional constraints for model training. That is, during model training, the objective function should guide the failure time predictions for scenarios with and without battery replacement to show no significant difference. 16.2.2 Embedding prior knowledge in equipment maintenance model. The importance of counterfactual predictions. In the training process of existing individual treatment effect estimation methods, the observed time of samples can only serve as the label or boundary condition for the factual failure time prediction, and cannot provide information for the counterfactual failure time prediction. The original SCI net. In each sample's two potential outcomes UT1 and UT0, only one outcome is the observed outcome, and the other is the counterfactual outcome. If his input into the other branch network GT1T, HT1T, and UT1T, at this time the sample's actual maintenance plan does not match 1T, then the network output YIT1T represents the predicted value of the counterfactual failure time. Since observational data does not have labels or boundary condition information related to counterfactual failure times, existing methods cannot guide the predicted value YIT1T to approach the corresponding counterfactual failure time. In order to fully utilize the prior knowledge, we will add a prediction branch for the counterfactual outcome YIT1T based on the CSA model and further design the loss function to use prior knowledge information to guide the predicted values to approach the corresponding counterfactual failure times. We call the improved model the equipment maintenance model with embedded prior knowledge (EMPK) model. Counterfactual prediction network architecture design. Architecture of the CSA with the addition of counterfactual prediction branches. Architecture of the EMPK. Loss function design. Prior knowledge that YT1 YT00 or YT1 YT00 can provide valuable information for the counterfactual prediction branches of the EMPK model. This section will discuss how to determine the loss function using prior knowledge information under different scenarios where T01, not maintained, i.e. not treated, 01, censored, uncensored, and Y0 or Y0, clear benefit, no clear benefit according to prior knowledge. With prior knowledge Y0, say T0, 1, and Y0. T0, 0, and Y0. T1, 1, and Y0. In this scenario, censoring of the failure time results in YT11, hence the treatment potential outcome YT1 has a lower bound 1, and the non-treatment potential outcome YT0 is a counterfactual outcome. At this point, based on the prior knowledge YT1, YT00, and YT1, 1, it is impossible to determine the relationship between the counterfactual failure outcome YT0 and the observed time 1. Therefore, in this situation, prior knowledge cannot provide effective information for the training of the counterfactual model. Be with prior knowledge Y0 I T1 or 0 and Y0. T1 or 0, 1 and Y0. 16.2.3 Experiments with simulation data. Experiment setting. Experimental results. Quantitative results. Methods. PIOC. Percent V. Percent V. Percent V IMPK. 279.23. Minus 4.21%. 211.43. Minus 2.35%. 73.24. Minus 8.84%. CSA. 291.49. 0%. 216.51. 0%. 80.34. 0%. Casual survival. 292.78. 0.44%. 215.96. 0.25%. 127.29. 58.44%. After 342.71. 17.57%. 239.72. 10.72%. 180.08. 124.15%. Cox 375.33. 28.76%. 252.37. 16.56%. 144.65. 80.05%. The EMPK model is compared with the following algorithms: the CSA model 8, the casual survival model 19, the accelerated failure time model with a log-normal distribution 23, and the Cox proportional hazards model 24. The simulation results are presented in Table 16.1. As can be seen from Table 16.1, the Cox model and the AFT model have the largest individual treatment effect estimation errors PEHE and average treatment effect errors 8. The CSA model and the casual survival model have close individual treatment effect estimation errors, which are reduced compared to the Cox model and the AFT model, indicating that the representation learning-based CSA model and the casual survival model have some effect on balancing confounding variables. Compared to the CSA model, the EMPK model proposed in this chapter further reduces both the individual treatment effect error and the average treatment effect error, outperforming all other methods on the selected dataset. This demonstrates that prior knowledge can provide effective information for counterfactual analysis models, enhancing the algorithm's estimation performance. 16.3 Equipment Maintenance Model based on multivariate variables. In observational data, in addition to confounding variables, there may also exist certain variables that exclusively correlate with either the maintenance strategies or the failure time 525. For example, maintenance funds directly affect to the choice of maintenance strategy. Abundant maintenance funding could increase the likelihood of selecting expensive maintenance strategies. However, expensive maintenance strategies could not ensure a proportional extension of the failure time. For another example, the unmeasurable level of internal degradation in equipment solely impacts the failure time and typically does not influence the maintenance strategies. Additionally, there may be variables that are unrelated to both the maintenance strategies and failure time. According to the definitions in Literature 25-26, variables that affect both the maintenance strategies and failure time are confounding variables, and variables that exclusively correlate with the maintenance strategy allocation without any relation to failure time are termed instrumental variables. Those related to failure time while unrelated to the maintenance strategy allocation are identified as predictive variables, whereas all other variables are categorized as noise variables. A substantial amount of research has been dedicated to addressing the challenge of disentangling and reconstructing multi-type variables in the context of individual treatment effect estimation, particularly when the outcome data is either continuous or binary, such as 27, D2VD 25, Dr. CFR 28, and RCFR methods. In the context of estimating individual treatment effects for data subject to censoring, the category of outcome data transitions beyond the realms of continuity or binary classification. This transformation renders previously effective methods inapplicable. Regrettably, the current research landscape has not yet yielded a strategy capable of precisely separating and reconstructing a spectrum of variables, encompassing instrumental variables, confounding variables, predicting variables, and noise variables, when outcomes are subject to censoring. Therefore, this chapter proposes a novel model for estimating individual treatment effects, termed SCMA, Separate Equipment Maintenance Analysis. This algorithm encompasses three components: variable separation, balanced reconstruction, and failure prediction. The chapter initially integrates the analysis of factors related to failure time with the problem of multivariate separation. It employs hypothesis testing based on factors associated with failure time to exclude instrumental variables and noise variables. A feature extraction network is then designed, leveraging deep orthogonal regularization technology to separate confounding variables from predictive variables. Subsequently, a balancing network is constructed to equate the influence of confounding variables. By aggregating the balanced confounding variables with predictive variables, the algorithm builds a balanced representation of information related to individual treatment effects within the feature space. Ultimately, the algorithm estimates the individual treatment effect by predicting the difference in potential failure times under treated and untreated conditions. 16.3.1 Preliminaries. In the analysis of censored data, univariate analysis is commonly used to exclude variables that are unrelated to the failure time. The methods for univariate analysis include the logrank test 29 and the Cox univariate regression model 30. 16.3.2 Separate Equipment Maintenance Analysis. The diagram of separate equipment maintenance analysis. Variable separation model. The separation model consists of two parts. First, it excludes instrumental variables and noise variables from the set of instrumental variables, confounding variables, predictive variables, and noise variables. Considering that instrumental variables are only related to the maintenance plan and not to the failure time, and noise variables are unrelated to both the maintenance plan and failure time, it is possible to select variables that are only related to failure through hypothesis testing methods. This allows for the elimination of the influence of instrumental and noise variables. We refer to this transformation as the I transformation, as shown in Fig. 16.5. The second part of the separation model further constructs a confounding variable representation network C and a predictive variable representation network A, and introduces corresponding maintenance plan prediction networks C and A based on the predictive performance for the maintenance plan, confounding variables and predictive variables are separated. Balanced reconstruction model. After the separation model, the retained information is directly related to failure time, but confounding variables can lead to inaccurate estimation of individual treatment effects. Therefore, in the balanced reconstruction model, a balanced representation space for confounding variables is first established, making the impact of predictive variables and balanced confounding variables on treatment close to zero. At this point, the two types of variables can be aggregated to obtain complete information related to individual treatment effects after removing selection bias. Failure prediction model. 1633 experiments with simulation data. Experiment setting. In this section, simulated data are generated according to the method in reference 32. The dimensions of the instrumental variables, confounding variables, predictive variables, and noise variables in the data are MI, MC, MA, MN 5555. This chapter compares the SCMA with the following algorithms: I, the CSA Model 8, the Casual Survival Model 19, the Cox Proportional Hazards Model 24, and the Aft Accelerated Failure Time Model 33. Experimental results. Comparison for factors related to failure time. T1, T0, 2, Pi2, PXI1, 1.02, 0.308, 0.633, 0.527, XI2, 2.016, 0.0438, 2.211, 0.027, XI3, 3.104, 1.91E3, 0.436, 0.663, Xi4, 0.708, 0.479, 0.231, 0.818, XI5, 2.318, 0.0204, 2088, 0.0368, XC1, 1233, 2I16, 0.533, 0.594, XZ2, 1469, 2I16, 0045, 0.964, XZ3, 1116, 2I16, 2.703, 6.86I3, XZ4, 1244, 2I16, 0.974, 0.33, XZ5, 2.615, 8.92I3, 1024, 2I16, XN1, 0.1, 0.8, 0.6, 0.4, XN2, 0804, 0.421, 171, 0.0873, XN3, 0.004, 0.95, 4.3, 0.04, XN4, 0.307, 0.759, 0237, 0.813, XN5, 0.9, 0.3, 0.4, 0.5, XA1, 14.14, 2I16, 0836, 0.403, XA2, 1444, 2I16,
0.405, 0.685, XA3, 1.606, 0.108, 10.46, 2I16, XA4, 0.346, 0.729, 16.78, 2I16, XA5, 1026, 0.305, 12.16, 2I16. Comparison of ITE estimation and treatment prediction accuracy. Methods. IoT. Maintenance. Prediction. Percent V. Percent V. Percent V SCMA. 71.07. 25.4%. 35.18. 23.6%. 5.62. 27.4%. C0701. A0538. CSA. 95.25. 0%. 46.07. 0%. 7.74. 0%. Casual survival. 173.29. 81.9%. 98.14. 113%. 19.27. 148.9%. COGS. 137.33. 44.2%. 46.41. 0.74%. 20.36. 163.1%. Left. 153.61. 61.3%. 71.56. 55.3%. 13.54. 74.9%. After excluding instrumental and noise variables, confounding or predictive variables are used to continue network training, and the results of individual treatment effects are shown in Table 16.3. Among them, C represents the accuracy of network CZI in predicting the maintenance plan, and A represents the accuracy of network AZI in predicting the maintenance plan. C being 0.7 indicates good predictive performance, which suggests that network CZI contains information related to maintenance, i.e., confounding variable information. Meanwhile, A being close to 0.5 indicates that network AZI has no value in predicting the maintenance plan, which is because network AZI contains information unrelated to maintenance, i.e., predictive variable information. The experimental results show that the outcomes of information extraction by network CZI and AZI are consistent with the expected goals, i.e., network CZI has extracted confounding variable information, and network AZI has extracted predictive variable information. In terms of performance in estimating treatment effects, let represent the value of each evaluation metric, and %V indicate the change rate compared to the baseline model CSA. It can be observed that the individual treatment effect estimation error and the average treatment effect estimation error of the SCMA model are all lower than those of the CSA model. The individual treatment effect estimation error and the average treatment effect estimation error of the causal forest model and the AFT model are higher than those of the SCMA model and the CSA model. The estimation error of the Cox proportional hazard model also has higher errors than the SCMA model and the CSA model. The simulation results indicate that the SCMA algorithm can effectively enhance the estimation accuracy of individual treatment effects, which has potential value for the individual formulation of equipment maintenance plans. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format,
as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the licensed material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. GWDB, Causal Inference for Statistics, Social and Biomedical Sciences, An Introduction. Cambridge University Press, 2015. 2b. Causality for Machine Learning, First ed. Association for Computing Machinery, New York, NY, USA, 2022, p. 765-804. 3. Hogan, J.W. and Biometrics 75-2, 708-709, 2019. 4d. Causal Inference Using Potential Outcomes, Design Modeling Decisions. J. Stat. 100, 322, 331, 2005. 5. Yao Lz Li S Li Y J A, A Survey on Causal Inference. ACM Trans. Data 15.5, 2021. 6. U FDD, Estimating Individual Treatment Effect, Generalization Bounds and Algorithms. INS Ds YW. Proceedings of the 34th International Conference on Machine Learning, Series Proceedings of Machine Learning Research. 70. PMLR 611, 2017. 3076-3085. 7. FDUD, Learning Representations for Counterfactual Inference, 2018. 8. PSSMJ-LR, Enabling Counterfactual Survival Analysis with Balanced Representations. In Proceedings of the Conference on Health, Inference, and Learning Series. ACM CHIL 21. ACM 2021. 133-145. 9. Glass TA Goodman SN MA JM, Causal Inference in Public Health. Rev. Public Health 34, 6175, 2013. 10. MA Causal Inference, What If? In Robbins, J.M. ed. Taylor and Francis Boca, 2024. 11. Lee Z. X. S., A Survey of Deep Causal Models and Their Industrial Applications, 2024. 12. MCF Y. M. J. S. Min J. He X. Rich SN M. IE J. Causal Inference and Counterfactual Prediction in Machine Learning for Actionable Healthcare. Nature Mock. 2. 369, 375, 2020. 13. Peters, J. D. B. Elements of Causal Inference, Foundations and Learning Algorithms, 2017. 14. Survival Analysis, Models and Applications. Survival Analysis, Models and Applications, 2012. 15. Luo Y. Peng J. Ma J. When Causal Inference Meets Deep Learning. Nature Mock. 2. 426, 427, 2020. 16. T. A. D. Manny S. Explaining Deep Learning Models Using Causal Inference, 2018. 17. J. A. J. A. J. J. K. F. S. K. J. M. M. Glynn R. J. Effects of Adjusting for Instrumental Variables on Bias and Precision of Effect Estimates. J. 17411, 121322, 2011. 18. P. Lei Y. Reddy CK, Machine Learning for Survival Analysis, A Survey, 2017. 19. Y. M. E. Wager S. R. Estimating Heterogeneous Treatment Effects with Right-Censored Data via Causal Survival Forests. J. R. Stat. So. Sir. B. Stat. 85-2, 2023 MathNet. 20. E. J. J. Controlled Trials, the Gold Standard for Effectiveness Research. Bajay OG. J. and 125-13, 1716-1716, 2018. 21 mg AEC MRANJW RAJJ Amir E as first-line therapy in patients with advanced child B hepatocellular carcinoma, a meta-analysis. J Cancer 105 19 2018. 22 Hammer SM, DA Hughes MD, H, RT, RH Henry WK, MM, JP, M, MS, TC. A trial comparing nucleoside with combination therapy in infected adults with SEED4 cell counts from 200 to 500 per cubic millimeter. New England J. Med. 33515, 10811090, 1996. 23 P. Lay Y. Reddy CK, Machine Learning for Survival Analysis, a survey 2017. ABS 170804649. 24 SM, GG, Lay, SI, Consistent Individualized Feature Attribution for Tree Ensembles 2019. 25 K. P. Lay B. M. Yang S. F. Treatment Effect Estimation with Data-Driven Variable Decomposition. Proc. AAAI Conf. 31-2-2017. 26 K. P. H. Lee B. Tao J. Wu F. Yang S. Data-Driven Variable Decomposition for Treatment Effect Estimation. IEIE Trans. Data. 34-5-2122-134, 2022. 27 C. DM V. Adapting Neural Networks for the Estimation of Treatment Effects, 2019. 28 N. R. Learning Disentangled Representations for Counterfactual Regression. In International Conference on Learning Representations, 2020. 29 DG M. Survival Curves in the Lagrange Test, 2012. 30 SI. The Statistic in Proportional Hazards Hypothesis Testing. J31-2, 203-2, 11, 1989. 31 Wu A. Yuan J. K. Li B. Wu R. Q. Y. Wu F. Learning Decomposed Representations for Treatment Effect Estimation. IEIE Trans. Data. 35-5-4989-500-1, 2023. 32 L. J. Lay F. Estimating Heterogeneous Survival Treatment Effect in Observational Data Using Machine Learning. Stat. Med. 4021, 4691 4713, 2021 MathNet. 33 H. UB IH MS. Random Survival Forests. Stat. 23 2008. 17. Nonlinear Quality-Related Fault Diagnosis. Abstract. Over the past decade, quality-related fault detection and diagnosis, as an important branch of multivariate statistical process monitoring, has become a critical component of industrial process monitoring. As one of the pioneering research teams in this field, we have achieved significant research outcomes. In particular, we have proposed many effective methods in nonlinear quality-related fault modeling, detection, isolation, and root cause analysis. In this chapter, we will provide a detailed summary and review of these methods and validate them through simulations using numerical examples and industrial case studies. We hope this will serve as a valuable reference for future research. Nomenclature. A number of latent variables for PLS. Composite statistic. See covariance matrix of Xi. Feature vector. Contribution of variable 2. Feature matrix. 2H. 2 distribution. Principal subspace of D, LWPR local model positive distance metrics. Residual space of D Euclidean distance matrix. P loading matrix of X E cross covariance matrix of and Y Q loading matrix of Y. Residual space of YR scalar set. Kernel function. M-dimensional vectors set. A B. F distribution. M. NM matrices set. G scaling factor. Reconstruction contribution 2. Number of latent variables for KPLS. T score vector. HI conditional entropy rate. T-score matrix. I subscript of observation data, corresponding to the number of rows of the data matrix. Random noise with zero mean. J subscript of variable, corresponding to the number of columns of the data matrix. W weights for LWPR local model. T2. Threshold for T2 statistic. X observation sample for multidimensional process variables. SBI. Threshold for SBI statistic. Centers of local subsets. K number of LWPR local models. Online sample. K kernel sample matrix. X process variable matrix. L number of quality variables. X principal subspace of XM number of process variables. X residual space of X. Regression coefficient matrix of X and Y observation samples for multidimensional quality variables. Regression coefficient matrix of T and Y quality variable matrix. Regression coefficient matrix of and YY principal subspace of YN number of training samples. Pseudo-inverse. N2. Normal distribution. 1NN dimensional column vector of ones. Number of principal components. NN identity matrix. 17.1 Introduction. Modern industrial production is characterized by large-scale operations and complex processes. Alongside improving control system performance, it is essential to ensure the safety, efficiency, and reliability of these systems, which places high demands on the monitoring and fault diagnosis of industrial processes. Since process information is often hidden in vast amounts of historical data, data-driven methods are naturally chosen as an effective monitoring tool for such processes. 1. Compared to model-based approaches, the main advantage of data-driven methods is their reliance solely on measurable process data, without the need for explicit models. As a typical data-driven technology, multivariate statistical process monitoring, MSPM, has demonstrated its effectiveness in numerous industrial applications. 2.4. Several popular data-driven methods are described and compared in the literature. 5, including principal component analysis, PCA, partial least squares, PLS, regression, and subspace-assisted approach, SAP. Notably, nonlinear characteristics are prevalent in real industrial processes. These processes tend to exhibit behavior that is more complex than linear processes, making it challenging to describe them with simple linear models. As a result, the design and implementation of fault detection models for nonlinear processes require more sophisticated algorithms and models. To address this, methods such as kernel PCA KPCA 6 and kernel PLS KPLS 7 have been introduced, which map process variables to a feature space 8, thereby mitigating the nonlinearities among variables. The introduction of the kernel trick significantly simplifies the computation of these methods, making the implementation of KPCA and KPLS-based fault detection as simple as PCA and PLS-based methods. Quality-related fault detection, FDD 911, is a research hotspot for MSPM extracted from the manufacturing industry. The concept originated from the work of Joe Al. 9 has seen significant development over the past decade. 12. It examines the interesting phenomenon that not all process faults inevitably lead to fluctuations in product quality. Ignoring fault alarms that do not impact product quality can greatly reduce unnecessary plant downtime and maintenance, leading to economic benefits. 13.14. The goal of FDD is to achieve a more targeted categorization of process faults, distinguishing those that affect product quality from those that do not. Among them, Peng al. 15 proposed the first nonlinear quality-related fault detection method based on the KPLS model, called Total KPLS (TKPLS). Shortly thereafter, al. 16 extended the linear approach used in 17 to a nonlinear version based on the KPLS model. And al. 18 implemented another nonlinear method using the KPLS model and singular value decomposition, SVD. Although the above nonlinear methods show promise in detecting quality-related faults, they still have shortcomings in terms of stability, computational efficiency, and diagnostic logic complexity. In this chapter, we will summarize the last 10 years of nonlinear quality-related fault detection methods, in which the local weighted projection regression (LWPR) method models the nonlinear process through LWPR and monitors each local model using a modified PLS-based fault detection scheme, and the global diagnostic output of the system is calculated from the normalized weighted average of all local models 1920. The improved kernel method involves only eigenvalue solving and SVD, which has a simple logic and uses only two subspaces 21. The modified kernel least squares (MKLS) method takes full advantage of the correlation between the feature matrix and the output matrix to ensure the stability of the design method, and eliminates the iterative computation of the KPLS model with the determination of the number of latent variables, which makes it more efficient to implement 22. The kernel direct decomposition (KDD) algorithm directly decomposes the feature matrix into two orthogonal components based on the complete correlation between the feature matrix and the output matrix without the need to build a regression model, and it is simpler in design than the traditional methods 23. The kernel principal component analysis kernel variable equivalent replacement (KPCAKSER) method, by establishing the proportionality between the variance, covariance matrix of the centralized process variable matrix and the centralized kernel matrix, converts the nonlinear detection indicators into explicit quadratic forms of the variable samples, which in turn allows for the direct application of contribution plot and reconstruction-based contribution (RBC) methods with very limited computational effort to kernel-based fault diagnosis 24. The kernel principal component analysis canonical correlation analysis (KPCACCA) method achieves low algorithmic complexity 25 while maintaining high interpretability by using a score matrix T for CCA modeling. The orthogonal kernel principal component regression (OKPCR) method constructs an OKPCR model for orthogonal decomposition of the feature space and applies the transfer entropy algorithm to the new model to analyze the causality between the candidate fault variables of the diagnosis to find the exact root cause of the fault 26. Finally, the validity of the proposed method is through numerical examples and the Tennessee-Eastman (TE) process, which is hoped to provide a potential reference value for subsequent research in related fields. 17.2 Locally weighted projection regression-based fault detection method. 17.2.1 PLS and PLS-based fault detection algorithms. 17.2.2 Modified PLS algorithm. 1 NYTX 1 NTXTX plus 1 NTX TXTXN. 1 pagination perform SVD on matrix TT000T 17.11 where LMLL. 2 construct the orthogonal projections and on span and span respectively, i.e. TT3 project X onto and respectively to obtain 2 orthogonal subspaces X and XXT span 17.12 XD span 17.13. Compared with the traditional PLS model, the above process realizes the ideal decomposition of X and Y shown in 17.1 and 17.9 and avoids the detrimental effects of incomplete decomposition of the PLS algorithm on fault detection. The modified model provides a clearer interpretation of the correlation model and has a smaller computational load. 17.2.3 LWPR learning model. 1. The system should satisfy the basic assumption of LWPR, which is a local low-dimensional distribution. The system should satisfy the basic assumption of LWPR, which is a local low-dimensional distribution. 2. To obtain satisfactory learning results, the learning parameters of LWPR should be selected reasonably. To obtain satisfactory learning results, the learning parameters of LWPR should be selected reasonably. For the first point, a large amount of real-world data satisfies this assumption. Fortunately, researchers can get guidance from the supplemental documentation of LWPR, in which the authors provide a detailed description of the choice of learning parameters 28. 17.2.4 LWPR-based fault detection scheme. 1. In the offline modeling phase, an LWPR model is trained with normal samples, and the modified PLS fault detection algorithm is implemented in each local model. In the offline modeling phase, an LWPR model is trained with normal samples, and the modified PLS fault detection algorithm is implemented in each local model. 2. In the online monitoring phase, the weights of one sample over all receptive fields are calculated, followed by the appropriate test statistics for each local model. The weighted average of all test statistics in these local models constitutes the global diagnostic output. In the online monitoring phase, the weights of one sample over all receptive fields are calculated, followed by the appropriate test statistics for each local model. The weighted average of all test statistics in these local models constitutes the global diagnostic output. 1 TRNM 1 TRNL 17.3 Modified Kernel-Based Fault Detection Method 17.3.1 KPLS Algorithm 1 Let I1 Y1 YK1 K Let I1 Y1 YK1 K2 Let be the first column of Y. Let be the first column of Y. 3 Calculate TK. Calculate TK. 4 Normalize TTT. Normalize TTT. 5 Calculate CI. Calculate CI. 6 Normalize. Normalize. 7 Determine if T converges. If so, skip to step 8. If not, repeat steps 3 through 6. Determine if T converges. If so, skip to step 8. If not, repeat steps 3 through 6. 8 Calculate Ki plus 1 in to tt Ki in to tt. Y plus 1 in to tt y. Calculate Ki plus 1 in to tt Ki in to tt. Y plus 1 in to tt y. 9 Save parameters ttt uu. Save parameters ttt uu. 10 Let I plus 1 and repeat steps 2 through 9 until I. Let I plus 1 and repeat steps 2 through 9 until I. Previous research has further decomposed the KPLS models described above. While these methods demonstrate high effectiveness, they are still associated with considerable computational overhead due to the iterative properties of KPLS. In the following section, we introduce a modified kernel method termed MKPLS, which offers a more streamlined implementation. 17.3.2 Modified Kernel Method 1. Calculate the mean of the eigenvalues. Calculate the mean of the eigenvalues. 2. Search for eigenvalues in descending order until the nth eigenvalue is less than the mean, then n1. Search for eigenvalues in descending order until the nth eigenvalue is less than the mean, then n1. So far, by solving the eigenvalue problem in 17.47, the feature matrix has been transformed into score matrix T. As a result, the process faults now included can be reflected by the monitoring results of T17.3.3 Modified Kernel Method-Based Fault Detection Scheme. 17.4 Modified Kernel Least Squares-Based Fault Detection Method. 17.4.1 KLS Model. 1. Establish a kernel least squares KLS model to calculate the regression coefficient matrix between and y, whereby contains a complete correlation between and y. Establish a kernel least squares KLS model to calculate the regression coefficient matrix between and y, whereby contains a complete correlation between and y2. Project onto the spatial span and the corresponding orthogonal complementary spatial span, respectively, such that has the opposite correlation to the output projection matrix. Project onto the spatial span and the corresponding orthogonal complementary spatial span, respectively, such that has the opposite correlation to the output projection matrix. 3. Design of test statistics in the subspace corresponding to the projection matrix for quality-related fault detection. Design of test statistics in the subspace corresponding to the projection matrix for quality-related fault detection. 17.4.2 MKLS Model. Now let us return to 17.81. For the SVD of 17.81, we have the following theorem. U1 U1 URN U2 U plus 1 U N RNN. The above provides a detailed derivation of the proposed MKLS method. In the next section, we will design a new nonlinear fault detection method based on the conclusions drawn. 1743 MKLS-based fault detection scheme. In the previous section was decomposed into and based on its full correlation with why this section addresses the final step, designing appropriate statistics for the corresponding subspaces of and given an online sample, and following the procedure outlined in sect. 1733, it is mapped into the feature space F, resulting in calculate the online kernel sample nu and center it to obtain K nu. Since rank W1 W1T rank W1T, we have rank W1T, therefore, W1 is a suitable candidate for T2 statistic. 17.5 Kernel Direct Decomposition-Based Fault Detection Method. 17.5.1 KDD Algorithm. Above is the detailed derivation of the proposed KDD algorithm. Based on this conclusion, we will design a new nonlinear quality-related fault detection method in the next section. 17.5.2 KDD-based fault detection scheme. In the previous section was decomposed into and based on its full correlation with why this section focuses on designing appropriate statistics within the subspaces, and first, for a new online sample, we map it into the feature space F, resulting in Rm. The corresponding zero-mean online kernel vector is denoted as K nu T. Since S rank U11 U11 T rank U11 TS, we have rank U11 TS. Therefore, U11 is a suitable candidate for T2 statistic. 17.6 Kernel Principal Component Analysis Kernel Sample Equivalent Replacement-Based Fault Detection and Diagnosis Method. 17.6.1 KPCA-based fault detection and diagnosis. One physical meaning is not intuitive, as can be seen from 17.175. The expression of Cj is so complex that it is difficult to intuitively understand its physical meaning. Physical meaning is not intuitive, as can be seen from 17.175. The expression of Cj is so complex that it is difficult to intuitively understand its physical meaning. 2. Algorithm scalability is limited. Cj is not an explicit quadratic form of, making it challenging to extend to KPCA or integrate with other PCA-based fault detection and diagnosis algorithms, such as RBC, using 17.175. Algorithm scalability is limited. Cj is not an explicit quadratic form of, making it challenging to extend to KPCA or integrate with other PCA-based fault detection and diagnosis algorithms, such as RBC, using 17.175. 3. Computational effort is huge for a single sample. 17.176 needs to perform MN2 differential operations. Assuming that a sample consists of 6 variables and there are 1,000 training samples, the total computational time for 17.176 in the MATLAB simulation on our computer is about 2 hours. In addition, adding the computational time for 17.175 and 17.177, this is far from acceptable in practice. Computational effort is huge for a single sample. 17.176 needs to perform MN2 differential operations. Assuming that a sample consists of 6 variables and there are 1,000 training samples, the total computational time for 17.176 in the MATLAB simulation on our computer is about 2 hours. In addition, adding the computational time for 17.175 and 17.177, this is far from acceptable in practice. To address the above problem, we will introduce a new solution idea based on kernel sample equivalent replacement, KSER, in the next subsection. 17.6.2 KSER-based fault diagnosis idea. Since all variables contribute equally to, the contribution of each variable to is determined only by. Furthermore, it can be observed from 17.181 that if there is some proportionality between and K nu, then can be expressed as explicit quadratic form of. Note that this would be very useful because it enables KPCA-based fault diagnosis methods to use contribution plot or RBC directly, without the need to calculate kernel gradients, thus greatly simplifying the computational effort and diagnostic time of kernel-based methods. Up to this point, the key to the KSER method is to find the proportionality between and K nu. Next, we will seek the proportionality and give a proof. 1763 KSER Theory and Derivation. 1764 KPCA KSER-based fault diagnosis scheme. 1. Normalize each C to ensure that all variables contribute equally to the C1N1N12XN2, 17.199. 2C is further divided by the sum of all normalized contributions, J1MC, to eliminate the influence of smearing effects. CCJ1MC 17.2. The corresponding threshold is suggested to be chosen as C2 plus 1M2, 17.201, where CC1CT 17.7 kernel principal component analysis canonical correlation analysis-based fault detection and diagnosis method. 17.7.1 KPCA-CCA model. In the previous section, we established the KPCA model for where the score matrix T contains all the kernel principal components, KPCs of the feature matrix. Next, T will be used as input data along with Y to build a canonical correlation analysis CCA model. 17.7.2 KPCA-CCA-based fault detection indicators and fault diagnosis algorithms. 17.8 Orthogonal kernel principal component regression and transfer entropy for fault detection and root cause diagnosis. 17.8.1 OKPCR model. 17.8.2 KSER-based OKPCR fault diagnosis scheme. 4 C2X-TUTT and 1-1-TUTX 4 C2X-TTUTT 1-TKT-T and 1-1-TUTT 1-TKT-TX 17.8.3 Transfer entropy-based root cause analysis. 17.9 Simulation and case studies. 17.9 1 Numerical simulation study. Fault 1 A step deviation occurs in X1, X1 plus F. Fault 1 A step deviation occurs in X1, X1 plus F. Fault 2 A step deviation occurs in X2, X2 plus F. Fault 2 A step deviation occurs in X2, X2 plus F. Fault 3 A slope deviation occurs in X1, X1 plus K200F. Fault 3 A slope deviation occurs in X1, X1 plus K200F. Fault 4 A slope deviation occurs in X2, X2 plus K200F. Fault 4 A slope deviation occurs in X2, X2 plus K200F. LWPR-based detection results under Fault 1. A prediction results. B T2 and T2 statistics. LWPR-based detection results under Fault 12. A prediction results. B T2 and T2 statistics. Detection results based on improved kernel method. A Fault 1. B Fault 2. MKLS-based detection results. A Fault 1. B Fault 2. KDID-based detection results. A Fault 1. B Fault 2. KPCA-CCA-based detection results. A Fault 1. B Fault 2. Detection and isolation results based on OKPCR under Fault 1. A detection result. B isolation result. Detection and isolation results based on OKPCR under Fault 2. A detection result. B isolation result. The simulation results of the LWPR-based fault detection method are shown in Figs. 17.1 and 17.2, where T2 denotes the quality-related detection indicator of the monitoring subspace X and T2 denotes the quality-unrelated detection indicator of the monitoring subspace X for Fault 1. The detection results are shown in Fig. 17.1. As shown in Fig. 17.1. The predicted output of LWPR starts to deviate from the true value when the fault occurs at the 201st sample. As shown in Fig. 17.1b, the T2 and T2 statistics accurately detect Fault 1 in time. For Fault 2, the detection results are shown in Fig. 17.2. Since Fault 2 is quality unrelated and does not affect the output Y, the LWPR predicts the output of the nonlinear system well. In Fig. 17.2b, the T2 statistic remains stable and responds accurately to the effect of the fault on the predicted output, and the T2 statistic detects the occurrence of the fault well. The fault detection results based on the modified kernel method are shown in Fig. 17.3, with the kernel function parameters set to C103. The fault is injected at the 201st sampling moment, at which time the T2 and T2 statistics quickly detect the occurrence of the fault. As shown in Fig. 17.3 and b, the T2 statistic can accurately differentiate between quality-related fault 1 and quality-unrelated fault 2. For this numerical example, the fault detection effect is similar to that of LWPR. However, the kernel method simplifies the process by eliminating the need for segmented and extensive parameter tuning required by the LWPR model. The results of MKLS-based fault detection are shown in Fig. 17.4 with C104. In Fig. 17.4, a strong alarm occurs for the 2 statistic, indicating that fault 1 has a significant effect on the quality variable. Whereas for fault 2, it can be seen from Fig. 17.4b that the fault only has an alarm in, while it does not have any alarm in 2. Hence it can be readily understood that a fault occurs from the test result, but that fault does not affect the quality variable. The results of KDD-based fault detection are shown in Fig. 17.5 with S1C104. The 2 statistic is responsible for the monitoring of quality-related faults, and the is responsible for the monitoring of quality-unrelated faults. In Figs. 17.5 and b, the 2 and statistics give accurate and fast alarms for both faults 1 and 2, and the extent to which the faults are correlated to the quality variables can be easily and accurately determined from the changes in the 2 statistics. Similarly, the results of KPCA-CCA-based fault detection are shown in Fig. 17.6 with C145. In Fig. 17.6 and b, both T2 and T2 statistics make accurate and fast alarms, and it can be easily determined whether the faults are quality-related or not from the T2 statistic. The results of OKPCR-based fault detection and isolation are shown in Figs. 17.7 and 17.8 with C145. For fault 1, since variable x1 affects x3, x4 and the output y, the T2 statistic efficiently provides quality-related fault alerts, and the model isolates the faulty variables x1, x3, and x4 relatively accurately. For fault 2, the faults in variable x2 affect only x4 and is unrelated to why the T2 statistic rapidly develops fault alerts, while no alerts occur in T2. Therefore, the fault can be classified as a quality-unrelated fault, and the model accurately isolates the fault variables x2 and x5. It is worth noting that a small number of normal variables are misclassified as fault variables due to smearing effects. This is a common issue in contribution plot, RBC, and most fault diagnosis methods. FDRs of quality-related detection indicators under fault 1 and FARs under fault 2%. FLWPR, MKPLS, MKLS, KD, KPCA-CCA, KPCR, T2, T2, 2, 2, T2, T2, 0.1, 100 a 10B, 100 a 05B, 100 a 10B, 100 a 10B, 100 a 10B, 100 a 05B, 0.2, 100 a 15B, 100 a 10B, 100 a 10B, 100 a 10B, 100 a 10B, 100 a 05B, 0.3, 100 a 15B, 100 a 10B, 100 a 20B,
100 a 15B, 100 a 15B, 100 a 10B, 0.4, 100 a 20B, 100 a 15B, 100 a 20B, 100 a 20B, 100 a 40B, 100 a 10B, a FDR, B far, FDRs of quality-related detection indicators under fault 3 and FARs under fault 4%. FLWPR, MKPLS, MKLS, KOI.D, KOI+CICCI, KPCR, Tai2, Tai2, 2, 2, Tai2, Tai2, 0.001, 88 a 05B, 87 a 05B, 87.5 a 05B, 88 a 10B, 85 a 10B, 88 a 05B, 0.002, 93 a 05B, 93.5 a 10B, 93.5 a 05B, 94 a 10B, 91.5 a 10B, 94 a 05B, 0.003, 95.5 a 10B, 96.5 a 10B, 96 a 10B, 95.5 a 15B, 94.5 a 15B, 96 a 10B, 0.004, 98 a 15B, 98 a 15B, 97 a 15B, 96.5 a 20B, 96.5 a 15B, 97 a 10B, a FDR, B far, 1792 TA process case study. Of TA, there are 21 known faults in TIDV1 to IDV21, which can be broadly categorized into three classes from the point of view of their impact on output. Why the first category has a serious impact on Y, such as IDV6, IDV8, IDV12, and IDV18. The second category has effects on Y for some time due to the presence of a fault-tolerant controller, FTC, and these effects are eliminated as the FTC becomes fully functional, e.g. IDV1, IDV5, etc. The third category has almost no effect on Y, such as IDV4, IDV9, IDV11, IDV14, etc. FDRs of quality-related detection indicators for 21 types of faults in TE processes, %. Fault LWPR, MKPLS, MKLS, KOI.D, KOI+CICCI, KPCR, Tai2, Tai2, 2, 2, Tai2, Tai2, IDV1, 36.25, 26.13, 40, 40.5, 39.65, 27.18, 68, IDV2, 20.63, 84.88, 96, 27.63, 23.84, 17.76, 31.38, IDV3, 8.13, 5, 6.63, 3, 2.89, 3.9, 7.13, IDV4, 18.75, 17.75, 5, 0.38, 0.38, 2.27, 3.63, IDV5, 30.63, 26.5, 15.88, 19.38, 19.32, 17.38, 24.75, IDV6, 92.5, 95.63, 97.38, 96.13, 95.36, 100, 100, IDV7, 35, 26.38, 29, 34.88, 34.76, 29.47, 40, IDV8, 60, 53, 58.88, 57.88, 57.72, 62.22, 77.13, IDV9, 0, 1.38, 2.88, 1.75, 1.63, 2.52, 8.75, IDV10, 18.75, 10, 20.25, 29.5, 29.61, 21.91, 78.3, IDV11, 8.75, 5, 1.63, 1, 1, 7.81, 7.88, IDV12, 62.5, 43, 66.25, 69.38, 69.13, 64.61, 77.63, IDV13, 81.25, 73.5, 86.5, 75.88, 75.53, 79.22, IDV14, 1.88, 1.25, 0.5, 0.88, 0.88, 3.4, 7, IDV15, 7.5, 13.5, 5.88, 1.25, 1.25, 7.17, 5, IDV16, 5.63, 4.75, 17, 19.13, 19.07, 10.38, 73.75, IDV 17, 17.5, 3.88, 9.38, 41, 39.4, 47.61, 53, IDV 18, 82.5, 72.92, 86.13, 86.25, 86.45, 85.26, 85.25, IDV 19, 2.5, 1.38, 3.5, 0.38, 0.38, 6.29, 11.5, IDV 20, 10, 20.88, 3.25, 23.63, 23.59, 70.4, 23.25. IDV 21. 13.13. 16.5. 13.75. 31.13. 30.87. 0.38. 19.63. Fault diagnostic results of the 170th sample RBC for IDV14. Diagnostic computation time of the proposed method and TKPLS for IDV14. Fault proposed TKPLS offline, online, offline, online, IDV14. 5.81942 S00335593 S24H3H fault isolation results for IDV14. Transfer entropy coefficient for IVD14. TJ X2, X9, X11, X21, X23, X32, X2, 0, 07807, 03067, 05715, 00043, 08089, X9, 0.7807, 0, 0.4732, 0.1279, 0.7413, 00310, X11, 0.3067, 04732, 0, 02993, 0.2179, 04078, X21, 0.5715, 01279, 0.2993, 0, 0.6178, 01504, X23, 0.0043, 07413, 02179, 06178, 0, 07820, X32, 0.8089, 0.031, 0.4078, 0.1504, 0.782, 0. Causality analysis result for IDV14. 17.1 Conclusion. In this contribution, we summarized nonlinear quality-related fault diagnosis methods proposed over the last 15 years. These methods are particularly well-suited for data-based monitoring of industrial nonlinear processes and can effectively differentiate between quality-related and quality-unrelated faults. In particular, our proposed LWPR, modified kernel, MKLS, KDD, KPCACCA, and OKPCR-based methods can effectively model nonlinear processes and enable separate detection of quality-related and quality-unrelated faults in the subspaces of opposite correlations to the output, without mutual interference. Additionally, the KSER technique we proposed has been successfully applied to nonlinear diagnostic problems based on kernel functions. By transforming the nonlinear detection index into an explicit quadratic form of variable samples, the contribution plots and RBC can be directly applied to the kernel function-based fault diagnosis with minimal computational effort. To further eliminate the smearing effect, we propose the RBC isolation algorithm to minimize the impact on fault isolation. Moreover, we have successfully applied the transfer entropy algorithm to the new model to analyze the causal relationship between the candidate fault variables, thereby identifying the accurate root cause of faults. To make a correct final decision, a rational evaluation method and decision logic are provided. Finally, the effectiveness of the proposed methods is by the fault diagnosis results from a numerical example and the TE process.
Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the licensed material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Yin S Ding SX X Luo H. A review on basic data-driven approaches for industrial process monitoring. IEIE Trans. And Electron. 6111, 6418, 642, 8, 2014. 2J Casey. Online batch process monitoring using dynamic and dynamic models. 57-1, 6375, 2002. 3 EL LH RD. Fault detection in industrial processes using canonical variate analysis and dynamic principal component analysis. Lab. 51-1, 8193, 2000. 4 Cherry G.A. Chin, S.J. Principal component analysis based on a combined index for semiconductor fault detection and diagnosis. IEIE Trans. Manuf. 19-2, 159, 172, 2006. 5 Yin S Ding SX A H P. A comparison study of basic data-driven fault diagnosis and process monitoring methods on the benchmark Tennessee Eastman process. J Process Control 22-9, 1567, 1581, 2012. 6 Lay JM CK SW PA Lay IB. Nonlinear process monitoring using kernel principal component analysis. 59-1, 223-2, 34, 2004. 7 R L. Kernel partial least squares regression in reproducing kernel space. J Mach. Learn. Raise. 297 123, 2001. 8 J. Quality relevant nonlinear batch process performance monitoring using a kernel-based multi-way non-latent subspace projection approach. J Process Control 24-1, 5771, 2014. 9 Zhou D. Lei Ji Zhou Chin S. Total projection to latent structures for process monitoring. Ali J 56-1, 168 178, 2010. 10 Zhou Chin S. Survey on Data-Driven Industrial Process Monitoring and Diagnosis. Rev. Control 36-2, 222-34, 2012. 11 K H Z Ding SX Peng K. A comparison and evaluation of key performance indicator-based multivariate statistics process monitoring approaches. J Process Control 33, 112, 126, 2015. 12 Sun CY Yin YZ HB Ma HJ. A quality-related fault detection method based on the dynamic data-driven algorithm for industrial systems. IEIE Trans. 19-4, 3942, 3952, 2022. 13 Peng K. K. Dong J. U. B. Quality-relevant fault detection and diagnosis for hot strip mill process with multi-specification and multi-batch measurements. J. Franklin. Math. 352-3, 987-1006, 2015. 14 G. Luo H. Peng K. Quality-related fault detection using linear and nonlinear principal component regression. J. Franklin. Math. 353-10, 2159-2177, 2016 MathNet. 15 Peng K. K. Lei G. Quality-related process monitoring based on total kernel model and its industrial application. Math.
2013. 16 Y Sun R Fan Y. Fault diagnosis of nonlinear process based on reconstruction. Lab 140 49 60 2015. 17 Zhou Chin S. Y. Quality relevant and process relevant fault monitoring with concurrent projection to latent structures. Ali J 59 2 496 504 2013. 18 Q Y. Quality related fault detection approach based on dynamic kernel partial least squares. Raise 106 242 252 2016. 19 G Yin S. O. and base data-driven fault detection approach for nonlinear process monitoring. IEIE Trans. And 10-4 2016 2023 2014. 20 Yin S Ding SX PAA Study on Modifications of Approach for Process Monitoring. IFAC Proc. 44-1 12389 12394 2011. 18th IFAC World Congress. 21 G Jiao J. Nonlinear fault detection based on an improved kernel approach. IAAE Access 6, 11017 11023 2018. 22 G Jiao J. A kernel least squares based approach for nonlinear quality-related fault detection. IAEE Trans. And Electron 64-4 3195 3204 2017. 23 G Jiao J Yin S. A kernel direct decomposition-based monitoring approach for nonlinear quality-related fault detection. IAEE Trans. And 13-4 1565 1574 2017. 24 G Jiao J Yin S. Efficient nonlinear fault diagnosis based on kernel sample equivalent replacement. IAEE Trans. And 15-5 2682 2690 2019. 25 G Yang J Y Han J Jiao J. Based quality-related fault detection and diagnosis method for nonlinear process monitoring. IAEE Trans. And 19-5 6492 6501 2023. 26 Jiao J W W G. Quality-related root cause diagnosis based on orthogonal kernel principal component regression and transfer entropy. IAEE Trans. And 17-9 6340 76356 2021. 27 Dale B.S. MacGregor J.F. Improved Algorithms. J. 11-1 7385 1997. 28 SSS. A library for locally weighted projection regression. J. Mach. Learn. Raise. 9 623 626 2008 MathNet. 29 C. GH. Singular value decomposition and least square solutions. Maths. 14 403 420 1970. 30 E. Yao K. Some properties of singular value decomposition and their applications to digital signal processing. Signal process. 18-3 277 289 1989 MathNet. 31 Peng KX K Gang Li. Online contribution rate-based fault diagnosis for nonlinear industrial processes. Acto. 43 423 430 2014. 32 UA HH Chin SJ. Reconstruction-based fault identification using a combined index. And Raise. 4020 4403 4414 2001. 33 CF Zhou Chin S. Reconstruction-based contribution for process monitoring. 45-7 1593 1600 2009. 18. Data-based quality-related fault diagnosis scheme for fault detection and root cause diagnosis. Abstract. Quality-related fault detection and root cause diagnosis are the key problems in fault diagnosis framework,
which are the effective ways to ensure operational safety and product quality. In this chapter, a modified canonical variable analysis (MCVA) model is developed for quality-related fault detection. Subsequently, the classical generalized reconstruction-based contribution (GRBC) is used for fault identification. Then a transfer entropy causality analysis method is put forward for root cause diagnosis of quality-related faults. In the end, sufficient simulation experiments are conducted by a typical industrial process, the hot rolling process, HRP, to demonstrate the superiority of the developed framework compared with some classical algorithms. 18.1 Preliminaries and Problem Formulation. CVA is a classical subspace identification method, which realizes dimensionality reduction of high-dimensional data by maximizing the correlation between variables. Due to this method is closely related to partial least squares, PLS, CVA has been widely used in fault detection for dynamic processes with sequence dependence. The CVA method uses correlation coefficient to obtain the correlations between process and quality variables. The degree of correlation between variables cannot be fully reflected, thus affecting the quality-related fault detection effects for dynamic processes. Therefore, in this chapter, the problem to be solved is to improve the traditional CVA method, aiming at increasing the quality-related fault detection performance. After that, fault identification and root cause diagnosis methods are presented. 18.2 MCVA-based quality-related fault detection. In order to describe the correlation between process variables more completely and reflect the associated degree of correlation, inspired by Yin's work 3, in this chapter, the mutual information MI is used for replacing the correlation coefficient, and an MCVA-based quality-related fault detection method is proposed. The degree of correlation between variables is measured by analyzing the similarity between the joint and edge probabilities. If MJ L0, it indicates that J and L are independent of each other, and there is no information interaction between them. If MJ L0, it indicates that there has information interaction between them. The larger the value is, the stronger the information interaction is. Based on the above dynamic modeling processes, assume that Q is the maximum order of canonical correlation. The associated space is the canonical correlation subspace. By means of designing suitable monitoring statistics and control limits, quality-related fault detection can be realized. 18.3 Root cause diagnosis of quality-related faults. After the occurrence of a quality-related fault is detected using the MCVA method, the next step is to identify the variables related to the fault, so as to diagnose the root causes. In order to address this issue, based on the traditional GRBC8 and TE9 methods, a new root cause diagnosis framework is designed for quality-related faults. 18.3.1 Contribution-based quality-related fault identification. 18.3.2 TE-based causality analysis. It can be seen that TI is an asymmetric measurement. The directional information and dynamic information among quality-related fault variables can be clearly reflected by the joint probability P, which can be estimated by the KDE10 of the proposed quality-related fault diagnosis scheme. 18.4 Verification study. In this section, the practicality of the proposed data-based quality-related fault diagnosis scheme is validated by the actual datasets of HRP, and some comparison experiments are conducted. 18.4.1 Background presentation and data description. Schematic layout of the HRP. As the core and background production process in this section, the finishing rolling process, FMP, contains thousands of process control variables, loops, and subsystems. The FMP covers 7 stands. Each stand is comprised of a couple of supporting rolls, a couple of working rolls, and the associated hydraulic devices. The rolling force detection devices are commonly installed at the lower parts of supporting rolls to measure the rolling forces. The average rolling gaps are controlled by the high-precision hydraulic servo systems to guarantee the thickness and flatness. More information about HRP can be referenced in 11. Description of process and quality variables in FMP. Variable type description.
unit, U1, U7. Measured, average gap of stand I1, 7. U8, U14. Measured, total force of stand I1, 7. Mn, U15, U20. Measured, work roll bending force of stand I2, 7. Mn, Y quality, finishing mill exit thickness of strip. Settings, method, LMLFKNCVA. 20, 1, 3, 3, 60, MCVA. 20, 1, 3, 3, 63. 1842 Analysis and Discussions. CVA-based quality-related fault detection results. Figures 18.3 and 18.4 present the quality-related fault detection results by the traditional CVA and the new method, respectively. By comparison, it can be seen that both methods can detect the fault in real time at the 2000th sampling point. However, after the fault ends, the CVA-based method presents false alarms. The false alarm rate FAR reaches 4.68%, while the MCVA-based method is only 0.26%. Figure 18.5 shows the GRBC-based fault identification results. It can be seen that variable 4 has the largest GRBC value. As the fault propagates, the values of variables 11, 12, 6, etc. are also affected. It can be shown that the new method can not only identify the quality-related fault variables, but also display the GRBC value in real time, which has a good fault identification effect. In order to diagnose the root cause more accurately, variables 4, 11, 12, 6, 19, 13, and 14 are selected as the quality-related fault variables from the candidate datasets by the quantitative standard. New approach-based quality-related fault detection results. GRBC-based online identification results for the fault. 18.5 Concluding remarks. The calculated values of for fault 1. 4, 6, 11, 12, 13, 14, 19, 4, 0, 0.446. 0.337, 0.561, 0.488, 0.356, 0.851, 6, 0, 0, 0.322, 0.269, 11, 0.438, 0, 0.778, 0.443, 0.337, 0.221, 12, 0.216, 0, 0.198, 0.331, 0.21, 13, 0, 0, 0.096, 14, 0, 19, 0.166, 0.422, 0, TE-based causal map for the quality-related fault. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license
and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1. Dr. S. Taylor J. Canonical Correlation Analysis, an overview with application to learning methods. Neural, 16 2639 2664 2004. 2. pp. Y. Nonlinear Dynamic Process Monitoring using Canonical Variate Analysis and Kernel Density Estimations. Aided. 27 1557 1562 2009. 3. Yin XR, Canonical Correlation Analysis Based on Information Theory. J. Ainul, 91 161 176 2004 MathNet. 4. W. Storer RHC, Disturbance Detection and Isolation by Dynamic Principal Component Analysis. Lab 30 179 196 1995. 5. K. YAW, ZW Ding SX Peng KX, Unit Level Modeling for KPI of Batch Hot Strip Mill Process using Dynamic Partial Least Squares. In Proceedings of the 17th IFAC Symposium on System Identification, 48. 1005-1010, 2015. 6. Chin, S.J., Survey on Data-Driven Industrial Process Monitoring and Diagnosis. Rev. Control 36, 222-34, 2012. 7. Lee J.M. Chin, S.J. Lee, I.B., Fault Detection and Diagnosis Based on Modified Independent Component Analysis. EJ 52, 35013514, 2006. 8. Lee G. C.F. Chin, S.J. Joe, D.H., Generalized Reconstruction-Based Contributions for Output-Relevant Fault Diagnosis with Application to the Tennessee Eastman Process. IEIE Trans. Control. Technol. 19 11 14 1127, 2011. 9. T. Measuring Information Transfer. Rev. 85 461 464, 2000. 10. BW, Density Estimation for Statistics and Data Analysis. Chapman and Hall, London, 1986. 11. Ma L. Dong J. Peng KX, a novel data-based quality-related fault diagnosis scheme for fault detection and root cause diagnosis with application to hot strip mill process. Control. 67 43 51, 2017. 19. Fault Injection, Test Verification, and Platform Implementation Technology for Traction Drive Systems of Rail Transit Vehicles. Abstract. To address the urgent need for a fault testing and verification platform for traction drive systems in rail transit vehicles, this chapter focuses on the technical challenges of fault injection, fault testing and verification, and platform implementation in the development of semi-physical simulation platforms for traction drive systems. This chapter outlines some new methods and technologies for the developing high-speed train traction drive system fault testing and verification platforms, and then introduces a real-time simulation platform that integrates real-time simulation, realistic fault behavior simulation, random fault testing, and fault diagnosis algorithm assessment for traction drive systems in rail transit vehicles. Finally, a real-time simulation platform for fault testing and verification of high-speed train traction drive system, developed in cooperation with a leading unit of traction drive system in China, is introduced. The platform can not only realistically simulate the common fault scenarios in high-speed trains, but also objectively and comprehensively evaluate the fault diagnosis algorithm, providing a test and verification environment and basis for further optimization and debugging of the fault diagnosis algorithm and whether it can meet the decision of applications. 19.1 Background. Diagram of traction drive system. The traction drive system, as the core part of energy transmission and conversion for high-speed trains, is often regarded to as the heart of high-speed trains, as shown in Fig. 19.1. It is not only a critical system for ensuring the safe operation of high-speed trains, but also a primary source of frequent faults 1, 2. If any fault or safety hazard in the traction drive system is not diagnosed in real time and addressed promptly, it could trigger a chain reaction of accidents, forcing the train to stop and posing significant risks to life and property. To mitigate such risks and ensure operational safety, scholars both domestically and internationally have conducted extensive research on reliability methods and fault diagnosis technologies for the traction drive system. Test and validation platforms are essential tools for advancing research in related theories and technologies. To ensure the safe and reliable operation of real vehicles, while reducing development costs, shortening the development cycle, and reducing on-vehicle debugging time and verification time, all technologies must undergo laboratory simulation experiments, testing, and validation and evaluation before being deployed. 3. Unlike verification platforms for normal operation scenarios, the testing and validation of fault diagnosis technology must be conducted under fault conditions. The simulation of faults in large-scale and complex systems is both hazardous and risky, as it involves numerous fault types, intricate mechanisms of system fault evolution, or complex manifestations of symptoms, making it impractical to achieve through simple fault injection setups. Fault testing originated in the fields of aerospace and military equipment sectors and spans the entire design and development process. By boldly hypothesizing and extensively testing all possible failure scenarios, comprehensive performance evaluations of the system under test are conducted. These evaluations provide a foundation for decisions on reliability design and performance optimization, reducing the risk of failures and ensuring successful task execution. Therefore, fault testing and verification platforms have become incubators and accelerators for promoting the practical application of reliability theory. However, systematic and in-depth research on fault testing and verification platforms for high-speed trains in China is still lacking. At the same time, high-speed rail operations are encountering increasingly complex operating conditions. With the global development and competition in high-speed train technology, many new methods and technologies that can enhance the safety of high-speed rail operations urgently need to be through testing for application. Therefore, conducting research on the construction of a fault testing and verification platform for traction drive systems of rail transit vehicles is of great significance for improving the safe operation level of rail transit vehicle traction drive systems and the overall performance of high-speed rail vehicles. To this end, this chapter will provide an overview of the latest research findings on fault injection, testing and verification, and platform implementation technologies for traction drive systems in rail transit vehicles. On this basis, it will introduce a semi-physical simulation platform for fault testing and verification. This platform integrates real-time simulation, realistic simulation of fault operation behavior, random fault testing, and assessment of fault diagnosis algorithms for traction drive systems in rail transit vehicles. 19.2 Research Status and Key Issues. 19.2 Rail Transit Vehicle Testing and Verification Platform. Comparison of platform implementation schemes. Implement. Method. Experimental. Cost. Test data. Reliability. Simulated. Failure risk. Test. Period. Platform implementation. Difficulty. Physical. High. Slow. High. Virtual simulation. Low. Moderate. Low. Hardware in the loop real-time simulation. Moderate. Fast. Moderate. Real-time simulation platform. Semi-physical simulation platforms combine the advantages of physical and virtual simulation platforms and overcome their shortcomings, attracting significant attention in recent years. These platforms typically consist of physical parts and real-time simulation components. Depending on the simulation object of the real-time part, semi-physical simulation can be divided into two methods: rapid control prototyping (RCP) and hardware in the loop (HIL), as shown in Fig. 19.2. In HIL, the physical part is the actual controller, while the real-time simulation represents the controlled system, with the simulation clock fully synchronized with the controller's clock. HIL not only achieves results comparable to physical experiments, but also reduces development cycles, lowers testing costs, and enhances safety. Additionally, HIL offers repeatability and controllability, making it more suitable for the research and development of real-time fault diagnosis technologies compared to physical or RCP simulations. However, existing semi-physical simulation platforms for high-speed train traction drive systems mainly focus on normal system operation and control algorithm verification, and are not directly designed to simulate fault conditions. While recent platforms have introduced methods to simulate abnormal conditions in certain subsystems or functional modules, these methods remain limited. On the one hand, common fault injection techniques are insufficient for constructing system-level fault injection testing platforms that can handle diverse and complex fault scenarios. On the other hand, they cannot simulate the spatio-temporal impact of the subsystem operations on the entire vehicle. 1922 Fault injection. Fault injection, a fault simulation technology first proposed in the 1970s, initially received little attention. However, it gained significant traction in the 1990s and quickly became a prominent topic in reliability research. The essence of fault injection is to artificially introduce faults of specific types into the target system in order to observe and analyze the system's behavior under fault conditions. Common fault injection techniques can be divided into three categories: hardware-based, software-based, and simulation-based fault injection methods. Hardware-based fault injection more closely replicates real-world faults, but when simulating faults in systems with high integration, complex structures, and tightly sealed components, fault locations may be inaccessible, limiting the feasibility of many hardware fault injections. Software-based fault injection is more cost-effective and easier to control, but it is limited to faults related to software components. Studies have shown that 2/3 of faults cannot be addressed through software fault injection. Simulation-based fault injection offers broader fault coverage, greater controllability, and enhanced, while also being cost-effective. However, it requires time-consuming model development, and the credibility of the faults depends on the accuracy of the model. In a semi-physical real-time simulation environment, the possible fault scenarios that may occur in the traction drive system are divided into two categories: 6, accessible and inaccessible fault locations. 1. For fault scenarios with accessible locations, they mainly refer to the simulation objects within the real-time simulator of a semi-physical real-time simulation. When injecting faults into these objects, it is possible to make full use of the fault detection and isolation data obtained from various analyses, simulations, and tests during the development process. Test injections can be carried out in a layered, decomposed, and arbitrarily combined manner. And theoretically, any detail of known executable faults within the range of simulation can be injected. Hierarchical schematic diagram of high-speed train traction drive system. 2. For fault scenarios with inaccessible locations, this mainly refers to scenarios where fault injection cannot be achieved by opening or disassembling the object under test, such as the actual controller in the hardware-in-the-loop (HIL) real-time simulation platform. Due to the high level of and plug-in packaging of the internal components of such object, testing encounters challenges when access to critical locations is restricted, making it impossible to inject faults by disassembling or opening these components. 1923 Simulation Credibility Assessment. Simulation credibility is the most important metric in evaluating the performance of simulation systems. Whether the simulation credibility meets the requirements directly impacts the success or failure of the application of the simulation system. Concerns about the credibility of various simulation models were recognized early in the development of simulation technology. In 1962, AND's comprehensive assessment of the Bloodhound missile system simulation marked the beginning of credibility assessment effort. It was not until the 1990s that simulation credibility assessment gained widespread attention and became a prominent topic in the field of system simulation research. The utility function-based method, which originates from similar theoretical principles, is an effective approach for quantifying basic indicators in the field of simulation credibility assessment. The operational faults of rail transit vehicle traction drive systems, characterized by heterogeneity, multidimensionality, and multi-level symptoms evolution, present significant challenges for the credibility assessment of fault injection results. On the one hand, there is a lack of research focused on credibility assessment of high-speed train simulations. On the other hand, homogeneity quantification methods are primarily designed for one-dimensional or planar simulation data, and there are no reported methods for assessing the homogeneity of heterogeneous and multidimensional credibility indicators. Therefore, the existing simulation credibility assessment methods are ineffective in addressing the challenges posed by the spatiotemporal correlation and causal characteristics of fault symptom evolution in traction drive systems, and cannot meet the requirements of real-time fault simulation and verification. Additionally, different dimensions, attributes, and rules of various assessment methods raise the question of how to transform various quantitative and qualitative indicators into comprehensive quantitative variables. The application of similarity and equivalence principles to the credibility assessment of fault testing injection in inaccessible fault locations also leads to inconsistencies in group assessment results, potentially distorting assessment outcomes and introducing biases into decision-making processes. 19.2.4 Performance Assessment of Computational Algorithms. The performance assessment results of computational algorithms directly affect their applicability to real-world vehicle-mounted applications. Algorithm performance assessment is typically divided into qualitative and quantitative methods. Qualitative assessment emphasizes observation, analysis, induction, and description, but the resulting evaluations are often vague and generalized, with a significant margin of error, making precise judgments difficult. This approach is most suitable when it is challenging to reasonably compare algorithm performance due to the inability to describe quantitative indicators. Reference 2 used robustness, cost, and ease of implementation for a qualitative comparison to assess the performance of open-circuit fault diagnosis in traction converters, highlighting the superiority of various diagnostic algorithms. Comparatively, Ref. 7 employed evaluation indicators such as refinement, real-time performance, and portability to qualitatively compare various modeling methods for addressing the modeling of open-circuit faults in traction converters. Utilizing statistical data, quantitative assessment establishes and applies mathematical models to calculate the values of various indicators of the computational algorithms. This approach delivers more objective and empirically validated outcomes, making performance comparisons intuitive and clear, and thus widely adopted. Regarding the diagnosis of ground faults in traction drive systems, Ref. 8 used indicators such as fault detection rate, fault detection delay, and fault isolation rate to verify and assess the performance of the proposed method. Reference 9 employed fault detection rate, fault false alarm rate, and detection delay to evaluate the sensor fault detection method for traction drive systems. Additionally, references used indicators such as fault miss rate, false alarm rate, diagnostic accuracy, and detection delay to assess the performance of the proposed methods for diagnosing minor faults in traction drive systems. However, there is currently no unified standard or industry specification for the performance assessment of high-speed train fault diagnosis algorithms. The academic community places greater emphasis on the robustness and timeliness of algorithms, while the industry focuses more on indicators such as usability and safety. The divergence in assessment priorities has limited the application of many advanced fault diagnosis algorithms in engineering practice. Therefore, establishing standardized and practical performance assessment indicators for fault diagnosis algorithms is crucial for accelerating the implementation of these algorithms in vehicle-mounted systems. 19.2.5 Implementation of fault testing and verification through hardware-in-the-loop simulation. As shown in Table 19.1, compared to physical and virtual verification platforms, the semi-physical simulation platform has a distinct advantage in providing a fault test verification system with low test cost, high safety, and high accuracy. To ensure the real-time performance of the semi-physical platform, simulation objects within the real-time simulation component must utilize high-performance processing chips to efficiently solve real-time simulation models. Comparison of real-time calculating for simulator. Jib, operation, mode, operation, frequency, average, time, range, impact of, computational, load, unit, price, shortcomings, DSB, serial, J, milliseconds 2, microseconds, high, low, slow average model, solving speed greatly, affected by the amount of, computation, FPGA, parallel, M, nanoseconds, low, high, limited resources, timing constraints. As shown in Table 19.2, compared to DSP chips, FPGA chips achieve nanosecond-level computing speed at the cost of hardware resources, introducing specific constraints on hardware and timing resources. This imposes more stringent requirements on real-time simulation modeling, especially in fault injection modes. The inclusion of fault injection models further exacerbates the resource allocation conflicts between hardware and timing, potentially leading to timing errors when hardware resources are limited. If not properly handled, this could prevent real-time solution of models, thereby restricting the range of fault modes or scenarios that can be simulated. Therefore, optimizing resource allocation for real-time simulation in fault injection modes is a critical challenge in developing validation platforms for hardware-in-the-loop environments. 19.3 Fault injection for semi-physical simulation. Accessible faults can be classified based on their characteristics into three categories: faults with spatial migration, faults with temporal evolution, and those with spatiotemporal changes. 19.3.1 Fault injection based on signal conditioning. For faults with spatial migration characteristics in the traction drive system, if the occurrence of the fault affects the input and output variables of the fault object, the system signals, i.e., model inputs-outputs, will inevitably change. These changes will be reflected in both the electrical signals from sensor feedback and the control signals from the controller. According to this characteristic, a signal conditioning-based method 11 can be used to simulate the significantly changed control electrical signals, fault scenario signals, at the signal level after a fault occurs. Assuming that faults are denoted by EFT, D123D, where D is the number of the fault types. For a specific fault EFT, est1 SZ is the corresponding fault scenario signals, whereas the fault scenario signal for Z123 and Z is the total number of fault scenario signals when fault EFT occurs in the fault object. Finally, according to the impact of the fault on the system, the original input or output variables of the fault object are replaced by the fault scenario signal generated by signal conditioning. This completes the process of fault injection and simulation using signal conditioning. 19.3.2 Fault injection based on model replacement. For faults with temporal evolution characteristics, if a fault in the traction drive system is caused by the failure or performance degradation of certain components within the system, some of which can be manifested as changes in the electrical parameters that describe the component's behavior. In some cases, failures or performance degradation may lead to changes in the circuit structure, which cannot be captured by the normal system model. And changes in electrical parameters will further cause changes in model parameters, embedding information about component failures. In contrast, changes in the circuit structure require an expansion of the existing normal working model, along with analysis and mechanism descriptions for specific fault working conditions, to develop a corresponding fault mechanism model. Subsequently, the fault mechanism model of the fault object is connected in parallel to the input end of the normal model M when simulating a certain type of fault EFT. The output signal Y of the normal model M of the fault object is disconnected, and the output signal Y of the fault model is connected to obtain the initial settings of the fault-sensitive parameters in the fault mechanism model. According to the real-time calculated fault-sensitive parameters, the updated fault-sensitive parameters are used to replace the initial settings in the fault model, thereby achieving fault scenario simulation based on model replacement. 19.3.3 Fault injection based on the hybridization of signals and models. For faults in the traction drive system with spatiotemporal characteristics, the occurrence of system failures not only changes the original circuit structure, but also alters electrical signals. Some faults, however, may have incomplete fault mechanism descriptions or produce signal changes that are subtle or difficult to describe. For such faults, relying on a single fault injection method may result in an incomplete fault scenario description, that is, inaccurate representation, which does not conform to the purpose of fault injection and will affect the reliability of subsequent fault diagnosis technology application verification. Therefore, considering the complexity of the faults themselves and the limitations of single fault injection methods, it is necessary to propose a hybrid fault injection method to address the fault simulation injection of complex fault scenarios in the traction converter, enabling a more comprehensive and accurate representation of such fault conditions. The core concept of the hybrid fault injection method based on signals and models is as follows. First, analyze the characteristics of the fault scenario and divide it into parts that can be described either by mechanism models or through fault scenario signal. Then decompose these two parts and also the parts that cannot be described. The describable parts are described using either the model replacement-based fault injection method or the signal conditioning-based fault injection method. Next, for the content of the fault scenario that cannot be described by a single fault injection method, analyze the coupling relationship or spatiotemporal correlations between the undescribed and described parts in the model and signal changes after faults occur. In addition, an alternative fault injection method is employed. A higher-level controller, based on the identified coupling or spatiotemporal relationships, coordinates the fault injector controllers to appropriately modify and set fault parameters, such as the fault trigger time, severity, and type. 19.3.4 Fault injection in inaccessible locations. For inaccessible faults, fault injection and simulation are carried out by establishing a fault propagation characteristic model. First, based on the circuit topology, find the component N that is adjacent to and accessible for the fault object M. N is generally a virtual simulation object in the real-time simulation system. Construct the fault propagation characteristic model NTM, where M and N are the fault mechanism models for the physical fault object M and component N, respectively represented as MSU and NSU, and T is the generalized transfer function between the fault mechanism models M and N. This transforms the inaccessible fault M at the fault object M into an accessible fault N at the adjacent component N. Then, based on the impact of the fault type on the system, use the first three fault injection methods described in this section to achieve the injection and simulation of fault N. 19.3.5 Fault injector design technique. Schematic diagram of fault simulator based on signal model hybridization. Based on functionality, the control section of the fault injector is divided into two functional layers, the command data transceiver layer and the fault simulation configuration layer. 1. Command data transceiver layer. This layer consists of the real-time data acquisition unit, command distribution unit, and working mode configuration unit. The real-time data acquisition unit collects data from sensors, calculates the system's operating state variables and environmental parameters based on the collected data, and forwards this information to the working mode configuration unit. The command distribution unit receives user commands from the host computer, analyzes the fault types and parameters, and transmits these settings to the working mode configuration unit. The working mode configuration unit is responsible for dynamically adjusting the working mode and configuration information for fault injection simulation based on the user settings and real-time system status, and for sending fault simulation configuration information to the fault simulation configuration layer. 2. Fault simulation configuration layer. This layer consists of the signal conditioning control unit and the model modification control unit. The signal conditioning control unit receives signal configuration information from the command data transmission layer, sends standardized fault signal parameter information and command signals to the signal conditioning module, and controls the working state of the signal conditioning module. The model modification control unit receives model configuration information from the command data transmission layer, sends sensitive parameter information and model selection signals to the model modification module, and directly sends fault model switching signals to the fault object to control the working state of the model modification module. 19.4 Fault testing and verification. 19.4.1 Simulation credibility assessment under fault injection model. To address the numerous challenges in the credibility assessment of fault injection results, a credibility index determination method based on the transformation is first employed. This method divides the credibility of assessment indicators into overall credibility and characteristic credibility, providing a quantification model for indicator credibility. It also facilitates the preliminary selection of individual dynamic assessment indicators under fault symptom evolution simulation. Next, considering both evaluation indicators and expert evaluations, a complex simulation system credibility group evaluation method based on relevant assumptions is proposed to enhance the objectivity of group evaluations for fault simulation credibility in high-speed train traction drive systems 13. Finally, in response to the issue of non-uniformity in group evaluation results of credibility, the literature 14 proposed a simulation credibility group evaluation method based on a generalized fuzzy soft set with correlation groups. Subsequently, an evaluation model considering correlation relationships was established, describing the correlation between indicators and experts, integrating the fuzzy TOPSIS technique for order of preference by similarity to ideal solution method. This approach enables the final credibility values to be represented by precise numbers, enhancing the accuracy of group evaluation results of credibility. It also provides an effective solution for the credibility evaluation of fault symptom evolution simulations with spatiotemporal correlation and causal characteristics. 19.4.2 Construction of the Performance Evaluation Index System for the algorithm to be tested. Main process of the fault diagnosis system. From the perspective of fault diagnosis timing, an effective fault diagnosis algorithm should possess the following three capabilities. 1. Rapid response to faults. This capability highlights the algorithm's responsiveness, ensuring it can diagnose even minor faults as early as possible within a reasonable threshold and detect faults as promptly as possible after they occur. 2. Accurate fault determination. This emphasizes the effectiveness of the algorithm, aiming to correctly detect faults while minimizing false positives to avoid missing any actual faults. 3. Fault localization, classification, and severity determination. This capability focuses on the algorithm's ability to accurately pinpoint the fault's location, classify its type, and determine its severity. 1. Responsiveness indicator group. 2. Effectiveness indicator group. 3. Discernment indicator group. 4. Key evaluation indicators. 5. Comprehensive evaluation indicator. The aforementioned diagnostic algorithm, using the test results of n random fault injections, adopts a three-tier evaluation indicator system. By assigning weights, it can accommodate the performance evaluation requirements of fault diagnosis algorithms under different situations. Based on the characteristics of the algorithm to be evaluated and the need for objective and comprehensive assessment, this method establishes a three-level evaluation indicator system by selecting evaluation indicators and highlighting maintainability and diagnostic reliability. The three-tier evaluation indicator system is outlined 15, as shown in Table 19.3. 19.5 Implementation of fault test and verification of semi-physical simulation. 19.5.1 Fault injection system architecture for co-simulation. Three-level-based performance evaluation index for fault testing. Composite performance indicators, key performance indicators, basic performance indicators, maintainability indicator group, average detection delay, sensitivity, composite performance indicators, detection availability indicator group, detection rate, false positive rate, misdetection rate, diagnostic reliability indicator group, diagnostic reliability indicator group, diagnostic reliability indicator group, diagnostic reliability indicator group. The information control system of high-speed trains consists of multiple subsystems, such as the traction drive system, braking control system, and network control system. During train operation, the states of these subsystems are interrelated and mutually influential. For instance, a fault in the traction motor of the traction drive system not only reduces the train's power performance, but also affects the braking control system, resulting in decreased braking efficiency. Therefore, a fault in one subsystem can cause abnormal operation within that subsystem and propagate through interconnections, impacting the performance of other subsystems. Real-time simulation system architecture for fault testing in high-speed train information control systems. Real-time simulation structure for fault testing and verification of high-speed train information control systems based on HLARTI. 2. Subsystem-level fault injection, collaborative real-time simulation architecture. Furthermore, the occurrence, evolution, and propagation of fault symptoms in any component of the traction drive system are also closely related to the coupling relationships between components within the system. It is highly challenging to implement fault injection simulation for systems that respond at multiple spatial scales, among different elements components within the same level, and between different levels and multiple temporal scales, nanoseconds, microseconds, milliseconds. To address this, a real-time simulator architecture based on a dual-chip DSP plus FPGA can be employed. 16. Depending on the dynamic response requirements of the controlled object, the architecture maximizes the use of chip resources, enabling real-time collaborative simulation across varying dynamic response scales in the traction drive system. Specifically, virtual simulation objects with high model response and computational speed demands, such as traction converters and the electrical parts of traction motors, are processed on FPGA cards with nanosecond-level computational capabilities. Meanwhile, virtual simulation objects with lower model response and computational speed demands, such as the mechanical parts of traction motors, control desks, and train control centers, are processed on CPU cards. For parameters in the mechanism models of virtual simulation objects that remain constant over time, a time-invariant parameter separation method is applied. These parameters are first isolated from the mechanism models, then merged. And the merged parameters are used to simplify the mechanism models, thereby reducing FPGA resource usage. Given that the operation of various components in the traction drive system is interrelated and mutually influential, both among elements components at the same level and across different levels, a fault in the traction converter not only affects its own operating state, but also impacts other components through the coupling relationships, thereby affecting the overall system's electrical field changes. On one hand, the computational response times of different components in the traction drive system in the real-time simulator vary, involving nanoseconds, microseconds, milliseconds, etc. On the other hand, the injection scales of 3 different fault injection methods in terms of temporal characteristics are also affected by the fault object and type, involving multiple time scales. Therefore, when implementing fault injection simulation on a hardware-in-the-loop (HIL) traction converter semi-physical platform, it is necessary to take into account the system's varying response scales. Subsystem-level fault injection architecture for the traction converter oriented toward hardware-in-the-loop cooperation. 1952 Real-time simulation timing and computational resource optimization under fault injection. Compared to DSP chips, FPGA chips, while achieving nanosecond-level computation speeds at the expense of hardware resources, introduce unique constraints on hardware and timing resources. This imposes stricter requirements for modeling simulation objects in real-time simulation, especially under fault injection modes. The inclusion of fault injection models further exacerbates resource allocation challenges, potentially leading to timing errors when hardware resources are limited. If not handled properly, real-time model computation may fail, restricting the range of fault modes or scenarios that can be simulated. Therefore, optimizing resource allocation for real-time simulation in a semi-physical environment under fault injection mode is critical for building an effective verification platform. Real-time simulation through FPGA is achieved by sacrificing computational resources for speed to ensure responsiveness and real-time performance. Considering factors such as the variety of system fault types and the complexity of scenario descriptions, real-time simulation must optimize timing resources while minimizing the occupation of logical resources. First, traverse all the timing start and end points in the sequential logic circuits of the system model, as well as the combinational logic circuits in between, and establish the timing-directed graph G0 for the normal operation state of the system and the timing-directed graph 0 under fault injection. Let G0 G01 G0 I G0 I, where G0 I represents a timing vector subgraph in G0, I is the number of timing vector subgraphs in G0, and each timing vector subgraph contains several nodes and directed edges. Here represents a node and is a directed edge between nodes and. After incorporating the fault injection model, the timing-directed graph under fault injection becomes G0010J0J, where 0J represents a timing subgraph in 0, and J is the number of timing vector subgraphs in 0. Then traverse and calculate the time margin for each timing path in G0 and 0 to obtain the time margin sets SL0 and S0 for G0 and 0, respectively. Identify the subset of time margins S0 in S0 that become less than 0 due to the introduction of the fault injection model. S0 is a subset of S0. Finally, for paths with a time margin less than 0, introduce new nodes to segment the paths in 0's timing paths. Suppose n are two adjacent nodes on a path and the time margin slack 0. A new node needs to be inserted between and to segment the path. After that, slack 0 and slack 0. Iteratively update the time margin for each timing path until the time margin between adjacent nodes on each path is greater than or equal to 0 and less than the minimum time margin in G0. The optimized timing-directed graph is then obtained, completing the timing optimization under fault injection. 1953 Implementation Technology of Fault Test Semi-Physical Platform. Real-time fault testing and verification hardware-in-the-loop platform for traction drive system. Interface of the developed fault test software. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S, and the source, provide a link to the Creative Commons license, and indicate if you modified the licensed material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1H B Ding SXB, Data-Driven Fault Diagnosis for Traction Systems in High-Speed Trains, A Survey, Challenges, and Perspectives. IEIE Trans. Transpo. 23-3, 1701-716, 2022. Tu Yang C Gui W Z J Peng T Yang C HR Ding SX, Voltage Difference Residual-Based Open Circuit Fault Diagnosis Approach for 3-Level Converters in Electric Traction Systems. IEIE Trans. Power Electron. 35-3, 3012-302-8, 2020. 3 Yang C Peng T Yang C Wen C Wei G, Fault Testing and Validation Simulation Platform for Traction Drive System of High-Speed Trains in Chinese. ACTA 4512, 2218-2232, 2019. 4 Johnson B.W. Smith D.T., T.A., A Survey of Fault Simulation, Fault Grading and Test Pattern Generation Techniques with emphasis on the feasibility of VHDL-based fault simulation. Technical Report RLTR 97-110, Virginia University Charlottesville, P. 130, 1997. 5 R. N. Duras J. Madeira H. Verification and Validation of Real-Time COTS Products Using Fault Injection Techniques. In 2007 6th International IEEE Conference on Commercial Off-the-Shelf, COTS-Based Software Systems, ICC-BSS 07. 233-242. 6 Yang C Peng T Tau H Yang C Gui W. Review of recent research on fault injection for high-speed train information control systems in Chinese. Sin Inform 50 465 482 2020. 7 Tau H Peng T Y Z C Gui W. Open circuit fault analysis and modeling for power converter based on single arm model. Electronics 86 633 648 2019. 8Z Lei X Yang C Peng T Yang C H Gui W. A data-driven ground fault detection and isolation method for main circuit in railway electrical traction system. ISA Trans 87 264 271 2019. ComScience article S00190 578183047737. 9 HBWH Data-driven detection and diagnosis of incipient faults in electrical drives of high-speed trains. IEIE Trans Electron 666 47 16 4 725 2019. 10 HTJCSS Real-time simulation of MMCs using CPU and FPGA. IEIE Trans Power Electron 31 259 267 2015. 11 Yang C Peng T Yang X Gui W. A fault injection strategy for traction drive control systems. IEIE Trans Electron 64-7 57-19 5727 2017. 12 Yang C Fault Modeling and Fault Injection Approach for Traction Converters in High-Speed Train Master Dissertation, in Chinese. Central South University, China, 2017. 13 Lei S Peng X Peng T Yang C. A group evaluation method for complex simulation system credibility based on two-order additive fuzzy measure. In 2016 Chinese Control and Decision Conference, CCDC. 147 154, 2016. 14 Li S Peng X Peng T. Aggregation method for simulation credibility index based on group generalized fuzzy soft sets with correlations in Chinese. Control 33 1 126 134, 2018. 15 Peng T Fang D Yang C Z Tau H W G J T. A random fault injection-based diagnosis algorithm evaluation method. China Patent CN 201811638187 December 30, 2018. 16 Yang X Yang C Peng T Z B GUI W. Hardware-in-the-loop fault injection for traction control system. IAIEJ Emerge. Top Power 62 696 706, 2018. 17 Yang X. Real-time fault simulation and diagnosis for traction control system of high-speed train. The dissertation in Chinese. Central South University, China, 2018. Process monitoring, fault diagnosis, and tolerant control for complex industrial systems, LUO. 1. Space projection-based fault diagnosis for LDTV systems. Abstract. In this chapter, issues of fault detection and estimation for linear discrete time-varying, LDTV, systems are addressed by using space projection technique in the framework of H-filtering. Firstly, an H-fault detection filter, FDF, is constructed for residual generation, the design of which is formulated as a minimization problem of a certain quadratic form. Then, by means of projection and innovation analysis in spaces, a solution to such an H-FDF is derived. Moreover, to estimate faults in LDTV systems with a reduced communication rate, an event-triggered H-filter is constructed. By equivalently converting the H-filtering issue into a certain minimization problem of indefinite quadratic form subject to LDTV systems with non-uniform sampling periods, a space projection-based solution to the event-triggered H-fault estimator is derived in terms of recursions, achieving a complete decoupling of estimation error from the event-triggered transmission error. Also, a less conservative and more computationally attractive implementation algorithm is developed. 1.1 Introduction. Over the past 4 decades, model-based fault diagnosis has made great progress both in theoretical research and engineering applications. See e.g. 1.5. Noting the nonlinearity of most practical systems and the mathematical of a nonlinear system with a linear time-varying process, fault diagnosis for linear discrete time-varying (LDTV) systems has attracted much attention. 6.11. In this line of research, one of the key issues is to improve the robustness of the designed fault diagnosis system to disturbances and the sensitivity to faults. When L2 norm-bounded disturbance is concerned, methods of H filtering, H2, and high H optimization are mostly used to address this issue. 7, 8, 12, 13. Especially in H filtering formulation, a fault detection filter, FDF-based residual generator, is usually constructed in the sense of minimizing the error between residual and the concerned fault. Now a great number of achievements on H filtering-based fault diagnosis are developed for linear time-invariant LTI systems, wherein the involved H minimization problem is usually addressed by means of linear matrix inequality, LMI technique 14-15. Regarding LDTV systems subject to L2 norm-bounded disturbances, H filtering-based residual generation requires solving a set of LMIs at every time step, which would lead to a heavy computation burden and conservative results since only sufficient conditions were obtained in most LMI-based results. As a powerful mathematical tool, space theory has been extensively studied since 1980s in the fields of control engineering, signal processing, as well as fault diagnosis. 1620. The pioneer works on linear estimation in indefinite metric space, i.e. the space can be found in 1618. Later, a great number of literature on space-aided filtering and H filtering, including estimation and smoothing, has been increasingly reported for various types of control systems. See AG. 21-25. Regarding space-based fault diagnosis for LDTV systems, an early work can be found in 12, in which the concerned fault vector was augmented as a state, and then the fault estimation issue in H filtering framework was converted into finding a minimum of a quadratic form function in space. In 13, the design of an FDF-based fault detection system was formulated as a finite horizon H smoothing problem and solved by means of space projection technique. In the sense of high H optimization, a space-aided FDF design for LDTV systems was given in 26. A space-based solution to parity space-based fault detection has been also investigated in 27. In recent years, one popular trend is applying space techniques to cope with fault diagnosis issues for more complex systems such as nonlinear systems. 28-29, systems with delayed states 9-21, and various uncertainties. 21. On the other hand, event-triggered strategy has gained increasing interests in fault diagnosis for complex control systems aiming at saving communication resources. 30-34, while event-triggered fault estimation for LDTV systems remains an open topic. In the research line of event-triggered linear estimation, data packets are transmitted to the estimator only when the event conditions are satisfied. In this manner, appropriate estimation performance at a reduced communication rate can be achieved. Especially in the framework of standard event-triggered H filtering, an estimator is designed by using LMI techniques such that the L2 induced gain from the disturbances to the estimation error is less than a prescribed level. See e.g. 35-39. Unfortunately, the so-called event-triggered transmission error between the latest measurement received by the estimator and the current measurement of the plant is inevitable, which may result in considerable degradation of H filtering performance. In addition, applying LMI techniques can only provide sufficient conditions, and the computational costs are heavy. Hence, how to achieve full decoupling of the estimation error from the event-triggered transmission error and obtain a less conservative solution with light computational burden remain challenging tasks in event-triggered H fault estimation for LDTV systems. Thanks to the merits of space projection in addressing H filtering issues, in this chapter, we investigate the space projection-based fault detection and estimation issues for LDTV systems in the framework of H filtering. To this end, preliminaries of space projection is reviewed in Sect. 1.2. A space projection-based HFDF design scheme is given in Sect 1.3, followed by an event-triggered H-fault estimation approach in Sect 1.4. Some remarks are given in Sect 1.5 to conclude this chapter. For ease of description, the following notations are applied throughout this chapter. Notations: MT stands for the transpose of the matrix MX0, respectively. X0 means that the real symmetric matrix X is positive definite, respectively, negative definite. Denotes the set of n-dimensional vectors. KL20N means that K0T, KK, the elements in space are denoted by boldface letters, and the elements in Euclidean space are denoted by normal letters. VKWK stands for the space inner product of VK and WK. LYII0K denotes the linear space spanned by Y0, Y1, YK. KLYII0IK means the projection of XK onto linear space LYII0IK1, two preliminaries of space-based projection. In comparison with the well-known space and Euclidean space, space has some specific characteristics that contribute the advantages of space-based optimal fault diagnosis for LDTV systems. In this section, preliminaries of space-based projection is briefly reviewed, which is presented for completeness, and more details about spaces can be found in 18. A projection in space and its basic property are given in the following definition. Different from the space where a projection always exists and is unique, the existence condition of a projection in space is in the following lemma. For the convenience of our later discussion, in the subsequent of this chapter, we without loss of generality make the standing assumption that the N is 1.3 Space projection-based H-fault detection. With the aid of space projection technique, this section presents an H-fault detection method for LDTV systems, the core of which lies in constructing an FDF in the sense of minimizing the H criterion. To this aim, the design of HFDF issue is formulated as solving a minimum problem of a certain quadratic form. By means of projection and innovation analysis in space, a sufficient and necessary condition for the minimum is derived, and a solution to the HFDF is obtained by recursively computing recursions. 131. An H-filtering formulation of FDF with residual feedback. It is worth mentioning that the residual signal RK in 1.2 can be regarded as an improvement of the standard residual signal, concerning the accommodation term V2K plus 1YK plus 1CK plus 1XK plus 1K. In case that K plus 1 FK plus 1 0 at time step K plus 1, the fault term would has no influence on the available output YK plus 1, and higher fault detection performance can be achieved through such an accommodation term. Noting that the residual RK is feed back to the state updating equation through term L3K RK, we call such an FDF a closed-loop residual generator. Note that Vzen can be expressed into a linear combination of n, dn, and fn, and jn is hence an indefinite quadratic form of x0 dn, fn n. Remembering the self-inner product of a vector in space is indefinite but not necessarily positive as required in space, in what follows, a scheme of space projection is presented for HFDF design. 132. Space projection-based design of HFDF. With respect to addressing 1.1, the basic idea of designing the HFDF-based residual generator 1.2 is to construct an equivalent projection problem in space, and then derive sufficient and necessary conditions for the minimum of Jn by using space optimization. On this basis, a recursive computation algorithm is developed for the implementation of HFDF. The existence conditions of the minimum of Jn. For K12n, suppose that P1I01, K1, P2I, IK, K plus 1, 2K, and K are calculated by 1.15116, 1.19120, 1.26, and 1.27, respectively. Then the solution of problem 1.1 exists if and only if 2K0 and K0. Moreover, the minimum of Jn can be obtained by using 1.28. Recursive implementation of the HFDF. Remembering that our original task is to find parameters Li K I123 V1K and V2K plus 1 in 1.2, guaranteeing the positiveness of the minimal Jn. In this subsection, a solution to this problem is given based on Theorem 1.1. For K12n, if 2K0 and K0, then FDF 1.2 with parameter matrices given in 1.29 is an HFDF satisfying 1.3. Calculation of Lie K I1 23V1K and V2K plus 1. 1.4 Event-triggered H-fault estimation using space projection. Space-based H-fault estimation for LDTV systems has been investigated in 20 to reduce the communication rate between the LDTV system and the fault estimator. In this section, we give an event-triggered H-filtering method for fault estimation. By means of space projection, an equivalent relationship of the developed estimator with appropriate space filter is established, guaranteeing that the estimation error is completely decoupled from the event-triggered transmission error. On this basis, sufficient and necessary conditions for the existence of the event-triggered H estimator are derived, and a feasible solution is given in terms of recursions. 141 Formulations of event-triggered H fault estimation. 142 Existence conditions for the minimum of JX0WV. 143 Recursive implementation of the event-triggered H estimator. Note from 1.39 that the augmented observation plus 1 involves not only X plus 1, but also the one-event delayed state X. We cannot derive X1, S1, and further S by immediately using the method of 18. Similar to the time-triggered H-fixed lag smoothing in 40, the techniques of reorganized innovation analysis will be utilized to find a solution of the event-triggered H estimator. For given 0 and P00 satisfying 1.56, an event-triggered H estimator satisfying 1.36 exists if and only if the conditions 1.43 with 1.51153 hold true for 0ji, wherein P1 plus 1 and P plus 1 are computed respectively by 1.48150, 1.54, and 1.55. If this is the case, a solution of Sk for K plus 1 can be obtained by using 1.57159, and the recursions of X and X plus 1 are given by 1.6162. In this case, it also follows P10 for 0ji. Implementation of event-triggered H fault estimation. 1.5 Conclusion. In this chapter, methods of space projection-based fault detection and estimation for LDTV systems were developed in the framework of H filtering. Towards fault detection, the design of an HFDF with residual feedback was formulated as a minimization problem of a certain quadratic form, and then was addressed by means of space projection in terms of recursion computation. Furthermore, by augmenting the fault vector as state, an event-triggered fault estimator under H criterion was constructed using space projection technique that delivers a complete decoupling of the estimation error from the event-triggered transmission error. Moreover, thanks to the recursion implementation, the developed event-triggered H fault estimation approach is more computationally attractive than traditional LMI methods. It is worth mentioning that this chapter focuses on the design of HFDF for residual generation purpose. As another important part of fault detection, residual evaluation involving threshold setting should be further investigated to guarantee satisfactory fault detection performance. Moreover, for the designed event-triggered H fault estimator, the reduction of data transmission will undoubtedly result in the degradation of estimation performance. Since the designed event-triggered H fault estimator is independent of the event-triggering mechanism, the developed space projection-based solution can be applied immediately to event-triggered H estimation schemes with any event-triggering conditions different from 1.33. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S, and the source, provide a link to the Creative Commons license, and indicate if you modified the licensed material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Ding SX, Model-Based Fault Diagnosis Techniques, Design Schemes, Algorithms, and Tools, 2nd. Springer, London, UK, 2013. 2 Ding SX, Advanced Methods for Fault Diagnosis and Fault-Tolerant Control. Springer, Berlin, Germany, 2020. 3J RJ, Robust Model-Based Fault Diagnosis for Dynamic Systems. Academic Publishers, Boston, MA, 1999. 4R Fault Diagnosis Systems, An Introduction from Fault Detection to Fault Tolerance. Springer, Berlin, Heidelberg, 2006. 5MMJM, Diagnosis and Fault Tolerant Control, 3rd. Springer, Berlin, Heidelberg, 2016. 6 Ding SX, Optimal Fault Detection and Estimation, A Unified Scheme and Least Square Solutions. IFAC Papers Online 5124, 465 472, 2018. 7M Ding SX Ding EL, Optimal Fault Detection for Linear Discrete Time-Varying Systems. 46.8, 1395-1400, 2010 MathNet. 8M Ding SX Han QL Al. Parity Space-Based Fault Estimation for Linear Discrete Time-Varying Systems. IEIE Trans. Control 55.7, 1726-1731, 2010 MathNet. 9 Shen B Ding SX Z, Finite Horizon H Fault Estimation for Linear Discrete Time-Varying Systems with Delayed Measurements. 49.1, 293-296, 2013 MathNet. 10 Li X Zhou K, A Time Domain Approach to Robust Fault Detection of Linear Time-Varying Systems. 45.1, 94-102, 2009 MathNet. 11 Wan Y Dong W Yi H, Integrated Trade-off Design of Fault Detection System for Linear Discrete Time-Varying Systems. IIT Control Theory, and 7.3, 455-463, 2013 MathNet. 12M S H, Space-Based H Fault Estimation for Linear Discrete Time-Varying Systems. Actus 3412, 1529-1533, 2008 MathNet. 13M Zhou D Ding SX, on designing H fault detection filter for linear discrete time-varying systems. IEIE Trans. Control 55.7, 1689-1695, 2010 MathNet. 14M Ding SX Lam J H, an LMI approach to design robust fault detection filter for uncertain LTI systems. 39.3, 543-550, 2003 MathNet. 15J Yang G J, an LMI approach to H-index and mixed H fault detection observer design. 43, 1656-1665, 2007 MathNet. 16B SAID AHT, Linear Estimation in Spaces Part I Theory. IEIE Trans. Control 41-1, 1833-1996. 17B SAID AHT, Linear Estimation in Spaces Part II, Applications. IEIE Trans. Control 41-1, 3449-1996. 18B SAID AHT, Indefinite Quadratic Estimation and Control, A Unified Approach to H2 and H Theories, Siam, 1999. 19 Shen B, A Survey on the Applications of the Space Theory in Signal Estimation. Systems and Control. Open Access J21, 143-149, 2014. 20M Lay S Y, Robust H Fault Detection for Uncertain LDTV Systems Using Space Approach. J. Control 94, 1637-1649, 2013. 21D Y Lees Y Al. H fault estimation for 2D linear discrete time-varying systems based on space method. IEIE Trans. Man. 4812-2072-079, 2017. 22J L, A Theoretical Framework of Robust H Unscented Filter and its Application to Power System Dynamic State Estimation. IEIE Trans. Signal Proc 6710 2734 2746 2019. 23J.L. A decentralized H-infinity unscented filter for dynamic state estimation against uncertainties. IEIE Trans. Smart Grid 10.5 4874880 2018. 24M Ding SX Han QL Al. A space-based approach to event-triggered H filtering for linear discrete time-varying systems. 135 110001 2022 MathNet. 25 Li Th Ra WST Al. Robust filtering via space estimation. IIE Proc Control Theory. 151 1 5963 2004. 26M Ding SX Joe D. A new scheme of fault detection for linear discrete time-varying systems. IEIE Trans. Control 61 9 2597 2602 2016 MathNet. 27M Song Y Ding SX. Parity space-based fault detection for linear discrete time-varying systems with unknown input. 59 121 26 2015 MathNet. 28M D Joe D. A space approach to H filtering of discrete time nonlinear systems. IEIE Trans. Circuits. Irregular Papers 61 9 2644 2652 2014. 29 Qs Y Al. Fault estimation for a class of nonlinear time-variant systems through a space-based approach. Measurement Control 5334 541 550 2020. 30 SM Al. Event-triggered fault detection and isolation for discrete time linear systems. IIT Control Theory. 10.5 526 533 2016 MathNet. 31XX Al. Fault detection filtering for nonlinear switch systems via event-triggered communication approach. 101 365 376 2019 MathNet. 32XF Al. Event-triggered fault detector and controller coordinated design of fuzzy systems. IEIE Trans. Fuzzy. 26.4 2004 2016 2018. 33 Li Q Shen B Al. Event-triggered H state estimation for state-saturated complex networks subject to quantization effects and distributed delays. J. Franklin. 355 2874 2891 2018 MathNet. 34 YCP. Adaptively adjusted event-triggering mechanism on fault detection for networked control systems. IEIE Trans. 47 8 2299 2311 2017. 35 Dong H Z Ding D. Event-based filtering for discrete time-varying systems. In Proceedings of the 20th International Conference on Automation and Computing. 116 121. University, Bedfordshire, UK, 2014. 36 X Han QL. Event-based H filtering for sampled data systems. 51 55 69 2015 MathNet. 37 Sun Y J Z. Event-triggered filtering for nonlinear network discrete time systems. IEIE Trans. End. 6211 71 63 7170 2015. 38 H Su X H Yang F. Distributed event-triggered H-state estimation for TS fuzzy systems over filtering networks. J. 354 9 3763 779 2017 MathNet. 39 X Wen Y P Lam H. Event-triggered fuzzy filtering for nonlinear dynamic systems via reduced-order approach. IEIE Trans. Fuzzy. 27 6 1215 1225 2019. 40 HL. Control and estimation of systems with input-output delays. Springer Berlin 2007. 20. Canonical correlation analysis-based fault detection methods. 20.1. With the rapid development of the industrial Internet of Things and enabling technologies, such as advanced sensors and enhanced computing power, large volumes of data can now be easily collected in modern industrial processes for tasks like control, monitoring, and predictive maintenance. 1, 2. The physical interactions and feedback control mechanisms inherent in these processes result in widespread correlations among the collected variables. In statistics, dependence refers to any statistical relationship between two random variables or bivariate data. Generally, correlation indicates how closely two variables are related, although it often specifically pertains to their linear relationship 3. It is important to note that correlation does not necessarily imply a causal relationship. In the context of process monitoring and fault detection, correlations are valuable as they may reveal predictive relationships that can be utilized practically. Over the past few decades, multivariate analysis (MVA), which accounts for correlations among random variables, has been extensively explored in the realms of process monitoring and fault diagnosis. 4. Alongside techniques such as principal component analysis (PCA), 5, partial least squares (PLS), and independent component analysis (ICA), canonical correlation analysis (CCA) has emerged as a popular MVA tool for process monitoring and fault diagnosis. 6. A key distinction of CCA compared to other MVA methods is its strong connection to mutual information. 7. The concept of correlation did not emerge spontaneously. It was first introduced by Francis in the late 19th century. 8. Harold Hotelling introduced CCA in 1936 for studying relationships between two sets of variables, though the initial motivation was not related to industrial data analysis. 9. CCA was later employed by and 10 to quantify the information that one random function contains about another. Subsequently, 11 utilized CCA to analyze the information structure between the future and past states of discrete time stochastic processes, obtaining two representations defined by sets of canonical variables that project past information onto the future and vice versa. Although the CCA technique used in this work is similar to traditional CCA, it shifts the focus from static MVA to dynamic time series analysis. This is particularly relevant in industrial contexts, where data are often collected as time series at regular intervals. Building on this work explored CCA for system identification, filtering, and control of general linear systems represented by state space models, leveraging the information criterion AIC for determining state order 12. Unlike the conventional CCA in multivariate statistical analysis, this approach, termed canonical variate analysis (CVA), involves solving a related reduced-rank prediction problem, with the solution derived from the CCA of past and future covariance. Following contributions, CVA has been employed for process monitoring and fault detection. 1316. In such applications, the fundamental idea is to identify a state space model of the system in question, and subsequently detect anomalies either within that state space or behaviors that significantly deviate from it. For example, utilized a CVA-based fault detection method to monitor a chemical process. 17. In CVA-based monitoring methods, the state space model must first be established, and anomalies are typically classified into two categories, those affecting the state space and those that diverge from it. However, strict categorization of these anomalies can be challenging, as faults are often unknown and their occurrences may alter process dynamics. Furthermore, for monitoring tasks, it may not always be necessary to identify a state space model. Motivated by these observations, Ding proposed two CCA-based process monitoring methods for detecting faults in both static and dynamic processes. 18. Conventional CCA assumes that the residual signals follow a distribution, which limits its applicability. Moreover, modern processes are often large-scale, with different operational units being physically interconnected and exhibiting mutual correlations. To enhance monitoring performance, it would be beneficial to utilize both local measurements and data from neighboring blocks. However, many existing MVA-based plant-wide monitoring approaches decompose the entire process into several or blocks, detecting faults or monitoring each block using only local measurements, and then aggregating the local fault decisions at a fusion center. Therefore, motivated by the above observations, this chapter presents two representative CCA-based methods, a CCA-based fault detection method for non-processes and a correlation-based distributed fault detection method. 20.2 Basics of CCA. 22.1 Analysis of CCA. The following lemma shows that L and M are the square root inverses of the covariance matrices, and respectively. It should be noted that, with above lemma, both whitening and correlating two random vectors can be performed by CCA. The following lemma shows how to compute the canonical correlations. It follows from 20.15 that 1,2T2V comparing this with 20.13 gives the desired results. 22.2 Calculation of CCA. In practice, there are often two sets of random variables, such as the inputs and outputs of a plant or two units in cascaded systems. However, their mean values and covariances are typically unknown. Therefore, to determine the mapping matrices for CCA, estimated values must be used. We are now in a position to prove the following theorem, which shows important properties of CCA technique. In a similar way, 20.25, 20.26, and 20.27 can also be proved. This completes the proof. 20.3 CCA-based fault detection method for non-processes. A fault detection method generally consists of two main components, residual generation and an evaluation function. Due to the power and efficiency of statistical hypothesis testing, it is often used as the evaluation function. In this section, we first present the CCA-based residual generation process, followed by an introduction to two approaches for determining the threshold of the corresponding test statistics when the residual signal follows either a or a non-distribution. 23.1 Residual generation. Therefore, based on the discussion in Appendix, the 12-test statistic with residual R1 can achieve optimal fault detection when a fault occurs in U subspace. The U subspace is divided into two subspaces. The one is correlated with Y subspace and the other is uncorrelated with Y subspace. The U subspace is divided into two subspaces. The one is correlated with Y subspace and the other is uncorrelated with Y subspace. The Y subspace is also divided into two subspaces. The one is correlated with U subspace and the other is uncorrelated with U subspace. The Y subspace is also divided into two subspaces. The one is correlated with U subspace and the other is uncorrelated with U subspace. Thus, for fault detection in the Y or U subspace, the generalized CCA-based fault detection method is optimal when using the test statistic 22 or 12. Moreover, as long as faults do not appear simultaneously in both the Y and U subspaces, the generalized CCA-based method also remains optimal for detecting faults in each individual subspace. 23.2 Threshold setting. After obtaining the residual vectors, the next step is to define an appropriate threshold for the constructed T2 test statistics. In the following sections, we discuss two different scenarios for the distribution and non-distribution. Non-distribution. If the residual vector follows a distribution, setting the threshold for the 12 and 22 statistics is straightforward and can be achieved using standard distribution tables 1. However, in the case of non-residual signals, determining the threshold becomes significantly more challenging. In this section, we focus on setting the appropriate threshold in non-scenarios. We first introduce the definitions of false alarm rate FAR and fault detection rate FDR, which are important performance indicators influenced by the threshold. Then an approach for threshold setting is proposed. In the last subsection, we briefly summarize the procedures for applying the proposed method. For evaluating the performance of fault detection methods, the conventional approach is to assess false alarms and detection alarms. Given the time instance of the onset of a false alarm is an event where an alarm is triggered in the absence of a fault, while a detection alarm indicates an alarm triggered when a fault is present. From a probabilistic standpoint, the false alarm rate FAR and fault detection rate FDR are defined as the probabilities of false and detection alarms, respectively. Let J and represent the test statistic, and the corresponding threshold, respectively. The definitions of FAR and FDR are as follows: 20. For the T2 test statistic, the threshold is typically based on the assumption that the residual signal follows a distribution. However, if the residual is a threshold derived under assumptions cannot be used effectively for real-time fault detection. A standard solution to this problem is to use distribution estimation-based approaches, such as mixture models, GMM, or kernel-based techniques 1521. These methods, however, require the selection of appropriate kernel parameters or the number of mixture components. Although such methods are widely used to address non-cases, the desired detection performance is highly dependent on selecting suitable parameters, which are often determined heuristically or through trial and error. Recall that an appropriate threshold can be set for a specific confidence bound, which in this paper is represented by the FAR. The primary objective of determining a threshold is to reduce FAR to an acceptable level. Ideally, the best threshold is one that results in zero FAR. However, this is often achieved at the cost of a lower FDR. Threshold setting is challenging, especially when dealing with uncertainties, and remains a complex topic in both academia and industrial applications. A common practical approach is to determine the threshold based on sufficient repeated testing under varying operational conditions. For example, thresholds for sensor fault detection in electronic stability programs, ESP, are set through extensive testing under different driving conditions 22. In this section, we propose a randomized algorithm, RA-based method for threshold setting, which follows a similar approach. The proposed algorithm consists of two main steps: FAR estimation and threshold update. 1. The basics of RA for our study. For BI01, we have then the following theorem. 2. RA-based threshold setting. To calculate the FAR, several approaches are available. For instance, a numerical approximation approach presented in 25 is straightforward to use but may have a significant estimation error. Alternatively, a theoretical approach was proposed in 26, which is based on a probabilistic framework but is more complex for practical application and requires an analytical expression. In this work, we utilize a numerical approximation approach based on a randomized algorithm, which is simple for practical implementation while maintaining an acceptable estimation error. 23.3 Application to the TDCS of high-speed trains. The schematic diagram of TDCS. In traction mode, the transformer receives a single-phase high AC power S from the grid, which it steps down to a lower voltage, single-phase AC power, that is supplied to the rectifier. The output voltage UD1 plus 2 of the rectifier is stabilized at a given value by the DC link. The inverter then converts the DC link output into three-phase AC voltage current, 0 ISD and 0, providing power to drive the motor. Consequently, the train can accelerate to a given speed, which is set by the driver control room. Additionally, and represent the gate control signals for the traction control unit, TCU, which are sent to the power transistors of the rectifier and inverter, respectively. Variables in TDCS. No. Description. Variable. Input-output. 1. AC voltage of grid side. Input. 2. AC current of grid side. Input. 3. A phase of converter current. Output. 4. B phase of converter current. Output. 5. C phase of converter current. Output. 6. Speed of the train. Output. 7. Voltage of DC link. 1. Output. 8. Voltage of DC link. 2. Output. A fault injection benchmark simulation platform has recently been developed to verify fault diagnosis methods 27. This platform consists of fault injection modules and the traction drive control system, TDCS, with fault injection implemented at both component and device levels. The fault injection benchmark is available online at Index E and provides 23 fault scenarios. In this study, we consider 10 typical faults, as listed in Table 22. Brief description of typical TDCS faults. Fault IDs. Description of faults. Fault type. Fault location. 1. The IGBT device in converter is open. Offset fault. Converter. 2. Converter power periodic. Offset fault. Converter. 3. The output signal is constant offset. Offset fault. Sensor. 4. The sensor drift. Drift fault. Sensor. 5. The sensor gain fault. Random. Sensor. 6. Sensor open fault. Offset fault. Sensor. 7. TSIU digital mode fault. Offset fault. TSIU. 8. TSIU register mode fault. Offset fault. TSIU. 9. Motor air gap faults. Offset fault. Motor. 10. Motor bar broken faults. Offset fault. Motor. Application of the proposed method to TDCS. For this case study, the 2 variables and in are selected as inputs, while the remaining 6 variables are treated as outputs. The TDCS data consists of 2 datasets, the training dataset and the test dataset. The data from normal operation is referred to as the training data. The trajectories of the 8 variables during normal operation are shown in Fig. 20.2. The trajectories of the fault-free variables. Results and discussions. This section evaluates the monitoring performance of the proposed fault detection (FD) methods. As introduced in 18, a robust FD method should be insensitive to variations in data outside the training set, sensitive to all possible system faults, and prompt in detecting faults. Robustness is commonly using the false alarm rate FAR, as previously discussed. Fault detection sensitivity is by the fault detection rate FDR, while the promptness is denoted by the detection delay DD, which measures the time taken to detect a fault after its occurrence. Since the threshold is determined based on the desired FAR, only FDR and DD are used here to assess the detection performance of the FD methods. The detection performance of the proposed method is compared with the conventional CCA-based method using all faults described earlier. The superiority of the CCA with RA over the conventional method is demonstrated in Table 23. For all faults, the CCA with RA achieves better FDR performance, largely due to the non-nature of the system. The detection delay DD results for both the CCA with RA and the conventional method are also shown in Table 23, with DD measured in terms of the sample interval. The proposed method generally detects faults earlier than the conventional method, providing operators with more time to take safety measures. Detection results in terms of FDR and DD. Fault IDs. FDR of 12. FDR of 22. DID of 12. DID of 22. CCA with RA %. CCA %. CCA with RA %. CCA %. CCA with RA. CCA. CCA with RA. CCA. 1. 54.58. 24.47. 100. 99.35. 126.2. 737.9. 0.3. 101.8. 2. 18.19. 8.98. 75.79. 37.98. 122.1. 260.2. 34.7.
1079.2. 3. 22.23. 1.5. 94.87. 92.67. 126.3. 1492.3. 0. 0. 4. 2.51. 0. 79.94. 1.41. 3719.7. 540.5. 77,124.1. 5. 10.95. 1.29. 98.97. 93.03. 188.9. 4,740.6. 0. 0. 6. 20.67. 2.6. 97.33. 92.37. 135.1. 734.2. 0. 0. 7. 100. 100. 100. 100. 0.2. 0. 0. 0. 8. 9.17. 1.51. 72.95. 1.25. 462.7. 19,535.4. 0.8. 9. 56.19. 40.22. 95.85. 61.06. 146.5. 155.3. 0. 0. 10. 60.01. 35.12. 75.61. 40.99. 81.3. 111.7. 0. 0. Detection results of fault 1 for CCA. Solid test statistics dashed, assumption-based threshold, raw-based threshold. Detection results of fault 4 for CCA. Solid test statistics dashed, assumption-based threshold, raw-based threshold. Detection results of fault 8 for CCA. Solid test statistics dashed, assumption-based threshold, raw-based threshold. Detection results of fault 9 for CCA. Solid test statistics dashed, assumption-based threshold, raw-based threshold. 23.4. A schematic of a 7-stand HTRM process, where the control systems of different stands communicate with each other through Ethernet through HTRM. The raw steel slab is milled to the exit steel slab. 20.4 Correlation-based distributed fault detection method. In a hot tandem rolling mill HTRM process, the operating performance of mill stands can determine the quality of steel products, thus should be properly monitored. Unlike previous work, which focused on a single stand or multiple stands together, this chapter proposes an improved statistical fault detection (FD) method for real-time process monitoring of a target stand by considering its correlation with neighboring stands. First, it is that the detection performance of the traditional statistical FD method can be improved by reducing the influence of noises in process data. Then, a distributed CCA-based FD method is developed to reduce the influence at the target stand by means of the compressed data transmitted from neighboring stands through a communication network. Furthermore, the proposed method can decrease the transmission and computational costs incurred by the centralized CCA method, which makes it applicable to the HTRM process. A hardware-in-the-loop simulation is finally carried out to validate the proposed method, where better monitoring performance is shown compared with the existing methods. 24.1 Motivation. It has currently become accepted practice in the steel manufacturing industry that the overall process should be properly monitored in spite of using advanced control methods,
since even a small fault or unpermitted change, if ignored, may lead to tremendous safety and economic losses. 29. One solution to this problem is the application of FD methods, which can determine not only whether and when the process under supervision is not operating well, but also to determine the potential root cause once an abnormal operation is detected. 3033. Although model-based FD method can be implemented if process model exists, obtaining such models for steel manufacturing processes is often difficult due to the complex nature of the process. Instead, data acquisition and management systems are commonly installed in modern industrial plants. For example, in an HTRM process, as shown in Fig. 20.7, the rolling and bending forces, the gap between two working rollers, the rotating speed of rollers, and different control signals can be measured, transmitted, and finally stored in the plant database. With the rapid growth in amount of available data, process engineers are now with the challenge of dealing with big data. 3435. Furthermore, common processes, such as the HTRM process shown in Fig. 20.7, are increasingly becoming interconnected. Thus, using process data to monitor complex industrial systems has recently become a topic of interest. In fact, the operating conditions of an industrial process can be monitored using data analytics-based FD methods. First of all, historical data are properly modeled by various data modeling methods to extract features that can reflect normal operating conditions. Then, the online operating condition can be decided by examining whether any change occurs in features 1, 2931. Among different data analytics methods, the commonly used ones focus on determining the boundary features of normal data, such as support vector and nearest neighbor-based methods. 36. Once the distance from the real-time data to the boundary feature is larger than a threshold, a fault alarm can be triggered. When the obtained features well fit the actual boundary of normal operation data, better detection performance will be achieved. Another widely used technique is the multivariate statistical methods, such as principal component analysis (PCA), independent component analysis (ICA), and partial least squares (PLS)-based methods, as well as their variants and extensions 30, 35, 37, 38. Unlike above methods, these methods focus on determining features of the normal operation data using low-dimensional latent variable data. It is also assumed for these methods that a clearer and more detailed interpretation of the normal data leads to a lower missing alarm rate (MAR). Then, the real-time data that cannot fit to the established latent variable model will be an indication of a fault. Considering the uncertainties in the data due to noises, FD statistics like the T2 and the generalized likelihood ratio, GLR test statistics, are often used for the decision-making process. 139. Note that once a fault has been detected using a multivariate statistical FD method, contribution analysis and causality analysis-based methods can be performed to identify the potential fault root cause. 36, 37. Due to the simplicity and efficiency in processing huge amount of process data, multivariate statistical methods are nowadays widely accepted in practice. Above statistical FD methods are developed considering the entire uncertainties corrupted in process data. Recently, modifications have been made to provide a fault information for modeling, such that uncertainties in original data can be, to some extent, reduced, and then the FD performance is accordingly improved. 4143. For example, if the latent variables affected by a given fault are known beforehand, then solely monitoring these affected latent variables would be straightforward and effective to detect this fault. 42. However, in many practical cases like the HTRM process, the amount of available information about the faults is considerably limited, especially compared with the massive amounts of normal operation data. Thus, it can be difficult to apply this approach to most industrial applications. It is often the case in process industry that parts of uncertainties like noises are normal variations within the process. They mainly come from upstream processes or caused by the local controller, which, compared with the measurement uncertainty, are always predictable. Reducing the influence of such uncertainties by means of data processing methods would improve the FD performance, in particular for statistical methods. 40. Previous applications of data-driven FD methods to the HTRM process monitoring have focused on two different schemes. In the first one, simultaneously monitoring of the whole plant is under consideration. That is, FD methods are developed using the data from multiple stands, like 7 stands as shown in Fig. 20.744-45. Using these methods, the whole plant operation can be tracked, while detailed operation of an individual stand is ignored. Differently, the second one is dedicated to monitoring the behavior of each stand, and data from an individual stand are used for developing FD methods 46. However, since the upstream stands can determine the offline setting and online performance of the systems, e.g. the bending and rolling force systems, in downstream stands, the operation of a stand can be better monitored if the information from its upstream stands is used. Motivated by above observations, objectives of this chapter are: 1. To demonstrate in the context of T2 test statistic that the fault can be improved when the covariance matrix of the noises is reduced. 2. To propose a correlation-based statistical FD method that reduces the covariance of the noises. 3. To extend the proposed method to a distributed form that makes it applicable to the monitoring of an HTRM process. 4. To show the applicability of the proposed method using a cloud-edge-end collaborative prototype system. Notation: let be the m-dimensional Euclidean space, M be the set of n-m real matrices, Im be the m-dimensional unit matrix, represent the trace of a matrix, range T denote the space spanned by the columns of T, X represent a normally distributed vector with mean vector and covariance matrix, F denote the norm of a matrix, 2 be the 2 distribution with m degrees of freedom. 2 be the 2 distribution with m degrees of freedom and parameter 2. Let 2 represent the probability that 2 equals. 24 2 basic ideas and problem formulation. In this section, the basic idea of improving the detection performance of statistical FD methods via reducing uncertainties due to process and measurement noises is introduced. As well, the open problems of applying this idea to the monitoring of an HTRM process are formulated. A. Improved statistical FD methods via reducing uncertainties. Comparisons of FDR in sense of 2, 2212 gives FDR2 FDR1 to 2x denotes the probability density function of 2 distribution. If we have two vectors of data yobs I and yobs j, like data from two stands in the HTRM process, and they satisfy ye obs iyjjyi where and denote their covariance matrices and denotes their cross-covariance matrix. For the sake of simplicity, n0 iyjjyi is used in following deviations. Algorithm 14. 1 for j1 to m, let 0, 0t with 1. For j1 to m, let 0, 0t with 1. 2 do yjyj ft, 1 1t 1 yjf. Do yjyj ft, 1 1t 1 yjf. Comparison between T2 and improved T2 statistics for detecting the fault occurring in Y1. The red dashed line is the threshold with 005. Comparison between T2 and improved T2 statistics for detecting the fault occurring in Y2 and propagating to Y1. The red dashed line is the threshold with 005. B. Fault detection problem formulation in HTRM. Based on above analysis, it can be claimed that a stand in the HTRM process can be better monitored using statistical FD methods when the data from its neighboring stands can be accessed. However, a direct use of such a method may not be well suited in practice. In an HTRM plant, each stand is manipulated by a local programmable logic controller, PLC, and the measured data are also provisionally stored in PLC, then transmitted to the plant database. To guarantee a reliable and successful real-time monitoring, it would be favorable if the FD method can be performed directly using the PLC data rather than using data from the database. However, compared to personal computers or servers, the local PLC system is commonly limited in its computational resource. Thus, the centralized training of statistic 20.57 in a local PLC becomes difficult, especially in cases that the data dimension is significantly large. Therefore, it is suggested that the intensive computation of 20.57 can be assigned to all local PLC servers. Also note in Fig. 20.7 that different stands communicate with each other via Ethernet. Thus, when transmitting high-dimensional data is needed in the development of methods, the communication bandwidth should be considered 47. In fact, due to the inherent correlation between different variables in each stand, transmitting the compressed information rather than the raw data will save the transmitting cost. As a result, the practical needs in the HTRM process introduce a further issue to be addressed in this chapter, namely the improved statistical FD methods performed in a distributed manner, and meanwhile, useful information from a stand can be compressed and transmitted to those stands needed to monitor. 24.3 The distributed CCA-based FD method. Aiming at improving the overall FD performance, this section will introduce the typical correlation analysis tool, CCA, and demonstrate its use to reduce the influence of the noises. Moreover, modifications to CCA will be made to make it applicable to the HTRM process. The CCA method. Algorithm 15.1.48. 1. Estimate and 2. Perform an SVD on 1212 20.62. 3. Let L12U1J12V1 20.63. B. The distributed CCA method. In HTRM, the stand to be monitored is called the target stand, whose variables are denoted as YT. As shown in Fig. 20.7, there are K neighboring stands correlated to the target stand, whose variables are denoted as YN11, respectively. For the purpose of implementing CCA-based FD method, we would like to reformulate the CCA algorithm between YT and YN1T YNKTT with LK1 in a recursive form, so that projection vectors J can be obtained in a distributed manner. 1. Set 0 Q1 is the iteration index. Set 0 Q1 is the iteration index. 2. Randomly initialize L and J. Randomly initialize L and J. 3. Obtain +1 and +1 as a solution of LT, YNJ, SD. TL, NJ, K1, KQ range L range. TL, NJ. TL, NJ. K1, KQ range. K1, KQs. Range L range. Range L range. 4 +1 QQ +1 return to step 2. +1 QQ +1 return to step 2. Algorithm 16. 1. Set 0 and randomly initialize JKK for K1. K set 0 and randomly initialize JKK for K1. K2 for K neighboring stands. Each stand collects data and send Y with J1 to other neighboring stands in the target stand. For K neighboring stands, each stand collects data and send Y with J1 to other neighboring stands in the target stand. 3. At the target stand, collect data and run algorithm 15 on YJ and YJ with J1 to obtain and send G and Y with J1 to K neighboring stands. Collect data and run algorithm 15 on YJ and YJ with J1 to obtain and collect data and run algorithm 15 on YJ and YJ with J1 to obtain and send G and Y with J1 to K neighboring stands. Send G and Y with J1 to K neighboring stands. 4. At Q neighboring stand, run algorithm 15 on YNJ and YJ to obtain and J+1 partition J+1 as +1 0 J+1 GQ 0 K1 J+1 send GQ and to other neighboring stands in the target stand. At the K1 KQ neighboring stand, update JK +1 JK GK. Update +1 at the target stand. Run algorithm 15 on YNJ and YJ to obtain and J+1. Run algorithm 15 on YNJ and YJ to obtain and J+1. Partition J+1 as +1 0 J+1 GQ 0 K1 J+1 send GQ and to other neighboring stands in the target stand. Partition J+1 as +1 0 J+1 GQ 0 K1 J+1. Send GQ and to other neighboring stands and the target stand. At the K1 KQ neighboring stand, update JK +1 JK GK. Update +1 at the target stand. At the K1, Q neighboring stand, update JK plus 1 JKGK. Update plus 1 at the target stand. 5 set QQ plus 1, return to step 4 if QK plus 1 turns step 6. Set QQ plus 1, return to step 4 if QK plus 1 turns step 6. 6 if F is a small scalar e.g. 10-8 stop the algorithm and retain L, JK, and else return to step 2. If F is a small scalar e.g. 10-8 stop the algorithm and retain L, JK, and else return to step 2. Of the distributed CCA algorithm. Comparisons between centralized and distributed CCA methods. Performance type. Methods. Neighboring stand 1. Neighboring stand 2. Target stand. Transmission bandwidth. Centralized CCA. Distributed CCA. Computational complexity flops. Centralized CCA. O5M3. Distributed CCA. O2M plus 22 plus 2M3. O2M plus 22 plus 2M3. O4-2M plus M3. 24 applications to the HTRM process. In this section, the developed distributed CCA-based method will be applied to the real HTRM process monitoring problem. For this purpose, a cloud edge-end collaborative prototype system, including the data processing and stand communication systems, is built, and real data in normal and faulty operations are used to validate the applicability of the distributed CCA. A brief introduction to HTRM. A schematic of an individual stand in HTRM. The cloud edge-end collaborative prototype system. B. The cloud edge-end collaborative prototype system. Hardware configuration for the prototype system. Layer. Hardware configuration. End layer. PLC. VME cabinet with A021C board. Server. CPU. 11th Gen Intel R Core TM, i7-11700 at 2.5G. RAM. 32 GB. GPU. Intel R UHD Graphics 750 and NVIDIA T400. Edge layer. Server. CPU. 11th Gen Intel R Core TM, i7-11700 at 2.5G. RAM. 32 GB. GPU. Intel R UHD Graphics 750 and NVIDIA T400. Cloud layer. Server. CPU. Intel RR Platinum 80 358P CPU at 2.6G. RAM. 256 GB. GPU. 4 NVIDIA Force RTX 4090. Converging process for an L in distributed CCA algorithm. Reduced uncertainties by the distributed CCA method. Steel 1 2.7 Steel 2 3.95 Steel 3 5.1 6.621105 5.634105 3.311105 4.45410 3.30210 6.58810 See monitoring results and discussions. 1. 3 fault cases. In this application study, 3 typical fault scenarios are considered. The first one is caused by the malfunction of the hydraulic rolling force system in stand 4. It occurs during the process to produce 2.7 thickness steels, and because of it, stand 4 cannot mill the steel to the targeted thickness. Due to the automatic gauge control system, this fault will propagate to stand 5. The second fault is caused by a bending force sensor failure at stand 5. It occurs when producing 3.95 thickness steel, and will directly affect the bending force measurements at stand 5. This fault can cause the center buckle to form on the surface of steel. The third fault arises when the cooling water valve at stand 3 is blocked. This fault can instantly increase the surrounding temperature, and thus, the rolling force at stand 3 is decreased. Like the first fault, this fault will also propagate to stand 4 and 5. Monitoring results given by the T2 statistic and distributed CCA-based method for the first fault, the red dashed line is the threshold with 005. Monitoring results given by the T2 statistic and distributed CCA-based method for the second fault, the red dashed line is the threshold with 005. Monitoring results given by the T2 statistic and distributed CCA-based method for the third fault, the red dashed line is the threshold with 005. Based on above results, it can be concluded that the proposed method can effectively detect various faults in the HTRM process. Comparisons between the proposed method and commonly used methods in sense of FAR and FDR. Performance type. Type 2. PCA. KPCA. PLS. ICA. Fault 0 FAR. 0.067. 0.106. 0.11. 0.103. 0.098. Fault 1 FDR. 0.586. 0.681. 0.703. 0.768. 0.634. Fault 2 FDR. 0.065. 0.926. 0.896. 0.768. 0.805. Fault 3 FDR. 0.107. 0.747. 0.755. 0.781. 0.629. PCA. KPCIACA. Distributed CCA. 0.09. 0.15. 0.049. 0.06. 0.952. 1. 0.072. 0.901. 0.988. 0.228. 0.988. 1. 24.5. In this section, a correlation-based distributed multivariate statistical FD method has been proposed for real-time monitoring industrial processes. It has been shown that the detection performance of commonly used statistics can be enhanced when the influence of the noises is reduced. A CCA-based method has been introduced to reduce the uncertainty corrupting the dataset by means of the correlations with the other datasets. Furthermore, motivated by the actual problems met in the HTRM process, a distributed CCA method has been proposed such that neighboring stands' information can be efficiently transmitted to the target stand, and the required computations can be distributed to all neighboring stands. Finally, the whole proposed methods have been validated using real HTRM data and a CloudEdge collaborative prototype system, where better performance has been achieved compared with existing methods. 20.5 Conclusion. In this chapter, the fundamentals of CCA are introduced, along with two representative CCA-based fault detection methods, one for non-processes and one for plant-wide processes. For fault detection in non-processes, the CCA-based method is enhanced using a raw technique to derive more suitable thresholds for the test statistics. This approach is applied to the traction drive control system, TDCS, and its detection performance is compared to that of an assumption-based CCA method. FDR and DID are used to assess and compare the two methods. The proposed method demonstrates superior performance compared to the CCA method with assumptions, even though both methods detect some faults. For large-scale processes, a correlation-based distributed fault detection method is proposed. The distributed version helps reduce the influence of noise. The effectiveness of the distributed CCA-based method is demonstrated through application to a real HTRM process. The results indicate that the distributed method outperforms existing methods. 20.6 Appendix. In this appendix, the relation between T2 test statistic and optimal fault detection is introduced. Hence, for the T2 test statistic, a minimum covariance matrix is desirable to achieve optimal fault detection with a given significance level. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1 Ding SX, Data-Driven Design of Fault Diagnosis and Fault-Tolerant Control Systems. Springer, New York, 2014. 2 Chin S.J., L.H., Advances and Opportunities in Machine Learning for Process Data Analytics. Land 126, 465, 473, 2019. 3 W.K. Simmer, L., Canonical Correlation Analysis. In Applied Multivariate Statistical Analysis. 443, 454. Springer, New York, 2015. 4 Anderson, T.W., An Introduction to Multivariate Statistical Analysis. New York Tech. Rep. 1962. 5 H. B. N. Mao Z. Deep PCA-based real-time incipient fault detection and diagnosis methodology for electrical drive and high-speed trains. IEIE Trans. Techno. 67-6, 48-19-4830, 2018. 6J, Fault Detection and Diagnosis in Industrial Systems, Advanced Textbooks in Control and Signal Processing. And Robot. J. 2001. 7M Canonical Correlation, a Tutorial. Online Tutorial. 4 No. 5 2001. People. 8 SM, Francis' Account of the Invention of Correlation. Stat. 7379, 1989. 9 Harold H., Relations between Two Sets of Variates. 2834, 321, 377, 1936. 10 IA, Calculation of the amount of information about a random function contained in another such function. American Mathematical Society Translations. American Mathematical Society, 1959. 11 H, Representation of Stochastic Processes by Canonical Variables. Siam J. Control. 13-1, 162, 173, 1975 MathNet. 12 WE, Canonical Variate Analysis in Identification, Filtering, and Adaptive Control. In 29th IEIE Conference on Decision and Control. 596-6-4. IIIE's 1990. 13 YDE WE, Process Monitoring Using Canonical Variate Analysis and Principal Component Analysis. IFAC Proc. 39, 577, 582, 1997. 14 BC DA WE, Fault Detection Using Canonical Variate Analysis. Ind and Raise. 43-2, 458, 474, 2004. 15 PPY, Nonlinear Dynamic Process Monitoring Using Canonical Variate Analysis and Kernel Density Estimations. IEIE Trans. And
Inform 613645 2009. 16b XD RD Canonical Variate Analysis-Based Monitoring of Process Correlation Structure Using Causal Feature Representation. J Process Control 32 109 116 2015. 17 EL LH RD Fault Detection in Industrial Processes Using Canonical Variate Analysis and Dynamic Principal Component Analysis. Lab 51 8193 2000. 18 Z Ding SX K Lay Z Canonical Correlation Analysis-Based Fault Detection Methods with Application to Alumina Evaporation Process. Control 46 51 58 2016. 19 T Subspace Methods for System Identification. Springer, London 2005. 20 Ding SX Model-Based Fault Diagnosis Techniques 2nd. Springer, London 2013. 21 T J Martin E Probability Density Estimation via an Infinite Mixture Model Application to Statistical Process Monitoring. J.R. Stat Stat 55.5 699 715 2006. 22 Ding EL Fennel H Ding SX Model-Based Diagnosis of Sensor Faults for ESP Systems. Control 12.7 847 856 2004. 23 Tempo RGF Randomized Algorithms for Analysis and Control of Uncertain Systems. Springer 2005. 24 ZW Data-Driven Fault Detection for Industrial Processes, Canonical Correlation Analysis and Projection-Based Methods. Springer Wiesbaden 2017. 25 Yin S Ding SX A HYP A Comparison Study of Basic Data-Driven Fault Diagnosis and Process Monitoring Methods on the Benchmark Tennessee Eastman Process. J Process Control 22 1567 1581 2012. 26 K HY ZW Ding SX Peng KX A Comparison and Evaluation of Key Performance Indicator-Based Multivariate Statistics Process Monitoring Approaches. J Process Control 33 112 126 2015. 27 Yang CH Yang C Peng T Yang XY GUI WH A Fault Injection Strategy for Traction Drive Control System. IEIE Trans and Electron 64-7 57-19 5727 2017. 28 YW and JY Ma C Fault Detection of Non-Processes Based on Model Migration. IEIE Trans Control Technol 21-5 1517 1526 2013. 29 KP RD Perspectives on Process Monitoring of Industrial Systems. Rev. Control 4821 931 939 2016. 30 Chin SJ Survey on Data-Driven Industrial Process Monitoring and Diagnosis. Rev. Control 362 222 34 2012. 31 Z C Ding SX A Survey of Fault Diagnosis and Fault-Tolerant Techniques Part II, Fault Diagnosis with Knowledge-Based and Hybrid Active Approaches. IEIE Trans and Electron 62-6 3768 3774 2015. 32 Yin S Ding SX X Luo H A Review on Basic Data-Driven Approaches for Industrial Process Monitoring. IEIE Trans and Electron 6111 6418 642 8 2014. 33XZ From Model Signal to Knowledge, a Data-Driven Perspective of Fault Detection and Diagnosis. IEIE Trans and 94 22 26 223 8 2013. 34 Chin SJ Process Data Analytics in the Era of Big Data.
EJ 69 3092 3100 2014. 35 Yin S.O. Big Data for Modern Industry, Challenges and Trends. Prague. IIIA 103-2, 143-146 2015. 36 Z Song Z Ding SX B. Data Mining and Analytics in Process Industry, The Role of Machine Learning. IEEE Access 5, 20592-0616, 2017. 37 MacGregor JFCCM, Process Monitoring and Diagnosis by PLS Methods. EJ 45, 826-838, 1994. 38 Q Chin SJ Chai T, Unevenly Sampled Dynamic Data Modeling and Monitoring with an Industrial Application. IEIE Trans. End. 13.5 22032213, 2017. 39 D. Fault Isolation in Data-Driven Multivariate Process Monitoring. IEIE Trans. Control. Technol. 23.5 1841852, 2015. 40 MS PM. Integration of Data Uncertainty in Linear Regression and Process Optimization. EJ 5111, 3007-3019, 2005. 41 Y Fan Y Yang N. Fault Diagnosis of Processes Based on Similarities. IEIE Trans. End. Electron. 63.6, 26062614, 2016. 42 YW Fan Y Lay X. Comprehensive Correlation Analysis of Industrial Process. IEIE Trans. End. Electron. 6412, 94619468, 2017. 43 C. F. Fault Subspace Selection Approach combined with analysis of relative changes for reconstruction modeling and multi-fault diagnosis. IEIE Trans. Control. Technol. 24.3, 928-939, 2016. 44 Peng K. KU B. Dong J. Z. A quality-based nonlinear fault diagnosis framework focusing on industrial batch processes. IEIE Trans. End. Electron. 63.4, 2615-2624, 2016. 45 Ding SX Yin S Peng KX HY Shen B. A novel scheme for key performance indicator prediction and diagnosis with application to an industrial hot strip mill. IEIE Trans. End. 94, 2239-2247, 2013. 46 A.M.D. A brief review and a first application of time-frequency-based analysis methods for monitoring of strip rolling mills. J Process Control 35-2, 6579, 2016. 47 YJB. Robust Tracking Control of Network Control Systems. Application to a network DC motor. IEIE Trans. End. Electron. 6012 5864 5874, 2013. 48 Z Ding SX Peng T Yang CH GUI WH. Fault detection for non-processes using generalized canonical correlation analysis and randomized algorithms. IEIE Trans. End. Electron. 65-2, 1559-1567, 2018. 49 A.M. Distributed Canonical Correlation Analysis in Wireless Sensor Networks with application to Distributed Blind Source Separation. IEIE Trans. Signal Process 63118, 4804813, 2015 MathNet. 50 Bishop CM, Pattern Recognition and Machine Learning. Springer, London, 2014. 51 C Gong YS B Sarkar S. Bridge Damage Detection using Spatiotemporal Patterns extracted from Dense Sensor Network. Technol. 28-1, 14011, 2017. 52 A.M. Distributed Adaptive Estimation of Covariance Matrix Eigenvectors in Wireless Sensor Networks with application to Distributed PCA. Signal Process 104,
12135, 2014. 53 Q Chin S.J. Chai T. Concurrent PLS for decentralized monitoring of continuous annealing processes. IEIE Trans. And Electron. 6111, 6429, 6431, 2014. 54 Peng K. K. He X. Li G. Yang X. New kernel independent and principal components analysis-based process monitoring approach with application to hot strip mill process. IIT Control. Theory and 816, 1723, 1731, 2014. 55 Power PC User Instructions Set Architecture Book I, version 2.02, 2012. 56 I. Detection of Abrupt Changes, Theory and Application. Prentice Hall, New York, 1993. 21. Wind Turbine Converter Fault Detection, based on ACLSGAN Deep Forest. Abstract. Fault diagnosis is crucial for wind turbine converter, which often faces problems of the unbalanced samples of different categories. Thus, sample generation techniques are often used. However, traditional models like GAN are difficult to generate samples of specific categories. To address this problem, an ACLSGAN, auxiliary classifier least squares generative adversarial networks, model is used to optimize the training data of the fault diagnosis model. Moreover, a sample enhancement algorithm is proposed for anomaly detection of wind turbine converter based on an adversarial network with the least squares loss generation of auxiliary classifiers. In the ACLSGAN algorithm, the least squares loss function is used to alleviate the pattern collapse problem and enhance the stability and generalization ability of the model. With the introduction of auxiliary classifiers, ACLSGAN better learns to generate data distributions related to specific categories, which significantly improves the model ability to learn to generate data distributions and improves the quality of the generated samples. The generated samples are then used as training data to train the deep forest model to improve its performance and accuracy in the practical application of wind turbine converter fault detection. The experimental results show that compared with other oversampling methods, the ACLSGAN fault detection method achieves lower leakage and false alarm rates while ensuring high accuracy. 21.1 Introduction. Due to the interconnection of large power grids and the continuous development of the wind power industry, the structural design of WTG's wind turbine generator systems has become more and more complex and sophisticated with different functions. At the same time, the failure rate is also increasing because wind turbines are large-scale power generation equipment operating in complex environments for extended periods. However, wind turbine failure will be difficult to repair and need to spend a lot of time and resources. Since converter failure is one of the most common failures in WTGs, it is very critical to realize the detection of converter failures and accurate diagnosis of failures in order to improve the safety and reliability of WTG system operation, as well as reduce the operation and maintenance costs. 1.3. The study of the converter fault detection and accurate fault diagnosis is very critical to improve the safety and reliability of wind turbine system operation and reduce operation and maintenance cost. The purpose of fault detection is to diagnose various abnormal states or fault states of wind turbine converter components in a timely and accurate manner, to prevent or eliminate faults, and to improve the reliability, safety, and effectiveness of the operation of related components. 4. Fault detection methods can be divided into two categories: model-based and data-based methods. Model-based fault detection methods include parameter estimation method, state estimation method, equivalent space method, etc. Data-based fault detection methods include signal-based methods, methods based on statistical analysis, and methods based on machine learning. Data-based fault detection models are applicable to different scenarios. However, the data in industrial sites are characterized by imbalance, high dimensionality, and complexity and variety of data types. For target faults occurring in daily process operations, it is more common to have no or little available fault data in industrial scenarios.
Considering that many faults can be destructive and cause significant losses, few plants are allowed to run to a fault state in order to collect fault data samples to train a fault diagnosis system 5. Meanwhile, the unbalanced converter data samples remain a major challenge for intelligent fault diagnosis applications. In data sets with unbalanced categories, fault class samples are often the object of attention. The complexity of wind turbine converter faults and the difficulty to obtain fault samples lead to sample imbalance and state problems in fault diagnosis 6. For the converter data imbalance problem, the existing solution from the data point of view is mainly oversampling 7, 8, and data synthesis methods. From the perspective of diagnosis algorithm, the algorithm is learned by considering the differences in the cost function of different cases, which is mainly based on cost-sensitive learning algorithm. In literature 9, a modified data augmentation method is used to create new synthetic samples from a small number of class samples and classify the data in the target training set. In literature 10, k-means SMOTE algorithm is proposed by improving the SMOTE method and applying it to the oversampling technique to reduce the noise generation. In literature 11, an unbalanced classification method is developed for mechanical failure data based on the cost-sensitive framework of convolutional neural network, which effectively realizes the unbalanced classification of mechanical failure data by establishing a new cost-sensitive loss function to assign a larger cost to the minority class samples and a smaller cost to the majority class samples. Although the aforementioned methods can produce some effect in solving the sample imbalance problem, the data level method will cause the problem of overgeneration, overfitting, or changing the distribution of the original data when synthesizing new samples. At the same time, the cost-sensitive algorithm needs to set up the cost weights and the cost matrix reasonably. When the data imbalance ratio is too large, the improved effect is limited due to the lack of the feature information of the minority class samples. In 2014, Al. 12 proposed Generative Adversarial Network (GAN), which can extract the distributional features of samples in an unsupervised learning approach and generate new samples in a better way. Then Conditional Generative Adversarial Network (CGAN) 13, Deep Convolutional Generative Adversarial Network (DCGAN), and other improved models. 14 is further proposed and widely used in the fields of image recognition and fault diagnosis 15-17. Literature 18 proposes a GAN-based fault diagnosis method for reciprocating machinery and validates the effectiveness of the method in the case of data imbalance through experiments. Literature 19 proposes a method to improve GAN to generate artificial samples under mechanical fault conditions and perform cross-domain diagnosis. In literature 20, a one-dimensional convolutional neural network is utilized to construct an auxiliary classifier for data expansion, where the additional label information facilitates the generation of corresponding fault samples. The above GAN-based data generation methods have the ability to reconstruct data and recover data despite high dimensionality and large percentage of loss to some extent. However, the limitation of the loss function makes the GAN suffer from the problem of gradient vanishing during the training process. In order to enhance the ability of fault diagnosis for wind turbine converter, this paper develops the auxiliary classifier least squares generative adversarial network (ACLSGN) model with the deep forest model for fault diagnosis. The model is characterized by high accuracy, high detection rate of small samples, and fast classification speed on the basis of solving the data imbalance problem. On the data set, the deep forest model has the advantages of fewer and improved classification ability of input data. 21.2 Failure Analysis for Wind Turbine Converter. Structure of wind turbine converter. The accurate diagnosis and classification of wind turbine converter faults is of paramount importance in ensuring the stable operation of wind turbines. It is responsible for converting the unstable alternating current AC, generated by wind turbines, WTGs, into stable electricity for use in the power grid. Additionally, it oversees the regulation and optimization of the performance of the entire wind power system. The efficient operation of the converter ensures the quality of power, improves the efficiency of power generation, and reduces energy loss. However, converters operating in long-term and complex environments are exposed to a variety of potential failure risks, which not only affect power generation efficiency, but also may cause damage to the equipment and even lead to system downtime. 21.3 Methodology. 21.3.1 Generating Adversarial Networks. GAN is a deep learning architecture whose core concept is to generate realistic data samples through two competing neural network models, the generator and discriminator. 21.3.2 ACLS-GAN Algorithm. 21.4 ACLS-GAN Deep Forest-Based Fault Detection Model. In order to address the issue of data imbalance, enhance the detection rate of data samples, simplify the overall model, and reduce the time required for classification while maintaining accuracy, this paper proposes a wind turbine converter fault detection framework based on deep forest with an improved LSGAN generative model. The framework is comprised of two primary components, data preprocessing and the ACLS-GAN deep forest model. The overall execution process of this model is as follows. Firstly, the original data set is preprocessed to ensure that it conforms to the acceptable data types of this model. Then the preprocessed data is put into the ACLS-GAN data generation model for directional expansion of the sample data. Finally, the expanded data set is subjected to feature selection and extraction, and then inputted into the deep forest for data classification, and then the classification results are. The classification results are as follows. 21.4.1 Data Preprocessing. Data Cleansing. Data cleansing is the fundamental link in data analysis and modeling, with the objective of eliminating errors, noise, and inconsistencies in data through a series of processing techniques to enhance the accuracy and reliability of data. Data normalization. Raw data distribution of inverter temperature on rotor side. Data distribution after normalization of inverter temperature on the rotor side. 21.4.2 Feature selection. Correlation coefficient method. Spearman correlation coefficient method. Spearman correlation analysis is a non-parametric statistical method that is primarily employed to assess the monotonic relationship between two variables. The primary distinction between Spearman correlation analysis and correlation analysis is that Spearman analysis does not necessitate that the data adheres to a normal distribution and is capable of addressing nonlinear relationships. Random Forest Feature Importance Assessment Method. Random Forest RF combines the two ideas of cart trees and bagging and further optimizes the model on the basis of the original. RF model is a series of decision tree. The RF model is an integrated model composed of a series of decision trees, which are independent and identically distributed random vectors. Combining Spearman correlation coefficient analysis and random forest feature importance assessment helps to overcome the limitations of the respective methods, thus improving the accuracy and reliability of feature selection. First, correlation coefficient analysis can effectively capture linear correlations and identify simple linear relationships between features and target variables. Second, Spearman correlation coefficient analysis is able to capture nonlinear and complex relationships and identify the complex effects of features on target variables. Combining the two, linear and nonlinear, relationships between features can be considered comprehensively to assess the importance of features more comprehensively. In addition, the random forest feature importance assessment method is robust to feature interactions and can better handle high-dimensional data sets and complex relationships between features. Therefore, the combination of Spearman correlation coefficient analysis and random forest feature importance assessment method can improve the comprehensiveness and robustness of feature selection and provide a more reliable basis for subsequent modeling and analysis. 21.4.3 Fault Class Data Sample Oversampling. Schematic diagram of directional expansion of fault class data samples of ACLS-GAN model. During the training process, the loss function of LSGAN is employed to optimize the performance of the generator and the discriminator. The LSGAN loss function facilitates the resolution of the pattern collapse problem in generator training, thereby enabling the generation of more stable and realistic fault data samples. In parallel, the auxiliary classifiers of ACGAN are employed to intensify the competition between the generators and discriminators, thereby enhancing the quality and diversity of the generated samples. During the training process, both the wind turbine converter fault data samples and the condition information are considered to ensure that the generator is able to generate data samples that meet the expectations based on the condition information. Through repeated iterative training, an ACLSGAN model with excellent performance can be obtained, capable of generating high-quality, diverse, and condition-compliant fault data samples. Eventually, the trained ACLSGAN model will be used to generate more eligible data samples of wind turbine converter faults, which can then be used to expand the data set in a targeted manner and improve the performance of the machine learning model. In addition, the generated data samples can be utilized for practical applications such as fault diagnosis and data analysis, thereby providing support for research and applications in related fields. 2144 Deep Forest Model. Deep Forest is a tree model based on deep learning that combines the idea of random forests and the capability of deep learning. Its objective is to address the limitations of traditional machine learning models when dealing with large-scale, high-dimensional data. The Deep Forest model was developed by Peer, al., who proposed it in 2018. It is a deep learning model for large-scale remote sensing image classification. Schematic diagram of multigranularity scanning. Schematic diagram of cascade forest. Wind turbine converter fault detection based on ACLSGAN Deep Forest. 2145 converter fault detection method based on ACLSGAN Deep Forest modeling. The ACLSGAN Deep Forest-based wind turbine converter anomaly detection system employs an innovative approach that integrates generative adversarial networks and deep forests to overcome the limitations of conventional converter anomaly detection techniques. The ACLSGAN CSSVM health assessment method, which is based on ACLSGAN, is depicted in Fig. 21.7. First, the quantitative expansion of the few classes of abnormal sample data in the data set is achieved by the ACLSGAN model, which combines the advantages of the auxiliary classification generative adversarial network and the least squares generative adversarial network. This enables the generation of higher quality synthetic data, which leads to a more balanced data set and improves the model's robustness and generalization ability. Subsequently, anomaly detection is conducted using the Deep Forest model, which integrates the strengths of deep learning and random forests. This model is adept at processing large-scale, high-dimensional data and achieving accurate classification outcomes. Deep Forest is capable of extracting the comprehensive features of an image and efficiently detecting anomalies in an imbalanced data set through two key steps: multigranularity scanning and cascaded forest. In conclusion, the ACLSGAN Deep Forest system optimally exploits the strengths of generative adversarial networks and deep forests throughout the anomaly detection process. It integrates data expansion and anomaly detection to achieve precise detection of converter anomalies. The model's ability to identify anomalous samples is enhanced by the comprehensive utilization of generated data and real data, resulting in a reduction of false alarm rates and an improvement in the accuracy and stability of the detection process. The ACLSGAN Deep Forest Wind Turbine Converter Anomaly Detection System makes full use of the advantages of generative adversarial networks and deep forests, achieving remarkable results in the field of anomaly detection. 21.5 Experimental Analysis. 21.5.1 Data Description. Variation of power characteristic parameters of converter. Doubly fed wind turbine converter failure data. Timing, rotor, speed, converter, motor speed, converter, power W, wind, speed ms, converter, generator, torque Nm, operational, state, 2021-010-116-0800.
13.5867, 1357.4, 314.399, 5.608, 26.24. Short circuit. Failure. 2021-010-116-0900. 13.621. 1357.4. 319.2. 5.764. 26.33. Short circuit. Failure. 2021-010-116-1000. 13.6038. 1365.8. 320.1. 5.563. 26.6. Short circuit. Failure. Table 21.1 shows some of the data of a wind turbine operating in January 2021, and the recorded labeled data covers a number of parameters such as operating time, rotor speed, converter power, converter motor speed, wind speed, converter generator torque, and operating status. The SCADA system can collect a large number of parameters from the wind turbine's operation, which are characterized by complex features, complicated working conditions, and complex correlations among them. If all the parameters are used as input variables of the model will be too complicated. Meanwhile, due to the interference of irrelevant variables, it will reduce the accuracy of the model, increase the training time of the model, and reduce the accuracy of fault warning. Therefore, scientifically and reasonably selecting and screening the parameters that are highly correlated with faults and excluding irrelevant variables is the key to improving the capability of fault detection models. Lack of parameters or improperly selected parameters can negatively affect the model's accuracy, training speed, and generalization ability. Wind turbine data set. Data set. Status category. Total number of features. Sample category. Data set 1, 2, 13. Normal rotor side. Converter overheat faults. Data set 2, 13. Normal rotor side. Converter overheat faults. Data set 3, 13. Normal rotor side. Converter overheat faults. Description of wind turbine data set. Data set. Total number of samples. Normal class. Samples. Exception. Class samples. Unbalance. Data set 1. 32,561. 26,720. 5841. 4.575. Data set 2. 15,000. 13,974. 1026. 13.619. Data set 3. 5960. 5171. 789. 6.553. 2152. Data preprocessing. Visualization of data distribution. Visualization of data distribution after normalization. 2153. Sample feature selection. Correlation results of each parameter with generator power. State parameter is correlation coefficient. State parameter is correlation coefficient. Rotor speed 0.8576. Yaw-yawing speed 0.0158. Converter motor speed 0.859. Yaw position 0.2119. Wind speed 1 0.9752. Converter generator torque 0.9991.
Spearman's correlation results of each parameter with generator power. State parameter, Spearman's correlation, coefficient, state parameter, Spearman's correlation, coefficient, rotor speed, 0.831, yaw-yawing speed, 0.0218, converter motor speed, 0.8481, yaw position, 0.29, wind speed 1, 0.8487, converter generator torque, 0.951. Random forest feature importance assessment results. Serial number. Key feature. 1. Rotor speed. 2. Converter motor speed. 3. Nacelle outdoor temperature. 4. Nacelle temperature. 5. Wind speed 1. 6. Average wind speed 10 S7. Gearbox temperature output shaft 2. 8. Gearbox oil temperature oil inlet. 9. Gearbox lubrication filter outlet pressure. 10. Generator bearing temperature A11. Generator bearing temperature B12. Converter generator torque. 13. Converter power. Following the completion of a Spearman correlation analysis, it is common practice to remove redundant features. This is because correlation analysis helps to understand the linear correlation between features. The removal of highly correlated features allows for the simplification of the model, thereby enhancing its interpretability. This avoids the model being affected by redundant information. Nevertheless, correlation analysis may not be sufficient to capture nonlinear relationships and complex interactions between features. Consequently, the integration of random forest feature importance analysis represents an efficacious methodology. Random forests are capable of evaluating the extent to which each feature contributes to the model's predicted results, in contrast to the limitations of linear correlations. The analysis of feature importance in random forest models allows for a more comprehensive understanding of the impact of features on the model, which in turn facilitates more accurate feature selection and model optimization, as well as improved model performance and interpretability. Data set 1 was subjected to Spearman correlation analysis in order to identify 24 features exhibiting a high degree of correlation with the target variable. Subsequently, the aforementioned features were subjected to evaluation via the random forest model, with the objective of determining the relative importance of each feature. The difference between the importance of each feature and the average importance was then compared, with those features with a higher than average importance selected. This resulted in 13 features being retained, as shown in Table 5. The aforementioned features were then combined into a new subset, which was subsequently utilized as a novel feature set for data set 1. The feature selection method based on average importance enables the selection of features that have a high impact on the target variable, thus reducing the dimensionality of the data set while retaining key information. Finally, the utilization of this constructed feature subset for subsequent model training and evaluation can enhance the efficiency and interpretability of the model. 2154 Evaluation Indicators. Confusion matrix. Sorter. True category. Positive. Negative. Forecast category. Positive. Type A. FN. Negative. FP. TN. The significance of each item can be seen according to Table 21.7. Firstly, TP indicates the case where a fault actually exists and is correctly recognized as a fault by the diagnostic system. This is a reflection of the good performance of the model and one of the goals that the system is expected to achieve. Secondly, FP represents the case where the system incorrectly judges a normal state as a fault state, i.e., a false alarm. A high false alarm rate not only leads to unnecessary maintenance costs and resource wastage, but also may affect the normal operation of WTGs. Therefore, reducing the value of FP is one of the keys to improve the system performance. Turning to FN, it indicates the situation where a fault actually exists, but the diagnostic system fails to detect it, i.e., a missed report. The level of leakage rate is directly related to the safety and stability of WTG operation. Reducing the value of FN and minimizing the occurrence of missed alarms is essential to ensure the normal operation of WTGs. Finally, TN indicates a situation where the system correctly recognizes the normal state as normal. Although the value of TN is not usually used directly as an evaluation metric, it is an important aspect that reflects the performance of the system. In summary, the four factors FP, FN, TP, and TN together constitute the confusion matrix, which provides a comprehensive and quantitative method for evaluating the performance of the wind turbine fault diagnosis system. When optimizing the system, it is necessary to pay attention to the values of these four factors and strive to reduce FP and FN and increase TP and TN so as to improve the accuracy and reliability of the system. 2155 Experimental Results and Analysis. In order to demonstrate the distinctive and superior characteristics of the ACLSGAN model design, this study conducts comprehensive comparative experiments on 3 real-world WTG data sets. The experiments compare the performance of traditional oversampling methods, including SMOTE, borderline SMOTE, and GAN-based generative models, such as ACGAN and WGANGP. To ensure the fairness and validity of the experiments, the traditional oversampling methods utilize their default parameter settings, while the GAN-based generative models uniformly set the same, including the number of layers, hidden layers, and cross layers of the GAN, in order to eliminate potential influencing factors. In the experiments, the Deep Forest classifier was selected as the evaluation tool, and the performance of each oversampling method was meticulously evaluated. At each stage, the data set was divided into a 20% test set and an 80% training set to ensure the accuracy and reliability of the evaluation. In the training phase, the oversampling methods were trained using the training set and employed to generate new synthetic samples for a limited number of class samples. Subsequently, the newly generated samples are merged with the original data set to form a balanced new data set for training the classifier. Comparison results of ACLSGAN algorithm with other oversampling algorithms under 3 real data sets. Data set. Modeling approach. Evaluation indicators %. AVE recall. FAR. MAR. 1. Deep Forest. 90.2317E04. 35.3751E03. 10.3384E04. 72.3859E03. Smote Deep Forest. 91.8143E04. 63.2654E03. 12.3413E04. 52.9222E03. Borderline Smote Deep Forest. 89.5564E04. 63.9415E03. 10.5817E04. 50.6145E03. ACGAN Deep Forest. 92.6528E04. 65.349E03. 5.5134E04. 28.1469E03. WGANGP Deep Forest. 91.556E04. 62.5823E03. 2.6448E04. 47.7554E03. ACLSGAN Deep Forest. 93.8134E04. 75.5176E03.
1.1735E04. 15.8586E03. 2. Deep Forest. 82.1867E01. 25.1787E plus 00. 14.4568E01. 24.0511E plus 00. Smote Deep Forest. 76.0119E01. 78.9114E plus 00. 10.9869E01. 25.8117E plus 00. Borderline Smote Deep Forest. 81.9311E01. 72.119E plus 00. 10.0418E01. 13.2214E plus 00. ACGIN Deep Forest. 86.2321E01. 64.6213E plus 00. 11.4812E01. 8.4414E plus 00. WGANGP Deep Forest. 74.3132E01. 79.5917E plus 00. 5.2122E01. 17.8113E plus 00. ACLSGIN Deep Forest. 90.2165E01. 80.3419E plus 00. 3.4535E01. 5.0619E plus 00. 3. Deep Forest. 98.2312E03. 62.5826E02. 1.2627E03. 1.2526E02. Smote Deep Forest. 98.3114E03. 61.2215E02. 1.0215E03. 1.7515E02. Borderline Smote Deep Forest. 98.2823E03. 70.0625E02. 1.0320E03. 115E02. ACGIN Deep Forest. 98.5313E03. 67.3419E02. 0.5111E03. 1.4721E02. WGANGP Deep Forest. 97.7615E03. 59.8616E02. 0.6218E03. 1.2817E02. ACLSGIN Deep Forest. 98.6828E03. 72.111E02. 0.3208E03. 0.6411E02. In the field of wind turbine fault diagnosis, the performance of different data sets and modeling approaches can be evaluated using a series of metrics. Following a comprehensive comparison of numerous methodologies, the ACLSGAN model has emerged as a clear standout among the multitude of competing models. The ACLSGAN model exhibits superior recall and lower miss and false alarm rates compared to other oversampling methods, offering guaranteed accuracy. Firstly, with regard to the metric of recall, ACLSGAN demonstrates high performance on all three data sets. In dataset 1, the recall of ACLSGAN Deep Forest reaches 75.51%, which is a significantly higher value than that of other methods. This indicates that the model exhibits high accuracy in identifying actual faults and is capable of effectively reducing underreporting. In dataset 2, while other methods such as SMOTE and borderline SMOTE also enhance recall, ACLSGAN continues to rank at the top with its 80.34% recall.
In dataset 3, ACLSGAN also performs well with a recall rate of 72.1%, once more demonstrating its superiority in fault identification. Secondly, the ACLSGAN also demonstrates satisfactory performance in two key metrics: false alarm rate and leakage rate. The false alarm rate is defined as the proportion of normal states that the model incorrectly judges as fault states. In contrast, the leakage rate is defined as the proportion of actual faults that are not detected by the model. In dataset 1, ACLSGAN Deep Forest exhibits a false alarm rate of only 1.17% and a leakage rate of 15.85%, both of which are lower than those observed in other methods. In dataset 2, despite the relatively high false alarm rate and leakage rate, ACLSGAN still achieves a superior performance, with a false alarm rate of 3.45% and a leakage rate of 5.06% by optimizing the algorithm and structure. In dataset 3, the false alarm and leakage rates for ACLSGAN remain at a low level, further substantiating the effectiveness of the algorithm in reducing false alarms and leakage detection. Moreover, ACLSGAN exhibits high accuracy, a comprehensive evaluation metric. In dataset 1, ACLSGAN Deep Forest achieved an accuracy rate of 93.81%, which was higher than that of the majority of other methods. In datasets 2 and 3, while the degree of improvement in accuracy may vary depending on the specific characteristics of each dataset, ACLSGAN continues to demonstrate a high level of overall performance, with excellent recall, false alarm, and miss rate performance. The experimental and statistical results demonstrate that ACLSGAN exhibits superior performance in terms of the quality and diversity of the generated samples. ACLSGAN is capable of generating samples that are more diverse and closely aligned with the true distribution by constructing the structure of the adversarial network. This renders ACLSGAN more efficacious in addressing imbalanced classification issues and can markedly enhance the recognition accuracy of minority classes. In particular, ACLSGAN demonstrates superior performance compared to other oversampling methods. This can be attributed to the following reasons. 1. The ACLSGAN model incorporates the characteristics of generative adversarial networks and least squares loss functions, thereby enhancing the model's stability in generating samples and reducing its susceptibility to pattern collapse or overfitting. This stability ensures that the generated samples are of higher quality and diversity, thus more effectively balancing the distribution of categories in the data set. 2. The introduction of additional independent auxiliary classifiers by ACLSGAN allows the model to learn more about the categories while generating samples. This facilitates the model's comprehension and differentiation of the characteristics of distinct categories, thereby enhancing the precision of classification. 3. The ACLSGAN method produces samples of a higher quality and greater diversity. In contrast to traditional data balancing techniques, such as SMOT and borderline SMOT, which primarily achieve balance by replicating or interpolating a few classes of samples, ACLSGAN employs an advanced generative adversarial network structure. Through the application of intense adversarial training between generators and discriminators, ACLSGAN is capable of generating samples that exhibit greater diversity and a closer alignment with the underlying data distribution. This innovative approach confers a significant advantage upon ACLSGAN in the resolution of imbalanced classification problems, resulting in the generation of more accurate and reliable classification outcomes. 4. ACLSGAN demonstrates efficacy in addressing complex data sets. In the context of data with complex features and high dimensionality characteristics, ACLSGAN is capable of learning more information about the categories and generating more representative samples. In contrast, SMOT and borderline SMOT may be constrained in their ability to address this type of data due to their reliance on the similarity between samples or boundary conditions as a basis for generating new samples. In summary, ACLSGAN demonstrates excellent performance in terms of the quality and diversity of generated samples, the ability to handle complex data sets, as well as stability and convergent speed. This is achieved by combining the auxiliary classifiers and the least squares loss function, as well as optimizing the network structure and the loss function. This makes ACLS-GAN an advanced and effective oversampling method with a wide range of applications in the context of unbalanced classification problems. 21.6 Summary and Outlook. In light of the intricate fault causes and sample imbalance issues encountered in the field of wind turbine converter fault detection, this chapter delves into the selection of an appropriate classification and diagnosis model to enhance detection accuracy. In practical applications, due to the significant disparity in the number of fault samples from different categories, traditional GAN models frequently encounter difficulties in generating samples that align with specific categories, which impedes the attainment of the desired performance. To address this challenge, this chapter proposes the use of ACLS-GAN to optimize the training data of deep forest models. The core of ACLS-GAN's working principle lies in the synergy of its unique generator, discriminator, and auxiliary classifiers. The generator is responsible for learning the distribution of real data and generating new samples. In contrast, the discriminator is responsible for distinguishing between generated samples and real samples, and guiding the generator to optimize its generative capability through feedback signals. The introduction of auxiliary classifiers enables ACLS-GAN to focus on the category information of the generated samples, ensuring that the generated samples are closely related to specific categories. In the training process, ACLS-GAN initially enhances the quality and diversity of the generated samples through adversarial training of the generator and the discriminator. Concurrently, the auxiliary classifiers perform category judgments on the generated samples and provide category-related feedback to the generators. This feedback mechanism enables the generator to gradually learn how to generate samples that match specific categories, thus improving the quality and usability of the generated samples. The training process of the deep forest model is significantly enhanced by the samples generated by ACLS-GAN. The generated samples serve as high-quality training data, enriching the training set of the model and enabling deep forest to better learn the intrinsic laws and patterns of the data. Consequently, the classification performance of the deep forest model was markedly enhanced in subsequent fault detection tasks, accompanied by a notable reduction in the false alarm and missed alarm rates. In conclusion, ACLS-GAN provides more accurate and reliable data support for wind turbine converter fault detection through its distinctive operational methodology. This method not only addresses the issue of imbalanced samples, but also enhances the accuracy and reliability of fault detection. In the context of practical engineering applications, the interpretability of the model is often of paramount importance, and users must be able to comprehend the rationale behind the model's judgments and prediction process. To address the aforementioned issues, the following perspectives are proposed. 1. It is possible to explore the potential of fusing data from disparate sensors to create a comprehensive multimodal data set. 2. Transfer learning techniques permit the migration of models trained in specific scenarios to new scenarios. Cross-domain knowledge sharing facilitates the integration of data from disparate regions and manufacturers, enhancing the model's generalization performance and adaptability. 3. By enhancing the interpretability of the model, it can render the judgment results of the model more convincing, thereby facilitating user comprehension and in-depth analysis of the fault detection results. This work was supported in part by the National Natural Science Foundation of China Grant No. 62,173,050, the Natural Science Foundation of Hunan Province, China Grant No. 2023 JJ30051, the Major Scientific and Technological Innovation Platform Project of Hunan Province, 2024 JC1003, the Energy Conservation and Emission Reduction Hunan University Student Innovation and Entrepreneurship Education Center, Grant No. 2019. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S, and the source, provide a link to the Creative Commons license, and indicate if you modified the licensed material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1AMMPD, coordinated control of grid-forming converters and hydro generators to enhance frequency quality of future power system. Power Raise 212 108,456, 2022. Tuhan G. Sang S. X. Impedance analysis and stabilization control of the LCL-type wind power inverter under weak grid conditions. J. Ranu. Sustain. Energy 10-3, 2018. 3 Yuan C. Jo X Ma Y Z Jo Y C. Improved application of third-order LADRC in wind power inverter. Energies 1317, 4412, 2020. 4Q P H G Peng Z Yang X. Research on the dynamic characteristics of electric field distribution of the 1100 kV ultra-high voltage converter transformer valve side bushing using weakly gas conductance model. High volt 72-288-3, 2022. 5 Sun C Ma M Z S R X. Deep transfer learning based on sparse for remaining useful life prediction of tool in manufacturing. IEIE Trans. And Inform 15-4-2416-2425, 2018. 6XHY. One-shot fault diagnosis of wind turbines based on meta-analogical momentum contrast learning. Energies 15-9-3133, 2022. 7QW Ren J. Intrusion detection algorithm based on image-enhanced convolutional neural network. J and Fuzzy 41-1-2183-2194, 2021. 8HL Wu CQ Lei Z. An effective convolutional neural network based on SMOTE and mixture model for intrusion detection in imbalanced dataset. 177-107,315, 2020. 9 YMA HT. Improvement of power transformer insulation diagnosis using oil characteristics data preprocessed by Technique. IEIE Trans. 21-5-2363-2-373, 2014. 10G F Last F. Improving imbalanced learning through a heuristic oversampling method based on k-means and SMOTE. 465-120, 2018. 11J Lay C B J L. Prediction of wind turbine blade icing fault based on selective deep ensemble model. Based 242, 108,290, 2022. 12 IJM Su B Farley D S A Y. Generative adversarial nets. Adv. Neural. Process. 27-2014. 13M. Conditional generative adversarial nets, 2014. 14111784. 14A. Unsupervised representation learning with deep convolutional generative adversarial networks, 2015. 151106434. 15J Yang Z J Q WTK Adabal GAN. An improved generative adversarial network with imbalanced learning for wafer defective pattern recognition. IEIE Trans. Manuf 32-3-310-319, 2019. 16J H L X X Jiao L. Classification of images based on spatial spectral generative adversarial networks. IEIE Trans. Remote. Senza. 57-8-5329-5343, 2019. 17K W Lay Y Lay J He G Q. Spectral learning with generative adversarial network for anomaly detection. IEIE Trans.
Remote. Senza. 58-7, 52-24-5236, 2020. 18D F Long J RV S M Lay C. Generative Adversarial Network Selection Approach for Extremely Imbalanced Fault Diagnosis of Reciprocating Machinery. IAAE Access 7, 70643 70653, 2019. 19 Li X W Ding Q. Cross-domain fault diagnosis of rolling element bearings using deep generative neural networks. IAEE Trans. And Electron. 66-7, 55-25-5534, 2018. 20 SPR. Generative Adversarial Networks for Data Augmentation in Machine Fault Diagnosis. And 106, 8593, 2019. 21 J. K. Aldura, A. S. M. Joe D. A state-of-the-art review on wind power converter fault diagnosis. Energy Rep. 853415369, 2022. 22 W. J. Lay J. HSIGAN. A conditional image synthesis method with auxiliary classifier. IIIEJ. Top. Earth OBS. Remote. Senza. 14 33 2021. 23 P of outcome measures Z scores. BMJ 345, 2012. 22. Process monitoring and fault detection in industrial processes. Abstract. This chapter introduces 3 distinct frameworks for industrial system monitoring and prediction, aiming at enhancing the performance of fault detection and diagnosis, FDD, prediction of key performance indicators, KPIs, in large-scale industrial systems and process monitoring. First, a fault detection and diagnosis framework for large-scale nonlinear industrial systems using nonlinear multivariate analysis is proposed to deal with the nonlinear variable relationships, improving the detection of minor faults and revealing fault shifts between variables and groups. Then a new approach termed VBGM-MCCA for process monitoring is introduced, which integrates the variational Bayesian mixture model, VBGMM, with canonical correlation analysis, CCA, to effectively monitor the processes. Finally, a 2-stage multi-target domain adaptation framework, TSMAN, for predicting KPIs under uncommon operating conditions is presented, which leverages knowledge from common conditions to build predictive models. These methods all demonstrate potential for practical application in their respective fields. 22.1 A fault detection and diagnosis framework for large-scale industrial systems using nonlinear multivariate analysis. In a large industrial system with many variables, the relationships between variables are often nonlinear and very complex due to the presence of material, energy, and information flows throughout the system. In such industrial systems, fault detection and diagnosis, FDD, is strongly interfered by fault-free variables and thus becomes more difficult, especially for minor faults. In order to realize high-performance FDD in large-scale nonlinear industrial systems, this section proposes a FDD framework. In this framework, the system variables are first divided into several groups, and then the FDD is realized in the form of variable groups. The whole framework consists of 3 parts: mutual information, ME-based variable grouping method, GradKPCA-based group FDD method, and GradKCCA-based intergroup FDD method. The MI-based variable grouping method obtains the optimal variable grouping by maximizing the MI of each group. The GradKPCA and GradKCCA are used to extract the nonlinear variable relationships within and between each group, respectively. In addition to the ability to handle nonlinear variable relationships, this FDD framework offers other advantages such as improved detection of glitches and the ability to reveal fault shifts between variables and groups. The performance of the proposed methods is demonstrated through a numerical example and an industrial case study. Modern industrial systems are becoming increasingly complex. Some of these systems operate under harsh conditions such as high temperatures, pressures, and speeds. Failures due to internal and external disturbances seriously threaten their safety and operational performance.
Fast and accurate FDD is an effective way to avoid performance degradation of industrial systems. Owing to the application of sensor and computer technologies, industrial systems have collected a large amount of data that can be used for FDD. This promotes the quick development of data-driven FDD methods 1, 2, 4, 5, 102. The data-driven FDD methods require only operational data from industrial systems, with little dependence on system expertise. Data-driven FDD methods generally consist of two important components: a data model that represents the intrinsic characteristics of the industrial system, and a fault detection index (FDI) that is used to distinguish fault data from normal data. The data model is usually built using multivariate analysis methods, including principal component analysis (PCA), independent component analysis (ICA), and canonical correlation analysis (CCA). The FDI is defined based on the data model to monitor abnormal changes in the statistical attributes of the data, e.g., mean and variance. The T2 statistic 6, Q statistic 7, and divergence 8 are three most commonly used FDIs. Many industrial processes operate under closed-loop control and contain a large number of variables, which are known as large-scale industrial systems. In such systems, the relationships between variables are very complex due to the presence of material flow, energy flow, and distributed control loops throughout the system. How to extract and model the complex variable relationships from the data is a key issue in realizing data-driven FDD. For completeness, all meaningful variable relationships should be taken into account to avoid missing fault alarms due to information loss. For accuracy, using some of the variable relationships is sufficient to detect and diagnose specific faults, while involving other irrelevant variables may reduce the accuracy of fault detection and increase the difficulty of fault diagnosis. Both completeness and accuracy of fault detection should be considered in a good data modeling strategy. However, in most data-driven FDD approaches, fault diagnosis uses an integrated data model that contains all variable relationships. Although this ensures the completeness of fault detection, it may reduce the accuracy of detecting incipient and minor faults. In addition to data modeling, how to construct a good FDI is another key issue in FDD for large-scale industrial systems. When the FDI contains many variables, it may suffer from the amplification and masking effects of fault-free variables 9. With these two effects, the control limits of the FDI are enlarged by the involvement of the fault-free variables, and the increase in the FDI may be partially offset by the interference of the fault-free variables. As a result, when a few variables are faulty, the FDI may not exceed the control limit, thus reducing the fault detection performance. In order to extract important features and remove redundant information from high-dimensional industrial data, dimensionality reduction methods such as PCA and CCA are widely used in FDD methods 10-12. Applying dimensionality reduction methods on system data generates a set of latent variables that are specific combinations of original system variables and represents the relationship between the system variables. Important fault information is usually carried by only a few key latent variables. A FDI defined by key latent variables has better fault detection capability because amplification and masking effects can be reduced by removing those irrelevant latent variables. However, the selection of key latent variables is very difficult because they vary with faults. To address this problem, Luo al. proposed an adaptive latent variable selection method for fault detection 13. A drawback of traditional dimensionality reduction methods is the lack of sparsity of the resulting latent variables, each of which contains all the original variables. Such latent variables are difficult to interpret and are subject to intervariable interference. To overcome these drawbacks, sparse multivariate analysis methods, e.g., sparse PCA, have been applied to FDD 14-15. Sparse latent variables only preserve important correlations between few original variables, while discard those unimportant variable correlations. Sparsity makes the latent variables much easier to interpret and more sensitive to changes in the important correlations of original variables, which is favorable for FDD. However, in order to achieve sparsity of latent variables, a part of the data information is lost, which may reduce the ability to detect some faults. It is not easy to make a trade-off between the conflicting goals of achieving representation sparsity and minimizing information loss. For large-scale industrial systems, FDD methods have also been developed through the use of modeling approaches 7-16. In these approaches, the whole system is divided into multiple blocks, each corresponding to a subsystem or functional unit. A separate model is created for each block, which is used to implement FDD within each block. After performing block partition, each block contains only a small number of variables, and variable correlations between different blocks are eliminated. This helps to minimize the amplification and masking effects caused by the fault-free variables, thus improving FDD performance. A disadvantage of the approach is that implementing block partition requires specialized knowledge about the industrial system. When the connections between different units or subsystems are complex, it is difficult to obtain suitable block partition results. Recently, a FDD approach has been developed to overcome the drawbacks of the approach 17. In this approach, the variables of an industrial system are grouped into several groups by means of a data-driven variable grouping algorithm without using any specialized knowledge about the industrial system. In addition, the correlation of variables within each group and between different groups is simultaneously used for FDD, thus avoiding information loss and ensuring good FDD performance. Despite these advantages, this FDD approach can only measure and model linear relationships between variables, but cannot reveal nonlinear multivariate relationships. This drawback makes it inapplicable to nonlinear systems. Several fault detection methods have been developed to address the nonlinear nature of industrial systems 1820. Most of them use kernel-based multivariate analysis methods to build data models 21-22, such as kernel PCA and kernel CCA. In these methods, the raw data are implicitly mapped via kernel functions into a kernel-induced feature space, where the mapped data are modeled by linear methods. Traditional kernel-based multivariate analysis methods need to solve an optimization problem containing a high-dimensional kernel matrix that represents nonlinear data features. The computational complexity of the kernel matrix is high and proportional to the cube of the number of samples. Due to this drawback, traditional kernel-based methods are not applicable to large-scale data sets. In addition, the relationship between the original variables and data features in the kernel-induced space is not clear, which increases the difficulty of implementing fault diagnosis. In addition to kernel methods, deep learning methods have also been applied to develop fault detection methods for nonlinear systems 23-27. Owing to the use of multi-layer neural networks, deep learning methods are more powerful than kernel methods in extracting nonlinear features from data. However, they also have two drawbacks. First, building and updating deep neural networks is time-consuming, which is not conducive to real-time fault detection. Second, it is difficult for neural networks to recognize the relationship between input variables and extracted nonlinear features, increasing the difficulty of fault diagnosis. To improve the computational efficiency, some new nonlinear extensions to PCA and CCA have been proposed, such as GradK-CCA 28, Randomized Nonlinear CCA RNCCA 29, and Randomized Nonlinear PCA RNPCA 29. The GradK-CCA is a variant of KCCA, which has an additional constraint that each projection direction in the kernel feature space has a preimage in the original data space 28. The RNCCA and RNPCA perform linear CCA and PCA on a stochastic nonlinear mapping of data 29. Due to the high computational efficiency, these nonlinear methods are applicable to large-scale data sets. They have great potential for use in large-scale nonlinear industrial systems for FDD. However, this research topic received little attention. To address the above problems, a new FDD framework for large-scale nonlinear industrial systems is proposed in this paper. In this FDD framework, the system variables are first divided into several groups, and then the FDD is realized in the form of variable groups. This FDD framework consists of three parts: a variable grouping method based on mutual information, an intergroup FDD method based on nonlinear CCA, and a group FDD method based on nonlinear PCA. This framework has some advantages, including the ability to handle nonlinear variable relationships, the ability to reveal fault shifts between variables and groups, and the improved detection ability to small faults. These advantages are illustrated through a numerical example and an industrial case study. This section has three main contributions as follows. 1. Two nonlinear multivariate analysis methods, GradKPCA and GradKCCA, are developed for modeling nonlinear relationships among variables. Similar to the traditional KPCA and KCCA, GradKPCA and GradKCCA discover nonlinear variable relationships through kernel functions. However, they require the projection vectors in the kernel feature space to have a pre-image in the original data space, thus avoiding the use of kernel matrices. This modification greatly reduces the computational complexity, making GradKPCA and GradKCCA applicable to large-scale data sets. 2. A variable grouping method is proposed to group the variables of an industrial system. This method uses mutual information, MI, to measure multivariate dependence and produces optimal variable groups by maximizing the MI of each group of variables. 3. Based on GradKCCA and GradKPCA, the intergroup and group FDD methods are proposed. The group FDD mainly focuses on faults that destroy the relationships of variables within groups, while the intergroup FDD focuses on faults that destroy the variable relationships between groups. They form a FDD framework for large-scale industrial systems. 22.1.1 Nonlinear multivariate analysis methods. Nonlinear CCA. Nonlinear PCA. 22.1.2 Fault detection and diagnosis framework. Variable grouping based on mutual information. 1. Estimating mutual information of variables. A MI-based method is developed for grouping variables into non-overlapping groups based on the dependencies between variables. This method includes the following three main steps. Step I. Determine the center of a new group. For ungrouped variables x1, x2, computing the MI of M1 variables excluding the variable, denoted as 1xi I12, and then selecting the variable that minimizes 1xi as the center of a new group. Step II. Initialize the new group. Computing the MI of every variable in the set X with the central variable x, denoted as I2 xx, and then finding out the variable x that has the largest MI value, i.e. I2xx max x I2, x initializing the variable group as VGXX. Step III. Enlarge the new group. Computing the increase in the MI of the variable group when a new variable is added to the VG group. If the maximum MI increase is greater than 0, adding the variable with the largest MI increase to the VG group. Repeating this step for the remaining variables until no new variables are added to the VG group. Additional variable groups can be obtained by repeating the above three steps for the remaining ungrouped variables. The variable grouping process stops if the desired number of groups is reached, or if the number of remaining ungrouped variables is less than 2. Group FDD based on GradKPCA. Intergroup FDD based on GradKCCA. FDD procedure. The FDD procedure of industrial systems is shown in Fig. 22.1. The whole procedure consists of two phases: offline analysis of reference data and online FDD of new samples. Each phase contains the following steps. Stage I. Offline analysis of reference data. Step I1. Normalize the reference data to 0 mean and unit variance. Step I2. Divide variables into J groups by applying the variable grouping method on reference data. Step I3. Compute projection matrices W, U, and V by performing GradKPCA and GradKCCA on reference data of variable groups. Step I4. Compute 2, J2, Ci1j, and ij of all reference samples in every group. Step I5. Compute confidence limits Tj2, Trj2, Ci1j, and Crij using KDA. Stage II. Online FDD of new samples.
Step II1, normalize the new sample. Step II2, a group FID, compute 2 of in each group. Mark as normal if 2TJ2 in all groups. Otherwise mark as faulty, and then compute variable contributions CI1J to identify faulty variables. Step II2B, intergroup FDD, compute J2 of in each group. Mark as normal if J2TR J2 in all groups. Otherwise mark as faulty, and then compute variable contributions, IJ, to identify faulty variables. FDD procedure of industrial systems. 2213 case studies. A numerical example. Fault 1, the mean of x3 and x7 increases to 2, x5 x1 plus x2 plus x33 x42 plus 1, and x10 x7 plus x93 plus 2. Fault 2, the mean of x3 and x7 increases to 2, x5 x1 plus x2 plus x33 x42 plus 1, and x10 x7 plus x92 plus 33 and 2005. Fault 3, the mean of x3 and x7 increases to 2, x5 1 plus x2 plus x3 x42 plus 1, and x10 x7 plus x93 plus 2. Fault 4, the mean of variables x3 and x7 increases to 2, x5 x1 plus x2 plus x3 plus 22 x42 plus 1, and x10 7 plus x9 plus 2. MI of variables in a VG1 and BVG2 after adding a new variable into the group. Faulty samples in each fault dataset are detected by the FDD method. The nonlinear method based on grad KPCA plus grad KCCA is compared with the kernel method based on KPCA plus KCCA and the linear method based on PCA plus CCA. The grad KPCA, KPCA, grad KCCA, and KCCA use the polynomial kernel Kx, Yx plus R'd with D2 and R0. The matrices W, U, and V consist of the first two projection vectors. The performance of fault detection is evaluated using two indicators: the false alarm rate FAR, which is the percentage of normal samples that are detected as faulty, and faulty sample detection rate FSDR, which is the percentage of faulty samples that are detected as faulty. FAR percent and FSDR percent of three methods for 4 fault datasets. Fault variable group nonlinear method, linear method, kernel method, grad KPCA, grad KCCA, PCA, CCA, KPCA, KCCA, FAR, FSDR, FAR, FSDR, FAR, FSDR, FAR, FSDR, FAR, FSDR, FAR, FSDR, 1, VG1, 0.3, 28, 1.7, 83, 0.3, 6.7, 1.7, 86.6, 0.3, 25.1, 1, 26.3, VJ2, 0.7, 38, 0.3, 37, 0.7, 8.6, 0.3, 34.4, 0.7, 35.4, 0.3, 27.6, 2, VG1, 3, 27.9, 0.7, 88.3, 1, 9.9, 0.7, 88, 3, 25.6, 2.7, 27, VJ2, 0.3, 15.3, 1.3, 45.9, 0.3, 8.3, 0.7, 40, 0, 10.4, 0, 16, 3, VG1, 1, 20.6, 2.7, 86.9, 1.3, 10.9, 2.7, 84.7, 1, 19.1, 1.7, 18.7, VJ2, 0, 37.9, 2.7, 53.3, 1.7, 19.1, 1.7, 47.9, 0.6, 34, 0.3, 32.3, 4, VG1, 1, 15.9, 1, 89.4, 0.3, 2.4, 1, 90.4, 1, 13.1, 1, 8.9, VJ2, 1.3, 31.6, 1, 37.9, 0.7, 2.3, 1.3, 40, 1, 29.3, 1, 28.4. An industrial case study. 1. Process description. FDD procedure of industrial systems. Simulation data are obtained from the V-process model. A total of 45 variables are measured, including 22 manipulated variables and 23 process variables, as shown in Table 22.2. The reference dataset contains 2,700 normal samples that are collected in normal operating conditions. The 10 disturbances shown in Table 22.3 are introduced in the V process to produce fault datasets. Each fault dataset has 200 samples, and a disturbance is introduced at the 100th sample. The disturbances 5, 6, and 8, 10 are continuous disturbances that last from the 101st sample to the 200th sample. The other disturbances are intermittent disturbances that last for only a few samples. 2. Variable grouping results. Variables of the V process. No. Process variable. Units. No. Manipulated variable. Units. V1. Vaporizer pressure. V24. Fresh O2 feed. Min. V2. Vaporizer level. V25. Fresh C2H4 feed. Min. V3. Vaporizer temp. CV26. Fresh H feed. Min. V4. Heater exit temp. CV27. Vaporizer steam duty. Kcal min. V5. Reactor exit temp. CV28. Vaporizer vapor exit flow. Min. V6. Reactor exit flow rate. Min. V29. Vaporizer heater duty. Kcal min. V7. FEHE cold exit temp. CV30. Reactor shell temp. CV8. FEHE hot exit temp. CV31. Separator liquid exit flow. Min. V9. Separator level. V32. Separator jacket temp. CV10. Separator temp. CV33. Compressor heater duty. Kcal min. V11. Compressor exit temp. CV34. Absorber liquid exit flow. Min V12. Absorber pressure. V35. Circulation cooler duty. K cal min. V13. Absorber level. V36. Scrub cooler duty. K cal min. V14. Circulation cooler exit temp. CV37. CO2 removal inlet flow. Min. V15. Scrub cooler exit temp. CV38. Purge. Min. V16. Gas recycle flow rate. Min. V39. FEHE bypass ratio. V17. Organic product flow rates. Min. V40. Column reflux. Min. V18. Decanter level organic. V41. Column reboiler duty. K cal min. V19. Decanter level aqueous. V42. Column condenser duty. K cal min. V20. Decanter temp. Say V43. Column organic exit flow. Min. V21. Column bottom level. V44. Column aqueous exit flow. Min. V22. Fifth tray temp. CV45. Column bottom exit flow. Min. V23. H tank level. Fault data sets of the V process. No. Variable. Disturbance. Start time. End time. 1. V2. Step change to 0.73. 101st min. 103rd mins. 2. V10. Plus 1 C per 13 S101 min. 150th min. 3. V20. Plus 0.5 C per 13 S101 min. 110th min. 4. V28. Plus 0.3 per 13 S101 min. 150th min. 5. V3. Ramp decrease from 119 C to 116 C101 min. 200th min. 6. V13. Step change to 0.45 and then ramp increase to 0.5. 101st min. 200th min. 7. V24. Random change between 0 and 1. 101st min. 130th min. 8. V40. Random change between 4.8 and 5.1. 101st min. 200th min. 9. V25 V29. Random change between 0.6 and 1 V25, and ramp increase from 9100 to 10,300 V29. 101st min. 200th min. 10. V28 V38. Plus 0.3 per 13 S V28, and step change to 0.0035 V38. 101st min. 200th min. Variable groups of the V process. Group. Variable. Group. Variable. VG1. V37, V38, V40. VJ2. V17, V19, V21, V23, V25, V26, V30, V32, V35, V36, V43, V45. VJ3. V1, V6, V24, V28. VG4. V13, V20, V21, V33, V34, V41, V42. VG5.
V2, V5, V7, V12, V14, V16, V22, V27, V29, V39. 3. Fault detection results. Faulty samples and fault datasets are detected using the FDD method. The nonlinear method based on grad KPCA plus grad KCCA is compared with the kernel method based on KPCA plus KCCA and the linear method based on PCA plus CCA. The grad KPCA, KPCA, grad KCCA, and KCCA use the polynomial kernel Kx, Yx2. In each variable group, the number of projection vectors in the matrices W, U, and V is equal to the variable number. The traditional PCA-based method that does not group variables is also used for comparison. A combination of T2 and SBE statistics is used in the PCA-based method to detect faults 44. The T2 statistic is defined using the first 35 principal components, PCs, that correspond to the largest eigenvalues, while the remaining 10 PCs are used to define the SBE statistic. FAR% and FSDR% of 4 methods for 10 fault datasets. Fault nonlinear method, linear method, kernel method, PCA method, grad KPCA plus grad KCCA, PCA plus CCA, KPCA plus KCCA, TTT, FAR, FSDR, group, FAR, FSDR, group, FAR, FSDR, group, FAR, FSDR, 1, 2, 86, VG1, 1, 80, VG1, 0, 60, VG1, 0, 67, 2, 2, 85, VG1, 1, 76, VG1, 5, 65, VG2, 2, 67, 3, 2, 36, VG1, 5, 34, VG1, 0, 30, VG1, 3, 18, 4, 3, 81, VG1, 3, 84, VG1, 0, 60, VG1, 1, 68, 5, 3, 97, VG5, 3, 97, VG5, 2, 96, VG5, 3, 94, 6, 3, 100, VG4, 7, 100, VG4, 4, 100, VG4, 1, 100, 7, 4, 100, VG2, 2, 100, VG2, 7, 86, VG2, 2, 100, 8, 3, 100, VG1, 2, 100, VG1, 0, 100, VG1, 2, 100, 9, 2, 100, 3, 100, 2, 100, 1, 100, 10, 0, 100, VG1, 1, 100, VG1, 0, 100, VG1, 2, 100, FSDR percent of 5 groups of the nonlinear method for 10 fault datasets. Fault VG1, VG2, VG3, VG4, VG5, inter, 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 1, 60, 75, 68, 60, 6, 40, 20, 33, 34, 42, 2, 59, 74, 67, 57, 4, 17, 30, 24, 17, 62, 3, 30, 36, 12, 3, 1, 3, 3, 2, 0, 4, 4, 79, 22, 34, 19, 6, 8, 0, 11, 11, 11, 5, 0, 31, 2, 18, 1, 54, 2, 97, 97, 87, 6, 77, 100, 99, 100, 45, 100, 100, 100, 99, 100, 7, 79, 97, 91, 99, 47, 91, 24, 68, 64, 85, 8, 100, 100, 97, 90, 0, 91, 3, 70, 0, 97, 9, 89, 100, 100, 100, 91, 100, 28, 100, 100, 100, 10, 100, 100, 26, 100, 5, 100, 1, 100, 3, 100. Group monitoring charts for the fault dataset 4. A VG1, BVG2, CVG3, DVG4, and EVG5. Variable contributions in VG3 at the 101st sample of fault 4. Values of the variable V28 in the fault dataset 4. 4. Fault diagnosis results. Faulty variables are identified using the contribution-based fault diagnosis method. For example, the fault 4 is firstly detected at the 101st sample by the group T2 statistic of the group VG3, as shown in Fig. 22.4. Variable contributions in the group VG3 to the T2 value of the 101st sample are calculated. Figure 22.5 shows the contribution plot. The variable V28 contributes much more than the other 3 variables, and the contribution of V28 exceeds the corresponding confidence limit. Therefore, the variable V28 is the faulty variable causing fault 4. This diagnostic result agrees with the actual cause of the fault 4, which is a disturbance in V28, see Table 22.3. Figure 22.6 shows the values of V28 in the fault dataset 4. It is clear that the variable V28 deviates from normal values between the 101st and 150th samples. Variable contributions at the 101st sample in a VG2 and BVG5 for fault 9. Values of a V25 and BV29 in the fault dataset 9. Identified faulty variables for 10 faults. Fault sample group fault sample group 1 101st VG5 Vi2 Vi2 6 101st VG4 Vi13 Vi13 2 101st VG5 Vi10 Vi10 7 101st VG3 Vi24 Vi24 3 101st VG4 Vi20 Vi20 8 101st VG1 V40 V40 4 101st VG3 Vi28 Vi28 9 101st VG2 VG5 V25 V16 V29 V25 V29 5 103rd VG5 Vi3 Vi3 10 101st VG1 VG3 V38 V28 V28 V38 AIFV Identified Faulty Variable AFV Actual Faulty Variable. This section proposes a FDD framework for large-scale nonlinear industrial systems. This FDD framework divides the system variables into groups firstly, and then implements FDD in the form of variable groups. The framework contains 3 parts: an MI-based variable grouping method, a grad KPCA-based group FDD method, and a grad KCCA-based intergroup FDD method. This FDD framework has 3 main advantages. First, it can deal with nonlinear variable relationships, because the MI, grad KPCA, and grad KCCA have the ability to measure and extract nonlinear variable relationships. In particular, grad KPCA and grad KCCA have much less computational complexity compared to KPCA and KCCA, making them applicable to large-scale datasets. Second, it improves the ability to detect minor faults, because the variable grouping reduces the interference of fault-free variables on faulty variables. Thirdly, the variable relationships within each group and between different groups are used simultaneously in FDD, which improves fault detection performance and can reveal fault transfer between variables and groups. These advantages are illustrated by a numerical example and an industrial case study. 22.2 Process monitoring using variational Bayesian inference and canonical correlation analysis. Industrial processes often operate under various modes, making fault detection a critical task. This section introduces a new approach termed VBGMM-CCA, which integrates the variational Bayesian mixture model, VBGMM, with canonical correlation analysis, CCA, for effective monitoring of multimodal processes. By combining VBGMM's ability to automatically identify operational modes with CCA's robust local fault detection capabilities, this method offers a comprehensive monitoring solution. Initially, VBGMM is used to analyze unlabeled historical process data, determining the number of operational modes and clustering the data accordingly. Subsequently, local CCA models are developed to examine the relationships between input and output variables. Fault detection residuals are produced within each local CCA model, and monitoring statistics are derived. Finally, a Bayesian inference-based probabilistic index is utilized to combine the monitoring results from all local models, thereby enhancing the overall robustness of the monitoring system. The proposed scheme's effectiveness is demonstrated through numerical examples and experimental studies on a multi-phase fed-batch penicillin fermentation process. Monitoring industrial processes is essential for ensuring safety and improving product quality. These processes often produce vast amounts of unlabeled data across various operational modes, making data labeling both difficult and costly. To tackle this issue, this study proposes the VBGMMCCA method for effectively monitoring multimodal processes. The key advantage of this method is its capability to automatically discern the number of operational modes from historical data and subsequently cluster the data. Following this, local CCA monitors are created to model the relationships between process inputs and outputs. During the real-time monitoring phase, the active operational mode is determined by employing a probabilistic density function, and the condition of the process is assessed using the corresponding CCA-based monitoring system. Additionally, a probabilistic monitoring metric is established to bolster the system's reliability. Compared to traditional methods, this approach offers more reliable and informative monitoring results, as it not only assesses the process status but also identifies the nature of any detected faults. In the realm of long-term operations, process monitoring is essential and is drawing increased attention 3437. Modern industrial processes can be highly intricate, and the corresponding mathematical process models might not always be accessible. However, there is a wealth of process data rich with valuable information 1:38:39. Data-driven methods have gained prominence, with multivariate statistical process monitoring (MSPM) techniques being particularly widespread 4043. Fundamental MSPM methods include principal component analysis (PCA), partial least squares (PLS), and canonical correlation analysis (CCA). PCA is utilized to extract key variance information from process data and is often used to address collinearity issues 4446. PLS is primarily employed for monitoring processes related to quality or key performance indicators 4748. Reference 52 describes a MATLAB toolbox that includes a range of PLS extensions. CCA, a powerful multivariate analysis method that examines the relationships between two sets of random variables, has garnered increasing interest in recent years 4952. CCA is typically employed for process monitoring through two main approaches. The first approach utilizes CCA for feature extraction and dimensionality reduction, followed by analyzing these features to determine the process status 5456. The alternative method employs CCA to establish correlations between pairs of process variable sets, which is then used to generate residuals for fault detection. In 49, CCA was applied to map process inputs and outputs, encompassing manipulated and measured variables, to create fault detection indicators. In 51, CCA was applied to evaluate correlations between different operational units in distributed monitoring, demonstrating the method's efficacy. A neighborhood modeling strategy addressed the issue of missing data in distributed monitoring 57. Similarly, CCA was used for monitoring non-processes 58 and batch processes 52. A mixture CCA method was developed for monitoring quality-related aspects 59. Recently, a monitoring scheme combining deep belief neural networks with CCA, known as Deep Correlated Representation Learning, was proposed for nonlinear process monitoring 60. Despite the successes of these CCA applications, current CCA-based monitoring methods are limited to single operational modes. Currently, due to varying market demands, different reaction phases, and changes in the production environment, processes typically operate in multiple modes 61-63. Monitoring such processes is crucial, and various monitoring strategies have been proposed to address this need 64-65. A significant hurdle in this field is pinpointing the quantity of operational modes within historical datasets and ascertaining the current mode of a real-time data point. Numerous clustering algorithms, including K-means 66 and mixture model GMM 67, have been implemented to tackle this issue. However, conventional approaches frequently necessitate predetermined cluster counts, which may be challenging to estimate in practical scenarios. The finite GMM has been proposed for process monitoring to automatically ascertain the number of operational modes 68-69. In 68, the Jane FJ algorithm was introduced, which determine the number of components using the minimum message length criterion. Using the FJGMM as a foundation, a probabilistic monitoring framework was subsequently developed in '69. More recently, an efficient, unsupervised GMM learning algorithm that employed variational methods to identify the number of components has gained attention 70. This approach, known as variational Bayesian inference, treated mode parameters and latent variables as hidden variables 70. The variational Bayesian GMM (VBGMM) considers the number of clusters as an adjustable parameter during the expectation maximization M iteration 70-71. VBGMM not only automatically determines the number of clusters, but also addresses the mode identification problem effectively. In this research, an approach that integrates variational Bayesian mixture models, VBGMM, with CCA, termed VBGMM-CCA, is proposed for effective fault detection within processes exhibiting multiple modes. This approach leverages the automatic mode identification capability of VBGMM and the superior correlation characterization of CCA. The key contributions of this study are as follows. First, proposing the application of several localized linear models to encapsulate the overall multi-phase process dynamics, thus enhancing the capability of CCA-based monitoring to handle intricate process behaviors. Second, utilizing variational Bayesian inference to automatically determine the number of necessary local linear models for historical process data, effectively eliminating outlier influence. Third, developing a Bayesian inference probability (BIP) index that combines results from different models, enhancing the robustness of CCA-based monitoring. 22.2.1 Preliminaries and Motivation. This section outlines the notations used throughout the study. K represents the number of components, while N stands for the number of observations. Variables A and B denote the number of variables. The process input and output are indicated by U raw and Y, respectively, with XUTTM plus B, representing a combined measurement of input and output. The mixing coefficient is, the precision matrix is, and includes parameters such as mean and covariance, and the normal distribution density function is N. X refers to observed variables, while Z denotes hidden variables. Canonical correlation vectors are represented by J and L. The residual vector is R, and rank A is the rank of matrix A, is the identity matrix with the columns, and E denotes the expectation. The probability of event A is prob A. The process noise vector is, the significance level is, the degrees of freedom are, and the scale matrix in the VBGMM algorithm is V. Standard conventions apply to other notations. VBGMM. CCA. Problem formulation. Illustration of process data. 22.2.2 VBGMM-CCA process monitoring. VBGMM-CCA monitoring procedures. Procedures of VBGMM-CCA monitoring scheme. Step 1. Historical operation mode identification. VBGMM is utilized to analyze the historical process data. Initially, a relatively large number of operational modes is, and VBGMM automatically determines the actual number of modes. Each sample is then assigned to its corresponding mode. It should be highlighted that certain detected modes might consist of a limited number of data points, potentially due to significant errors or outliers. Such modes do not accurately reflect actual operational states within the process's historical context. As a result, these irregular modes, along with their corresponding data points, should be disregarded from the recognized modes to streamline real-time computational processes. Step 2. Local CCA model establishment. After collecting samples for each operational mode, a local CCA monitoring model is developed for each mode. To establish the CCA monitoring model for samples within a single operational mode, the following steps are carried out. First, the dataset undergoes a standardization process to adjust for mean and variance. Second, the dataset is categorized into two groups, the input variables, labeled U, and the output variables, labeled Y. Next, a CCA is conducted on U and Y to identify the local canonical correlation vectors, denoted as J and L5, the thresholds are established. The process is iterated until CCA models are successfully developed for every operational scenario. Step 3. Online Operation Model Identification. Step 4. Process Status Identification. Characteristic Analysis. Characteristic 1. Feasibility Analysis. The proposed VBGM-MCCA method autonomously determines the number of local linear models needed to describe the entire process. By excluding samples with the lowest probability, the impact of outliers can be mitigated. Within each local model, an optimal fault detection residual is produced, enhancing the effectiveness of local fault detection monitoring. Characteristic 2. Computational Burden Analysis. The suggested monitoring approach boasts high computational efficiency. Unlike traditional GMM methods, the VBGMM algorithm treats the number of required models as an parameter, significantly enhancing efficiency. Characteristic 3. Advantage in local fault detection. The strength of the VBGM-MCCA approach is its ability to use CCA for identifying local faults that impact either the process input or output specifically. Rather than relying on a single overall statistic, it offers detailed information about the nature of the detected fault 51. Characteristic 4. Monitoring robustness. The VBGM-MCCA technique amalgamates the results from various local models into a single BIP index. By utilizing a probabilistic monitoring framework, this method mitigates the effects of erroneous mode recognition, thus bolstering the reliability of the monitoring system 69. Significantly, the VBGM-MCCA constructs monitoring models based on historical process data. In real-world applications, the process might be non-stationary due to changing operational conditions over time, meaning it does not stay fixed at a steady model. If these varying conditions are not accounted for in the process history, VBGM-MCCA might misinterpret them as faults. In such cases, a comprehensive condition analysis is valuable for understanding the process behavior 74. 22.2.3 Experimental Studies. Numerical example. Under normal operational conditions, 200 data points of per operational mode are produced for training. These data points are unlabeled and pooled together. Figure 22.11 illustrates the mode detection outcomes utilizing VBGMM, which identifies 4 separate modes. However, the third mode, which contains a minimal number of detected points due to substantial errors, is not recognized as a genuine mode. Modes that constitute less than 2% of the overall data are excluded. Following this, a CCA-based monitoring model is developed for each valid mode. Finally, a test dataset is assembled to assess the monitoring system's effectiveness. The process operates in the first mode from the first to the 100th point, with a ramp change of 0.05 t50 applied to U1 between the first and the 100th point, where t represents the time instant. Starting at the 101st point and ending at the 200th, the system transitions into its second operational state, preceded by a 4.5 unit step increase in the variable U2 between the first and 100th points. Then, from the 201st to the 300th point, the system operates in its third state, during which a 4.5 unit step increase in the variable Y3 is implemented between the 251st and 300th points. Figure 22.12 illustrates the mode identification results, confirming that the operation mode has been successfully identified. Historical data mode identification result. Monitoring results for the numerical example. Online monitoring mode identification result, BVBGM-MCCA, CVBGM-MCCA with BIP, DVBGM-MCCA, EVBGM-MT2, and FFJ-GMM with BIP index. Monte Carlo test results of different methods. A Monte Carlo simulation is conducted 1,000 times to evaluate the performance. The mean normalized deviation ratios, NDRs, for VBGM-MCCA with deterministic mode identification, referred to as DCCA, VBGM-MCCA with BIP, referred to as PCCA, VBGMM, VBGM-MCCA, and the GMM from 69 are depicted in Fig. 22.13. The VBGMM with BIP indices exhibits superior monitoring performance with the lowest NDR. When it comes to model complexity, a comparison is made between the FJGMM and VBGMM. The FJGMM requires about 1.69 S per operation, while the VBGMM only needs around 0.17 S, making the VBGMM more computationally efficient in this study. Batch-fed penicillin fermentation process. BPFP serves as a standard benchmark problem extensively utilized to evaluate the effectiveness of monitoring schemes 7577. Characterized by its pronounced nonlinear behavior and multi-stage nature, this process can be divided into three main stages: microbial growth, antibiotic production, and cellular degradation. Throughout the fermentation cycle, various parameters such as temperature, pH level, substrate density, and oxygen saturation levels play a critical role in the yield of penicillin. Despite the importance of monitoring BPFP, it remains a complex task fraught with challenges. Appendix Figure A1 shows the simulation toolkit produces process data, incorporating 16 variables as outlined in Table A175. The duration of each batch is 400 H. Initial settings and target values are provided in Table A2. With a data collection frequency of once per hour, a total of 400 data points are recorded per batch. A total of 100 batches are simulated under standard operational conditions, and the collected process data are utilized for training the model. Figure 2214 presents the historical mode detection outcomes based on VBGMM. The process data are categorized into 7 unique modes, indicating that 7 components are required to precisely represent the historical process conditions. Despite there being only 3 primary phases in a batch run, multiple modes may be required to represent each phase due to significant nonlinearity within the phases. For assessing the monitoring system's efficacy, a batch under standard operating conditions and 3 batches with distinct faults were simulated. The faults are characterized as follows. Fault 1 involves a stepwise alteration in the agitator power between the 150th and 300th data points. Fault 2 features a gradual change in the agitator power over the same range. Fault 3 consists of a gradual change in the aeration rate from the 150th to the 300th data point. Mode identification results of BPFP historical data. Monitoring results for BPFP normal batch. Online mode identification results BVBGMMCCA, CVBGMMCCA with BIP, and D conventional GMM. Monitoring results for BPFP fault 1. Online mode identification results BVBGMMCCA, CVBGMMCCA with BIP, and D conventional GMM. Monitoring results for BPFP fault 2. Online mode identification results BVBGMMCCA, CVBGMMCCA with BIP, and D conventional GMM. Monitoring results for BPFP fault 3. Online mode identification results BVBGMMCCA, CVBGMMCCA with BIP, and D conventional GMM. This study introduces a fault detection method for process monitoring based on VBGMMCCA. The core concept leverages VBGMM's capability for automatic mode identification and CCA's strength in modeling local operation modes. Initially, VBGMM determines the number of operation modes from historical process data. Following this, the data are grouped into clusters, and a localized CCA-based fault detection model is established. Subsequently, fault detection residuals are determined, and monitoring metrics are formulated. To enhance monitoring robustness, a BIP index is introduced. The efficacy of the suggested monitoring framework is validated through practical applications, including a numerical simulation and a multi-stage BPFP scenario. The proposed VBGMMCCA method excels in 3 key areas. Firstly, it can automatically identify the number of operation modes, a crucial feature for practical applications. Secondly, the CCA-based local monitoring effectively determines the process status and characterizes detected faults. In conclusion, the monitoring approach functions on a probabilistic basis, which strengthens the reliability of the monitoring procedure. 22.3, a two-stage multi-target domain adaptation framework for prediction of key performance indicators based on adversarial network. In treatment processes, the construction of performance evaluation models to predict key indicators under uncommon operating conditions is challenging due to the lack of labeled data. Domain adaptation can address this issue by leveraging knowledge from common conditions to build predictive models for uncommon ones. Given the costs associated with data labeling, it is reasonable to assume that only data from the most prevalent condition are labeled. Hence, all domain adaptation tasks share a single source domain. Under this assumption, most domain adaptation methods necessitate multiple mappings of the same source data and training several task-specific predictors across different tasks, leading to additional computational expenses. To counteract this, a stepwise domain alignment strategy is proposed, comprising two steps. Firstly, the latent features of the source domain are extracted and fixed subsequent to this step. Secondly, target domains from various tasks are mapped to this established feature space to achieve domain alignment. Following this strategy, a two-stage multi-target adversarial adaptation network, TSMAN, is introduced for forecasting the effluent quality index, comprised of and coupled with a generative adversarial network. Furthermore, techniques such as parameter initialization and multi-kernel maximum mean discrepancy optimization are suggested to enhance the stability and predictive accuracy of the TSMAN respectively. Experiments conducted on datasets generated by the benchmark simulation model No1 demonstrate that the TSMAN not only exhibits exceptional prediction precision and robustness, but also enables efficient multi-target domain adaptation. Additionally, these experiments validate the efficacy of both parameter initialization and MKMMD optimization. Effective treatment can aid in alleviating water scarcity and achieving efficient water reuse. However, the ASM commonly employed in treatment plants 104 frequently experiences fault conditions, which can result in economic losses for the plants. Effluent Quality Index, EQI 88, 118, 119, is a standard evaluation criterion used in treatment processes WWTP. It incorporates measurements of total suspended solids TSS, chemical oxygen demand COD, biochemical oxygen demand BOD, total nitrogen TKN, and nitrate nitrogen NO to reflect the quality of the effluent 118. Predicting the EQI can assist decision makers in assessing the effectiveness of the treatment and making timely adjustments to prevent abnormal operating conditions, which is of significant importance 84-86. Given the abundance of data that can be collected from the actual WWTP, data-driven methods are viable for constructing predictive models for the EQI. However, the instability of the ASM leads to a variety of operating conditions, and models built under common operating conditions often fail to produce acceptable results under uncommon conditions due to differences in data distribution 1 of 5. Moreover, constructing specific predictive models for each operating condition is impractical, as labeling all data for all operating conditions would be extremely time-consuming. Domain adaptation can address this issue by leveraging knowledge from common conditions to build predictive models for uncommon ones. With common operating conditions as the source domain and uncommon conditions as the target domain, EQI prediction under different uncommon conditions can be defined as multiple domain adaptation tasks. The advantage of this approach is that only the data from the source domain needs to be labeled. Furthermore, considering the time and labor costs associated with data labeling in actual treatment plants, it is reasonable to assume that only data from the most common operating conditions are labeled, while data from other relatively uncommon conditions remain unlabeled. Thus, EQI predictions under different uncommon conditions can further be defined as an unsupervised multi-target domain adaptation task, where all domain adaptation tasks share the same source domain. Domain alignment strategies. The conventional strategy for multi-target domain adaptation tasks be the proposed stepwise strategy for multi-target domain adaptation tasks. Under the assumption of the aforementioned WWTP, suppose there exists one most common operating condition, the source domain, and n uncommon operating conditions, the target domains. As shown in Fig. 22.19, for n-target domains, traditional domain adaptation methods require mapping the source domain n times and training n task-specific EQI predictors. Despite all domain adaptation tasks sharing the same source domain, this results in additional computational costs. This implies that traditional domain alignment strategies have limited practicality in WWTPs. To address this issue, a progressive domain alignment strategy is proposed, which divides the traditional domain alignment process into two steps. As illustrated in Fig. 22.19b, in the first step, latent features of the source domain are extracted and then fixed. In the second step, the target domains are mapped to the fixed feature space of the source domain to reduce the differences between domains. For n-target domains, the progressive strategy only requires mapping the source domain once and training a single general EQI predictor, which is the key difference between the proposed strategy and widely adopted domain alignment strategy. Based on the two steps of the proposed strategy, we introduce a two-stage multi-target adversarial adaptation network, TSMAAN, for predicting the EQI under uncommon operating conditions in WWTPs. In the first stage, an I-95 is used to extract the source latent features. Then in the second stage, a GAN is employed to align target domains with the source domain. In addition, considering the instability of the adversarial model, two strategies are proposed to improve the comprehensive performance of the model. Firstly, inspired by the classic transfer learning approach of pretraining, the parameters of the well-trained encoder from the I are utilized to initialize the generator of the GAN, aiding the generator's convergence and thereby improving model stability. Secondly, we incorporate MKMMD between the source and target domains into the generator's loss function to reduce the discrepancy between the target and source domains, thus improving the model's prediction accuracy on the target domains. To avoid multiple mappings and enhance the practicality of domain adaptation models in multi-target domain adaptation tasks, a stepwise strategy is proposed. First, the source data is mapped once to obtain latent features. Then target data from different tasks are mapped to the feature space of the source domain to achieve domain alignment. To avoid multiple mappings and enhance the practicality of domain adaptation models in multi-target domain adaptation tasks, a stepwise strategy is proposed. First, the source data is mapped once to obtain latent features. Then target data from different tasks are mapped to the feature space of the source domain to achieve domain alignment. Based on the two steps of the proposed strategy, a two-stage domain adaptation model, TSMAAN, is introduced. In the first stage, TSMAAN utilizes an I to extract latent features from the source data. In the second stage, it employs a GAN to align the target domains with the source domain. This two-stage approach enables efficient adaptation to multiple target domains while saving computational costs. Based on the two steps of the proposed strategy, a two-stage domain adaptation model, TSMAAN, is introduced. In the first stage, TSMAAN utilizes an I to extract latent features from the source data. In the second stage, it employs a GAN to align the target domains with the source domain. This two-stage approach enables efficient adaptation to multiple target domains while saving computational costs. To further improve the performance of TSMAAN in terms of stability and prediction accuracy, enhancements such as parameter initialization and MKMMD optimization are proposed. To further improve the performance of TSMAAN in terms of stability and prediction accuracy, enhancements such as parameter initialization and MKMMD optimization are proposed. 22.3.1 Related work. Autoencoder are generally capable of learning a compact representation of input data and are widely employed for reducing data dimensions as well as extracting features. In this study, we employ an I as the primary feature extraction tool. Multi-kernel MMD. In this study, MKMMD is used to measure the discrepancy between the source and target domains. Generative adversarial network. Furthermore, GAN is also widely used in domain adaptation tasks 113-115. Specifically, the generator is utilized to extract data features, while the discriminator classifies the features of the source and target domains. Through adversarial optimization, the generator can effectively reduce the disparities between the source and target domains and learn domain-invariant features to deceive the discriminator. Therefore, in this study, we construct an adversarial model based on GAN to achieve domain alignment. 22.3.2 Proposed Method. Problem definition. Assuming that and denote the input spaces of the source and target domains, respectively, and P represent their corresponding probability distributions. This study operates under the framework of unsupervised marginal domain adaptation, UMDA. Specifically, it assumes that, but P. The aim of this research is to sequentially learn feature representations for both the source and target domains in two distinct stages, with the objective of minimizing the divergence between P and P. For clarity, the ensuing discussion on TSMAAN will predominantly address a single domain adaptation task. Architecture of TSMAAN. The proposed TSMAAN framework, an unsupervised multi-target domain adaptation model, is depicted in Fig. 22.2. It is evident that TSMAAN comprises a two-stage model. The architecture of the proposed TSMAAN. TSMAAN consists of an I green, a GAN blue, and an EQI predictor yellow. The training process of TSMAAN consists of two stages, the source feature extraction stage upper part and the domain alignment stage lower part. For different target domains, the second stage will be repeated. Is the source domain data is the extracted source features, XS is the reconstructed source data, and YS is the predicted EQI. Is the target domain data is the extracted target features, YT is the predicted EQI, N denotes the number of target domains, and ELD is the domain label. The init module and the MKMMD2 module are used respectively to initialize the generator and compute the discrepancies between domains. Based on 22.62, 22.63, and 22.64, it is observable that the source and target domains do not share the same feature extractor. The feature extractor for the source domain is the encoder of the I, whereas the feature extractor for the target domain is the generator of the GAN. In other words, feature extraction for the source and target domains is performed independently. This represents the main distinction between the proposed TSMAAN, a specific type of domain adaptation model, and traditional structure-based unsupervised domain adaptation models. In multi-target domain adaptation tasks, TSMAAN necessitates the performance of the first stage only once, followed by the repetitive execution of the second stage to complete all tasks. In contrast, traditional domain adaptation models involve repeated mapping of the source domain, incurring higher computational costs. Improvement strategies. Based on the previously mentioned research, this study introduces two enhancement techniques aimed at boosting both the stability and predictive performance of the model: initialization of parameters and optimization using MKMMD. 1. Parameter initialization. Firstly, to improve the stability of the adversarial model, we employ a parameter initialization strategy for the generator, which helps promote the convergence of the adversarial model. Specifically, after optimizing the I, the parameters of the well-trained encoder are to the generator for initialization. It is worth noting that the generator and encoder in TSMAAN share identical architectures. Two-stage adversarial adaptation. According to 22.65, the generator has two optimization objectives. The first is to maximize the domain classification error, that is, aiming to deceive the discriminator, and the second is to minimize the MKMMD, which helps the generator learn better feature representations. This also indicates better domain alignment results and higher prediction accuracy. Furthermore, MKMMD can be viewed as a penalty term that reduces the divergence of the adversarial model, thereby enhancing the model's stability. Inspired by existing studies 120, 121, 123, we introduced a trade-off parameter to accommodate the additional optimization objective. Through adversarial iterative optimization of the generator and discriminator, the train generator is able to fully deceive the train discriminator, signifying that and are sufficiently similar. This indicates that the generator has successfully mapped the target domain data into the latent feature space of the source domain, achieving domain alignment. Finally, with as input, the universal predictor trained in the first stage can generate EQI predictions under non-normal operating conditions. In this study, the TSMAAN is optimized with the atom, and the overall algorithm of TSMAAN is summarized in Algorithm 1. 22.3.3 Experiment and Discussion. In this section, the data sets generated by benchmark simulation model No1 BSM1 103 are used to evaluate the proposed TSMAAN. Data set preparation of BSM1 as depicted in Fig. 22.21, a BSM1 can be divided into two main parts, the bioreactors and the secondary clarifier. In BSM1, there are 5 bioreactors. The first 2 bioreactors are anoxic tanks without aeration, while the last 3 bioreactors are aerobic tanks with aeration. The flows sequentially through the 2 anoxic tanks and the 3 aerobic tanks, where nitrogen and carbon are removed by activated sludge. Afterward, a small portion of the mixed with sludge is recycled back to the anoxic tank through internal circulation, while the majority of the flows into the secondary clarifier for sedimentation. Once the is fully settled, the treated water is discharged from the top layer of the secondary clarifier, and the excess sludge is extracted from the bottom. Part of this excess sludge is recycled back to the anaerobic tank, while the rest is discharged. Observational variables in BSM1. Variable, symbol, unit, the concentration of total nitrogen in the effluent. Tn, GnM3, the concentration of total COD in the effluent. DCOD, GCODM3, the concentration of total ammonia nitrogen in the effluent. GnM3, the concentration of total solids in the effluent. TSS, GSSM3, the concentration of total BOD5 in the effluent. TBOD5, GBOD5M3, the concentration of readily biodegradable substrate in the influent. SL, GCODM3, the concentration of total ammonia nitrogen in the influent. GnM3, the concentration of dissolved oxygen in third reactor. SO3, GCODM3, the concentration of nitrate nitrogen in third reactor. SNO3, GnM3, the concentration of ammonia nitrogen in third reactor. SNH3, GnM3, the concentration of dissolved oxygen in fourth reactor. SO4, GCODM3, the concentration of dissolved oxygen in fifth reactor. SO5, GCODM3, the concentration of nitrate nitrogen in fifth reactor. SNO5, GnM3, the concentration of ammonia nitrogen in fifth reactor. SNH5, GnM3, the concentration of readily biodegradable substrate in fifth reactor. SS5, GCODM3. Note COD is the chemical oxygen demand. BOD5 is the biochemical oxygen demand over 5 days. Furthermore, in order to represent different operating conditions in the real-world treatment process, WWTP, the maximum growth rate of autotrophic bacteria, μ, in the first reactor, and the oxygen transfer coefficient, Kla, in the fourth reactor are chosen as operation variables. The reason is that the variation of Kla and μ can simulate typical operating conditions in the actual WWTP, and there are significant discrepancies between these conditions. Especially, Kla influences the dissolved oxygen levels in the, which in turn influences the removal of ammonia-nitrogen in the nitrification reaction, and its variations lead to different operating conditions. We assign different Kla values to simulate changes in dissolved oxygen levels, resulting from variations in air blower operation in real-world scenarios. A higher Kla indicates excessive aeration from the air blowers, while a lower Kla signifies blower malfunctions or inadequate aeration. Additionally, mu reflects the activity of autotrophic bacteria in reactors, influencing the removal of ammonia, nitrogen, and phosphorus, with its variations leading to different operating conditions. We assign different mu values to simulate changes in autotrophic bacteria activity caused by external environmental fluctuations in real-world scenarios. A higher mu corresponds to favorable conditions like temperature and pH, while a lower mu indicates less favorable external environments. It is important to note that these changes in operating conditions are common in real-world WWTP. Operating conditions of the BSM-1. Operating condition mu Kla 1 0.5 240 2 0.7 240 3 0.9 240 4 0.5 360 5 0.5 480 Domain adaptation tasks. Task source domain, target domain, mu 1d, Kla 1d, mu 1d, Kla 1d, 1 0.5 240 0.7 240 2 0.5 240 0.9 240 3 0.5 360 0.7 240 4 0.5 360 0.9 240 5 0.5 480 0.7 240 6 0.5 480 0.9 240. In this experiment, the operating condition with mu05 and Kla 240 is regarded as the most common operating condition, that is, the source domain. It is important to note that different real-world treatment plants may use various technologies, and the sources of, as well as the intended uses of the treated water can differ. As a result, there is no universal guideline for defining what constitutes common and uncommon operating conditions. To ensure fairness and to entirely demonstrate the effectiveness of TSMAAN, operating condition with mu05 and Kla 360 and operating condition with mu05 and Kla 480 are also treated as source domains, and further experiments were conducted. Finally, 6 domain adaptation tasks are established with the 3 chosen source domains. In each task, the training and testing sets are split in a 7:3 ratio, providing 940 samples for training in both the source and target domains. The remaining 404 samples from the target domain are used for testing. Details of these domain adaptation tasks are provided in Table 2210. Experimental configurations. To demonstrate the effectiveness of the proposed TSMAAN, comparisons are made between TSMAAN and several classical domain adaptation methods, including TCA, DDC, DAN, and DANN, focusing on stability and prediction accuracy. Specifically, DDC and DAN are based on the structures outlined in references 79-80, respectively. In order to ensure that the subnetworks in each model have the same learning ability, all subnetworks in DANN and TSMAAN, including the generator, discriminator, encoder, decoder, and predictor, are three-layer neural networks. It should be stated that in order to meet the task requirements, the convolutional layers in DDC, DAN, and DANN have been replaced with fully connected layers, with all hidden layers having 32 neurons. Additionally, the latent feature dimensions for all methods in this experiment are set to 6. As a result, all adaptation layers used for extracting latent features consist of 6 neurons. Using the source domain data for training and the target domain data for testing, the prediction results of a multi-layer perceptron, MLP, are provided to demonstrate the necessity of applying domain adaptation methods to address the domain shift problem. Like the predictor, the MLP also utilizes a three-layer structure. Another crucial task is setting the bandwidth of kernels, as it directly influences the performance of MMD and MKMMD. Specifically, when is small, the denominator of the exponential term in 22.3 is reduced, making the Euclidean distance between samples have a greater influence on the output of kernel function. Even minor variations between samples can be detected, potentially causing the model to. When is large, the denominator of the exponential term in 22.3 becomes large, reducing the influence of changes in Euclidean distance between samples on the output of the kernel function. This weakens MKMMD's ability to accurately assess differences between the source and target domains, leading to poor model performance. For MMD is typically chosen using the median heuristic 93. For MKMMD, a set of kernels is used with varying 2, 10 to 10, increasing by a factor of 2, and with set to 193, 111. Based on the aforementioned configurations, the TSMAAN is trained using the atom with a learning rate of 10.4 and a batch size of 64. The model undergoes 200 iterations for both feature extraction and predictor training, and 1,500 iterations for domain alignment. Consistent with the domain adaptation stage of TSMAAN, DDC, DAN, DANN, and MLP are also trained using the atom, with 1,500 iterations allocated for domain alignment. Comparison of prediction results from TSMAAN and classical models. Tasks, Index, TSMAAN, DCA, DDC, DAN, DINN, MLP 1 R2 0.88800001 0.8670000 0.816034 0.876010 0.83400034 0.1410134 RMSE 0.7370004 0.810000 0.940088 0.77300033 0.90300087 1.78100136 MAI 0.570004 0.607000 0.7620083 0.69800069 1.2740122 2 R2 0.82100006 0.801000 0.71700042 0.79100041 0.71500029 0.82311145 RMSE 0.90700015 0.964000 1.1360086 0.97400095 1.1640070 2.4060755 MAI 0.73500014
0.7570000, 0.94800083, 0.82800093, 0.90300047, 1.63200464. 3. R2 0.88700001, 0.86100000, 0.80800040, 0.8690022, 0.8060024, 0.2630293. RMSE 0.740005, 0.827000, 0.9600100, 0.79600068, 0.9850062, 1.62300320. MAA 0.5860005, 0.63100000, 0.7870101, 0.64100064, 0.75500052, 1.1460205. 4. R2 0.81700003, 0.7860000, 0.70800054, 0.78400049, 0.68300050, 0.2620565. RMSE 0.91800008, 0.9990000, 1.1530111, 0.98901113, 1.2140091, 2.04200481. MAA 0.75500008, 0.790000, 0.97200102, 0.83300099, 0.97200063, 1.390290. 5. R2 0.8890002, 0.860000, 0.810035, 0.8720016, 0.7920042, 0.4140198. RMSE 0.7330007, 0.8320000, 0.9570090, 0.78800048, 1.0090094, 1.45200256. MAA 0.5730005, 0.6390000, 0.78400087, 0.6420048, 0.7650064, 1.0820215. 6. R2 0.81800006, 0.785000, 0.707065, 0.7920038, 0.7290029, 0.07900317. RMSE 0.91500015, 1.002000, 1.1530130, 0.973092,
1.1140052, 1.770282, MAI 0.74500016, 0.79700000, 0.9710126, 0.82400089, 0.88400043, 1.2790198. Results and discussion. 1. Effectiveness of TSMAAN in EQI prediction. The means and variances of the performance indexes for all methods, after 25 independent runs on the 6 domain adaptation tasks described above, are summarized in Table 2211. The highest R2 and lowest errors are bolded. From the experimental results, the following conclusions can be drawn. A DDC and DANN show acceptable performance on most tasks, suggesting that the MMD optimization in DDC and the adversarial optimization in DANN are both effective in achieving domain alignment. B. DAN outperforms DDC, which can be attributed to 2 factors. First, DAN has 2 additional adaptation layers, enhancing its learning capability. Second, the use of MKMMD in DAN is a more effective metric for measuring the discrepancy between source and target domains compared to MMD. C. TSMAAN achieves the highest average R2 and the lowest average RMSE and MAE across all tasks compared to other methods. Additionally, TSMAAN's prediction results have lower standard deviations than other methods, except for the non-deep method TCA, indicating superior accuracy and stability. D. MLP fails to achieve positive R2 on some tasks, underscoring the importance of domain adaptation methods in addressing the domain shift problem in WWTP. Box plots of R2 for domain adaptation models. A task 1 B task 2, C task 3, D task 4, E task 5, F task 6. Curve comparing EQI observed values red line and predicted values blue line on task 2. A TSMAAN B TCA C DDC D DAN E DANN F MLP. Prediction error on task 2. A TSMAAN B TCA C DDC D DAN E DANN F MLP. To provide a more comprehensive comparison of the prediction accuracy of the models, Fig. 22.22 presents box plots of R2 for the domain adaptation models on all tasks. Compared to DDC, DAN, and DANN, TSMAAN demonstrates higher average prediction accuracy. By analyzing quartiles and lengths of the box plots, it is evident that the prediction results of TSMAAN have a narrower distribution range, reflecting a greater degree of stability. To offer a more intuitive comparison of prediction accuracy among different domain adaptation models, Fig. 22.23 presents the prediction results of the models on a subset of test samples from Task 2. To more clearly represent the differences in prediction performance among different models, certain regions are highlighted with red boxes. Figure 22.23 illustrates that TSMAAN provides the best fit to the observed values compared to other models on the randomly selected test samples. Additionally, Fig. 22.24 displays the error curves for different models. As illustrated in Fig. 22.24, the error curve of TSMAAN exhibits a smaller range, which is also highlighted with red boxes. Visualization of feature distributions of source domains. Feature distributions of the source domains for Task 1 red square and Task 2 blue dot. Our original distributions, BTCA, CDDC, DDAN, EDANN, FTSMAAN. 2. Effectiveness of TSMAAN in lowercase. Theoretically, TSMAAN can reduce computational costs by avoiding multiple mappings. To validate this, principal component analysis PCA 99 is used to reduce data dimensions and visualize feature distributions of the source domains before and after domain alignment, as shown in Fig. 22.25. For simplicity, tasks 1 and 2, which share the same source domain, were selected as examples, as depicted in Fig. 22.25. Figure 2225b, C, D, and E illustrate that after domain alignment, the feature distributions of the source domain for tasks 1 and 2 are different. This illustrates that TCA, DDC, DAN, and DANN map the source data twice, even though tasks 1 and 2 share the same source domain. Moreover, to predict EQI, these models require training two task-specific predictors using different source features extracted from tasks 1 and 2. In contrast, Fig. 22.25f demonstrates that TSMAAN, constructed using the proposed stepwise strategy, avoids mapping the same set of source data multiple times. Specifically for Task 1, TSMAAN extracts the latent features from the source domain in the first stage, and then maps the target data to the feature space of source domain for domain alignment in the second stage. For Task 2, TSMAAN skips the first stage and directly maps the target domain data to the feature space of source domain, and achieving domain alignment by repeating the second stage. Based on 22.7 and 22.71, Fig. 22.26 presents the total flops for DDC blue, DAN green, DANN yellow, and TSMAAN red across different numbers of tasks. As shown in Fig. 22.26, DDC and DAN exhibit significantly higher flops compared to DANN and TSMAAN, primarily because the former two models have more network layers and hidden nodes. The total flops of DAN are lower than that of DDC, as the number of nodes in the adaptation layers of DAN is smaller than in its feature extraction layers, and DAN has more adaptation layers but fewer feature extraction layers than DDC. For a single task, flops of DANN are lower than those of TSMAAN, as TSMAAN includes an additional decoder in its source feature extraction module. However, for multiple tasks, TSMAAN shows the lowest flops, demonstrating its ability to save computational costs in multi-target domain adaptation tasks. Additionally, Fig. 22.27 shows the training time of the models under the same number of iterations. TSMAAN requires less training time compared to DAN. The training time of TSMAAN is very close to that of DDC because calculating MKMMD takes longer than calculating MMD. However, for domain adaptation tasks involving more than two target domains, the training time of TSMAAN remains lower than that of DDC. On the other hand, the training time of TSMAAN is longer than that of DANN for two main reasons. Firstly, TSMAAN involves the calculation of MKMMD, which is time-intensive. Secondly, DANN uses a gradient reversal layer, GRL, which reduces training time during adversarial optimization. To address this, a variant of TSMAAN called TSD replaces MKMMD with GRL for domain alignment. As Fig. 22.27 shows, TSD achieves shorter training times than DANN. Therefore, we can conclude that when using similar domain alignment methods, such as MMD, MKMMD, or adversarial mechanisms, the two-stage model requires less training time. Total flops for domain adaptation models. Total training time for domain adaptation models. Comparison of prediction results from TSMAANs with different strategies. Tasks. Index. TSMAAN. TSMAAN without. MKMMD. TSMAAN without. Init. TSMAAN without. Init and MKMMD. 1. R2. 0.88800001. 0.83900014. 0.6110161. 0.5630220. RMSE 0.7370004. 0.8920036. 1.3310283. 1.4280382. MAI 0.5700004. 0.6730038. 1.0160207. 1.0980307. 2. R2 0.8210006.
0.7890024, 0.55905151, 0.5060168, RMSE 0.9070015, 0.9950046, 1.40256, 1.5030252, MAI 0.7350014, 0.7870035, 1.0930193, 1.2120231, 3, R2 0.88700001, 0.8760009, 0.640091, 0.6250182, RMSE 0.740005, 0.7860032, 1.3050173, 1.3170303, MAI 0.5860005, 0.6060026, 1.0270137, 1.0410267, 4, R2 0.81700003, 0.7460039, 0.5810122, 0.5060226, RMSE 0.91800008, 1.0900086, 1.3720205, 1.4820333, MAI 0.75500008, 0.890058, 1.0910155, 1.1740277, 5, R2 0.8890002, 0.8530019, 0.6340158, 0.570150, RMSE 0.7330007, 0.8460056, 1.3020287, 1.4390269, MAI 0.5730005, 0.6340032, 1.0160218, 1.1560252, 6, R2 0.81800006, 0.80035, 0.482035, 0.4570190, RMSE 0.91500015, 0.9590077, 1.52600217, 1.5680297, MAI 0.74500016, 0.7760059, 1.2090167, 1.2670246. 3. Effectiveness of parameter initialization and MKMMD optimization. As mentioned earlier, parameter initialization and MKMMD optimization are introduced in this study to enhance the performance of TSMAAN. To verify their effectiveness, we propose the following model variants based on the original TSMAAN. The TSMAAN without parameter initialization, TSMA, the TSMAAN without MKMMD optimization, TSMAND, and the TSMAAN without both parameter initialization and MKMMD optimization, TSMAAN-ID.
These variants were applied to the previously defined domain adaptation tasks, with the prediction results displayed in Table 2212, where the highest R2 and the lowest error values are bolded. Taking Task 1 as an example, compared to the original TSMAAN. The TSMAANI shows a 31.19% decrease in R2, an 80.6% increase in RMSE, and a 78.25% increase in MAE. The TSMAND exhibits a 5.52% decrease in R2, a 21.03% increase in RMSE, and an 18.07% increase in MAE. The TSMAANID demonstrates a 36.6% decrease in R2, a 93.76% increase in RMSE, and a 92.63% increase in MAE. These results suggest that the prediction accuracy of all TSMAAN variants decreased significantly compared to the original model. Additionally, the standard deviations of the prediction results for TSMAANI, TSMAAND, and TSMAANID were higher than those of the original TSMAAN, indicating that the stability of these variants also decreased. Figure 2228 presents box plots of R2 for TSMAAN variants across all tasks. By analyzing the quartiles and box plot lengths, it is evident that both TSMAANI and TSMAANID exhibit instability after removing parameter initialization. Similarly, TSMAAND and TSMAANID show a reduction in average prediction accuracy after excluding MKMMD optimization. When parameter initialization is applied to TSMAANID, resulting in TSMAAND, both stability and prediction accuracy improve significantly. On the other hand, TSMAANI, which applies MKMMD optimization, improves average prediction accuracy but only enhances stability for certain tasks, such as tasks 1 and 6. Additionally, when MKMMD optimization is applied to TSMAAND, creating the original TSMAAN, it further boosts prediction accuracy. Thus, it can be preliminarily concluded that MKMMD optimization enhances prediction accuracy, while parameter initialization improves both stability and accuracy. Box plots of R2 for TSMANs. A Task 1 B Task 2, C Task 3 D Task 4 E Task 5 F Task 6. Curve comparing EQI observed values red line and predicted values blue line on Task 2. A TSMAAN B TSMAAND C TSMAANI D TSMAANID to further analyze the impact of parameter initialization and MKMMD optimization on TSMAAN. We displayed the loss curves for TSMAANID green line, TSMAANI blue line, and TSMAAN red lines. As shown in Fig. 22.31 and B, without any optimization strategy, TSMAANID operates as a two-stage adversarial model, and its generator and discriminator loss curves fluctuate significantly. When parameter initialization is applied, as in TSMAAND, these fluctuations are noticeably reduced, illustrating that parameter initialization helps the model converge and improves its stability. Moreover, after 1500 iterations, TSMAAND achieves a lower loss value for the generator and a higher loss value for the discriminator compared to TSMAANID. This suggests that a generator initialized with can more effectively learn target domain feature representations and confuse the discriminator than a randomly initialized generator. As shown in Fig. 22.31 C and D, when MKMMD optimization is applied to TSMAAND, resulting in TSMAAN, the generator's loss increases while the discriminator's loss decreases. This occurs because the MKMMD optimization has a significant influence on the overall model optimization, which reduces the effectiveness of the adversarial optimization between the generator and discriminator compared to before. However, previous experimental results have clearly demonstrated the positive impact of MKMMD optimization on improving the model's prediction accuracy. Moreover, the fluctuations in the loss curves are further reduced with MKMMD optimization, indicating that MKMMD, acting as a penalty term, prevents the model from diverging and enhances its stability. In conclusion, both parameter initialization and MKMMD optimization contribute to improving the performance of TSMAAN by enhancing its stability and prediction accuracy. Prediction error on Task 2. A TSMAAN B TSMAND C TSMANI DTS-MAN-ID loss curves of generators and discriminators. Of the loss curves of generators from TSMAAN-ID, green line, and TSMAAN-D, blue line. B. The loss curves of discriminators from TSMAAN-ID, green line, and TSMAAN-D, blue line. C. The loss curves of generators from TSMAAN-D, blue line, and TSMAAN, red line. D. The loss curves of discriminators from TSMAAN-D, blue line, and TSMAAN, red line. Sensitivity analysis. In this section, we conduct experiments to analyze the sensitivity of hyperparameters in TSMAAN. First, we vary the trade-off parameter within the range 10-1-100-10-1102+, and the average prediction performance of TSMAAN across 6 tasks is presented in Fig. 22.32. The TSMAAN achieves the highest R2 and the lowest RMSE in prediction when 10. When plus, the model abandons adversarial optimization, and the decrease in prediction accuracy demonstrates the necessity of using adversarial models. Next, we adjust the trade-off parameter within the range 10.5, 10.4, 10.3, 10.2, and the average prediction performance of TSMAAN across 6 tasks is illustrated in Fig. 22.33. The model achieves its best prediction performance when the learning rate is set to 10.4. Average prediction performance of TSMAAN across 6 tasks with varying R2B RMSE. Average prediction performance of TSMAAN across 6 tasks with varying learning rate. In this study, a stepwise domain alignment strategy is proposed to enhance the practicality of domain adaptation models in WWTP. Building on this strategy, we introduce a 2-stage multi-target adversarial adaptation network, TSMAAN, designed to predict the EQI under uncommon operating conditions in WWTP. Additionally, parameter initialization and MKMMD optimization are incorporated to further improve the overall performance of TSMAAN. The datasets generated by BSM-1 under various operating conditions are used to evaluate the proposed TSMAAN. Experimental results demonstrate that TSMAAN achieves superior stability and prediction accuracy compared to classical methods in multi-target domain adaptation tasks. Furthermore, due to its 2-stage structure, TSMAAN avoids multiple mappings and reduces computational costs. Additionally, several variants of TSMAAN are tested on the same domain adaptation tasks to verify the effectiveness of parameter initialization and MKMMD optimization. The results confirm that both parameter initialization and MKMMD optimization significantly enhance the stability and prediction accuracy of TSMAAN. The TSMAAN proposed in this study is designed to predict key indicators under uncommon operating conditions in WWTP. In the future, we aim to enhance the performance of the model, with one potential area of improvement being the optimization of hyperparameters, which could further benefit the overall performance of the model. Additionally, the model will be refined to better meet the practical needs of the treatment industry. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. Appendix AVBJMM details. Flowsheet of the penicillin cultivation process 75-78. Measured variables of the fed batch penicillin fermentation process 75-78. Variable No. Variable description. Input 1. Aeration rate LH. 2. Agitator power W. 3. Substrate feed rate LH. 4. Substrate feed temperature K. 5. Acid flow rate LH. 6. Base flow rate LH. 7. Cooling water flow rate LH. Output 8. Substrate concentration GL. 9. Dissolved oxygen concentration GL. 10. Biomass concentration GL. 11. Penicillin concentration GL. 12. Culture volume L. 13. Carbon dioxide concentration GL. 14. pH 15. Bioreactor temperature K. 16. Generated heat kcal. Initial conditions and set points to simulate the penicillin cultivation process 75, 78. Initial conditions. Range. Substrate concentration GL. 15, 17. Dissolved oxygen concentration L. 112. Biomass concentration GL. 0.1. Penicillin concentration GL. 0. Culture volume L. 101-103. Carbon dioxide concentration L. 0.51. Hydrogen ion concentration H plus L. 10.5. Bioreactor temperature K. 297-299. Generated heat kcal. 0. Set points. Aeration rate GL. 8.9. Agitator power W. 29-31. Substrate feed flow rate LH. 0.0390045. Substrate feed temperature K. 295-296. Bioreactor temperature K. 297-298. pH 4.95505. References 1Z. Review on data-driven modeling and monitoring for plant-wide industrial processes. Lab 171, 1625-2017. 2 Park YJ Fan SKS, CY, a review on fault detection and process diagnostics in industrial processes. Processes 8-9, 2020. 3QXB, review and perspectives of data-driven distributed monitoring for industrial plant-wide processes. And Raise 5829, 12899 12912, 2019. 4ALM-BMS, fault diagnosis in industrial chemical processes using interpretable patterns based on logical analysis of data. Expert 95 368 383, 2018. Online ComScience article S0957417417307984. 5 Santos MR Costa BSJ CGG LA, an evolving approach for fault diagnosis of dynamic systems. Expert 189 115983, 2022. Online ComScience article S0957417421013324. 6 Mason RL Young JC, multivariate statistical process control with industrial applications. Social and Maths 2002. Online SIAM Org ABS 10113719780898718461. 7T P MacGregor JF, analysis, monitoring, and fault diagnosis of batch processes using and multi-way. J process control 54 277-284, 1995. IFAC Symposium, Advanced control of chemical processes. Online. ComScience Article 0959152495000019 M8, L, J, U, X, J. Fault detection in dynamic systems using the divergence. Control. 43 39 48 2015. Online. ComScience Article S0967066115001008. 9 Luo L Su M Bao S Mao J Tong C. Improvements to the T2 statistic for multivariate fault detection. Ind and. Raise. 5845, 20692 20709, 2019. Online. Org 1010-219B04112. Tendong Y Chin, S.J., a novel dynamic PCA algorithm for dynamic data modeling and process monitoring. J Process. Control. 67-111, 2018. Big Data, Data Science for Process Control and Operations. Online. ComScience Article S0959152417300094X11 Peng, X Ding, SX, W, W, F. Distributed process monitoring based on canonical correlation analysis with partly connected topology. Control. 101, 104,500, 2020. Online. ComScience Article S0967066120301209. 12 Song B, H Tan, S Tau Y. Orthogonal canonical correlation analysis for quality-related plant-wide process monitoring. IEIE Trans. End. Inform. 17-9, 6368-6378, 2021. 13 Luo L Bao S Mao J. Adaptive selection of latent variables for process monitoring. Ind and. Raise. 5821, 90759086, 2019. 14 SM, A. Real-time fault detection and diagnosis using sparse principal component analysis. J Process. Control. 67-112-128, 2018. Big Data, Data Science for Process Control and Operations. Online. ComScience Article S095915241730-0677. 15 Luo L Bao S Tong C. Sparse Robust Principal Component Analysis with Applications to Fault Detection and Diagnosis. Ind and. Raise. 58-3, 1301-309, 2019. 16 Wan X Tong C. Luo L. Distributed Statistical Process Monitoring based on Canonical Correlation Analysis. Ind and. Raise. 59-3, 1193-1201, 2020. 17 Luo L Peng X Tong C. A framework for fault detection and diagnosis in large-scale multivariate systems. J Process. Control. 16579, 2021. 18 MF H. Fault detection of uncertain nonlinear process using interval-valued data-driven approach. 205 3645, 2019. 19 JCM Pontes KV I.M. Fault detection and diagnosis in dynamic systems using weightless neural networks. Expert. 84 200 219, 2017. 20 KEM Y Lao L Yang SH. A review of kernel methods for feature extraction in nonlinear process monitoring. Processes 8-1, 2020. 21 XXS CJ. Fault discriminant enhanced kernel principal component analysis incorporating prior fault information for monitoring nonlinear processes. Lab. 162, 2134, 2017. 22 RMOMFN. Online reduced kernel principal component analysis for process monitoring. J Process Control 61, 111, 2018. 23 Peng C. D. Monitoring Multi-Domain Batch Process State Based on Fuzzy Broad Learning System. Expert. 187, 115,851, 2022. 24 Q. S. XEH. F. Data-Driven Two-Dimensional Deep Correlated Representation Learning for Nonlinear Batch Process Monitoring. IEIE Trans. And Inform 16.4, 2839-2848, 2020. 25 Lan T. Tong C. H. X. Luo L. Nonlinear Process Monitoring Based on Decentralized Generalized Regression Neural Networks. Expert. 150, 113,273, 2020. 26 C. J. Yi L. Sparsity and Manifold Regularized Convolutional Autoencoders-Based Feature Learning for Fault Detection of Multivariate Processes. Control. 111, 104,811, 2021. 27 H. Sun S. Jin B. Sequential Fault Diagnosis Based on LSTM Neural Network. IEEE Access 6, 12,929, 12939, 2018. 28 V. S. J. Large-Scale Sparse Kernel Canonical Correlation Analysis. INS K. R. International Conference on Machine Learning, SIR. Proceedings of Machine Learning Research. 97. 36th International Conference on Machine Learning, ICML, Long Beach, CA 2019. 29 D. S. AJ Z. B. Randomized Nonlinear Component Analysis. In Uxing IET. International Conference on Machine Learning, Cycle 2, SIR. Proceedings of Machine Learning Research. 32. 1359-1367. International Conference on Machine Learning, Beijing, People's R. China, 2014. 30 J. S. Singer Y. T. Efficient Projections onto the L1 Ball for Learning in High Dimensions. In Proceedings of the 25th International Conference on Machine Learning, SIR. ICML 08. 272-279. Association for Computing Machinery, New York, NY, USA 2008. 31 Thomas J.A.T. Cover M. Bibliography. 510-525. John and Sons, 1991. 32 A. H. P. Estimating Mutual Information. Rev. E69-6, 2004. Art. No. 66,138. 33 R. Dave K. T. M. A nonlinear dynamic model of a vinyl acetate process. End. Raise. 4220, 4478 4487, 2003. 34 Ding, SX, Data-Driven Design of Fault Diagnosis and Fault-Tolerant Control Systems. Springer, 2014. 35 Z Ding SXC, Real-Time Fault Diagnosis and Fault-Tolerant Control. IEIE Trans. End. Electron. 62.6, 3752-3756, 2015. 36 C. A quality-relevant sequential phase partition approach for regression modeling and quality prediction analysis in manufacturing processes. IEIE Trans. 11.4, 983-991, 2013. 37 Q. X. Parallel PCA-KPCA for Nonlinear Process Monitoring. Control. 80, 1725, 2018. 38 Chin, S.J. Process Data Analytics in the Era of Big Data. EJ69, 3092-3100, 2014. 39 Q. B. Distributed Monitoring for Large-Scale Processes Based on Multivariate Statistical Analysis and Bayesian Method. J Process Control 46, 7583, 2016. 40 Chin S.J. Statistical Process Monitoring, Basics and Beyond. J1789, 48502, 2003.
41J-Z Song Z, non-industrial process monitoring with probabilistic independent component analysis. IEIE Trans. 14.2, 1309-1319, 2016. 42J Han Z, fault diagnosis method of joint Fisher discriminant analysis based on the local and global manifold learning and its kernel version. IEIE Trans. 13.1, 122-133, 2015. 43Y Yin S, recent advances in key performance indicator-oriented prognosis and diagnosis with a toolbox, KIT. IEIE Trans. And Inform. 15.5, 2849-2858, 2018. 44P MacGregor, J.F., multivariate SPC charts for monitoring batch processes. 37.1, 4159, 1995. 45Y Yin S, recursive total principal component regression based fault detection and its application to vehicular cyberphysical systems. IEIE Trans. And Inform. 14.4, 1415, 1423, 2017 MathNet. 46Q X B, performance-driven distributed PCA process monitoring based on fault-relevant variable selection and Bayesian inference. IEIE Trans. And Electron. 63.1, 377-386, 2015. 47 Li G Chin S.J. Zhou D, geometric properties of partial least squares for process monitoring. 46.1, 204-210, 2010 MathNet. 48Y Yin S, recent results on key performance indicator-oriented fault detection using the DBKit toolbox. In IECON 2017, 43 Annual Conference of the IEEE Industrial Electronics Society. 71037108. IAIA 2017. 49Z Ding SX K Lei Z Z, canonical correlation analysis-based fault detection methods with application to alumina evaporation process. Control. 46 5158, 2016. 50Z K Ding SX YA Z, improved canonical correlation analysis-based fault detection methods for industrial processes. J Process Control 41 2634, 2016. 51 Q Ding SX Y X, data-driven distributed local fault detection for large-scale processes based on the GAR-regularized canonical correlation analysis. IEIE Trans. And Electron. 6410, 8148, 8157, 2017. 52 Q FEH X, multivariate statistical monitoring of key operation units of batch processes based on time-slice CCA. IEIE Trans. Control. Technol. 27.3, 1368, 1375, 2018. 53 LH EL RD, fault detection and diagnosis in industrial systems. Springer Science and Business Media 2000. 54 Q Chin SJ Chai T, dynamic concurrent kernel CCA for strip thickness relevant fault diagnosis of continuous annealing processes. J Process Control 67 1222, 2018. 55 B D X Yang F RD, canonical variate analysis-based contributions for fault identification. J Process Control 26 1725, 2015. 56 Q Chin SJ, concurrent quality and process monitoring with canonical correlation analysis. J Process Control 60 95 103, 2017. 57 Q X B, neighborhood variational Bayesian multivariate analysis for distributed process monitoring with missing data. IEIE Trans. Control. Technol. 27.6, 2332, 339, 2018. 58 Z Ding SX Peng T Yang C GUI W, fault detection for non-processes using generalized canonical correlation analysis and randomized algorithms. IEIE trans. And electron. 65-2, 1559-1567, 2017. 59YBXM, a mixture of variational canonical correlation analysis for nonlinear and quality-relevant process monitoring. IEIE trans. And electron. 65-8, 6478-6486, 2017. 60QX, learning deep correlated representations for nonlinear process monitoring. IEIE trans. And inform. 1512 6206 209 2018. 61 Peng X Tang YWF, process monitoring and fault detection, a sparse modeling and dictionary learning method. IEIE trans. And electron. 64-6, 4866-4875, 2017. 62 W Fan YY, process monitoring based on data-driven method. J. Franklin. 354-6, 2613-2627, 2017. 63 Joe L. J. Z Song Z Shan S, process monitoring based on switching dynamic latent variable model. IEIE trans. And electron. 6510, 8184-8194, 2018. 64 C Yao Y F F, statistical analysis and online monitoring for processes with between-mode transitions. 6522, 59615975, 2010. 65 C W Chin Y F, comprehensive subspace decomposition with analysis of between-mode relative changes for process monitoring. And raise. 5412, 31543-166, 2015. 66 Peng K KUB Dong J Z, a quality-based nonlinear fault diagnosis framework focusing on industrial batch processes. IEIE trans. And electron. 63-4, 2615-2624, 2016. 67 SW Park JH Lay IB, process monitoring using a mixture model via principal component analysis and discriminant analysis. 28-8, 1377-1387, 2004. 68 MAT Jane AK, unsupervised learning of finite mixture models. IEIE trans. Pattern anal. Mach. 24-3, 380-1396, 2002. 69 J Chin SJ, process monitoring with Bayesian inference-based finite mixture models. EJ 54-7, 1811-1829, 2008. 70 Bishop CM NM, pattern recognition and machine learning. Springer 2006. 71 N AG, variational learning for mixture models. IEIE trans. Man. B36-4, 849-862, 2006. 72 MS HF CP Ho TY Hung CH, a variational Bayesian approach for unsupervised clustering. In Frontier Computing, Theory, Technologies and Applications. 651-660. Springer 2016. 73 Johnson R.A. D.W. Al. Applied Multivariate Statistical Analysis. Prentice Hall Upper Saddle River, NJ 2002. 74 C.B. A full-condition monitoring method for non-stationary dynamic chemical processes with and slow feature analysis. EJ 64-5, 1662-1681, 2018. 75 GCA, a modular simulation package for fed batch fermentation, penicillin production. Land. 2611, 1553-1565, 2002. 76 X Kano M. Lay Y, locally weighted kernel partial least squares regression based on sparse nonlinear features for virtual sensing of nonlinear time-varying processes. Land. 104, 164, 171, 2017. 77YQ Li B L, Joint Individual Monitoring of Parallel Running Batch Processes Based on MCCA. IEEE Access 6, 13005 13014, 2017. 78 Lay JM C Lay IB, Statistical Process Monitoring with Independent Component Analysis. J Process Control 14.5, 467 485 2004. 79 Long M Y J Jordan M, Learning Transferable Features with Deep Adaptation Networks. In International Conference on Machine Learning. 97 105. PMLR 2015. 80 EJNKT Deep Domain Confusion, Maximizing for Domain Invariance 2014. 14123474. 81 YE H German P H F Marchand M V, Domain Adversarial Training of Neural Networks. J Mach. Learn. Raise. 17-1, 2096-2030, 2016 MathNet. 82X M Y Yang Q Lei J, Assessment of Data Suitability for Machine Prognosis Using Maximum Mean Discrepancy. IEEE Trans. And Electron. 65-7, 5872-5881, 2017. 83 Pan SJ IW JT Yang Q, Domain Adaptation via Transfer Component Analysis. IEEE Trans. Neural. 22-2, 199-210, 2010. 84 CF Y M, a supervised bidirectional long short-term memory network for data-driven dynamic soft sensor modeling. IEEE Trans. 71 113, 2022. 85 J Yang C Li Y Lan L Luo Q MPARNN, a novel attention-based recurrent neural networks for total nitrogen prediction. IEEE Trans. And Inform. 1810 65 16 6 525, 2022. 86 X Q Z Yuan J, using LSTM neural network based on improved PSO and attention mechanism for predicting the effluent COD in a treatment plant. IEEE Access 9, 146,082 146096, 2021. 87 H Corona FMLMR, shall we use hardware sensor measurements or soft sensor estimates? Case study and a full-scale WWTP. Environ. Model End. 72 215 229, 2015. 88 HHYFM, Modeling of Treatment Processes Using Dynamic Bayesian Networks Based on Fuzzy. IEEE Access 8, 92,129 92140, 2020. 89 MWT Van MC, Activated Sludge Models ASM1, ASM2, ASM2D, and ASM3. IWA Publishing 2000. 90 WM, Activated Sludge Modeling and Simulation. Water. Technol. 2346, 10111023, 1991. 91 KM, A, MJ, HP, B, AJ, Integrating Structured Biological Data by Kernel Maximum Mean Discrepancy. Bioinformatics 2214, E49, E57, 2006. 92 Pan SJ Yang Q, A Survey on Transfer Learning. IEEE Trans. Data. 2210, 1345, 1359, 2009. 93 ADH S Pontal MKBK, Optimal Kernel Choice for Large-Scale Two-Sample Tests. ADV. Neural. Process. 25 2012. 94 IJM Su B Farley D S A Y, Generative Adversarial Networks. ACM 6311, 139 144, 2020 MathNet. 95 Y Yao H S, Autoencoder-Based Dimensionality Reduction. 184 232 242, 2016.
96 Wilson G. Cook, DJ, A Survey of Unsupervised Deep Domain Adaptation. ACM Trans. Techno. TISD 115146, 2020. 97 ASKHR, A Brief Review of Domain Adaptation. ADV. Data. 877 894, 2021. 98 AK, Sensitivity Analysis of the Secondary Settling Tank Double Exponential Function Model. Water. On line 7, 2002. 99 R Ma YSS, Principal Component Analysis. In Generalized Principal Component Analysis. 2562. Springer 2016. 100 CWMGCZ, Decoupling of Eco-Environmental Damage in China's Economic Development. Total. Environ. 789, 147,980, 2021. 101 JDJ, Do we really need to access the source data? Source Hypothesis Transfer for Unsupervised Domain Adaptation. In International Conference on Machine Learning. 60286039. PMLR 2020. 102 SMAO H Ding Z Y Deep Decision Tree Transfer Boosting. IEIE Trans. Neural. Learn. 312 383 395, 2019 MathNet. 103 Alex J L J K U I Pons M L C J Al. Benchmark Simulation Model No. 1 BSM1. In Report by the IWA on Benchmarking of Control Strategies for WWTPs. 1 2008. 104 Nelson M. H. S. Analysis of the Activated Sludge Model Number 1. Maths. 22.5 629 635 2009. 105 H.M. To Annotate or Not. Predicting Performance Drop Under Domain Shift. In Proceedings of the 2019 Conference on Empirical Methods in Natural Language Processing and the 9th International Joint Conference on Natural Language Processing, EMNLP-IJCNLP. 2163-173, 2019. 106 X, X, and A, Study on Modeling and Simulation of BSM1 with. In Recent Advances in Computer Science and Information Engineering. 861-866. Springer 2012. 107 DJ JJ, A Review of ADM1 Extensions, Applications, and Analysis, 2002-2005. Water. Technol. 54.4-110-2006. 108G QSJO M by JJ A, Artificial Neural Networks for Water Quality Soft Sensing and Treatment, A Review. Rev. 123, 2021. 109 YYZ Yang W, Time-Weighted Kernel Sparse Representation-Based Real-Time Nonlinear Process Monitoring. IEIE Trans. And Inform. 18.4-24-11-2421, 2021. 110 J. Multiple Granularities Generative Adversarial Network for Recognition of Wafer Map Defects. IEIE Trans. And Inform. 18.3-1674-1683, 2021. 111 Long M. Y. Z. J. Jordan M.I. Transferable Representation Learning with Deep Adaptation Networks. IEIE Trans. Pattern Anal. Mach. 4112-3071-3085, 2019. 112 Long M. J. Y. Sun J. P.S. Deep Learning of Transferable Representation for Scalable Domain Adaptation. IEIE Trans. Data. 28.8-2027-2040, 2016. 113 Yuan, Y. Li, Y. Z. Li, R. X. Joint Domain Adaptation Based on Adversarial Dynamic Parameter Learning.
IEIE trans. Emerge. Top. 54 714 723 2021. 114 Y H Lay T. Learning class-aligned and generalized domain-invariant representations for speech-emotion recognition. IEIE trans. Emerge. Top. 44 484 89 2020. 115 SMJ. Sparse adversarial unsupervised domain adaptation with deep dictionary learning for traffic scene classification. IEIE trans. Emerge. Top. 112 2023. 116 Lay Q H Z Joe N Sun W S Lay J FDCGAN. Amplitude feature deep convolutional GAN for fingerprint construction in indoor localization systems. IEIE trans. Emerge. Top. 53 468 480 2021. 117 A Pratap A Singh AK. Generative adversarial neural machine translation for phonetic languages via reinforcement learning. IEIE trans. Emerge. Top. 71 191 99 2023. 118 U Pons MN I Alex J JKC JPP. Benchmark Simulation Model No 2. General Protocol and Exploratory Case Studies. Water. Technol. 56 8 67 78 2007. 119 AP Pons MN M H. Implementation of extended statistical entropy analysis to the effluent quality index of the benchmarking simulation model No. 2. Water 61 86 103 2014. 120 Han T C Yang W D. Deep Transfer Network with Joint Distribution Adaptation. A new intelligent fault diagnosis framework for industry application. ISA trans. 97 269 281 2020. 121 YLJJW. Unsupervised domain adaptation for non-intrusive load monitoring via adversarial and joint adaptation network. IEIE trans. And Inform. 18-1 266 277 2021. 122 Long M J Ding G Sun J PS. Transfer feature learning with joint distribution adaptation. In Proceedings of the IAIE International Conference on Computer Vision. 2200 2207 2013. 123 Wu Y R Ma H He Q S Wu J. Adversarial Domain Adaptation Convolutional Neural Network for Intelligent Recognition of Bearing Faults. Measurement 195, 111,150, 2022. 23. Data-driven robust closed-loop monitoring approaches for industrial systems. Abstract. This chapter presents data-driven robust closed-loop monitoring approaches with unknown disturbances, utilizing subspace mapping and adaptive observer techniques. In the subspace-aided approach, a subspace for unknown disturbances is constructed. By analyzing the projection relationships among subspaces of different signals within the process data, the stable kernel representation, SKR, of the closed-loop system under disturbance is identified. It involves constructing a residual generator to effectively decouple the residuals from the unknown disturbances, thereby achieving a data-driven robust closed-loop monitoring strategy. In the adaptive observer approach, a closed-loop adaptive estimation framework against unknown disturbances is presented to cope with the correlation between control inputs and noises by integrating the prior knowledge of the controller. An observer-based joint estimation algorithm is constructed using the noise-independent variable as new input, which solves the biased estimation problem under closed-loop feedback and achieves online disturbance estimation and real-time correction with parameter and state estimates. 23.1 Introduction. In recent decades, model-based fault diagnosis techniques have been extensively studied and validated in academia and industry, and many successful applications have been demonstrated. 1.3. With the continuous improvement of product quality and control accuracy requirements, industrial systems are becoming more complex, and many intelligent systems and equipment are used to enhance the safety and reliability of the whole process and improve overall control performance. Therefore, the process monitoring system has become a key module in the development. These modules are designed to assess the state and efficiency of the process accurately and propose appropriate maintenance actions promptly when anomalies are found. Advances in communication technologies, data networking systems, and computer science have contributed significantly to the popularity of data-driven approaches in both theoretical and practical domains, and data-driven techniques offer significant advantages. On the one hand, they save time and reduce the need for significant engineering effort in the modeling process. On the other hand, these techniques can effectively extract valuable anomaly or fault information from existing process data. Many academic surveys and practical implementations of data-driven fault diagnosis methods will be found in the literature, as mentioned in 412 and other works. Data-driven fault diagnosis methods include various multivariate statistical approaches that analyze the correlations among measured process input-output (I/O) data 4.6. Another approach involves subspace-aided techniques, which design process monitoring and control systems based on identified process models 7, 13, 15. In 8, it allows the direct design of monitoring and control systems based on the identified data-driven realization of the stable kernel representation (SKR) of the dynamic process, later extended in 16, which does not require a detailed model identification. While traditional subspace-aided design effectively addresses the dynamic behavior of processes, it often ignores the impact of the disturbances during subspace identification, which can lead to biased model identification and consequently result in inadequate monitoring and control performance. Recent studies have started addressing this issue. For example, 17 presents a robust monitoring approach for static processes that isolates the maximum effect of the disturbances. In a recent work by Luo al. 19, the open-loop design for dynamic processes with deterministic disturbances is explored using a projection technique that decomposes process data into subspaces of different signals. Further development on practical applications can be found in 2022. Data-driven approaches also play a huge role in the accurate estimation of system dynamics. Considering the changes in process parameters and operation conditions, the adaptive mechanism is integrated with the observer-based methods. Then accurate monitoring and diagnosis can be achieved using the adaptive observer algorithms. As direct designs from process data, adaptive observer algorithms can accurately estimate the system parameters and states online without exact system parameter information. In the past decades, adaptive observer-based approaches have been studied and developed for process monitoring, diagnosis, and control 23-24. Since the adaptive observer performs simultaneous estimation on the state variables and unknown parameters of the process, the estimation errors can be fully regulated with an integrated adaptive estimation mechanism 25. In contrast to the traditional estimation procedure, which performs parameter estimation first and then design observers, the adaptive observer approach allows an integrated estimation procedure. With zero mean noise, which is independent of the I/O signals, and appropriate parameter settings, the estimation errors of the adaptive observer can converge exponentially to 0.26, 27. Despite being able to perform adaptive estimation based only on I/O data, the adaptive observer is very sensitive to noises and disturbances, which are mixed in the measurements. They can lead to biased or even divergent estimation, results 28. To cope with these problems, researchers have devoted substantial efforts to improving the robustness of the adaptive observer 29. Using noise information to adjust the gain or adding a moving window design is an alternative to reduce the effect of noises. As for unknown disturbances, 30-31 designs an adaptive observer-based disturbance estimator. Luo al. 32 combine the projection-aided method with the adaptive observer to remove the effects of disturbances from measurements. It is important to note that the above progress is considered for the case of open-loop systems. Most of the practical systems are operated and measured in a closed-loop structure due to the requirements of stability and reliability 34-35. The control inputs are generally generated from the feedback loop, through which the process outputs are passed to the controller. Therefore, the control input and output noises in a closed loop are coupled 33. This characteristic violates the convergence condition of the adaptive observer algorithm. So the performance of the parameter and state estimation results cannot be guaranteed if the adaptive observer is used in a closed loop 36-37. The design in a closed loop is a focus that has been neglected by existing adaptive observer-based methods. Aiming at achieving accurate estimation in a closed loop against the coupling problem, the traditional methods mainly include the following types 38. The first one directly identifies the entire closed-loop structure, and then the system dynamics are split based on the controller information. Another approach regards the inputs and outputs of the controlled plant as new outputs, and the closed-loop reference inputs and noises are treated as new inputs, followed by estimation in an open-loop way 39. Most of these closed-loop methods do not allow online estimation. Therefore, it is necessary to carry out the design of a closed-loop adaptive observer. Besides, the unknown disturbances need to be taken into account as well 40. In this chapter, we focus on a novel data-driven approach based on the closed-loop subspace identification technique 4143 and study the subspace-aided robust closed-loop monitoring approach. Differing from existing methods, the approach decomposes the closed-loop data into different subspaces, where the kernel subspace with enhanced robustness against unknown disturbance can be further determined. In addition, a closed-loop data-driven joint estimation algorithm based on the adaptive observer is developed. The decoupling is combined with factorization on the controller, and accurate estimation of parameters, states, and disturbances can be achieved online with an integrated adaptive robust estimation mechanism. The rest of this chapter is organized as follows. In Sect 23.2, the preliminaries and problem formulation are described. A subspace-aided robust closed-loop monitoring approach is presented in Sect 23.3. In Sect 23.4, an adaptive robust closed-loop monitoring approach is presented. We provide the conclusions in Sect 23.5. 23.2 Preliminaries and Problem Formulation. 23.2 System Descriptions. 23.2 Data-driven realization of the multiplication operator. The data-driven realizations of the SIR and SKR of GZ are then by the definitions of SKR and SIR. The truncation operator plus defined in 23.9 is the data-driven realization of the multiplication operator MG, which is the truncated operator of GZ. For the truncation operator, plus converges to an identity operator when it is true that plus GG and therefore MG. 23.2.3 Adaptive Observer. By integrating the adaptive mechanism to the extended residual generator in 23.2 and 23.21, the adaptive observer algorithm can be obtained. It is implemented online with 3 subsystems for co-estimation of all parameters and states, which are residual generator, auxiliary filter, and parameter estimator. Only system I/O data are required for the whole estimation process. The residual generator and parameter estimator can perform state and parameter estimation, respectively, and the former generates a residual, which describes how much the observer model differs from the real model. The residual signal is used to correct the parameter estimation. The auxiliary filter calculates the auxiliary terms used to adjust the parameter and state estimates based on the information matrices. Residual generator xk plus 1k plus plus, k plus plus 1k plus 1k, 23.24 rk cox k plus q k 23.25. Auxiliary filter plus 1 plus, 23.26 co q 23.27. Parameter estimator k plus 1k plus k, 23.28 plus 1, 23.29. Standard feedback control structure.
23.2.4 Problem formulation. The problem of bias estimation arises when an adaptive observer is applied using only and measurements. This is because the coupling between the control inputs and the noises destroys the convergence of the adaptive observer. The standard feedback control loop in Fig. 23.1 is well posed and internally stabilized by the feedback controller KZ. The standard feedback control loop in Fig. 23.1 is well posed and internally stabilized by the feedback controller KZ. The tracking reference should satisfy the persistently exciting PE condition, which is uncorrelated with the state vector X and the unknown noise sequence. The tracking reference should satisfy the persistently exciting PE condition, which is uncorrelated with the state vector X and the unknown noise sequence. 23.3 Subspace-aided robust closed-loop monitoring approach. 23.3 relationship between the closed-loop I/O data. 23.3 the row space of the unknown disturbance. Period disturbance. Period disturbance. Non-periodic disturbance. Non-periodic disturbance. 23.3 robust data-driven realization of the SKR and monitoring. Is uncorrelated with X and L plus M holds and N is sufficiently large such that NTT and NTT are of full row rank. L plus M holds and N is sufficiently large such that NTT and NTT are of full row rank. Is uncorrelated with X and plus 2 plus 1 holds and N is sufficiently large such that NTT and NTT are of full row rank. Plus 2 plus 1 holds and N is sufficiently large such that NTT and NTT are of full row rank. 23.3.4 Case study. The monitoring result of subspace-aided closed-loop approach. The monitoring result of subspace-aided robust closed-loop approach. Distribution of residuals between traditional method and proposed robust method. The Quanto-Quanto plot, QQ plot, illustrates the correspondence between the quantile values of sample data and those of a normal distribution. In this study, Fig. 23.4 demonstrates the degree of proximity between the residual data obtained through two approaches and a normal distribution. Specifically, due to its inadequate consideration of disturbance factors, the conventional closed-loop approach results in residual incorporating disturbance, leading to notable deviations between the residual data points and the normal distribution baseline. Conversely, by constructing the subspace for unknown disturbances, the robust closed-loop approach effectively decouples disturbances from the residuals, exhibiting a higher degree of normality. This comparison emphasizes the capability of the robust closed-loop residual generator to suppress unknown disturbances. Effectively reducing the impact of unknown disturbances ensures a more reliable analysis. 23.4 Adaptive Robust Closed-Loop Monitoring Approach. 23.4.1 Decoupling of the control inputs and noises. To address the biased estimation problem of the adaptive observer induced by coupling, factorization is performed on the controller to construct a noise-independent variable. 23.4.2 Adaptive Robust Estimation Mechanism. To achieve a joint estimation of parameters, states, and disturbances of GZ in a closed loop against unknown disturbances, an adaptive robust estimation mechanism is established based on 23.1 and 23.101. 23.4.3 Stability and Convergence Analysis. 23.4.4 Case Study. Estimation results with closed-loop adaptive estimation algorithm of disturbances in different dynamics. Parameter estimation errors with open closed-loop adaptive estimation algorithms under disturbances in different dynamics. Residuals with open closed-loop adaptive estimation algorithms under disturbances in different dynamics. The proposed closed-loop algorithm can perform system dynamic and disturbance estimation online without prior information. Figure 23.5 shows the disturbance estimation results. The initial estimates are set to 0, and the algorithm is activated from 100s under any disturbance dynamics, the estimates can always converge to the reference values. The closed-loop algorithm provides unbiased parameter estimation under disturbances, as shown in Fig. 23.6. In contrast, the open-loop adaptive observer suffers from significant parameter estimation errors. The errors are dependent on the dynamics of disturbances. In Fig. 23.7, the residuals of the open-loop adaptive observer fluctuate dramatically, while the closed-loop algorithm shows unbiased residuals under any form of disturbances. The proposed closed-loop algorithm is effective in capturing the system dynamics under unknown disturbances, which indicates that the proposed algorithm is more robust than the general adaptive observer and shows unbiased estimation effects in the closed-loop system. 23.5 Conclusion. In this chapter, we introduce robust data-driven monitoring approaches by subspace mapping and adaptive observer techniques for closed-loop systems with unknown disturbances. In the subspace-aided approach, the subspace of unknown disturbances is explored to identify the stable kernel representation of the closed-loop system under disturbances, effectively decoupling the disturbances from the residuals. In the adaptive observer approach, a joint estimation algorithm is developed, enabling online estimation of unknown disturbances and real-time correction of parameters and states. Open access. This chapter is licensed under the terms of the Creative Commons Attribution Commercial No Derivatives 4 International License, org licenses by N40, which permits any non-commercial use, sharing, distribution, and reproduction in any medium or format, as long as you give appropriate credit to the original author S and the source, provide a link to the Creative Commons license, and indicate if you modified the license material. You do not have permission under this license to share adapted material derived from this chapter or parts of it. The images or other third-party material in this chapter are included in the chapter's Creative Commons license, unless indicated otherwise in a credit line to the material. If material is not included in the chapter's Creative Commons license and your intended use is not permitted by statutory regulation or exceeds the permitted use, you will need to obtain permission directly from the copyright holder. References: 1R Fault Diagnosis Systems, An Introduction from Fault Detection to Fault Tolerance. Springer, Berlin, New York, 2006. 2M J. Diagnosis and Fault Tolerant Control, 2nd. Springer, Berlin, New York, 2006. 3Ding SX, Model-Based Fault Diagnosis Techniques, Design Schemes, Algorithms, and Tools, 2nd. Springer, New York, 2013. 4EL LH RD, Data-Driven Methods for Fault Detection and Diagnosis in Chemical Processes. Springer, London, 2000. 5LH EL RD, Fault Detection and Diagnosis in Industrial Systems. Springer, London, 2001. 6Chin SJ, Statistical Process Monitoring, Basics and Beyond. J. 1789, 48502, 2003. 7B R, Dynamic Modeling, Predictive Control and Performance